Welcome to this advanced journey through the depths of C#. This course is designed to elevate your programming proficiency, delving into intricate aspects like delegates, events, generics, async await tasks, and LINQ. Plus, you'll learn about .NET. With detailed code examples and best practice guidelines, you'll explore design patterns, user actions, queries, operators, C# attributes, and more. And you'll learn all of this from Gavin Lawn. Gavin is an experienced developer and freeCodeCamp team member. So, let's get started learning advanced C#.
Hi and welcome. I'm Gavin Lawn. I'm a full-stack software engineer with over 20 years of experience. Some of the more abstract concepts of the C# language, or any high-level programming language, can seem somewhat esoteric, even to many experienced developers. So my goal with this advanced C# course was to explain these more advanced abstract concepts in a simple and easy to understand way. I hope you enjoy this course and I hope you benefit from it.
So, what sort of topics do I intend to cover in the C# Advanced course? Here are a few examples. Delegates, events, generics, extension methods, lambda expressions, LINQ, asynchronous programming with async await, attributes, reflection, and more. So, what makes these kinds of topics more advanced than those discussed in the C# for Beginners course, where we covered basic concepts like methods, classes, arrays, data types, variables, enums, switch statements, if statements, loops, etc. If I had to pick one word that sums up the answer to that question, that word would be the word abstract. I've found what I believe to be an appropriate definition for the word abstract that in my view best fits the programming context. To consider apart from application or association with a particular instance. This definition sort of reminds me of the ancient philosophical theory or worldview attributed to the great ancient Greek philosopher Plato. This theory is known as the theory of forms or theory of ideas. I'm not going to go into too much detail regarding the theory itself, but basically the theory asserts that ultimate reality exists outside our temporal and spatial world. For example, the human form itself exists as a thing independently from the actual humans that exist in plural in our experience of our temporal and spatial realm. An even more simple example is that of the shape of a triangle. If I asked you to draw a triangle and I was to also draw a triangle, there would be subtle differences in our drawings, but essentially we would both be able to recognize the three-sided triangle shape in both of our drawings. There are forms that are universal. So in this sense, the triangle shape itself can be seen as an abstract concept, but instances of this shape can be found and recognized in our real-world experiences. So for example, in terms of programming, we have certain abstract concepts that exist on their own as universally recognizable patterns. These patterns can be implemented in our code to solve multiple real-world problems. It can be hugely advantageous to understand certain advanced abstract concepts that can then be appropriately applied in code to achieve better code reuse, cleaner code extensibility, flexibility of design, easier maintenance of code, separation of concerns, enablement of effective unit testing, and the provision for overall better performance and efficiency of our applications. If there is one downside to the implementation of certain advanced code patterns, it is that to someone unfamiliar with these advanced concepts, the code implementations of these advanced concepts can appear as somewhat esoteric. For most people, the more abstract a concept is, the more time is needed to understand the abstract concept. This, I would say, is the main difference between the concepts discussed in the C# for Beginners course and some of the concepts that we will cover in the C# Advanced course. Let's look at a basic code example. So this is just a basic example that I'll go through fairly quickly. It's not necessary to follow along with the example. I will, however, make the code example available on GitHub. Please see a link to the appropriate repository below in the description. So let's create a C# project based on the .NET Core Console Application project template. Let's name the project School HR Administration. Let's create a class library project and I'll name this HR Administration API. Within the class library project, let's first delete the class that is there by default and then add an interface named iEmployee. Let's add 4 property definitions to the iEmployee interface. ID as integer, first name as string, and this is an interface, so we of course don't need these public access modifiers preceding our property definitions. Last name as string and salary as decimal. Let's add an abstract class and name it employee base. Let's make this employee base abstract class implement the iEmployee interface. And let's make the salary property a virtual property. So now we have the basis in our HR Administration API class library project for a basic employee record. So from within our school HR Administration.NET Core Console application, let's make a reference to the HR Administration API class library project. Let's create a class named Teacher, and let's make the Teacher class inherit from the employee base abstract class. Let's ensure that our code includes a directive to the HR Administration API namespace. Let's create 3 other classes that inherit from the employee base class. These classes represent some other staff roles within the school. So, head of department, deputy headmaster, and headmaster. Let's say there is a requirement to sum up the annual salaries, including bonuses, for these members of staff. First, let's create a method named seedData. So the seedData method accepts a generic list which is strongly typed as iEmployee as an argument. Let's instantiate 5 employee objects and add each of the objects to the employees collection. For the sake of this example, I'm going to hard-code the property values for these 5 employee records. So let's say that a bonus is paid annually to each of these staff members, and the amount is based on seniority. So let's override the salary property and add an appropriate bonus for each of these employees. Let's say the teacher gets 2%, the head of department 3%, the deputy headmaster 4%, and the headmaster gets 5%. So let's address the requirement to calculate the sum total of staff salaries, including bonuses. So to do this, we can implement a for each loop in the main method that traverses the items in our employees list and sums up the salaries within the for each loop using the plus equals operator. We can then output the sum total of all staff annual salaries, including bonuses, to the console screen. Let's run the code. Great. We can use more advanced code to achieve the same thing literally through writing one line of code instead of the multiple lines of code used to create the for each loop, and the mathematical operation performed within the for each loop. So let's include a directive at the top of our code to the system.link namespace. By using the LINQ technology, we are able to provide the same solution with one line of code like this. Let's run the code. And we get the same result as before, but our code is more concise and much cleaner. So let's briefly look at some of the advanced C# concepts that have been applied in this simple example. My explanation at this point will be brief because each of these topics will be discussed in detail as the C# Advanced course progresses. Sum is an extension method provided in the system.link namespace. Let's see what happens if we comment out the system.link directive. The C# compiler immediately complains. The system.link namespace contains many useful extension methods, including the sum extension method. A lambda expression is passed into the sum method. The sum parameter accepts a delegate argument where the delegate contains a type definition parameter, i.e., the iEmployee type. And as you can see, there are several overloads to the sum method where the output type of the delegate can vary. So we are passing in a delegate that accepts an argument of type iEmployee and outputs a decimal value. So because we are summing up the salary field and the salary field is of type decimal, the delegate passed in the form of a lambda expression, has an output of type decimal. Notice the func keyword is used to define the delegate type parameter. Also notice the angle brackets following the func keyword, and within the angle brackets, the date type definitions are included. This is an implementation of generics. Even in this really basic example, a lot of complexity is abstracted away through the use of technologies like LINQ, extension methods, delegates, lambda expressions, and generics. I won't go into too much detail explaining these technologies in this video, because all of these technologies will be explored in detail in this course. Here is a brief definition of each of the technologies we have just discussed. LINQ stands for Language Integrated Query. LINQ enables the developer to write queries against strongly typed collections of objects by using language keywords and familiar operators. Extension methods enable the developer to add methods to existing types without creating a new derived type, recompiling, or otherwise modifying the original type. A delegate is a type that represents references to methods with a particular parameter list and return type. A lambda expression is a shorter way of representing an anonymous method using special syntax. The func type provides a way to store anonymous methods in a generalized and simple way. Generics introduce the concept of type parameters to the .NET framework, which make it possible to design classes and methods that defer the specification of one or more types until the class or method is declared and instantiated by client code. Let's abstract the object instantiation process for an employee through the use of a factory class. So we are going to implement the factory design pattern to implement this code. Let's first create an enum at the top of our code and name it employee type. Let's include the members of staff employee roles within the context of a school in the enumerator list. Okay, let's create a public static class named employee factory. Within this class, let's create a public static method named getEmployeeInstance that returns an object of the iEmployee type. Let's implement the code for this method, which simply instantiates an appropriate object based on the type of the employee. Let's write the code that returns the employee object to the calling code. Right, let's use our factory class to construct our employee objects within our seed data method. So we have now abstracted the construction of our employee objects. Let's run the code. But now let's go one step further. So within the HR admin API class library project, let's create a generic class named factory pattern. As discussed earlier, to someone not familiar with generics, this class may seem somewhat esoteric. The method in this class named createInstance instantiates an object generically. Even though the object is generically created, generics enables the code to be strongly typed, and therefore the code is checked at compile time. So let's go back to the calling code in the school HR administration project, and in the employee factory class, let's update the code that instantiates our employee objects through the utilization of the generic factory pattern class. We have abstracted the object construction process even further. So let's run the code. Great. So before I conclude this video, I want to highlight another reason why it is important to understand the more advanced concepts in C#. These advanced concepts are commonly used in various .NET project frameworks, like for example, ASP.NET MVC, Web API, and Xamarin. If you are a game developer that uses the Unity game engine, knowing the more advanced concepts in C# will also be hugely advantageous. You could create code for each of these types of applications or games without having a deep knowledge of the advanced concepts that are built into the frameworks or game engine themselves. But having a knowledge of these concepts is going to give you an advantage when building and maintaining your applications or games. So, for example, behind the scenes, as it were, reflection is used extensively in ASP.NET MVC. For example, when the controller and action names are passed from the root, reflection is used to find the corresponding method to invoke. Attributes are also used extensively to abstract away complexities and facilitate the reuse of common functionality. Asynchronous programming with async await is used here to increase performance. And generics is also commonly featured. With the Entity Framework data access technology, Lambda expressions and LINQ are commonly used. Entity Framework is commonly used in ASP.NET MVC applications and Web API applications. In the Web API framework, we see the same technologies being applied. Note that dependency injection is a built-in feature in the ASP.NET Core MVC and Web API project frameworks. Dependency injection will be explored in the C# Advanced course. In this Xamarin project, we can see here the use of attributes and generics is being applied here in code. In this game created with Unity, generics is commonly used. Attributes are also frequently applied. And these are just a few examples of how these advanced concepts are applied in commonly used project frameworks and the Unity game engine. In summary, what makes a concept in programming a more advanced concept? The more abstract the concept, the more difficult the concept is to understand for most people. Gaining an understanding of the more abstract advanced concepts can be applied to achieve better code reuse, cleaner code, extensibility, flexibility of design, ease of code maintenance, separation of concerns, the enablement of unit testing, and the provision for overall better performance and efficiency of our applications. The more advanced concepts are applied frequently in the various .NET project frameworks, like for example, ASP.NET MVC, Web API, and Xamarin. Understanding these advanced concepts will also be an advantage to game developers that create games using the Unity game engine. Some of the advanced concepts that will be explored in detail in this advanced C# course will be, for example, delegates, events, generics, extension methods, lambda expressions, LINQ, asynchronous programming with async await, attributes, reflection, and more. Hi and welcome. This video highlights the significance of the release of .NET 5. I've included this content as part of the C# Advanced course because I feel that this .NET upgrade is a game changer for .NET developers. This will not be a code-focused tutorial. I feel that in order to put C# in its correct context, we must understand the underlying plumbing, as it were, and how future .NET upgrades will affect us as C# developers. With the release of .NET 5, I thought it would be prudent to cover how this will change the context of our C# applications. So .NET 5 is expected to be released in November 2020. The first preview of .NET 5 is expected to be available in the first half of 2020 and will be supported by Visual Studio 2019 and Visual Studio Code. Here are some key features of .NET 5. A single unified platform for everything including Windows, Mac, web, mobile, cloud, IoT, gaming, machine learning, and data science. Managed by an open source community and supported by Microsoft. Cross-platform with any device anywhere. Supports all major platform capabilities for .NET Framework, .NET Core, and Xamarin, including Windows Forms, WPF, UWP, ASP.NET MVC, Entity Framework, LINQ, and so on. Scalable, fast, and high performance. Smaller development and packages. Support for the most productive IDEs and tools including Visual Studio, VS Code, VS for Mac, and Command Line Interface, CLI. Okay, let's go back in time to just before May 23rd, 1995. So what is the significance of this date? Well, this is the date that Java first appeared. So, what does the phrase close to the metal mean? And what does it have to do with anything? When programmers say a programming language or platform is close to the metal, this means the developer is able to programmatically manage an operating system's memory. So when Java came along in 1995, this was a huge deal. Compiled Java code ran within its own environment called the JVM. JVM stands for Java Virtual Machine. Write once, run anywhere, and automatic memory management. Before .NET Framework was released by Microsoft on February the 13th, 2002, Visual Basic 6 had been released in 1998. Visual Basic is a third-generation event-driven programming language developed for Microsoft's Component Object Model, COM. The first version of Visual Basic was released in 1991. Visual Basic was not a fully object-oriented language and was event-driven. It was also tightly coupled with the Visual Basic IDE. So .NET Framework was a massive upgrade from this, and the .NET Framework Common Language Runtime resembled the Java Virtual Machine in many ways. Automatic memory management was achieved for Windows platforms, but write once, run anywhere had not yet been enabled through .NET. The .NET Framework could only run on Windows platforms. So the top similarities between the .NET Framework CLR, Common Language Runtime, and Java's JVM, Java Virtual Machine, include: they are both virtual machines, they both include garbage collection, they both employ stack-based operations, they both include runtime level security, They both have methods for exception handling. The .NET Framework provides developers with an abstraction that sits above the operating system, a virtual machine, i.e. the Common Language Runtime, and a suite of APIs, i.e. BCLs or base class libraries. The .NET Framework provides thousands of base class libraries that aid the developer with common development tasks, interoperability, multiple .NET languages, for example, VB.NET, F#, and of course C#, can be included and interact with each other in the same application. This is possible because the higher level .NET languages are first compiled into the intermediate language. The intermediate language is then compiled at runtime into machine language through just-in-time compilation. The .NET Framework also provides memory management, security, and exception handling. .NET Framework, although a massive evolution from VB6 and COM, is not modular and is not cross-platform. It has to be installed in its entirety, and it can only run on a Windows platform. The latest version of the .NET Framework is version 4.8. This version was released on April 18th, 2019. So let's go back in time to the release of Mono. Mono was first released on June the 30th, 2004. It is a free and open source project to create an ECMA standard compliant .NET Framework compatible software framework, including a C# compiler and a common language runtime. Originally created by Simian, it was later acquired by Novell and is now being led by Xamarin, a subsidiary of Microsoft, and the .NET Foundation. So Mono provided a .NET runtime implementation which allowed C# code to be compiled and implemented on multiple platforms. .NET Core's initial release was in June 2016. .NET Core is a free and open source managed computer software framework. It is a cross-platform successor to the .NET Framework. .NET Core is similar to Mono in that it enables cross-platform portability. It is an open source and cross-platform framework. .NET Core can be said to be a more agile version of .NET Framework because only the components required for a particular application need to be deployed to the target computer. .NET Core has been optimized for the cloud and can also run inside a Docker container, which makes it an ideal runtime environment for microservices. The latest release of .NET Core is version 3.1 and was released on the 3rd of December 2019. So at this point, we have .NET Framework, Mono, and .NET Core providing different implementations of .NET. So you can see how it could be difficult for developers, for example, to be sure if a particular .NET base class library component dependency would be supported across relevant .NET implementations. So in order to create uniformity across these implementations of .NET, Microsoft introduced the .NET Standard. .NET Standard is a set of APIs that all .NET platforms have to implement. It was introduced to unify the .NET platforms and prevent future fragmentation. For more comprehensive information on what is supported by the .NET Standard, please check out this table that can be found at this URL. .NET Standard was a great step forward in terms of providing uniformity across .NET platforms. But wouldn't it be great to have one framework to rule them all? So why .NET 5 and not .NET Core version 4? Microsoft is following the version progression of the .NET Framework, where, as mentioned earlier, the latest release of the .NET Framework is version 4.8. So this is why the next release of .NET is .NET 5. It follows from the .NET Framework versioning rather than the .NET Core versioning. So what is the significance of .NET 5? .NET 5 will be open source and you will be able to use it to target Windows, macOS, iOS, Android, tvOS, watchOS, and WebAssembly, and more. I recommend reading this blog from Richard Lander, the program manager of the .NET team. This blog post was written on the 6th of May 2019 and can be found at this URL. Here are some significant quotes from the blog post. From the inception of the .NET Core project, we've added around 50,000 .NET Framework APIs to the platform. .NET Core 3.0 closes much of the remaining capability gap with .NET Framework 4.8, enabling Windows Forms, WPF, and Entity Framework 6. .NET 5 builds on this work, taking .NET Core and the best of Mono to create a single platform that you can use for all your modern .NET code. We intend to release .NET 5 in November 2020, with the first preview available in the first half of 2020. It will be supported with future updates to Visual Studio 2019, Visual Studio for Mac, and Visual Studio Code. The blog post goes on to say the following: everything you love about .NET Core will continue to exist. Open source and community-oriented on GitHub, cross-platform implementation, support for leveraging platform-specific capabilities such as Windows Forms and WPF on Windows, and the native bindings to each native platform from Xamarin. High performance, side-by-side installation, small project files SDK style, capable command line interface CLI, Visual Studio for Mac, and Visual Studio Code integration. Here's what will be new. You will have more choice on runtime experiences. Java interoperability will be available on all platforms. Objective-C and Swift interoperability will be supported on multiple operating systems. Core FX will be extended to support static compilation of .NET, ahead of time AOT, smaller footprints, and support for more operating systems. We will ship .NET Core 3.0 this September, referring to September last year, 2019, .NET 5 in November 2020, and then we intend to ship a major version of .NET once a year, every November. And note the depiction of the release schedule timeline. In 2021, .NET 6, 2022, .NET 7. So no more .NET Framework or .NET Core, but rather one unified open source cross-platform framework. .NET 5 is a welcome release. So please let me know in the comments your thoughts on .NET 5. I think the move to unify features from .NET Framework, Mono, and .NET Core into one framework is a big step forward. This video serves as an introduction to Delegates, and is the first part of a video series on this advanced C# topic. We'll look at a broad overview of delegates in this video, so that we can understand delegates conceptually, and we'll also create a very basic example of using delegates in code. My aim is to explain these advanced concepts in a simple way. So what are delegates? A delegate can be described as a type-safe function pointer. A variable defined as a delegate is a reference type variable that can hold a reference to a method. In order for a delegate to reference a particular method, the delegate must define parameters with types that match the parameter types contained in the relevant method. The delegate must also define a return type that matches the return type of the relevant method. When a developer instantiates a delegate, the developer can associate its instance with any method with compatible parameters and return type. The developer can invoke or call the method through the delegate instance. Note that variance can be used in delegates, which means that the types defined for the parameter list and the return type of the delegate do not have to match exactly with the relevant method's parameter types and return type. In this video, we'll keep the example simple, but we'll discuss variance in an upcoming video. In the meantime, if you wish to read about variance, you can navigate to this URL. This webpage contains content on both covariance and contravariance. In this video, I'll introduce delegates through a basic example where a delegate can reference a static method and an instance method. We'll also look at multicast delegates, which allows the developer to invoke or call multiple methods through one delegate call. We'll also look at how a delegate can be passed as a parameter to a method and subsequently called within that method. In a later video on delegates, we'll explore how delegates are used for asynchronous callbacks and event handling in C#. We'll learn how we can take advantage of different types of delegates like action, func, and predicate to facilitate callbacks and add flexibility to our code. But let's first look at the basics in this introduction to delegates. So a delegate can reference both static methods and instance methods. Let's first look at how a delegate can reference static methods. Let's say we want to encapsulate functionality that logs text and includes a date timestamp preceding the text. In some situations, we want to have the ability to log the text to the console screen, and in other situations, we want to have the ability to log the text to a text file. So let's define a delegate that can reference a method that does not return a value and accepts one string argument. So to do this, we use the delegate keyword followed by the name of the delegate type we wish to define. Let's name this delegate logDel. So preceding the logDel delegate name, we have included the void keyword. This is because we want this delegate to reference a method that does not return a value. Then after the logDel delegate name, we can include brackets, and within the brackets, a list of parameters. So let's include one string parameter and name it text. So this delegate can reference methods that contain one string parameter and do not return a value. Note that we have included our delegate definition within the program class, which means this delegate type can be accessed from anywhere within the program class. We could have included this delegate definition outside the program class and within the delegate basic example namespace, if we wanted to extend the delegate's accessibility to anywhere within the delegate basic example namespace. In this example, we'll define the delegate's scope so that it is accessible from anywhere within the program class and not accessible from outside of the program class. Let's create a static method named logTextToScreen inside the program class. This static method contains the void keyword, which is used to indicate that the method does not return a value and contains one string parameter named text. The functionality within this method is very basic. We are simply writing the text argument's value to the screen with a date timestamp preceding the value stored in the text argument. You can see that the delegate type we have just defined, named logDel, contains a definition for a method that does not return a value and contains one string parameter. So the return type and parameter type defined in our delegate named logDel matches the return type and the parameter type in the logTextToScreen method signature. Let's go to our main method and define a variable as the logDel type. We do this by entering the logDel delegate name, followed by the variable we'll name logDel, then the equals symbol, followed by the new keyword to instantiate an object. We must then follow the new keyword with the name of the logDel delegate type, and then pass the name of the method that we want the logDel variable to reference into the logDel types constructor, like this. Then to call the method now referenced by the logDel variable, we can simply write the name of the variable that references the delegate and pass in the appropriate parameter to the delegate, like you would if you were calling a method. Note you are also able to invoke delegates through the use of the delegate types invoke method like this. But for this example, let's call the delegate without using the invoke method. Okay, so let's make this example slightly more interesting. Let's write code in the main method to prompt the user for the user's name, and let's pass the user's input as an argument to the logDel delegate. Let's run the code. And that works as expected. So what happens if we decide to include the date timestamp as a parameter in the logTextToScreen method's method signature? The C# compiler automatically complains. This is because the logTextToScreen method no longer conforms to the logDel delegate definition. So let's change the logDel delegate definition to accommodate a parameter of the datetime data type. Right, let's run the code. Great. So that gives us a basic idea of how delegates work. Let's change the code for the logTextToScreen method and the logdel delegate definition to how it was previously. I.e., let's remove the datetime stamp as a parameter for the logdel delegate definition, and let's also remove the datetime stamp parameter from the log text to screen method signature. Let's also update the log text to screen method implementation accordingly. So let's say there is a requirement to log the text to a text file. To implement this functionality, we can simply create a method that doesn't return a value and contains a string parameter. As we now know, this will allow this method to be referenced by a variable defined as the logdel delegate. So let's create a static method named logTextToFile that contains a string parameter and does not return a value. Let's implement code logic detail that writes the input from the user to a text file. Let's replace the logTextToScreen method name being passed into the logdel delegate during the construction of the delegate object with the logTextToFile method name. So our logdel variable is now referencing the logTextToFile method. So when the logdel delegate is called, this should invoke the logTextToFile method. Let's see if the user's input has been written to the relevant text file. Right, so let's navigate to where the log file should now have been created, which is the same directory path from where our code is run. And you can see that the user's input has been successfully written to the log file as expected. So we have now proven that we can reference static methods in delegate-defined variables. Let's now prove that delegates can also reference instance methods. Let's create a class named log. Let's move our static methods to the log class. And let's remove the static keyword from their method signatures because we want to test that instance methods can be referenced from delegates. Let's go to the main method and create an instance of the log type. Let's then pass the instance method named logTextToScreen into the logdel delegate constructor. Let's test the code. Great, the user's input is logged to the screen as expected. And for good measure, let's also test the logTextToFile instance method. Excellent. We are also able to call both methods through one delegate call. This can be done through the use of what's known as a multicast delegate. By using a multicast delegate, multiple objects can be assigned to one delegate instance by using the plus operator. Let's define two delegate variables as logdel on one line like this. Let's name the first delegate logTextToScreenDel and the second delegate logTextToFileDel. Let's instantiate the first delegate named logTextToScreenDel and ensure that it references the instance method named logTextToScreen. Let's instantiate the second delegate named logTextToFileDel and ensure that it references the instance method named logTextToFile. Let's create a multicast delegate named multilogdel and assign it a value, which is a combination of both the logTextToFileDel variable and the logTextToScreenDel variable. Note that these two delegate variables have been combined through the use of the plus operator. We are now able to call the log_text_to_screen method and the log_text_to_file method through one call to the multi-log_del delegate. Let's test the code. And the user's input along with a timestamp has been logged to the screen as expected. Let's see if the user's input has been logged to the relevant text file. And it has. Great. And lastly, let's demonstrate how a delegate can be passed as an argument to a method, then invoked by the method that receives the delegate argument. Let's create a static method in the program class named logText. This method does not return a value and contains a parameter defined as the log_del delegate type. And the logText method will simply serve as a wrapper function for calling the log_del delegate, which will be passed as an argument at runtime to the logText method. Let's go to the main method and pass the multi-log_del delegate as an argument to the logText static method. Let's test the code. So it has logged the user's text to the screen as expected. Let's also check whether the text has been logged to our log file. Excellent. So you could also pass the log_text_to_screen del object or the log_text_to_file del object as an argument to the logText method. So let's do this. Let's first pass the log_text_to_screen del object into the logText method and run the code. Great. And let's also test passing in the log_text_to_file del object to the logText delegate. Let's look at the appropriate text file. Excellent. So you can see how delegates can be used to separate design from implementation detail and facilitate flexibility of design in our applications. Please let me know in the comments section whether you have used delegates before in your code. If not, hopefully you will feel confident that you can use them in the future. I hope you have enjoyed this basic introduction to delegates. In the next tutorial, we'll dive deeper into delegates with a more detailed example. Hi and welcome. This is the second part of a tutorial on delegates. Please note that this tutorial is going to be quite code intensive, and I will be going through the code creation process fairly quickly. If you are struggling to follow along, my advice would be to download the code from GitHub and use this video as a guide. A link to the relevant GitHub repository is available in the description. The purpose of this video is to help you understand delegates and how they can be applied in code, and also how certain code design principles should be adhered to in order to create reusable, extensible, clean and easy to maintain code. Basically, we are going to build a club membership registration form and use delegates to implement field validation functionality. The advantage of using delegates for this purpose is that these delegates can be reused to validate fields for other forms that we may wish to add to our application in the future. This alludes to how delegates can facilitate extensibility of our design. We are effectively going to decouple validation from any one particular form. These delegates will be enabled to be reused to validate any appropriate fields for any form. So we have highlighted two advantages that can be gained through the use of delegates: code reuse, adherence to the code principle of DRY, which is an acronym for Don't Repeat Yourself, and code design flexibility. So in this example, we'll build a basic application using C# and the .NET Console project template. We'll use SQLite to store the data entered into our user registration form. We will then create a login form and write code to authenticate the user by validating the user's login information against relevant data stored in a table in a SQLite database. If you are not familiar with SQLite, please navigate to this URL for more information. You can also download a SQLite client application named SQLite Browser from this location. We'll create basic code using Entity Framework Core for appropriate database interactions. You may have noticed that I have used the .NET Core Console project template for all my tutorials thus far. There is a very good reason for this. We could implement the code we are about to write using the ASP.NET MVC framework. We can scaffold our code and leverage technologies like specific attributes provided in .NET to facilitate field validation. Separation of model views and controllers and functionality like dependency injection is inherently taken care of for us in the ASP.NET MVC framework. Please don't misunderstand me. Frameworks like ASP.NET MVC facilitate rapid application development, and I am a proponent of using such frameworks. The only problem is we run the risk of not fully understanding the underlying design and code principles that are abstracted away by such frameworks. We can easily and effectively develop web applications, for example, using frameworks such as ASP.NET MVC, without understanding the fundamental underlying principles that make such frameworks so effective. So because the .NET Core Console project template doesn't spoon-feed us, as it were, it can force us to think about fundamental design principles that facilitate, for example, code reuse, separation of concerns, the implementation of code design flexibility, and dependency inversion principle. With all that said, let's look at a bird's eye view of what our basic application will look like. We'll start with the main .NET Core Console project. We'll then create a standard class library project which will be referenced by our main .NET Core Console project. The .NET Standard Class Library project will be named Field Validator API and will contain two classes. One class will be named Common Field Validator Functions. It will contain a number of delegates which will encapsulate functionality for common validation, like for example, required field validation, string length validation, pattern match validation, field comparison validation, and date validation. The other class will be named Common Regular Expression Validation Patterns. This class will contain a number of common regular expression patterns that can be leveraged in our application. For example, a regular expression pattern used for validating an email address, a pattern that can be used to validate UK postcodes, a pattern that can be used to validate UK phone numbers, and a pattern for validating strong passwords. Within the main project, the .NET Core Console project, we'll create 4 folders. A folder named Data to store data-related classes and interfaces, a folder named Field Validators to store interfaces and classes relevant to field validation, a folder named Models to store our data structures. In this application, we are only going to implement one data structure, which will be a class containing user registration-related properties. And lastly, a folder named Views. This folder will contain one interface and classes relevant to the screens that will be presented to the user, namely the user login view, the user registration view, and welcome view, which is presented to the user once the user is authenticated through the use of the login view. There's also a main view which will be instantiated and run from within the main method. So this application serves as a simple example of how we can leverage delegates and design our applications to facilitate easy maintenance and flexibility of design. We are also going to create 3 ancillary classes within the root of the .NET Core Console application, namely Common Output Text, where we can store and make available, for example, heading text. Common Output Format, which we can use for changing the background and foreground color of our output text. And lastly, we'll create a class named Factory, which will abstract away the construction of our main view object. This will demonstrate a very basic example of the use of dependency injection and show an adherence to the last letter of SOLID, i.e. dependency inversion principle. So let's get started. First, let's create a .NET Core Console project. A solution, as always, will be auto-generated to house our project. Let's name this project Club Membership Application. The theme of this application will be a user registering for a cycling club. Right, so let's add a folder named Models. Let's add a class to our Models folder named User. Let's add properties to our user class. These properties will store the values entered by the user during the registration process. All of these properties must be public read-write properties, so they must have both getters and setters. So let's create ID as integer, first name as string, last name as string, password as string. Note that the password field will be stored in the user's database table without first being encrypted. I have not included any encryption code because encryption and decryption are beyond the scope of this tutorial. Date of birth as date time, phone number as string, address first line as string, address second line as string, address city as string, and lastly, postcode as string. Let's decorate the ID field with the database generate attribute and pass the enumerator list item value of database generated option.identity as an argument to the database generated attribute. So this is what is known as a code-first approach to developing an application that uses a database for data storage. We first create a model which is implemented as a C# class. Then we are able to run certain commands either through .NET CLI or Visual Studio to generate the data structure in our database from the models created within our application. In this application, we are going to run the relevant database commands through Visual Studio. Note, as an alternative, we could use the database-first approach, which would involve creating the database schema in the database and then generating the models from the database schema using appropriate database commands. We'll use the code-first approach in this application. So note that by decorating the ID field with the database-generated attribute the way we have done here, we are declaring that we wish to create the ID field as a primary key in the relevant database table, and that this ID field must auto-increment each time a new row is added to the relevant database table. So the next step is to install the relevant Entity Framework Core package. The package we need for this application is Microsoft.entityframeworkcore.sqlite. So let's browse for the relevant NuGet package using the NuGet Package Manager facility provided within Visual Studio. And let's install the Microsoft.entityframeworkcore.sqlite package. So the next step is to add a DB context class to our project. Let's first create a folder named Data. Let's add a class to the Data folder and name it Club Membership DB Context. So this class must inherit from the Entity Framework's DB Context base class. DB Context class resides in the Microsoft.entityframework core namespace. So let's create a directive to this namespace in our Club Membership DB Context class. And now let's override the DB Context base class's onConfiguring method. Within this method, we can configure a connection to the SQLite database that we wish to create and access. We are using the DB Context Option Builder object to configure our connection string. The connection string here is very basic. It contains a file path to our database file. The database file will reside in the same location from where our code will run. This is achieved by using the appdomain.currentdomain.base directory property to establish the path to our SQLite database file. We are then passing the DB Context Options Builder object to the DB Context class using a call to the base method. The next step is to create a table database structure for our relevant model class. So we only have one model class to worry about here, i.e. the user class. So we use the Entity Framework's DB-set generic type and pass the user type as a generic argument to the DB-set type to establish the type of property that will contain a reference to the user's table that will be generated in our SQLite database. Entity Framework will use this user's property to add data to the user's database table and retrieve data from the user's database table. We could also use the user's property to update data within the user's database table, but we won't need to implement database record updates in this application. So before we run the update-database command within Visual Studio's Package Manager console facility, we need to create what is known as a migration. So we can use the add-migration command for this purpose like this. Okay, so why has that failed? The reason is that we need to install the Microsoft.entityframework.tools NuGet package. So let's do this. Let's try to create the migration again. And this time it succeeds, and there's the migration class created for us. And you can see that the code in this class contains a method to create the users table. And it also creates a method to drop the users table. So in order to run the migration, we can run the update-database command like this. Okay, great. So let's see if our database has been created as expected. And it has, great. Let's open the database in the SQLite browser client facility to see if our users table has been created as expected. And it has, excellent. So now let's create a project that will serve as an API, providing reusable validation functionality. Let's remove the default class. And let's create a class named Common Field Validator Functions. Let's make this class public, and let's add 5 delegate definitions. The first delegate definition defines a delegate type that can reference a method used for the purpose of ensuring that a form field is not left empty. The second delegate defines a delegate type that can reference a method used for constraining the character length of a text field to between a minimum and maximum value. The third delegate definition defines a delegate type that can reference a method that validates a date. The fourth delegate definition defines a delegate type that can reference a method that can be used for validating a text input field value against a regular expression pattern. The fifth delegate definition defines a delegate type that can reference a method that validates a text field value against another text field value. We'll use this delegate to store a method reference to a method that provides functionality for ensuring that the user re-enters the user's chosen password so that it matches the original entry for the password field during the registration process. Let's create private static member variables for each of these delegates. Let's create the method implementations for each of these delegates, namely required field valid, string field length valid, date field valid, field pattern valid, and field comparison valid. So to expose our delegate objects to calling code, let's create a public static read-only property for each related delegate. With each of these public properties, we are creating a new delegate object of the appropriate delegate type and passing in the appropriate method name into the delegate types constructor. We are using a singleton pattern to ensure that only one instance of each of these delegate objects can be created. So let's create a class and name it Common Regular Expression Validation Patterns. I've already sourced 4 common regular expression patterns from the following useful website that can be found at this URL. I'll also include a link to this URL below in the description. I've copied the relevant regular expressions to Notepad. I'll copy and paste these regular expression patterns from Notepad into the Common Regular Expression Validation Patterns class. As stated earlier, the code for this tutorial can be downloaded from GitHub. Please see a link to the appropriate repository below in the description. Note that you are able to copy and paste these regular expression patterns into your code from the GitHub webpage at this URL. A link to this webpage has been included below in the description. Okay, so let's create a directory named Field Validators. This directory will contain field validator classes. Each validator class will correspond to a particular view. We'll create the view classes in a bit. Let's first create an interface named iFieldValidator. Let's make this a public interface. So within the club membership application.fieldValidators namespace, let's create a delegate definition named fieldValidatorDel. This is a very important delegate as it can reference a method that validates fields for any form. So for example, we are going to reference a method to validate our user registration form fields. But say for example, we needed to capture banking information. We could create a custom validator class for this purpose. And within a newly created banking form view class, we could reference an appropriate validator object derived from the validator class and use this validator object to validate the banking-related fields. So we will be using this delegate definition to create a delegate that references a method for validating fields presented to the user in our user registration view class. So the parameters defined for this delegate are field index, defined as an integer for the purpose of referencing a field value within an array of fields. Field value as string. This parameter will be passed the field value to be validated. Field array. This is an array that will store all validated fields for a particular view. And lastly, a parameter named field invalid message. And preceding this parameter's definition is the out keyword, which allows its value to be outputted to calling code. So if a field is invalid, a relevant message created within the relevant referenced method can be outputted to the calling code, which can then, for example, output the message to the user. So let's create a method signature for a method named initializeValidatorDelegates. A method that implements code for this method definition can be used to initialize the validation delegates that will be used for a particular view. Then fieldArray provides a definition for a read-only property that stores a reference to an array of field values. And lastly, ValidatorDel provides a definition for a read-only property that stores a delegate object that references a method responsible for validating the fields in a particular view. Let's create a class named fieldConstants. We are only going to store one enum in this class, which will be used to index an array which contains field values for the user registration form. Using enum list item values to index our array instead of integer values makes our code more readable simply because at a glance we can see exactly where our field resides in the relevant array. So let's create an enum named user registration field. And let's create an enum list item value for each of the fields in our user registration form. Great. So let's create a class that implements the iFieldValidator interface. So this class is named userRegistrationValidator. Let's define 4 constants at the top of the class. These will be used a bit later to validate our first name and last name field lengths. Let's create a delegate that will be used to determine if an email address already exists in the system. If an email address already exists, the user's entry will be deemed as invalid. Let's create a private member variable of the field validator del type. This delegate will store a reference to a method responsible for validating the user registration fields. Let's define a private member variable for each of our common validator delegates: required valid del, string length valid del, date valid del, pattern match valid del, and compare field valid del. Let's create a private member variable to store the delegate object that will reference a method responsible for checking if a user's email address input already exists in the system. Let's create a private member variable for storing an array of valid field values entered by the user. And let's create a property named fieldArray that will create a fieldArray object if one has not yet been created. Note how we are using the length property of the enum.getValues method to make appropriate space provisions for our fieldArray array. Each enum list item in our user registration field enum must have an index counterpart in the fieldArray array. Let's expose the validator del delegate through a public read-only property. And one thing I've forgotten to do is indicate that this class implements the iFieldValidator interface. So let's do this. And now let's initialize the appropriate validator delegates within the initializeValidatorDelegates method. Here we are referencing the delegates already wired up to their appropriate methods created for us in the common field validator functions class, which resides in the Field Validator API project. Let's create a private method that will be responsible for validating each of the fields used to register a club member. This method will be referenced by the field validator del delegate. Let's create the basic structure for the valid field method. Let's wire up the valid field method to the field validator del delegate within the initializeValidatorDelegates method. Okay, let's implement the code for the valid field method. Let's first convert the field index parameter to the user registration field enum for the purpose of creating more readable code. So the first field we wish to validate is the email address field. So let's write code to ensure that text has been entered into the email address field by calling the required valid del delegate for this purpose. So if the text has not been entered for this field, we wish to output an appropriate message. To do this, we can set the field invalid message parameter to an appropriate message. Note that the field invalid message parameter contains the out keyword in its definition, which means its value can be outputted to the calling code. So we also want to ensure that the user's email address input conforms to an appropriate regular expression pattern used for validating email addresses. We can do this by using the pattern match valid del delegate. And if the user has entered an email address but it is not in a valid format, we want to set the field invalid message output parameter to an appropriate message. So for the first name field, we must include validation so that the first name field can only contain a text value with a length that is between 2 and 100 characters. The last name field must also only contain a text value that has a character length between 2 and 100. The password field must contain a value that conforms to the following rules. It must contain at least one small case letter, one capital letter, one special character, and must be between 6 to 10 characters in length. An appropriate regular expression pattern is used to validate the password. The password compare field must contain a value, and its text value must be an exact match to the password field. Date of birth must contain a value and be a valid date. The phone number field must contain a value that conforms to a pattern defined for a valid UK phone number. Address first line must contain a value. Address second line must also contain a value. And address city must also contain a value. Postcode must contain a value that conforms to a pattern defined for a valid UK postcode. And you can see that the method returns a Boolean expression. If the field invalid message output parameter has not been set during the validation of a particular field, this means that the field is valid and a Boolean value of true will be returned to the calling code. However, if the field invalid message output parameter has been set to one of the validation messages, the field valid method returns false, because the field value inputted by the user has been deemed to be invalid by our field valid method. I know there is quite a lot of detail in that method. Please feel free to copy the code for this method, which can be found at the GitHub webpage at this location. Okay, so let's go back to the data folder. Let's add an interface named iRegister. Let's add a method definition named register that contains a string array parameter. The method that implements code for this method definition will accept a string array argument which will contain valid field data inputted by the user. and this field data will be saved to the users table in our SQLite database. This method definition must also return a Boolean value. Then let's create a method definition for a method that will be referenced by a validation delegate. The delegate will be executed in order to check if the email address entered by a user already exists in the database table named users. This method definition provides a definition for a method that contains a string parameter and returns a Boolean value. Right, let's create another interface and name this interface iLogin. This interface defines one method definition for a method that accepts two string arguments and returns an object of type user. Let's add a class named registerUser and indicate that this class implements the iRegister interface. So let's provide a code implementation for the register method. Let's instantiate a DB_context object from the club membership DB_context class within a using block. Let's create a user object and set its properties so we can save its values to the user's database table. Okay, there's a problem here. I forgot to include the email address field in the user model. So what we need to do is first update the user model. Then we need to add a migration. And update the database. Let's use the SQL Browser client application to see if our email address column has successfully been added to the user's database table. And it has. Great. Let's add a directive to the club membership application.fieldValidators namespace at the top of the code so that we can access the user registration field enum. And we can use the user registration field enum to index the field array passed into the register method. Using an enum for the index provides better readability of our code. We must ensure that we cast the enum values to integer values when using these values to index items within the field array. Once we have finished creating the user object, we can save it to the user's database table. Note that we simply pass the user object as an argument to the add method to add the data stored in the user object to the user's database table. And to confirm our intention, we must call the saveChanges method on the DB_context object to save the data stored in the user object to the user's database table. Let's now implement code for the email exists method. We can use the AnyExtension method provided in the system.link namespace to check if the email address text value passed into the method already exists within the user's database table. If it does, this method will return true. If it doesn't exist, this method will return false. And we can now go back to the user registration validator class and wire up the email exists method to the email exists del delegate. First, let's make sure that the register object derived from the register class that we just created is passed into the user registration validator class's constructor. Then let's wire up the email exists method provided in the register class to the email exists delegate within the initialize validator delegates method. We can then implement the appropriate validation code in the field valid method to check if the inputted email address already exists within the user's database table. Okay, so before we create our view classes, let's create two ancillary classes. Let's first create a class named Common Output Text. Let's create and implement three read-only static properties. One for returning the main application heading, one for returning a heading for the user registration view, and one for returning a heading for the user login view. So let's create three corresponding methods that write these headings to the console screen. Write main heading, write login heading, and write registration heading. Let's create another class and let's name this class Common Output Format. Let's create an enum named Font Theme with three enum list item values, namely Default, Danger, and Success. Let's create a method named Change Font Color that contains a parameter of type Font Theme. So if the font theme is equal to Danger, let's make the output font color red, and let's make the foreground font color white. If the font theme is equal to Success, let's make the background color green, let's make the foreground color white. Else if the font theme is equal to Default, let's reset our console screen to its default color settings. Right, let's create our view classes. Let's create a folder named Views. Within the Views folder, let's create an interface named iView. Let's make this a public interface. Let's create a method definition named runView, which contains no parameters and does not return a value. Let's create a property definition of type iFieldValidator. Note that each view can have 0 or 1 field validator objects associated with it. If, for example, the relevant view does not contain input fields and therefore does not need a field validator class, the appropriate property will be set to null. So let's add a new class named userRegistrationView. Let's add two private member variables, one of type iFieldValidator, the other of type iRegister. Let's indicate that this class implements the iView interface. Let's ensure that the field validator property returns the private member variable's value, which is of the same type. Let's create a constructor. This constructor contains two parameters, one of type iRegister and the other of type iFieldValidator. Let's appropriately assign our two private member variables, the object values, that will be injected into the user registration class's constructor when the user registration class is instantiated into an object at runtime. Let's create a private method named getInputFromUser. This method contains two parameters, one parameter of the user registration field enum type and the other of the string type. Let's create a local string variable named fieldVal. This string variable will store the user's input. Let's create a do loop. the do loop's condition returns true if the user's input is deemed invalid by the fieldValid method. So when the fieldValid method returns false within the while condition, the while condition returns true, which means the do loop will perform a subsequent iteration. The effect of this is an appropriate message will be outputted to the user, instructing the user that the input just entered is invalid. The user will then be prompted once again to enter a value for the relevant field. So the user will be prompted for a particular field's value until the user's input is deemed valid by the validation code. Let's write code within the do loop to prompt the user for the user's input for the appropriate field. Let's assign the user's input to the fieldVal string variable. In the fieldValid method, let's call the validator delegate and pass in appropriate arguments. Let's write code that will output text in an appropriate format when the user input is deemed as invalid. Let's write code in the runView method that will assign the user's input to a space within the field array if the user's input is valid. Let's write a private method that will save the user's registration information to the user's database table in our SQLite database. Let's call the register user private method from the runView method. Okay, so let's create the login view. Let's add a class to the views folder named user login view. Let's write code to indicate that we want the user login view to implement the iView interface. Let's auto-generate the iView members that we must implement. Let's set the field validator property to null because in this code example, we are not going to include validation on the login fields. We could add a custom validator class and implement validation code for the fields of this login view if we chose to do so. But in the interests of time, let's omit this functionality. Let's create a constructor that contains a parameter of type iLogin. Let's create a private member variable of the type iLogin. Let's assign the object argument that will be injected into the user login view class's constructor during the instantiation of the user login view class to this private member variable. So within the runView method, let's first write the application heading to the screen, and let's then write the login heading to the screen. So let's make sure we are writing the main heading to the screen within the runView method of the user registration view class. Let's go back to the user login view class. Let's write code to prompt the user for the user's email address. Let's assign the user's input to a local string variable. Let's write code to prompt the user for the user's password. And let's assign the user's input to a local string variable. Let's call the login method on the _login user object and pass in the two local variables containing the user's input into the login method. And this method returns a user object if the user is authenticated. So we need to check if the user object is not null, which means the login has been successful. And we'll write a to-do comment for now to indicate that we wish to implement code here to run the welcome view when the login is successful. We'll create the welcome view class in a bit, then replace the to-do comment with the code to run the welcome view. Else, if the login is not successful, we'll simply clear the screen and output a message stating that the user's entered credentials do not match any of the system's records. So let's create the welcome view. In the runView method of the user welcome view class, we are simply outputting a message welcoming the user to the cycling club. And let's replace the to-do comment in the runView method in the loginView class with code that creates a user welcome view object that invokes the runView method, which displays a welcoming message to the user on the console screen. So let's create the main view class. We'll set the field validator to null because this view doesn't have any fields that require validation. Let's implement code in the runView method. Let's write the application heading to the console screen. Let's prompt the user to press either the L key to log in or the R key to register. If the user presses the L key, the user will be presented with the login screen. If the user presses the R key, the user will be presented with the registration screen. So let's use the console.readKey method to capture the user's key press. Let's create an if statement structure so that the appropriate functionality can be executed depending on which key the user presses. And let's simply write goodbye to the screen when the user presses a key that isn't L or R. Let's create a constructor that contains two parameters. And let's create two corresponding member variables that will store the appropriate objects that will be passed into this constructor at runtime. Let's create a private method that will run the user registration view. Let's implement the code for this method, which simply invokes the runView method on the user registration view object, which is of type iView. And let's also write a private method that invokes the user login view. Let's go back to the if statement, and if the user has pressed the R key, we want to present the user registration view, and once the user is successfully registered, we want to present the user login view. If the user presses the L key, the user is presented with the login screen. So now we want to abstract the creation of the main view object. Let's create a class named Factory. Let's make it a public static class. Let's create a public static method named getMainViewObject that returns an object of the iView type. Let's create a login object. This object will be used to authenticate the user. But it looks like I forgot to implement the authentication logic. So let's create a class within the data folder and name it loginUser. We are going to need two namespace directives in this class. So let's create a namespace directive for the club membership.models namespace, and let's also create a namespace directive for the system.link namespace. This class must implement the iLogin interface, and let's auto-generate the members of the iLogin interface that must be implemented. So the iLogin interface only contains one method, a method named login. It contains two parameters. One is a string parameter for the user's email address, and the other is a string parameter for the user's password. And now we can simply write code that compares the user's email address and password with the records stored in the user's database table in our SQLite database. If the user is registered with the application, the first or default extension method returns a user object. If the user is not registered with the application, null is returned. So let's go back to the factory class and finish creating code that abstracts the construction of the main view object. So in order to create the main view object, we must create an object derived from the user login view class and an object derived from the user registration view class. In order to create an object derived from the user login view class, we must first create an object of the iLogin type, which will be injected into the constructor of the user login view class when the user login view class is instantiated as an object. In order to create an object derived from the user registration view class, we need to first create an object of type iRegister. The user registration view class's constructor also contains a parameter for a custom field validator object. So let's create an object of type iFieldValidator that derives from the user registration validator class. And in order to initialize the validation delegates, we must first call the initializeValidatorDelegates method on the object derived from the user registration validator class. So we can now create an object derived from the user registration view class. In order to create the object successfully, we must inject an object derived from the register user class and an object derived from the user registration validator class into the user registration view class's constructor. We can now also create an object derived from the user login view class and inject an object derived from the login user class into the user login view class's constructor. We are now able to inject the object derived from the user registration view class and the object derived from the user login view class into the main view class's constructor when constructing the object derived from the main view class. Then we can write code to return this object from the getMainViewObject method. So notice something very important that is going on here when we construct our objects. All our class's constructor parameters are not concrete types. They are interface types. We are adhering to the dependency inversion principle, which is represented by the last letter of the SOLID acronym. The dependency inversion principle states that classes should never depend on concretions, but rather should only depend on abstractions. So in this method, we have implemented very basic dependency injection functionality. So when the mainView object is created using the getMainViewObject method, an object derived from the user login view class and an object derived from the user registration view class is automatically injected into the mainView class's constructor. The mainView class's constructor contains two parameters that are of the iView type. The user registration view class implements the iView interface, and the user login view class also implements the iView interface. So now the way we have designed this application should allow for the calling client code to be rather simple. So in the main method, we can simply get an object derived from the mainView class by calling the factory class's getMainViewObject static method. See how clean the client code is. This is because we have abstracted away all the complexities of constructing an object derived from the mainView class. Then all we need to do is invoke the object derived from the mainView class's runView method to run this application. And that is our application pretty much written. But inevitably there will be bugs. Let's test the code. Let's press the R key so that we are presented with the user registration view where we'll register a user's information. So let's leave the email address field blank and press enter. Okay, and the required field validation message should have been presented. So why has this not worked? Okay, so in the field valid method within the user registration view class, I forgot to include a not operator in the if condition where the appropriate field validation delegate is invoked to test if the user's input is valid. So we want to output an appropriate message to the user when a field is deemed as invalid and subsequently prompt the user to try again. Let's test the fix and this time step through the code to make sure that the code is doing what we expect it to do. So let's once again leave the email field blank. Great, and this time the code that outputs an appropriate invalid field message is run. And what happens if we enter a valid field value on our second attempt at entering an email address? But this time we enter an invalid email address format. Great, that is working as expected. And now let's enter a correct email address. And we have another bug. This email address has not been saved to the system. So why is our application behaving as though a record with this email address already exists in the system? Right, so this time it is because I included a not operator where I should not have done so. Let's remove the not operator because we want a message to be displayed when an email address already exists in the system. Let's test the code again. Great, that is working as expected. So I don't like the formatting of the prompts at the moment. I want the user to enter the user's information on the same line as the prompt text. So let's make the appropriate fixes. Let's use the console.write method rather than the console.writeLine method to prompt the user for the user's input. And let's append a colon followed by a space to the prompt text for each of the user's input prompts. Okay, so let's test the code. Let's enter a valid email address. Let's enter a valid first name. And let's enter an invalid last name. And that is working as expected. We have included validation code whereby the first name and last name fields must contain a character length between 2 and 100. This time, let's enter a valid last name. Let's enter a valid password. And for the field where we have to re-enter our password, let's enter text that does not match the password we entered. Great, so the comparison fields validation functionality is working. And this time, let's re-enter our password correctly. Let's enter a valid date for the date of birth field. Let's make up an address for the first line of our address. And let's leave the second line of our address blank. Great, so our validation message is correctly advising that we must enter a second line of our address. So on the second try, let's enter a made-up second line for our address. Let's enter a valid city. And let's enter a postcode in a correct UK postcode format. Great, so we have successfully registered Carl Smith as a member of the cycling club. So let's press any key to continue to the login screen. And let's enter our credentials. Hi Carl, welcome to the cycling club. Great. So we have successfully been authenticated. But the welcome view should be displayed on its own screen, so let's fix this. In the runView method of the user welcome view class, let's clear the console screen before displaying the welcome message. So I've noticed that we are not being prompted for a phone number, so let's navigate to the runView method in the user registration view class and ensure that the appropriate functionality for the phone number field is added. Okay, let's test the code. And we can use the made-up data for Carl Smith again because I've removed the record we added earlier from the user's database table because a null value had been added into the phone number field. So let's enter some made-up but valid data into the user registration form. And let's open our SQLite database named clubmembershipdb.db in the SQLite browser client application. We can do this by dragging and dropping the data file onto the SQLite browser application's user interface like this. And we can now run a SQL query through the SQLite browser client application to check if the record for Carl Smith has been added to the users table. And has the phone number been added correctly this time? Yes, it has. Great. Let's enter another record. Let's test that we are now not able to enter Carl Smith's email address into the email field. Great. Let's enter information for a made-up character named Ethel Jones. And we can test some of the field validation functionality along the way. Okay, let's log in as Ethel Jones. Excellent. Let's log in as Carl Smith. Great. Hi and welcome. This tutorial has been created to help with your understanding of covariance and contravariance when using delegates in C#. In the first part of this tutorial on delegates, I've mentioned that the return type and parameter types of the method referenced by a delegate object must match the return type and parameter types defined in the relevant delegate's definition. But I also mentioned that the return type and parameter types of the relevant method definition don't have to match with the relevant return type and parameter type's delegate definition exactly. So what does this mean? The C# language allows for the developer to have a little bit of design flexibility when it comes to a delegate's compatibility with a method. Covariance and contravariance provide flexibility when matching a delegate definition with a method definition. Covariance permits a method to have a return type that is more derived than that defined in the relevant delegate. If you are unfamiliar with what is meant for a class to be more derived or less derived than another class that is a member of the same inheritance hierarchy, please check out 2 tutorials which were provided by this channel as part of a C# for Beginners course, one on C# inheritance and the other on C# polymorphism. A link to these tutorials can be accessed from the cards in the right-hand corner of your screen, and links to these tutorials have also been included below in the description. Contravariance permits a method that has parameter types that are less derived than those in the relevant delegate type. If you haven't yet subscribed, please consider subscribing and please ring the bell so that you can be notified of content on advanced C# concepts and much more. Let's look at a code example where we can demonstrate how covariance works when using delegates in C#. This example demonstrates how a delegate object can reference a method that has a return type that is derived from the return type defined in the relevant delegate's definition. So I'm going to create 2 factory methods. By factory method, I mean a method implemented for the abstraction of constructing a specific object and returning the relevant object to calling code. The first method will return an object of type IceCar, which is a user-defined class that we'll create representing a blueprint for an object that can store information for an ICE car. The second method will return an object of type EVCar, which is another user-defined class that we'll create representing a blueprint for an object that can store information for an electric car. Both of these classes will inherit from a base abstract class named car. We are going to create a delegate that defines a method definition that contains an ID parameter of type int and a name parameter of type string. The delegate type will return the car type which is the base abstract class from which a class named IceCar and a class named EVCar will inherit. This delegate type can be used to create an object that can store a reference to a method that returns a type that is derived from the car base type. This is at the heart of what covariance is regarding delegates. Even though the return types of the delegate and the method it references are not an exact match, because the return type of the delegate is the base class for the return type of the method, the C# compiler allows the delegate to reference the method. Let's create a .NET Core console application. I'll name the project and solution Covariance and Contravariance delegate example. Let's create an abstract class named car. Let's add two auto-implemented properties to the car user-defined class. One named ID of the integer data type, and the other named name of the string data type. Let's add a virtual method that doesn't contain any parameters and returns a value of type string. Let's name this method getCarDetails. This method is very basic and returns an interpolated string value containing the values for the ID and the name properties. So let's create our first class that inherits from the car abstract class. Let's name this class IceCar. And we are going to keep this example very basic so that we can focus our attention on the topic of this tutorial, namely applying covariance and contravariance when using delegates in C#. So let's override the getCarDetails method. This method will simply return an interpolated string value, which will contain a value returned from its base method counterpart, followed by the text, which will contain a hyphen followed by the text internal combustion engine, ICE. And let's create a class that is very similar to the IceCar class, but this class will serve as a blueprint for objects that store information about an electric car. So let's duplicate the IceCar class and change it so that it is appropriate for our EVCar class. So this class is named EVCar. So the getCarDetails method in the EVCar class will return an interpolated string value containing a value returned by its base method counterpart, which will contain the relevant car object's ID and name property values, followed by the string literal hyphen electric. So now let's create a factory class. Let's name it CarFactory and let's make this class a static class. And let's create a static method named returnIceCar that returns an object of type IceCar. This method contains two parameters, one of type int and the other of type string. And the code for this method simply returns an object derived from the IceCar type to the calling code. And let's create another method which is almost identical to the returnIceCar method. The only difference being that instead of returning an object derived from the IceCar type, it returns an object derived from the EVCar type. So the question is, can we reference either of these two methods from a delegate object where its delegate definition is an almost exact match of the returnIceCar method definition and the returnEVCar method definition? The only difference being that the delegate will define a method definition that returns the car type, i.e. a less derived type. So let's create a delegate named CarFactoryDel that defines a method definition that contains two parameters, one of type int and the other of type string, and returns a value of type car. So in the main method, let's define a delegate named CarFactoryDel and assign it the method name of returnIceCar. The returnIceCar method returns an object of type IceCar, and the delegate definition returns the car type. Notice that the C# compiler is not complaining about this because the IceCar type derives from the car type and covariance is allowed in C#. So let's write code to execute the delegate and assign the object to a variable named IceCar. So we'll give this car object an ID of 1 and a name of Audi R8. Let's write code to write the type of the object to screen. Let's write code to execute the object's getCarDetails method to retrieve the object's available information and write this information to the screen. And let's use the same delegate type to reference the return EVCar method. The EVCar type is derived from the car type. So because covariance is permitted in the C# language, the return EVCar method is deemed as compatible with the car factory del delegate. Let's run the code. And we have successfully demonstrated how covariance can work when using delegates in C#. So let's demonstrate how contravariance can work when using delegates in C#. So to demonstrate contravariance when using delegates in C#, we are going to create two delegates. Both delegates will be used to reference a method used for logging information about a car. Both delegate definitions will not return values. The first delegate definition contains one parameter of the ICE car type. The second delegate's definition contains one parameter of the EV car type. The key to relating this example to contravariance is that both of these delegates contain one parameter that inherits from the car type. Note that two delegate definitions contain a parameter that is more derived than the parameter contained in the method that these delegates will reference. The method that both of these delegates will reference will contain one parameter of type car. The method will not return a value. So let's first remove the lines of code not needed in this example demonstrating how contravariance works in C# when using delegates. Let's create the first delegate and we'll name it log_ICE_CAR_DETAILS_DEL. Let's create the second delegate and we'll name it log_EV_CAR_DETAILS_DEL. And now let's create the static method that will be referenced by both of these delegates. We'll name this method log_CAR_DETAILS. And notice how the parameter contained in its method definition is of type car. Note that the delegates that will reference this method will contain parameters that inherit from the car type. So let's implement the code for this method. The logic for this method is that if the type of object passed in as an argument to this method is of type ICECar, log the car's object type and information to a text file. We'll use the app_domain.currentDomain.base directory property to establish the path of the relevant text file so that it is created in the same path from where our code will execute. Else, if the type of object passed into the log_CAR_DETAILS method is of type EVCar, log the car's object type and information to the console screen. Else, throw an argument exception. So let's write code to reference the log_CAR_DETAILS method from our log_ICE_CAR_DETAILS_DEL delegate. Let's write code to execute the log_ICE_CAR_DETAILS_DEL delegate. Let's write code to reference the log_CAR_DETAILS method from our log_EV_CAR_DETAILS_DEL delegate. Let's write code to execute the log_EV_CAR_DETAILS_DEL delegate. Notice that even though the parameter contained in the log_ICE_CAR_DETAILS_DEL delegate definition is not an exact match of the parameter contained in the log_CAR_DETAILS method definition, the C# compiler does not complain when we write code where the log_ICE_CAR_DETAILS_DEL delegate references the log_CAR_DETAILS method. And the same is true when we write code where the log_EV_CAR_DETAILS_DEL delegate object references the log_CAR_DETAILS method. This is because the parameter type contained in the log_ICE_CAR_DETAILS_DEL delegate definition inherits from the parameter type contained in the log_CAR_DETAILS method definition. And the parameter type contained in the log_EV_CAR_DETAILS_DEL delegate definition inherits from the parameter type contained in the logCard details method definition. This example demonstrates contravariance when using delegates in C#, where a delegate's parameter may not match exactly with a parameter of a method that the relevant delegate object references. But if the relevant parameter in the relevant method definition is part of the same inheritance hierarchy and is less derived than the relevant delegate's parameter, this is allowed because contravariance is permitted in the C# language. Let's run the code. And this is an expected result. Let's see if the EV cars information has been logged to the relevant text file. Great! I hope you have enjoyed this tutorial on understanding covariance and contravariance when using delegates in C#. This is the fourth part of a video series on delegates. In this video, we'll look at the func, action, and predicate built-in generic delegates. So before we dive into this topic, we must have at least a basic understanding of generics. Generics is a topic that we'll explore in detail in upcoming videos, but for now a basic understanding will suffice. So what is generics? In C# version 2, generics was introduced. Generics makes it possible to, for example, design classes, methods, and delegates that defer the specification of one or more types until the class, method, or delegate is declared and instantiated by client code. Use generic types to maximize code reuse, type safety, and performance. A developer can create generic interfaces, classes, methods, events, and delegates. In this video, we'll look at three types of generic delegates that are provided in the C# language, namely func, action, and predicate. All of these generic delegates are available in the system namespace. Let's look at an overview of each of these built-in generic delegates before we look at basic code examples demonstrating their implementation. So let's first look at func. In this depiction, we can see the basic structure for a func delegate. The T represents a placeholder where the developer can pass a type parameter in order to strongly type the parameter relevant to the encapsulated method at compile time. The in keyword in this context means that the parameter type is contravariant. We are not going to be discussing covariance and contravariance in this video, because these topics were discussed in detail in the previous tutorial. There are 17 func delegates available in the system namespace. This func delegate, for example, can be used to encapsulate a method that contains no parameters and returns a value. There are 16 more func delegates. Here is a func delegate that contains one parameter and returns a value. Here is another func delegate that contains two parameters and returns a value. Func delegate definitions always return a value. The return type is always defined in the last type parameter, and the available func delegates allow for 0 to 16 parameter type definitions. Note that the last parameter declared in the func generic delegate defines the type of the returned value of the method that the func delegate encapsulates. The out keyword in this context means that the return type is covariant. The action generic delegates allow a developer to encapsulate a method that can have 0 to 16 parameters and must not return a value. The predicate generic delegate encapsulates a method that contains one parameter and returns a value that must be of the Boolean data type. A predicate delegate represents a method that defines a set of criteria and determines whether the specified object meets those criteria. Let's look at code examples using each of the built-in generic delegates, i.e. func, action, and predicate. At the end of the tutorial, we'll look at an example of using an extension method that takes a predicate as an argument. Let's start by looking at an example using the func built-in generic delegate. Let's create a .NET Core console project. I'll name this project and solution func action predicate examples. Let's create a public class named mathClass and add one method named sum. The sum method contains two parameters of the int data type and returns a value of the int data type. This method simply returns the integer result of the sum of two integer arguments passed into this method. Let's instantiate the math class in the main method. Let's use the generic built-in func delegate to encapsulate the sum method. All type parameters passed into the func delegate are of the int data type. The last type parameter represents the return type, and the first two type parameters represent the method's parameters data types. So as you can see, through the use of generics, we have made our func delegate compatible with the sum instance method. We have strongly typed the func delegate with the int data type for the parameter types and the return type. We can therefore use the func delegate to encapsulate the sum method. Let's write code to execute the delegate and then code to write the result to the screen. Let's test the code. Great! We can replace the sum method with an anonymous method using the delegate keyword like this. An anonymous method is, as the name suggests, a method that does not have a name. Let's test the code. Great! We can further abstract the method by removing the delegate keyword, the return keyword, the curly brackets, and the parameter type definitions. So here we have now reduced the functionality of the sum method to a lambda expression. A lambda expression is an anonymous function which, as discussed, is a defined function not bound to an identifier. We previously created the same function using the delegate keyword. A lambda expression is a shorter way of representing an anonymous method. Lambda expressions were introduced in C# version 3 along with LINQ. For more information on LINQ, please navigate to this URL. Let's test our code. Excellent. To further understand the func generic built-in delegates, let's create our own imitations of a few of the built-in func delegates. Let's call our delegates func2. And we can now replace the func keyword with func2 in our code. Great! But we don't need to do this because appropriate generic delegates are already available to us in the system namespace. Let's create a slightly more complex example where our delegate encapsulates a lambda expression that performs the functionality of adding two operands of the float data type together, then multiplies the result of this operation by a value that is of the int data type. Great! Let's create a more practical example where our lambda expression adds a bonus to an employee's annual salary. Great. So let's look at some examples using the action generic built-in delegate. So in this example, let's create a lambda expression that accepts fields for an employee record as arguments and outputs the employee details to the console screen. Note that the action delegate is used to encapsulate a method that does not return a value. So in this example, we'll output 3 fields of an employee record to the console screen: ID, first name, and last name. Great. Let's add an annual salary field. So to do this, we can use a different action delegate to accommodate this new field. Let's update the lambda expression accordingly. Let's add a gender field, which is of the char date type, and a Boolean field representing whether an employee is a manager or not a manager. So to achieve this, we need to use a different action delegate that can accommodate the 2 new fields. Excellent. So let's use an example where we'll use the predicate built-in generic delegate. Let's first create an employee class. Let's create a generic list that will contain 4 objects of the employee data type. Let's add some employee objects that contain made-up employee details to the employees list. Now let's create a method that will filter the employees list based on criteria that will be passed to the method in the form of a predicate. So this method simply traverses the employees list. If employee items within the list meet the criteria of the predicate passed into the method, the relevant item is added to another list that is returned to the calling code once all the items in the original list passed into this method have been traversed and evaluated. So let's call the filter employees method and pass in the employees list, followed by the lambda expression, which is encapsulated by a predicate delegate. Let's say our lambda expression in this example is used to return only male employees. Let's write code to traverse the list returned by the filter employees method and use the display employee records action delegate, which I have now renamed to display employee details, just for better readability, that we created in the previous example to write the relevant employee records to the console screen. Let's test the code. Great! Let's alter the logic of our predicate so that we return only details for employees that earn less than $45,000 a year. Great! Let's alter our logic so that we only return employee details for employees that are managers. Great! So we can abstract this code even further through the use of an extension method. So let's create a public static class named extensions. Let's copy the filter employees method to our extensions static class. Let's make the filter employees method public, and it must also be static. Then to finish making this method an extension method, all we need to do is add the this keyword before the first parameter. The first parameter is defined as a generic list that is strongly typed with the employee user-defined type. So the filter employee extension method should now automatically be available on generic lists that are strongly typed with the employee user-defined type in our main method. If you are not clear on extension methods, don't worry, extension methods will be discussed in detail in upcoming tutorials. Basically, through extension methods, the developer can add methods to existing types without creating a new derived type, recompiling, or modifying the original type. So let's see if we can access the filter employees method on the employees generic list. And there it is. It shows up in the IntelliSense as expected. So we no longer need to pass the employees list to the filter employees method as a parameter, and all we need to do is pass in the lambda expression. Let's test the code. Great! The system.link namespace contains a number of extension methods. Let's demonstrate how we can use an extension method which is available in the system.link namespace to achieve the same result. LINQ is beyond the scope of this tutorial. We'll look at LINQ in detail in upcoming videos. Let's include a directive to the system.link namespace at the top of our code. The where extension method is available on the generic IEnumerable type. The generic list type implements the IEnumerable generic interface. So now that we have added the system.link directive, the where extension method should now be available on the employees list object. So let's replace the filter employees method with the where method. The where method returns a value of type IEnumerable, so we must convert our result to a generic list using the toList explicit conversion method. Let's test the code. Great! So let's finish up by using the func delegate that we created earlier to add a bonus to the employee annual salary fields of each of our employee objects stored in the employees list. Let's test the code. Excellent! I hope you have enjoyed this tutorial on the three built-in generic delegates, namely func, action, and predicate. Hi and welcome. This is the fifth part of a video series on delegates. This is also the final part of this video series on delegates, but there are a lot more upcoming videos to be released as part of this advanced C# course. In this video, we'll look at how delegates can be used to encapsulate a callback method. So, what is a callback method? Basically, callbacks are simple functions which are used to notify the calling instance when an asynchronous code block has been executed and the result is available.
So I found a great code example on a Microsoft Docs webpage that uses a callback method encapsulated by a delegate to run code when asynchronous tasks have completed. The code in this code sample performs a basic function of retrieving the IP addresses associated with user-inputted domain names using the .NET built-in DNS static class. For example, if we input Microsoft.com, the DNS class, behind the scenes as it were, asynchronously looks up the IP addresses associated with the Microsoft.com domain name. I'm going to simply copy this sample code demonstrating the use of a callback method into a .NET Core console application. We can then demonstrate the code and go through the code step by step to understand how it works. Basically, this code demonstrates using asynchronous methods available in the built-in DNS static class to retrieve domain name system information for user-specified domain names. You can navigate to this URL to copy the relevant sample code, as well as read more information about the sample code. A link to this URL has also been included below in the description. So let's create a .NET Core console application. Let's name this project and solution DNS Async Callback Sample Code. Let's copy the code from the relevant web page and paste it into the project we have just created. So to do this, we can select all the code that has been auto-generated in our program.cs class file and paste the code currently copied to our clipboards over the selected code. Right, so let's start by running the code. So let's enter a few well-known domain names. This code has been written so that we can press the Enter key without entering anything at the input prompt as an indication that we are finished inputting our data. So let's enter a few domain names. So for the first entry, let's enter google.com. For the second entry, let's enter microsoft.com. And for the third entry, let's enter yahoo.com. Right, let's press the Enter key without entering anything at the command prompt to indicate that we are finished inputting our data. And in the output presented to the screen, we can see three headings, namely addresses for Google, addresses for Microsoft, and addresses for Yahoo. Under these headings are the IP addresses relevant to the domain names that we have entered. If you're interested in reading more about what DNS, i.e. Domain Name System is, please navigate to this URL. So let's go through the code to see how a delegate is used to encapsulate a method that is used as a callback method through the execution of the relevant delegate once relevant asynchronous tasks have been completed. So the first line of code in the main method instantiates a delegate named async callback. This delegate is built into .NET and is provided specifically for the purpose of encapsulating callback methods that are used during asynchronous operations. So I'm going to right-click the delegate name in the Visual Studio Code Editor and click the context menu item named Go to Definition. And here we are presented with the delegate definition of the async callback delegate. This delegate can encapsulate a method that doesn't return a value and contains one parameter of the iAsync result type. And if we look at the iAsync result type, this interface provides a standard definition for objects that are passed as an argument to the callback method. The relevant object that implements the iAsync result interface represents the status of an asynchronous operation. You can see here the async state read-only property gets a user-defined object that qualifies or contains information about an asynchronous operation. Okay, so let's go back to our code, and you'll see that a method name is passed into the constructor of the async callback delegate in the code written for the purpose of instantiating an object derived from the async callback delegate type. So our callback method is named process DNS information.
Let's have a brief look at this method. You can see its method signature conforms to the method definition defined in the async callback delegate. So we'll come back to this method in a bit. For now, let's go back to the code in the main method. So next, the code is prompting the user for domain names. And you can see that for each entry, the DNS.BeginGetHostEntry method is fired. DNS is a static class provided in .NET and provides simple domain name resolution functionality. The DNS.BeginGetHostEntry method asynchronously returns the Internet Protocol IP addresses for the specified host. You can see that our delegate named callback that encapsulates our callback method named processDNSInformation is passed as an argument to the DNS.BeginGetHostEntry method. Here the code essentially informs the DNS static class of the memory address of our designated callback method, which is stored in the callback delegate object. Note that above this line of code, we have a line of code that increments an integer variable named requestCounter. The number of asynchronous tasks is stored in the integer variable. Now, the reason why this incrementation is done in an unusual way here, whereby the .NET built-in interlocked.increment method is used for this purpose, is because each time our asynchronous process is kicked off, as it were, by the DNS.BeginGetHostEntry method, a new thread is created and executed in parallel, asynchronously, to the main thread. When each asynchronous process is finished processing, the callback method is executed on the main thread, and if we go back to our callback method, you can see that each time an asynchronous task completes, the request counter variable's value is decremented within the processDNSInformation callback method. So, because the timing of when this callback method will be called by potentially multiple threads is uncertain, we must ensure that the request counter variable is updated in a thread-safe way. Multi-threading solves problems with throughput and responsiveness, but in doing so, it introduces new problems, deadlocks, and race conditions. For more information in this regard, please navigate to this URL. So the next line of code monitors the state of the value of the request counter variable. When the request counter variable's value is 0, we know that all asynchronous tasks have completed, which means our output data is ready to be presented to the screen. So this while loop ensures that if our asynchronous tasks have not yet completed, that the subsequent lines of code responsible for outputting the results of the asynchronous tasks are only executed once the asynchronous tasks have completed. So this while loop will continue processing and outputting status information to the screen until the request counter variable has been decremented to 0 within the callback method, i.e. the processDNSInformation method. So let's look at the processDNSInformation callback method. And you can see the DNS.endGetHostEntry method is called to return the result of an asynchronous task. The DNS.BeginGetHostEntry method and the DNS.endGetHostEntry method are used for asynchronous processing. The DNS.endGetHostEntry method gets called from within the callback method. Remember, a reference to the callback method was passed as an argument to the DNS.BeginGetHostEntry method. This was done by passing the async callback delegate object stored in a variable named callback to the DNS.BeginGetHostEntry method as an argument. Remember, an async callback delegate object was coded to encapsulate the processDNSInformation method within the main method. This object was then passed as an argument to the DNS.BeginGetHostEntry method. So the application knows that an asynchronous task has completed because at this stage the callback method, processDNSInformation method, has been invoked. So within the callback method, it is safe to call the dns.endGetHost entry method to return the result of the asynchronous task to the calling code. So the results here are stored in an array list member variable named host data. The host data array list can be used to retrieve the relevant results and present the relevant results to the console screen. And you can see the code here in the main method responsible for outputting the results of each asynchronous task to the console screen. So the IP addresses relevant to the domain names entered by the user are written to the console screen. Let's run the code and enter some domain names. Excellent. Note that the code we have just demonstrated here uses the asynchronous programming model APM pattern, also called the iAsync result pattern, which is the legacy model that uses the iAsync result interface to provide asynchronous behavior. Microsoft recommends, moving forward, that we use the task-based asynchronous pattern, TAP, for asynchronous programming, which uses a single method to represent the initiation and completion of an asynchronous operation. The async and await keywords in C# add language support for the task-based asynchronous pattern. We'll look at the task-based asynchronous pattern TAP in detail in upcoming tutorials. This video serves as a demonstration of how delegates can be used to encapsulate callback methods and also serves as a brief introduction to asynchronous programming. We'll look at the recommended approach to asynchronous programming, i.e. the task-based asynchronous pattern, TAP, in upcoming videos. Please navigate to this URL for more information on asynchronous programming patterns available in C#. To summarize, in this 5-part video series on delegates, we discussed that a delegate is a reference type in C# that references a method that contains a particular parameter list and return type. We discussed that due to a concept called variance, the delegate definition does not have to exactly match the parameter types or the return type of the method that it encapsulates. Contravariance means that a delegate, for example, can reference a method where a particular parameter in the delegate's definition is more derived than the parameter counterpart contained within the method that it encapsulates. Covariance means that the return type in the delegate's definition can be less derived than the return type of the method that it encapsulates. We looked at 3 built-in generic delegates, namely func, action, and predicate. We looked at how these generic delegates can be used in code for better code reuse, type safety, and to improve performance. We also briefly looked at anonymous methods, lambda expressions, and extension methods. In this final video on delegates, we looked at how a delegate can be used to encapsulate a callback method that can be called once an asynchronous task is completed. We haven't looked at delegates in relation to events yet. An upcoming tutorial on events will include how delegates are used in relation to events in C#. I hope you have enjoyed this tutorial on asynchronous programming using delegates to encapsulate callback methods. And I hope you have enjoyed this video series on delegates. If you didn't fully understand all the concepts discussed in this video, please don't worry. The more you practice, the more you'll understand and the more proficient you'll become as a software engineer. Learning to become a proficient software engineer is a marathon and not a sprint. I'd also like to add that I think it is more important to understand the concepts behind the code rather than the code itself. Hi and welcome. This is the first part of a tutorial on C# events. In this video, we'll look at the basics of C# events by examining a piece of code taken from a Microsoft Docs webpage. For more content on advanced C# concepts like this and much more, please consider subscribing. And please ring the bell so that you'll be notified of future releases from this channel. I usually use my Windows PC to record my demonstrations, but I've decided to demonstrate this code example using Visual Studio 2019 Community Edition for Mac. It doesn't ultimately matter which code editor you use if you want to follow along. It makes no difference because this video is about the code, more specifically about the basics of what events are and how they relate to delegates. So I'm going to use Visual Studio 2019 for Mac Community Edition to create a .NET Core console project. You can name it what you like. I'll name this project Threshold Reached Event Application. I'm going to copy the code from the appropriate Microsoft Docs webpage and paste it over the code in the program.cs file like this. This code sample is available at this URL. So the code here performs a very basic function. It first generates a random integer value, which can be any non-zero integer value where the maximum value is 10. This integer value serves in this example as a threshold value. The code then prompts the user to press the A key to increment an integer value by a value of 1. When the integer value has been incremented to the extent that it reaches the threshold value, i.e. the generated random integer value, an event is raised, and the calling code handles the raised event by outputting text stating that the threshold value has been reached. The text also includes the date and time when the threshold value was reached, by the value that the user is able to increment by pressing the A key. So let's start by running the code, and then we'll look at the code in order to see how an event and a delegate have been implemented in the code. Let's press the A key until the threshold is reached. And the threshold has been reached, so the event is raised and the event handler outputs appropriate text to the console screen. So what exactly is an event in C#? Events are special kinds of multicast delegates that can only be invoked from within the class or struct where they are declared. If other classes or structs subscribe to the event, their event handler methods will be called when the class where the delegate has been declared raises the event. Events can be marked as public, private, protected, internal, or private protected. These access modifiers define how users of the class can access the event. For more information on access modifiers, please navigate to this URL. Events in .NET are based on the delegate model. The delegate model follows the observer design pattern, which enables the subscriber to register with and receive notifications from a provider. We'll discuss the observer design pattern in an upcoming video. An event sender pushes a notification that an event has happened, and an event receiver receives the notification and defines a response to it. An event is a message sent by an object to signal the occurrence of an action. Delegates were explored in detail in the last tutorial, the third part of this course. Links to the playlist on delegates have been included below in the description. You can also access this playlist through the card available in the top right-hand corner of your screen. Let's recap. What is a delegate? A delegate is a type that holds a reference to a method. A delegate is declared with a signature that shows the return type and parameters for the method it references. And it can hold references only to methods that match its signature. A delegate is thus equivalent to a type-safe function pointer or a callback. A delegate declaration is sufficient to define a delegate class. Right, let's look at our code example to see how an event can be implemented in C#. So an event can be fired through a user action, for example, button press, or through the code logic itself. In this example, the event is raised through the code logic. Here, we have a user-defined class named counter where an event is declared. The name of the event is threshold reached. Let's look at how this event is defined. So this event has a public access modifier. And to define an event, we must use the event keyword. Then the event keyword is followed by a built-in C# delegate named event handler. Delegates have many uses in .NET. In the context of events, a delegate is an intermediary, or pointer-like mechanism, between the event source and the code that handles the event. You associate a delegate with an event by including the delegate type in the event declaration. Let's select the event handler delegate name in the code editor. Let's right-click and select the Go To Declaration menu option. If you are using Visual Studio for Windows, this context menu item will be marked Go To Definition. So here you can see the event handler delegate declaration that can be used to store a reference to a method that contains a matching parameter list and return type to the event handler's parameter list and return type in the delegate definition. This is a built-in delegate provided in the system namespace. Notice the t-event-args generic parameter. There is another built-in event handler delegate of the same name also provided in the system namespace. This particular delegate declaration looks like this. The difference between this delegate and the one we are using is you are restricted to using the event-args class to provide event data to the event handler method using this delegate. Notice that in the definition of the event handler delegate that we are using, we are able to provide a type parameter through generics. This means we are not restricted to the use of the event-args class to pass data to the event handler method, and we can use a custom class for this purpose. Here you can see we are using the threshold reached event-args custom class where data about an event can be stored in two public properties, namely threshold and time reached. So this event handler delegate contains two parameters in its delegate definition. The first parameter is of type object, which allows for the calling code event handler method to accept an argument that references an object instance derived from the class where the relevant event resides. The this keyword can be used as a reference to the object that contains the event. So the this keyword can be used to pass a reference of the sender object to the appropriate event handler method when the relevant event is raised. The second parameter through generics allows a developer to define a type for this parameter. The advantage of being able to use generics with this delegate is that we are able to create our own custom user-defined type that can contain the relevant event data, which can be passed as an argument to an appropriate event handler method in the calling code. So let's look at a basic overview of the counter class, i.e. the user-defined type where our event is declared. Here we have two member variables, both of the integer date type. One to store the threshold value, the other to store a value that will be incremented by the user. So the threshold value is passed through by the calling code through a parameterized constructor when the calling code instantiates an object derived from the counter class. The passed-in argument is then stored in the member variable named threshold. Let's look at the add method. This method can be used to increment the member variable named total. The value stored in the total member variable is then compared to the value stored in the threshold member variable. If the value stored in the total variable, which is incremented by the user, reaches the value stored in the threshold variable, an event is raised. Let's look at the code responsible for raising the relevant event. Firstly, an object derived from the threshold reached event args class is instantiated. The threshold reached event args user-defined type is the custom type we have passed as a parameter to the event handler delegate. An object instantiated from the threshold reached event args class can be used to store event information. If you look at the threshold reached event args class, you can see that it contains two properties, one named threshold for storing the threshold value, and the other named time reached when the user incremented value stored in the total member variable reached the value stored in the threshold member variable. So these two properties are appropriately set on an object derived from the threshold reached event args class. This object is then passed into a method named onThresholdReached. The onThresholdReached method contains the logic for raising the appropriate event. In this method, code is first created where a variable named handler is used for referencing the threshold reached event. The next line of code is an if statement checking if the handler variable contains a value. If the handler variable is null, this means that calling code has not subscribed to the relevant event, which means no appropriate method has been designated on the client calling code to handle the relevant event when the event is raised. In a bit, we'll look at how a calling client can subscribe to an event that resides in a particular class. So, if, however, calling client code has subscribed to the relevant event, the handler delegate is invoked. This delegate will point to a method that has been defined in the calling client code. The relevant method is designated to handle the relevant event at the point where the calling client subscribes to the relevant event. So let's look at the calling client code. Let's go to the main method. So the first line of code is instantiating an object derived from the counter class. Note that the random.next method is being used to pass a non-negative random integer that is less than the specified maximum, which in this case is hard-coded to a value of 10. So the randomly generated number is our threshold, which will be stored in the relevant object derived from the counter class. So the object derived from the counter class is stored in a variable named C. Using the object referenced by the C variable, we are now able to subscribe to the event named threshold reached, which is declared in the counter class. So the code here is assigned a method that resides in the program class to the threshold reached event. We can do this because the method named C_threshold reached is compatible with the event handler delegate. In other words, the parameter list and the return type of the C_threshold reached method definition matches the parameter list and return type of the event handler delegate definition. The effect of this is that when the threshold reached event is raised from the add method within the counter class, the subscribed method in the calling code, i.e., the C_threshold reached method, will be invoked. A reference to the relevant object derived from the counter class or sender object is passed in to the C_threshold reached method, as well as the object that stores the relevant event data, in this case the object derived from the threshold reached event args class. Note how in this example the event handler delegate is an abstraction that allows any calling client that contains a method with a method definition that matches the event handler delegate definition to handle what happens when the relevant event is raised. This means the calling client is loosely coupled with the class where the event is declared. You see, the calling code doesn't have to know anything about the class where the event is declared, and the class where the event is declared doesn't need to know anything about the calling code. The event handler delegate, in this case, is used to establish a loose coupling. This is a key concept to understand when it comes to using events in C#, how delegates can be used to create a loose coupling between components. So let's watch this in action. Let's put a breakpoint in the code to a point where the value incremented by the user has reached the threshold value and the event is about to fire. We can then see what happens when the threshold reached event is raised. Let's run the code. And let's press the A key to increment the value that is compared to the threshold value until our breakpoint is hit, which means the user incremented value matches the threshold value. And there it is, our breakpoint has been hit. So, a variable named handler is set to the threshold reached event. The code checks if the handler variable is null. If the handler variable is not null, this means the calling code has subscribed to the event. So I'm going to put a break within the C_threshold reached method, which is the designated method for handling the relevant event. And when we step through the code, the threshold reached event is raised. The C_threshold reached method is invoked, and the C_threshold reached method handles the event in the custom way that the method has been coded. And if we look at the values associated with the two arguments passed into the C_threshold reached method, we can see that this is an expected result. We have the sender object, which is the object from where the event was raised, and we have an object derived from the threshold reached event args class, where the relevant event data is stored. And let's press F5 to run the code right through, and you can see the expected output presented to the screen. I hope you've enjoyed this video on the basics of events in C#. Please consider subscribing for more content on advanced C# concepts like this and much more. And please ring the bell so that you can be notified of future content released by this channel. If you feel you've gained value from viewing this video, please consider hitting the like button, and please feel free to share any of my videos with anyone you feel may benefit from their content. A link to the Microsoft web page that contains the code example I have used in this video is available below in the description. Hi and welcome. This video is the second part of a tutorial on events in C#. In this video, we'll create a practical example where multiple events exist in a class. We'll look at using add and remove accessors to encapsulate the functionality that gets executed when client code or calling code subscribes or unsubscribes to the relevant events. Code within the add accessor is executed when the client code subscribes to the relevant event. Code within the remove accessor is executed when the client code unsubscribes to the relevant event. We'll use the event handler list built-in C# collection class to store the relevant delegates associated with the relevant events when the calling code subscribes. The event handler list collection class is a built-in C# collection class that can be found in the system.component model namespace and is a collection specially suited for storing delegates. So here's the basic idea behind this code example. A device, could be any device, contains a thermostat which contains a heat sensor as well as a cooling mechanism. So we'll have a class to represent the device, a class to represent the heat sensor, and a class to represent the cooling mechanism. Each of these classes will implement an appropriate interface. So the heat sensor class will contain 3 events. One event that gets fired when the temperature of the device reaches or goes above 27 degrees Celsius, which is 80.6 degrees Fahrenheit. This event flags a warning alert. The cooling mechanism is switched on to cool the device back down to an acceptable temperature. We'll create another event that gets fired when the temperature of the device has reached or gone above 27 degrees Celsius and then subsequently falls below 27 degrees Celsius. This event flags an informational alert and the cooling mechanism is switched off. And lastly, we'll create an event that gets fired when the temperature reaches or goes above 75 degrees Celsius, which is 167 degrees Fahrenheit. This event flags an emergency alert. The device is shut down, and emergency services personnel are notified about the event. We discussed in the previous part of this tutorial that an event is raised either by the user's action, for example, the user clicks a button, or the code logic itself. In this example, we are going to use code logic to raise specific events. For more content on advanced C# concepts like this and much more, please consider subscribing and please ring the bell so that you'll be notified of future releases from this channel. Right, let's get started. Let's create a .NET Core console app, and let's name this project and solution Thermostat Events app. Let's start by building a custom class to store our event information. Let's name this class Temperature Event Args. And let's make this class inherit from the C# built-in Event Args class. We want our custom class to store the current temperature, so this will be the temperature at the time when an event is raised. And we also want to store the date and time when the event was raised. So let's create an auto-implemented property named temperature and define it as the double data type. Let's create another auto-implemented property named currentDateTime and define it as the datetime data type. Next, let's create an interface named iHeatSensor. And we'll include definitions for 3 events in the iHeatSensor interface. All the events are associated with the built-in C# delegate named EventHandler. And here we can pass our custom class, the one we have just created named TemperatureEventArgs, that will be used to store event information, as a generic parameter to the event handler delegate, So let's create a definition for an event that will be fired when the temperature reaches or exceeds a predefined emergency level. Let's create a definition for an event that will be fired when the temperature reaches or exceeds a predefined warning level. And lastly, let's define an event that will be fired when the temperature has reached or exceeded the warning level and subsequently falls below the warning level. So next, let's create a heat sensor class to implement the iHeatSensor interface. And we want to explicitly implement the events defined in our iHeatSensor interface for the heat sensor class. So one way we can do this is hover our mouse pointers over the red squiggly line under the iHeatSensor text, then select Show Potential Fixes, and then select Implement Interface explicitly. And now you can see Visual Studio has created our event implementations with add and remove accesses. Note that these add and remove accesses are very similar to the get and set accesses that are implemented for C# read-write properties. The add accesses will contain code that is fired when the client code subscribes to the relevant event. The remove accesses will contain code that is fired when a client unsubscribes to the relevant event. So we'll add code to the add and remove accesses in a bit. So one thing I forgot to do was include a method definition for running the heat sensor. Let's include the appropriate method definition in the iHeatSensor interface. And now you can see a red squiggly line under the iHeatSensor text in the class definition for the heat sensor class. This is because we are not implementing all the members of the iHeatSensor interface. So to fix this, we can hover our mouse pointers over the red squiggly line, click Show Potential Fixes, and then click Implement Interface. And you can see that Visual Studio generates a method implementation for the method that we had not yet implemented for the iHeatSensor interface, the runHeatSensor method. We'll implement code for the runHeatSensor method a bit later. Let's create two member variables at the top of the heatSensor class, both defined as double. The first member variable is named warning level, and the second member variable is named emergency level. These member variables will store values that serve as our triggers for when a relevant event should be raised. For example, if the temperature of the device rises above the emergency level, the appropriate emergency event is raised. So let's set these values within a parameterized constructor. So let's create a member variable named _hasReached warning temperature, and this is defined as the Boolean data type. We'll see the significance of this member variable in a bit. Let's create another member variable which will reference a collection of delegates associated with the events implemented in this class. We could use any of the appropriate collection classes in C# for storing these delegate objects, but we are going to use the built-in C# event handler list class for this purpose. So to use the event handler list class like this, we must include a directive to the system.componentModel namespace at the top of our code. As mentioned earlier, the event handler list class is a member of the system.componentModel namespace. We are going to use the event handler list class's addEventHandler method to add the appropriate delegates. The addEventHandler method accepts a key value of type object. For its first argument, this object value serves as a unique key for accessing values in the collection. And its second argument is a value of type delegate. The event handler list collection class allows the developer to store delegates that can be accessed within the collection using a unique key. We are also going to implement code using the remove event handler method to remove delegate objects from the relevant collection. The method definition for the remove event handler method is the same as the method definition for the add event handler method definition. Please navigate to this URL for more information on the event handler list class. So let's create 3 static read-only objects, which will serve as key values that can be used to access the relevant delegates from within the event handler list collection. Let's create another private member variable, which is an array of the double type, named _temperature data. So this array will store mock data to simulate data coming from the heat sensor at regular time periods. So this data will be used to simulate the heat sensor outputting temperature data. So let's create a method named seedData and populate the underscore temperature data array with data. Note that I'm deliberately including temperature data that is greater in value than 27, which will be used as our warning level. And toward the end, data that is greater in value than the emergency level, which will be set to a value of 75. This is so we can raise our events appropriately when the heat sensor outputs our mock values. Okay, so now let's implement the code for the add and remove accesses for the events that reside in the heat sensor class. So in the add accesses, all we want to do here is add the appropriate delegate to the event list handler collection, which is done at the point where the client code subscribes to the relevant event. So in the remove accesses, all we want to do is remove the appropriate delegate from the event list handler collection, and this is done at the point where the client code unsubscribes to the relevant event. You can see we are using the appropriate key objects when adding the relevant delegate to the collection. We are also able to use the appropriate key to remove the relevant delegate from our event list handler collection. So let's encapsulate functionality for raising the relevant events by creating 3 methods responsible for raising the relevant event for each of the events defined in the heat sensor class. Let's name the first method onTemperature reaches warning level. This method accepts one argument, which is our custom type named temperature event args. The temperature event args class is responsible for storing event data. Let's then write code to reference the relevant event using the underscore temperature reaches warning level key variable to reference the appropriate delegate within the underscore list event delegates object, which is derived from the event handler list class. When assigning the value stored in the underscore list event delegates collection object to the handler variable, we must typecast the delegate to the appropriate delegate type, which is the event handler delegate that accepts the temperature event args type as a generic parameter. Then we need to see if indeed the client code has subscribed to the relevant event. If the client code has subscribed, then the handler variable will not be null. So if the handler variable is not null, we can raise the relevant event by executing the handler delegate object and passing in the appropriate arguments to the handler delegate. The this keyword is the first argument which references the current object, which of course is an object of the heat sensor type. The second argument contains relevant event information and is of the temperature event args custom type. If you'll recall, we made provisions for storing the current temperature as well as the date and time of when the relevant event occurred in the temperature event args class. Right, and we can now repeat the same basic pattern for the other 2 methods responsible for raising the other 2 events declared in the heat sensor class. So let's implement a method to encapsulate raising the temperature falls below warning level event handler event. And let's implement a method to encapsulate raising the temperature reaches emergency level event handler event. And now let's implement a private method named monitorTemperature. This method simulates the heat sensor outputting temperature information for the device being monitored. So this method traverses the data stored in the underscore temperature data array, which contains our mock temperature data. Let's write code to display the temperature to the console screen each time a temperature is read from the underscore temperature data array. Then we can create an else-if ladder whereby we can compare the temperature output to the warning level and the emergency level. The emergency level has the highest value that will be evaluated, so this is the first value that will be evaluated. If the temperature is above the emergency level, the emergency event is raised. Else, if the temperature is above the warning level, but below the emergency level, the warning event is raised. Else, if the temperature was above the warning level and subsequently falls below the warning level, we can raise the temperature falls below warning level event. Note how we are using the underscore has reached warning level Boolean member variable to evaluate if the temperature falls below warning level event should be raised. The underscore has reached warning level variable must be set to true when the warning level reached event is raised so that the temperature falls below warning level event can be raised when the temperature subsequently falls below the warning level. When the temperature subsequently falls below the warning level, we must set the underscore has reached warning level variable to false. And for effect, I'm going to introduce a 1 second delay between iterations of the underscore temperature data array. As you can see, I'm using the system.threading.thread.sleep method for this purpose. I'm passing 1000 as an argument to this method. This value denotes 1000 milliseconds, which is 1 second. And let's finish off the heat sensor class by implementing code for the run heat sensor method. So we'll simply write the text heat sensor is running to the screen to indicate that the heat sensor is running. And then let's call the monitor temperature method. Okay, so let's create the interface for the cooling mechanism class. Let's keep this really simple. So this interface contains two method definitions, one named on and the other named off. As the names imply, these methods represent the behaviors of switching the cooling mechanism on and off. Let's create a class named cooling mechanism and implement the iCooling mechanism interface. And each method will simply write appropriate text to the screen. Let's create an interface named iDevice. This interface contains two method definitions, one named runDevice, the other named handleEmergency. We'll create the class that implements the iDevice interface in a bit, but let's first create a class to represent the thermostat. Let's first create an interface named iThermostat. This interface contains one method definition named runThermostat. Right, let's create a class named thermostat that implements the runThermostat method. Let's create a member variable of type iCooling mechanism. Let's create a member variable of type iHeatSensor, and let's create a member variable of type iDevice. Let's create two constants, one to store the warning temperature level, which is set to 27 degrees Celsius, and one to store the emergency temperature level, which is set to 75 degrees Celsius. Please note that these figures are arbitrary and serve only to help us with the code example. Let's create a parameterized constructor that accepts an argument of the iCooling mechanism type, an argument of the iHeatSensor type, and the iDevice type. We want the thermostat to have a reference to the device to which it is attached. Let's set the appropriate member variables to their counterpart arguments within the constructor. Let's create a method where we'll wire up the events contained in the heat sensor class. Let's name this method wireUpEvents to event handlers. So let's use the heat sensor object passed into the thermostat class to wire up all of the appropriate events. So to do this, we can write _heat sensor dot the event name, which is in this case temperature reaches warning level event handler, then followed by the += operator. Then we are able to press the tab key to auto-generate an appropriate method definition. Then we can rename the method if we choose and click the apply button to confirm the change. So let's write code to wire up the remaining events. So in the runThermostat method, let's add code to write that the thermostat is running. Let's call the wireUpEvents to event handler's private method. And lastly, let's call the run heat sensor method on the underscore heat sensor object. Let's write code for each of the client event handlers. So to handle the event, for when the temperature reaches or exceeds the warning level, let's first change the color of the font to dark yellow. Let's write warning alert. The warning level is between warning level and emergency level to the console screen. Let's then write code to switch on the cooling mechanism. Then when the temperature subsequently falls below the warning level, we want the font to change to a blue color. And let's write information alert, temperature falls below warning level is between warning level and emergency level. And then to handle the emergency event, let's change the font to a red color. Let's output emergency alert, emergency level is emergency level and above. And this event is handled slightly differently to the other event handlers because we are calling the underscore device object's handle emergency method. We are using the iDevice interface to handle the emergency event in the device object's code, which we'll soon implement. And we must make sure that each font color is reset after each event is handled. Okay, so now let's create a class to represent our device, i.e. the device that we are monitoring for temperature changes. Let's name it device, and within the class's definition, let's indicate that we wish to implement the iDevice interface. Let's hover our mouse pointers over the red squiggly line under the iDevice text, click Show Potential Fixes, and then click Implement Interface. And Visual Studio auto-generates implementations for the members of the iDevice interface for us. So let's implement code for the handle emergency method. And we'll simply write out a basic narrative of what should happen in the event of an emergency. So let's write sending out notifications to emergency services personnel to the console screen. And then in the event of an emergency, we also want to shut down the device. So let's create a private method named shutDownDevice. And this method simply outputs a narrative stating that the device is shutting down. Let's call the shutDownDevice private method from the handle emergency method. Let's implement code for the runDevice method. So let's simply output that the device is running to the console screen. Then we want to construct our objects for our cooling mechanism, heat sensor, and thermostat components. And we'll use their interface abstractions to define each of their types. And I've encountered a bit of a snag here when writing the code to construct the heat sensor object. We have already created the constants for the warning level and emergency levels in the thermostat class. I think these constants should rather be members of the device class and passed into the heat sensor class during the construction of the heat sensor object. So let's create the two relevant constants in the device class. And so that we can encapsulate the values of these constants and expose the values of these constants publicly, let's create two corresponding read-only properties. Let's first create definitions for these read-only properties in the iDevice interface. And then let's implement the code for these properties in the device class. And then within the thermostat class, which has a reference to the relevant device object, we can replace the references to the relevant constants that once resided in the thermostat class with references to the relevant read-only properties of the device object. Okay, let's then write the code to run the device from our main method. So let's write code to prompt the user to press any key to run the device. Then let's instantiate an object for the device. Then let's call the relevant object's runDevice method. Sorry, I know I'm jumping around here a bit. We still need to finish off the code for the runDevice method. Let's finish creating the thermostat object. Then let's call the object's runThermostat method. Let's run the code. And you can see by the status output the device is running, the thermostat is running, and the heat sensor is running. the temperature changes of the device can be seen with the output of each temperature to the console screen. A warning event is raised when the temperature exceeds 27 degrees Celsius. The cooling mechanism is then switched on. But there's an issue because when the temperature subsequently falls below 27 degrees Celsius, the relevant status is not being outputted to the screen. Instead, the code is raising the warning event. So let's investigate what is going on here. And the issue was caused, I think, because of all the copying and pasting. I forgot to change the call to the on temperature reaches warning level method to a call to the on temperature falls below warning level method. Obviously, a call to the on temperature reaches warning level method is inappropriate for the condition when the temperature has reached or is over the warning level and then subsequently falls below the warning level. So let's fix this issue and let's run the code. And that is a correct result. We can see the cooling mechanism is turned on when the temperature of the device exceeds the warning level. And when the temperature has been above the warning level and subsequently falls below the warning level, the correct event is raised. The correct status is therefore outputted to the screen in a blue font. And then the cooling mechanism is switched off. And we can see that all the events are firing correctly and being handled correctly. Toward the end, the emergency event is being handled correctly, which is in line with the mock temperature data that we created for this example. Great! I hope you have enjoyed this video on handling multiple events within a class, using the add and remove accessors. We also used the event handler list built-in C# collection class to add and remove the relevant delegates for when a user subscribes or unsubscribes to an event. Hi, and welcome to the third part of this tutorial on C# events. We have discussed that events can be triggered either by code logic or through a user's actions, for example, clicking a button. In the previous parts of this tutorial, we focused on events triggered by code logic. In this video, we'll focus on events triggered through user actions. So, in most of the tutorials provided by this channel regarding C#, the .NET Core Console App project template has been used as a starting point for creating the relevant sample code. This has been done deliberately so that we can focus on the language of C# and not be distracted by framework-related concepts. In this video, we'll do something a little bit different. We'll create a very basic code example, and we'll use the blank app Universal Windows project template to create the project responsible for the front-end functionality of our application. So we are going to develop a basic application using the UWP, or Universal Windows Platform Framework. This is so that we can look at how user actions, for example, a button click, can trigger events and how the relevant events can be handled appropriately in code. In this video, we'll show how a separation of concerns can be achieved whereby the front-end display functionality is loosely coupled with the back-end functionality. Specifically, we'll look at how events can be implemented to achieve this. So, one of the advantages that can be achieved by separating concerns is we can have one team that specializes in front-end design working on the look and feel of the application, and the back-end functionality can be developed by a completely different team. These two concerns can evolve independently from one another and in parallel to one another. The integration of the relevant components at an appropriate time can become a relatively trivial task. We are going to show how this loose coupling effect is achieved through the appropriate use of an event. A design pattern that can be used to achieve this loose coupling of front-end and back-end components is called MVVM, which stands for Model View, View Model. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you can be notified of future content released from this channel. Another advantage of implementing the MVVM design pattern to achieve this loose coupling of components is we are able to easily port, for example, the back-end functionality to other platforms. Let's say, for example, you have a particular app which is being distributed via the Microsoft Store. This app was written using the UWP framework. Let's say the app is selling really well. Marketing research tells us that there is a huge demand for this app to run on iOS and Android platforms. Time is a key factor in keeping the momentum of sales going for this application. So we want this app to be appropriated for iOS and Android platforms as soon as possible so that the app can be distributed via Apple's App Store for the iOS implementation of the app, as well as Google Play for the Android implementation of the app. So, we know that we can use the Xamarin technology to create a cross-platform app for iOS and Android devices. So, if we have designed our app appropriately using the MVVM design pattern, the back-end functionality that we have already created would not need to be recreated for the iOS and Android platforms. Please navigate to this URL for more information on Xamarin. A team specializing in Android and iOS front-end design could focus on the native front-end functionality for their respective platforms. Or the use of Xamarin Forms could also be utilized for the creation of the front-end design using XAML. We'll discuss XAML in a bit. The back-end code already created for the UWP version of the app can be reused for the Android and iOS apps created using the Xamarin technology. For more information on Xamarin Forms, please navigate to this URL. The appropriate use of the MVVM design pattern could make the integration of the front-end functionality with the back-end functionality a relatively trivial task. The details of MVVM are beyond the scope of this tutorial. Please navigate to this URL for more detailed information about MVVM. Model View, View Model. UWP stands for Universal Windows Platform. So a UWP application can run on any Windows device that runs Windows 10 or Windows versions greater than version 10. Windows 11 is due to be released on July the 29th, 2020. These devices can include PC, tablet, Xbox, HoloLens, Surface Hub, and Internet of Things devices. So we are not going to go into depth regarding the Universal Windows Platform. UWP demands an entire course on its own. If you want to learn more about Universal Windows Platform, please navigate to this URL. But let's look at a very basic example of loosely coupling back-end functionality from front-end functionality using events on the Universal Windows Platform. So let's create a project based on the blank app Universal Windows project template. Let's name this project and solution Employee UWP App. So once we click the Create button, we are prompted with a dialog box where we are able to choose the minimum version and target version that our UWP application will support. So to aid us with our decision, let's click on the link labeled Which version should I choose?, which is available in the bottom left-hand corner of the relevant dialog box. So we are presented with a web page, and at the end of the first paragraph on the web page it states, projects using .NET Standard 2.0 must have a minimum version of build 16299 or later. So we are going to develop our backend functionality using .NET Standard 2.0. So let's choose version 16299 from the drop-down list labeled Minimum Version. Right, let's add a standard library project to our solution. And let's name it Employee Component. This library will contain our backend functionality. So firstly, let's reference our Employee Component project from our UWP project. So let's right-click the References node within our UWP project and add a reference to the Employee Component project. Okay, let's delete the class that has automatically been generated. Let's create a class that will serve as our view model, and let's name this class Employee View Model. As the name suggests, a view model represents the data that will be displayed to the user. Let's make this class a public class. Let's write code so this class implements the iNotifyPropertyChanged interface. We must include a directive to the system.componentModel namespace. The iNotifyPropertyChanged interface is a member of the system.componentModel namespace. So to do this, we can hover our mouse pointers over the red squiggly line, click Show Potential Fixes, and then click Using System.componentModel. This interface contains an event that is key to how we can achieve a loose coupling between the backend component and the UWP frontend component that we'll soon develop. So, to implement the iNotifyPropertyChanged interface, let's hover our mouse pointers over the iNotifyPropertyChanged text, which has a red squiggly line under it, and click Show Potential Fixes, and then let's click Implement Interface. Note that a public event named PropertyChanged, which is defined as the delegate type PropertyChanged event handler, is generated for us. This event will be raised to the front-end code when a relevant property value in this class is changed. This example is going to be simplistic so that we can focus on the core concepts of this video, namely how events can be used to achieve a loose coupling between front-end and back-end components. So let's create a read-write property named firstName, and let's create a private member variable named _firstName. Let's encapsulate the _firstName private member variable within the firstName property. And within the set accessor of the firstName property, let's include code to raise the PropertyChanged event. So if the firstName property is changed, we want to raise the PropertyChanged event, which will have the effect of notifying the front-end view presented to the user that the relevant field must be changed on the front-end display, so that the change in value of the property is presented to the user. And this is a key concept to understand. When the view model is changed, the event notifies the actual view presented to the user of the change, and the change is then reflected in the view presented to the user. So the view presented to the user is never directly changed, for example by referencing an element of the view presented to the user. The underlying view model, which is part of the back-end code, is changed, and this change is propagated to the view presented to the user through the implementation of the PropertyChanged event. We'll demonstrate later on how the UWP front-end component subscribes to the PropertyChanged event to receive notifications when a relevant property value changes. Let's wrap the relevant functionality that raises the PropertyChanged event in a private method, and let's name this method NotifyPropertyChanged. Notice that this method accepts a string argument which will contain the name of the property that is changed. So now, within the set accessor of the firstName property, let's write code to call the NotifyPropertyChanged private method for when the firstName property is changed. And let's create auto-implemented properties for the other employee fields: ID, last name, annual salary, gender, and is manager. Let's create a class named Employees. We are going to be storing the employee view model objects in a generic collection type called an observable collection. The observable collection type represents a dynamic data collection that provides notifications when items get added, removed, or when the whole list is refreshed. For more information about the observable collection class, please navigate to this URL. So firstly, let's include a directive to the system.collections.object model namespace. The generic observable collection class is a member of this namespace. This class will simply contain a method that returns a collection of employee records. Let's create a public method named getEmployees. We want this method to return a collection of employee data. So the getEmployees method returns an object of type observable collection. The observable collection is a generic collection type, and we are able to strongly type the collection with the employee view model type. So let's include code within this method that creates a new observable collection object and assign the relevant object reference to a variable named employees. Let's write code to return the employees object. And I've made up some employee data for our employee view model objects that we can add to the observable collection object we have named employees. So to save time, let's navigate to a GitHub repository where I have already uploaded the code for this tutorial. So please navigate to this URL. Let's select the relevant code that adds the employee data to the employees observable collection and appropriately paste it into our code editors. We could have written code to retrieve this data from a data source, like for example a SQL Server database, but in the interests of keeping this code sample simple, we are using mock data as a substitute. The observable collection object represents a dynamic data collection that provides notifications when items get added, removed, or when the whole list is refreshed. We are going to use our observable collection type, which is strongly typed to store objects of type employee view model, to bind our collection of employee view model objects to a list view that we'll create in our front-end design when we develop the UWP component. Okay, so let's develop our UWP component. So the user interface for a UWP application is created using a declarative markup language named XAML, which stands for Extensible Application Markup Language. We are not going to go into the details of XAML in this tutorial, but here's a basic explanation of what XAML is. In a UWP application, XAML is used to define UI elements, data bindings, events, and other features. XAML elements map directly to Common Language Runtime object instances, while XAML attributes map to Common Language Runtime properties and events on those objects. For more information on XAML, please navigate to the following URL. So as mentioned earlier, I have already uploaded the relevant code sample to GitHub. In the interests of time, let's copy the relevant XAML from GitHub, and then we'll paste the XAML code over the XAML currently in the mainpage.xaml file. Right, so let's navigate to this URL. Let's copy all the XAML code from this page to our clipboards. And let's paste the XAML code in our clipboards over the XAML code currently in our mainpage.xaml file. And if we look at the XAML code, here you can see a blue squiggly line under the code where we are binding a list view data template element to the employee view model type. The reason for the blue squiggly line is because we need to compile the employee component so that our UWP project is referencing the relevant latest compiled assembly. So let's compile the employee component. And the blue squiggly line goes away. Great. And we can also see a design view rendering of our XAML code. If we take another look at the XAML code, you can see that the data binding functionality in the first name field includes a mode attribute which is set to the value of one way. This is an important part of the functionality that allows changes to the first name property of our employee view model objects to be reflected in the relevant list view displayed to the user. So in our code example here, we are demonstrating one-way binding from the view model to the list view element of the view. Let's write the code in the code behind file named mainpage.xaml.cs. The code we are going to write here will enable the user to select an employee record from the list view that is created through the XAML code, which will contain a collection of employee records. The user will then be able to dynamically change the first name field for the selected employee record by typing the new first name value into a text box and clicking a button to confirm the change. Let's create a member variable named _employeesOC, which is of the observable collection generic collection type and is strongly typed with the employee view model type. Let's create a public field named changeFirstNameCommand. This is a public field and is defined as the XAML UI command type. For more information on the XAML UI command type, please navigate to this URL. Let's write the code in the constructor of the main page class. Let's create a new object of type employees. So let's take a quick look at the XAML code. And you can see here, we have a list view named employee list. And you can see that there is data binding markup to bind the fields in the list view named employee list to each of the fields defined in our employee view model type. So let's go back to the mainpage.xaml.cs class. And let's write code to bind the data stored in the _employeesOC observable collection object to the employee list view. Note that the item source property in the employee list view is set to the _employeesOC observable collection. So let's go back to the XAML code. Notice here we have a button named btn change first name that contains an attribute named command. And this code is binding the btn change first name button to the public field named change first name command that we defined as the XAML UI command type in the main page class. Also notice that the command parameter attribute includes code that binds to the employee list view element. So let's go back to the mainpage.xaml.cs class and let's create a new XAML UI command object for the change first name command public field. And let's use the += operator to subscribe to the execute request event on the change first name command XAML UI command object. So after we have typed the += operator, we can press the tab key and a method with the appropriate method signature is generated for us. So when the user clicks the button named btn change first name, the code in this method will be invoked. So let's write the code for this method. Firstly, let's write code to get a reference to the employee list view object. We can use the args.parameter property to get a reference to this object. We must typecast this object to the list view type. Then let's write code to check if an item in the list view has been selected. If an item has not been selected, the selected index property will be -1. So if this selected index property is not -1, we can use the relevant list view object's selected index property to index the underlying observable collection object. And we want to set the relevant item's employee first name field to whatever the user types in the relevant text box. If we look at the relevant XAML markup code, we can see that a text box element is included in our markup. This text box can be used to rename a selected employee's first name field to whatever the user types in the relevant text box. So let's run the code. So the employee list view is not populating. Let's investigate why this is occurring. Okay, so we haven't included the code to assign the relevant observable collection object named underscore employee OC with a value returned by the employees class's getEmployees method. The getEmployees method populates the observable collection object with objects of the employee view model type and returns the relevant observable collection object to the calling code. So to fix the issue, let's write the code to assign the underscore employee OC variable with a value returned by the employees.getEmployees method. Let's run the code again. Great. That has resolved the issue. We can see that our list view is populated with employee view model data. Okay, so let's select the third record, and in the text box here, let's type Bob, and then press the button that is wired up to our change first name command object. And let's repeat the same process for some of the other employee records. Great. We are now able to change the employee record's first name field on the front-end display by updating the underlying observable collection. Note that the code is not updating the employee list view object directly. When the relevant underlying observable collection is changed, an event notifies the employee list view object of this change, and the relevant changes are reflected on the front-end display. If we look at the change first name command underscore execute request method that gets invoked when the btn change first name button is clicked, we can see that the underlying observable collection object is changed and the employee list object is not directly changed. This highlights the decoupling of the UWP front-end component from the employee component, which is responsible for data handling and business rules. For example, when the first name field was changed for the third employee record, the property changed event, which is a member of the iNotifyChanged property interface, was fired, signaling to the front end that there has been a change to the first name field in the relevant employee view model object, which must be reflected in the relevant list view front-end object. And just for fun, let's include code to make our application speak to the user. So I've already prepared the code that will make our application talk to us in the relevant GitHub repository. So let's navigate to this URL. Let's copy the speak async method to our clipboards and paste it into the mainpage.xaml.cs file. This method includes an asynchronous method call to the synthesized text to stream async method. In order to call the speak async method that we have just included within our code, we must appropriately include the async and await keywords. I'm also going to make a minor change in that I'm going to rename the underscore employee OC variable to underscore employees OC so that the code we have just created is consistent with the code in the relevant GitHub repository. Let's run the code.
Changing first name from Bill to Bob. Changing first name from Jamie to Don. Changing first name from Sally to Debbie.
Excellent. So to summarize, this code that we have just created shows how the iNotifyChanged interface and the generic observable collection can be implemented to loosely couple the front-end component from the relevant code within the back-end component. This loose coupling effect has many advantages, which can include reuse of components across disparate platforms, For example, let's say we have an initial application written to run on multiple Windows devices through the use of the appropriate UWP project template, and then at a later stage, we decide that we want this application to run on iOS and Android platforms. The component responsible for the implementation of business rules and data handling written using the standard library project template can be easily ported to run on the Android and iOS platforms without the need to change the relevant code. We do not need to rewrite this code for the Android and iOS platforms. Separation of concerns allows separate teams to work independently from one another. For example, the front-end XAML experts, or as the case may be, the Android and iOS front-end developers, could focus on the look and feel of the application and the user experience of the application, while not having to worry about the details of the business rules and the database handling functionality. A separate team that specializes in writing the business rules and database-related functionality can focus on this concern without worrying about the implementation detail of the front-end design. The front-end and back-end functionality can evolve independently from one another and in parallel to one another. The front-end and back-end components can then be seamlessly integrated with one another at an appropriate time. I hope you have enjoyed this tutorial on events raised through user actions in the context of a UWP application. UWP is a very powerful platform that can be used for creating rich user interfaces that can run on multiple Windows devices. Examples of related Windows-specific frameworks include WPF, or Windows Presentation Foundation, and WinForms. If you want to learn more about WPF, please navigate to this URL. And if you want to learn more about WinForms, please navigate to this URL. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of new releases from this channel. If you feel you have gained value from viewing this video, please hit the like button and please feel free to share any of the videos released from this channel with anyone you feel may benefit from their content. As always, the code created in this video can be downloaded from GitHub. A link to the relevant repository has been included below in the description.
Thank you, and take care.
Hi and welcome to the fourth part of this tutorial on C# events. This video is also part of a tutorial that serves as the fourth part of an advanced C# course. In this video, we'll focus on the observer design pattern. This is a very powerful design pattern and is suitable for any scenario that requires push-based notifications. The implementation of the observer design pattern entails subscribers registering to receive notifications from a provider. Push notifications simply means that the notifications are pushed from a central point to the relevant subscribers. The source of the push notifications is known as the provider, also known as the observable. Observers register with the provider, in other words, subscribe to the provider, and whenever a predefined condition, event, or state change occurs, one of the observer's methods is called by the provider. In this method call, the provider can also provide current state information to observers. So note that the observable can also be referred to as the provider, and observers can also be referred to as subscribers. So I'll be using these terms interchangeably throughout this tutorial. For more content like this on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future releases from this channel. In .NET, the implementation of the observer design pattern can be achieved when the subscribers class or observers implement the generic system.iObserver generic interface and the provider class implements the system.observable generic interface. The generic type represented here with the capital T represents the type, which can be a user-defined type that encapsulates the notification information communicated from the provider to its subscribers through push notifications. So the generic type, represented by the capital letter T in the interface definitions of both the provider class and the subscriber classes, is key to how loose coupling between provider and subscribers can be facilitated while still enabling rich and extensible data to be pushed from providers to subscribers. The system.iObservable and system.iObserver built-in .NET generic interfaces enable this pattern to be reused for multiple scenarios. The generic type represented by the capital T allows for user-defined types to serve as communication vehicles that can be extended without breaking the design of the relevant application. So let's look at a quasi-real-world example that can be used to explain the observer design pattern and give us an idea of when it is appropriate to use this design pattern. So we'll have to use our imaginations a bit to picture this example. Let's say a particular company owns a building with an automated security system. One of the functions of this security system is to identify external visitors arriving at the building, for example, to have a business meeting with one of the employees that work inside the building. So the process first involves the external visitor registering to visit the relevant employee on a particular day. Let's say that before an external visitor arrives at the building for the relevant visit, the external visitor must first register and during the registration process provide a clear photograph of the external visitor's face as part of the registration process. So when the external visitor arrives on the day of the visit and attempts to enter the building, a camera first scans the external visitor's face and subsequently sends the relevant pictorial facial information to a system whereby biometric artificial intelligence algorithms are applied to ascertain whether this particular visit can be authenticated, i.e., has this person registered, and if so, can this person be verified as the person claims to be? So this is essentially an automated authentication process. Once the relevant visitor has been identified, the visitor is automatically given access to the building. This triggers notifications to be sent to the building's security team and any internal staff members, i.e. employees of the company that owns the relevant building, who have subscribed to receive notifications regarding the relevant actions of the external visitors. The information that is sent to the subscribers, i.e. the notification data sent from the provider, contains information about the relevant external visitor and the time the relevant external visitor gained access to the building, and then subsequently, once the visit is completed, a notification is sent when the external visitor exits the building. Another notification will be sent to all subscribers from the provider when a predefined time is reached and all external visitors have exited the building. For example, the predefined time could be 6 p.m., which has been deemed the end of the working day for the relevant company. The rule could be that after this time, no external visitors can gain access to the relevant building. In this example, we'll refer to this time as the cutoff time. Okay, so as I've said, we need to use our imaginations a bit here because we are going to implement code for the scenario just described within a console app.NET Core framework. In other words, the code will be highly simplified so that we can focus on understanding the observer design pattern. So the provider in this example will be the security surveillance system used to identify external visitors that have registered to visit a member of staff within the relevant building on a particular day. This example will contain two types of subscribers. One of the types of subscribers that we will create will represent the security team. They must be notified of all significant movements of external visitors, for example, entering and exiting the building. The other type of subscriber will represent any individual internal staff member who has subscribed to receive relevant notifications regarding external visitors. This employee would subscribe because a visitor must have a point of contact inside the building in order to successfully register as an external visitor. When the external visitor is authenticated on the day of the visit, a notification will be sent to the security team as well as any employee who is registered as the point of contact for the relevant external visitor. Okay, let's look at an overview of the main classes that will be created for this example. So here is a class that represents the observable. This class will represent a central place where surveillance data is processed. We'll create two classes that represent two types of observer. The first class represents an employee, i.e. a person that works inside the relevant building, who wants to be notified when a particular external visitor enters the building. This class is named Employee Notify. The second class represents the security team, who must be notified when any external visitor enters or exits the relevant building. This class is named Security Notify. We have a class here named External Visitor, which represents an outside visitor to the relevant building. This class serves as the generic type argument to both the IObservable generic interface implemented by the observable class, as well as the generic argument to the IObserver generic interface, which is implemented by the observer classes. So this class allows data about the external visitor to be communicated from the observable object to its observer objects when the relevant notifications are sent. We have an iEmployee interface and an employee class that implements the iEmployee interface. The employee class provides a way to store details about an employee who works inside the relevant building. This class represents the employee details of a person who serves as a point of contact for an external visitor. An employee object is passed into the constructor of the employee notify class during the instantiation of an object derived from the employee notify class. So in summary, here are our main classes: employee notify, an observer class; security notify, an observer class; security surveillance hub, the observable class; iEmployee, an interface defining an internal staff member record; employee, a class that implements the iEmployee interface, so it represents an employee record; external visitor, a class representing the person that has registered to visit a member of staff that works inside the relevant building. This class represents a person that must be authenticated on the day of the relevant visit. Let's look at the class that will serve as our observable class. We'll name this class Security Surveillance Hub. This class represents a central location where surveillance system information is processed and will be responsible for notifying subscribers with the relevant information about an external visitor. So notifications will be sent to the relevant observers when an external visitor enters the building, and another notification will be sent to the relevant observers when an external visitor exits the building. Firstly, let's answer the question, how can we implement a class so that it can be instantiated as an observable object? The answer to that question is that a class that will be instantiated as an observable object must implement the IObservable generic interface. The IObservable generic interface is a built-in .NET interface that is a member of the system namespace. The next question is what makes the observable interface a generic interface? The IObservable interface is generic because the calling code is able to pass a type as a generic argument to a class that implements the IObservable generic interface. In our example, the type that we'll pass as the relevant generic type argument will be a user-defined type named external visitor. As you may have guessed, this class will represent an external visitor. We'll discuss the external visitor class in more detail a bit later. The IObservable generic interface contains one method definition. This method definition is for a method named subscribe. The subscribe method contains one parameter of a type that implements the IObserver generic interface. So this parameter is defined as an observer type. We'll discuss the IObserver generic interface a little bit later. So the subscribe method must be implemented by the type that implements the IObservable generic interface. The implementation of the subscribe method must contain functionality that is executed when an observer subscribes to receive notifications from the relevant observable object. So we've now looked at the essence of what we are trying to achieve here by implementing the observer design pattern. Let's get started and create the code example. Let's create a project based on the console app.NET Core project template. Let's name this project and solution Building Surveillance System Application. So for our first class, let's create a class that represents the external visitor. This class represents the information about an external visitor that will be sent to the relevant subscribers when an external visitor enters the building and subsequently exits the building once the external visitor completes the external visitor's visit. So let's create a public class and name it external visitor. Let's create the properties for the external visitor class. So let's create a property for ID defined as int, first name defined as string, last name defined as string, company name defined as string, job title defined as string, entry date time defined as date time. This property will store the date and time of when the relevant external visitor entered the building. Exit date time defined as date time. This property will store the date and time of when the relevant external visitor exited the building. And lastly, an auto-implemented property named employee contact ID, and let's define this property as int. This property facilitates the storage of the ID of the internal employee, i.e. an employee who works within the building, responsible for being the point of contact for an external visitor on the relevant day of the external visitor's visit. Great, and that is our external visitor class. So let's create our observable class. Let's create a public class named Security Surveillance Hub. As explained earlier, this class serves as a metaphor for a central location where security-related information is processed. So, for example, an external visitor's face is scanned before gaining access to the building, and this pictorial information is subsequently sent to the Security Surveillance Hub, where the biometric information in the relevant image is compared against registered image information captured when the external visitor registered to visit the building. So if the two pieces of information match, the visitor is granted access to the building, which will trigger notification information about the external visitor to be sent to the relevant observers. So as discussed earlier, in order for this class to represent our observable, it must implement the iObservable generic interface. So let's write the code to do this, and let's pass in the external visitor type as our generic type argument. What makes the iObservable interface a generic interface? It is a generic interface because we are able to strongly type the iObservable interface. The capital T within less than and greater than symbols in the iObservable interface definition means that we are able to replace the T with our C# type. When this is done, it means we have strongly typed our generic interface. So let's strongly type the iObservable interface with our external visitor class like this. Generics allows us to stipulate a particular type for the relevant type placeholder at compile time. Note that a capital T is commonly used to represent the generic type placeholder. Generic functionality can also be accomplished through the use of the .NET system.object type. As we know, all types in C# ultimately inherit from the system.object type. So we are able to typecast a variable at runtime to any managed .NET type. The advantage of using generics for the same purpose is that we can achieve the same functionality, but this is done at compile time. This provides the advantage of compile time type checks, ensuring type safety, as well as results in greater performance for our code because we are able to omit the need for runtime typecasting. Typecasting, which is performed at runtime, also carries the risk of incurring runtime errors. Please don't worry if you didn't understand this brief explanation of why generics is significant. Generics will be discussed in detail in upcoming tutorials. So let's develop the Security Surveillance Hub class. So you can see that there is a red squiggly line under the iObservable text in the class definition. This is the C# compiler letting us know that we have not yet implemented code for the member definitions of the iObservable generic interface in the Security Surveillance Hub class. So let's hover our mouse pointers over the red squiggly line, click Show Potential Fixes, and click Implement Interface. As you can see, there is only one method definition in the iObservable interface that we must implement in the Security Surveillance Hub class. This method is named subscribe. Notice how the subscribe method definition contains a parameter of type iObserver, and the iObserver parameter type definition is automatically strongly typed with the type definition with which we have already strongly typed the iObservable interface. So we have strongly typed the iObservable interface with the external visitor type, and this has propagated to the subscribe method definition when we automatically generated the method definition that is contained in the iObservable generic interface, i.e. the subscribe method definition. This is a key concept to understand when understanding how we are able to use the iObservable and iObserver generic interfaces to implement the observer design pattern. The generic type gives us a means for creating a loose coupling between the observable component and the relevant observer components. The generic type, both defined in the iObservable and iObserver interfaces, allows the developer to strongly type these two interfaces with a common type. In this example, we are strongly typing these two interfaces with the external visitor user-defined type. This will become clearer as we develop this example application. Right, let's implement the code for the Security Surveillance Hub class. So let's create two member variables. Both of these member variables are of the generic list type. Let's define the first one and name it _external visitors. As the name suggests, this list will store a list of external visitors. When an external visitor gains access to the building, the external visitor is added to the _external visitors list. And you can see that we are strongly typing the _external visitors list with the external visitor user-defined type. Let's include a directive to the system.collections.generic namespace. The second generic list we need to define will store a list of observers. So this list will contain objects that are derived from the iObserver generic type that is strongly typed with the external visitor user-defined type. Let's name this generic list variable _observers. So when an observer subscribes to receive notifications from the observable, the relevant observer is added to the _observers list. Conversely, if an observer unsubscribes, the relevant observer is removed from the _observers list. So the subscribe method will be the last method that we will implement. As discussed, the subscribe method has to be implemented because it is a member of the iObservable generic interface, which the Security Surveillance Hub class implements. For now, let's create a public method that gets called when an external visitor gains access to the building. Let's name this method confirm external visitor enters building. This method's parameters contains relevant information associated with an external visitor, namely ID defined as int, first name defined as string, last name defined as string, company name defined as string, job title defined as string, entry date time defined as date time, and employee contact ID defined as int. Then we can write the functionality to instantiate an external visitor object and set the properties of the object we have derived from the external visitor user-defined type with the values that will be passed as arguments to the confirm external visitor enters building method. Then let's write the code to add the newly created external visitor object to the _external visitors list. As mentioned, the _observers list is populated with observers. Observers are, of course, objects that have subscribed to be notified when certain conditions are met, for example, an external visitor entering the building. So this method represents an external visitor entering the building. The visitor has been authenticated and is automatically given access to the building. So let's use our imaginations, and let's say that when an external visitor enters the building, the framework in which our observable exists invokes the confirm external visitor enters building method. The observable can now notify all subscribers of this event, as well as send the relevant data pertaining to the event to all the relevant subscribers. In this particular example, the relevant data is encapsulated with the external visitor object, which is derived from the external visitor class. Remember, the iObserver generic interface is strongly typed with the external visitor user-defined type, which makes it easy to send the data to the relevant observer objects. The relevant observer objects are stored within the _observers list. So in order to notify the relevant observers with the relevant data, we can write code to traverse the _observers list and call each observer object's onNext method. Note that when we call each observer object's onNext method, we are passing the relevant external visitor object as an argument to the onNext method. This is how each observer receives notification data whenever the relevant event occurs. In this example, the relevant event is an external visitor gaining access to the relevant building. So how does the observable, i.e. an object derived from the current class we are creating, know that an observer object implements a method named onNext? And even further to that, how does the relevant observable object know that the onNext method accepts an argument of type external visitor? This is at the heart of how the observer pattern works in C#. Each observer object is derived from a class that implements the iObserver generic interface. If we look at the definition for the iObserver interface, we see three method definitions, namely onNext, onError, and onCompleted. The onNext method contains a parameter of a generic type. So when we create an observer class a bit later, we'll strongly type the iObserver interface that our class must implement with the external visitor user-defined type. This action will mean that the onNext method will be strongly typed with the external visitor user-defined type. So the external visitor type becomes a common communication facility between the observable and the relevant observers. So the fact that we know that each observer implements the iObserver generic interface means we know that each observer object implements a method named onNext. The fact that the iObserver interface for each observer class is strongly typed with the external visitor user-defined type means that we know the type of the argument that needs to be passed into the onNext method. The iObserver generic interface contains a definition for a method named onError. This allows for the observable to notify relevant observer objects if an exception occurs, and also provides information about the exception through the built-in exception type. We are not going to implement custom functionality for the onError method in this example. Each observer object must, however, implement code for the onError method because the definition for the method is contained within the iObserver generic interface. The last method that we need to talk about is the onCompleted method. So we will be implementing custom code for the onCompleted method in this example. The onCompleted method does not contain any parameters. The onCompleted method notifies the observers that the observable has finished sending notifications. So this method should be called for each observer when a condition is met, whereby no more notifications need to be sent to the relevant observer objects. In this example, the onCompleted method will be called on all observer objects within the _observers list when the relevant cutoff time has been reached on a particular day and all external visitors have exited the building. The cutoff time could be, for example, designated as 6 p.m. There may be external visitors who exceed this time constraint due to, for example, a meeting that goes on for longer than expected, or something of that nature. So two conditions need to be met for the onCompleted method to be invoked. A certain time in the day is reached, for example 6 p.m., and all external visitors have exited the building. So next, let's implement a method that is called when an external visitor exits the building. So let's name this method confirm external visitor exits building. This method is a public method that contains two parameters. One parameter, which is a value that serves as a unique identifier for an external visitor. It is defined as the int data type. The other parameter is named exit date time, and as the name suggests, this parameter denotes the date and time when an external visitor exits the building. So firstly, let's write code to find the external visitor within the _external visitors list. If the external visitor is not null, i.e. the external visitor is found within the underscore external visitors list, let's write code to update the relevant external visitor object's exit date time property to the date and time when the external visitor exited the building. Let's then write code to traverse the underscore observers list and call each observer's onNext method, and pass an argument to the onNext method of the relevant external visitor object to notify the observers that a specific external visitor has exited the building. So let's create another public method that will be called when the cutoff time is reached. So by cutoff time, I mean this is a time after which external visitors are not allowed to enter the building. So we need to use our imaginations for some of these methods because we are basically saying that this method is called when certain conditions are met. In this case, when a certain time in the day is reached. Just like, for example, when the external visitor enters the building, the confirm external visitor enters building method is invoked, or when the external visitor exits the building, the confirm external visitor exits building method is invoked. So let's create a public method that will be executed when the visitor cutoff time is reached. Let's name this method building entry cutoff time reached. So this method is called at a particular time, but we only want to call each observer's onCompleted method if all external visitors have left the building. The fact that the onCompleted method is called means that no further notifications will be sent from the observable object to the observer objects for a particular day. So we are going to use the LINQ technology to check if any external visitor objects exist within the underscore external visitors list. But first I'm going to extend the external visitor class to include a property named inBuilding. This property is of type Boolean, and we can set this property according to the external visitor's current location. So we want to set the inBuilding property value to true when the confirm external visitor enters building method is invoked. Conversely, we want to set the inBuilding property value to false when the confirm external visitor exits building method is invoked. So we can now use the inBuilding property value to check if there are still external visitors left inside the building after the cutoff time has been reached. If you don't fully understand this code, don't worry, LINQ will be discussed in detail in upcoming tutorials as part of this C# advanced course. If the count of external visitor objects within the underscore external visitors list that have their inBuilding property value set to true is equal to 0, this means that the cutoff time has been reached and all external visitors have exited the building, so we can now call the onCompleted method on all the observer objects that are currently in our underscore observers list. By calling the onCompleted method on these observer objects, this is notifying the relevant observers that no further notifications will be sent. Okay, let's implement the subscribe method. So notice that the subscribe method contains a parameter of type iObservable, which is a generic interface. The implementation of the iObservable generic interface in this class, i.e. the Security Surveillance Hub class, is strongly typed with the external visitor user-defined type. So this is automatically propagated through to the subscribe method definition, where the iObserver generic interface is also strongly typed with the external visitor user-defined type. Note that when an observer object subscribes to the observable object, the observer object passes a reference to itself into the subscribe method. The this keyword can be used for the purpose of referencing an object derived from the class in which the this keyword is implemented. We'll implement this code when we create the observer classes in a bit. For now, let's implement the code for the subscribe method. And the code for this method is pretty simple. We first check if the observer object exists within the underscore observers collection. If the observer object does not exist within the underscore observers list, this means that a new observer object is subscribing. So we can write code here to add the observer object to the underscore observers list, which means that the relevant observer is now subscribed. The subsequent lines of code traverse all the external visitor objects within the _external visitors list and notifies the new observer object of the current information related to external visitors that exist within the _external visitors list. Now notice that the subscribe method returns a type that must implement the built-in iDisposable interface. So we are now going to create a class named unsubscriber, and this class will implement the iDisposable interface. As the name suggests, the purpose of the unsubscriber class is to provide a facility for the observer objects to unsubscribe to the observable object, i.e. to elect to no longer receive notifications from the relevant observable object. The unsubscriber class implements the built-in iDisposable interface, which contains a definition for a method named dispose. When an observer object calls the dispose method, this action causes the relevant observer object to unsubscribe from the relevant observable object. So you can see that the subscribe method in the observable class, in this case the observable class is the class named Security Surveillance Hub, allows for an observer object to subscribe to the relevant observable object. The subscribe method returns a reference to the relevant unsubscriber object, which is derived from the class that we're about to create, i.e. the unsubscriber class that implements the iDisposable interface. The observer object can simply call the dispose method, which is a member of the iDisposable interface, to unsubscribe to the relevant observable object. The built-in iDisposable interface is a member of the system namespace. Let's create the unsubscriber class. As mentioned, the unsubscriber class implements the iDisposable interface, which contains a method definition for a method named dispose. So let's create the class definition for the unsubscriber class. Let's indicate that we wish to implement the iDisposable interface. Let's ensure that we are implementing all the members of the iDisposable interface. The iDisposable interface contains one member, a method named dispose. Let's create the constructor. You can see that this constructor contains two parameters. The first parameter is a list that contains observer objects. The second parameter is an observer object. So the functionality for this class is literally just to remove the passed-in observer object from the relevant observers list. So let's create two member variables. These member variables will be appropriately assigned the passed-in arguments to the constructor. Then the logic within the dispose method is simply to check if the relevant observer object exists within the relevant observers list. If it does, remove the relevant observer object from the observers list. The result of this action is that the relevant observer is unsubscribed from the relevant observable object and will therefore no longer receive notifications from the observable object. So let's go back to the subscribe method in the Security Surveillance Hub class, and let's return a new unsubscriber object derived from the user-defined type that we have just created. Note that the construction of the unsubscriber object entails passing a reference to the relevant observer and a list of all observers currently subscribed. Okay, so we have now written the code for the observable object. The class that defines the observable object is the Security Surveillance Hub class. So we can now create the classes that will represent our observer objects. We are going to create two classes which represent two types of observer objects. The first type we'll create is a class named Employee Notify. This class will represent an employee, a staff member that works in the building, that has been designated as the contact point for an external visitor. So this employee wants to know when the relevant external visitor has entered the building so that the employee can welcome the relevant external visitor at the entrance of the building. The second type or class will represent the security team, which must receive details of the external visitor when the external visitor enters the building and later exits the building. So let's first create code for the Employee Notify class. This class is an observer, so it must implement the generic iObserver interface. We also need to strongly type the iObserver generic interface with the external visitor type. So one way we can automatically generate the definitions for the members of the iObserver interface that we must implement is to hover our mouse pointers over the red squiggly line under the iObserver generic interface text within our class definition and click Show Potential Fixes and then click Implement Interface. And Visual Studio automatically generates default implementations for 3 methods. The method definitions for these 3 methods are members of the iObserver generic interface. The red squiggly line disappears because we now have implementations for the members contained in the iObserver generic interface. So in a bit, we'll implement more useful code for these methods. Before we create a constructor for this class, I want to create a definition for an employee record. Let's create an interface named iEmployee. We'll keep the employee record really simple. So let's create definitions for just 4 properties. ID as int, first name as string, last name as string, and job title as string. Let's create a class named employee that implements the iEmployee interface. So let's go back to the employee notify class and create the constructor for this class. So when an object is created from the employee class, we want an employee object to be passed into the constructor of the employee notify class. So let's include a parameter of the iEmployee type within the constructor definition. We want to adhere to solid principles. The last letter in the solid acronym is dependency inversion principle, which states that classes should not depend on concrete implementations, but should only depend on abstractions. This is why the parameter within this constructor is defined with an interface type rather than a class. So we are defining this parameter of type iEmployee rather than of type employee. Very basically, SOLID is an acronym representing a set of principles that are design principles that can be followed in order for a programmer to develop software that is easy to maintain and extend. We'll discuss SOLID principles in detail in upcoming tutorials. SOLID principles serve as a foundation for object-oriented design patterns, like, for example, the observer design pattern. These design patterns can be implemented to solve problems that have been repeatedly identified in real-world scenarios. If you wish to read more about SOLID principles, please navigate to this URL. So let's create an appropriate member variable of the iEmployee type, and within our constructor, let's assign the passed-in value to the member variable we have just created. So let's implement our code logic for our onNext method. Notice that the parameter contained within this method is of type external visitor. When we automatically generated our default method implementations through Visual Studio, the fact that we had strongly typed the iObserver interface with the external visitor user-defined type propagated through to the onNext method. So the purpose of the onNext method is that it gets called by the observable object every time it is appropriate to send out notifications to the relevant observers. This is how the observable object is able to send out notifications to each of its subscribed observer objects, because the observable object knows that each observer object implements the onNext method. So the observable object traverses all of its observers and calls the onNext method on each of its observer objects to send out the relevant notifications. Each observer is able to handle the notification through its custom implementation of logic within its onNext method. So the code we are about to write gets called when the observable sends out its notifications. In this case, we want the designated employee contact to receive a notification when the relevant external visitor has gained access to the building. So let's write the logic for this method. Firstly, let's assign the passed-in argument of type external visitor to a local variable named external visitor. Let's create an if statement. The condition for the if statement checks the external visitor object's employee contact ID property value against the ID property value of the employee object reference that is passed into the constructor of this employee notify object. If these two values match, this means that the relevant employee is the registered point of contact for the external visitor referred to in this particular notification. So we want to maintain an up-to-date local list of external visitors for this employee notify observer object. So let's define a member variable named _external visitors as a generic list that can store external visitor objects. So let's write code to check if the external visitor object passed into the onNext method exists within the _external visitors list. We can do this by using LINQ and checking if the ID of the external visitor object passed into the onNext method matches any of the external visitor object's ID properties currently stored within the _external visitors list. And we are assigning the result of the LINQ expression to a local variable named external visitor list item. So let's write a nested if statement where the if condition checks if the external visitor list item variable value is null. If it is null, the external visitor object does not exist in our local list containing external visitor objects. So let's add this external visitor object to our list. Then the next line of code simply outputs a message to the relevant employee that the expected external visitor has entered the building, and we can also include the external visitor's details within the message. So if the else part of the nested if statement condition is true, the external visitor has already visited, and the notification must refer to the relevant external visitor exiting the building. So the logic simply updates the in-building property of the relevant external visitor object within the _external visitors list to false. The relevant external visitor list item's exit datetime property is also appropriately updated with the relevant exit datetime property stored in the external visitor object passed in from the observable object to the onNext method of this object. So we have now implemented the logic for the onNext method of the employee notify observer class. So in the interests of time, we are not going to bother implementing code for the onError method. We'll simply retain the default implementation generated by Visual Studio in this example, but please note that this method provides a mechanism for observers to handle exceptions that may occur within the observable object. So now we must implement the logic for the onCompleted method. The purpose of this method is so that the observable object can notify the relevant observer objects when no further notifications need to be sent. In this example, there is a rule that the observer's onCompleted methods will be called from the observable object when a cutoff time is reached, for example, perhaps 6 p.m. on a workday, and all external visitors must have left the building. So a few external visitors may still be in the building past 6 p.m. For example, they may be in meetings that have gone on for longer than was first anticipated. The onCompleted method on all relevant observer objects will only be invoked from the observable object once all external visitors have left the building and the cutoff time has been reached. Let's say the cutoff time means that no further external visitors are allowed to gain entry into the building on a particular workday after a predefined cutoff time. So, if these conditions are met, the observable can notify all observers through the observer's implementation of their onCompleted methods, and this means that no further notifications will be sent. At this point, the relevant observer objects will have a complete list of external visitor objects that visited the building during the course of the day. The external visitor objects will contain relevant information like, for example, certain details about the external visitors, as well as their entry and exit times to and from the building on the relevant day. So the observer at this point is able to create a final report relating to the external visitor data on a specific day. So let's implement the code for the onCompleted method in the employee notify class. Let's say that the relevant employee is only interested in the details of those external visitors that were there to visit the employee during the course of that day. So in the onNext method, we have only added the external visitors where the relevant employee was registered as the external visitor's contact in the building. So we can simply output the details of external visitors stored within the _external visitors list for the implementation of the onCompleted method. So let's first write an appropriate heading to the console screen. This heading will simply contain the employee name followed by the text Daily Visitors Report. Let's write code to traverse the _external visitors list. Let's set the in-building property to false, because if this method is being invoked, this means that all external visitors have left the building and we want to keep our local copy of the _external visitors list up to date. Let's then write the details of each relevant external visitor to the console screen. This information serves as a final daily report for a specific employee and contains information about the external visitors that have visited the employee. So this is a report, and we want to space the columns for each of the outputted fields evenly. One way we can achieve this is by using the padWrite method, which is available on all string objects. The padWrite method accepts an integer value as an argument. So if, for example, we wish for the ID field to always occupy 6 character spaces, we can pass an argument of 6 to the padWrite method. So if, for example, the ID value only takes up 1 character space, the padWrite method will add the extra 5 character spaces, which will be empty spaces or white spaces, to the relevant field output. We can actually achieve the same effect when outputting variable values using an interpolated string, like this. So using the interpolated string technique, we can achieve the same thing and use less code. And that is the implementation for the onCompleted method of the employee notify class. So we also want to include a method that performs the action of subscribing to the observable. In this case, as we know, the observable is represented by the Surveillance System Hub class. So let's create a method named subscribe that contains a parameter named provider, which is of the generic interface type iObservable, and is strongly typed with the external visitor user-defined type. And to subscribe, we can simply write provider.subscribe and pass a reference to the current object using the this keyword to the observable's subscribe method. But remember that the observable subscribe method returns an object that implements the iDisposable interface. So let's create a member variable of type iDisposable. Let's name this member variable _cancellation. So now we can create a method named unsubscribe. The logic to unsubscribe the observer is simply _cancellation.dispose. So as mentioned, we also want to implement code for another type of observer class. So the class we'll create for this will be named security notify. And as the name suggests, this class denotes the security team that must receive a notification every time an external visitor enters the building, and a notification when the external visitor later exits the building. So let's include the iObserver generic interface that is strongly typed with the external visitor user-defined type within our security notify class definition. Let's auto-generate the methods that we must implement for the iObserver generic interface. So let's hover our mouse pointers over the red squiggly line, click Show Potential Fixes, and then click Implement Interface. So the first method we need to implement is the onNext method. The logic here simply checks if the external visitor object already exists within the _external visitors list. If it doesn't exist, we add the external visitor object passed into the onNext method to the _external visitors list. We then output notification text that is appropriate for the security-related observer to the console screen. If the external visitor does already exist within the _external visitors list, this means the relevant external visitor has just exited the building, so we must update the relevant properties for this external visitor object list item appropriately. So we update the in-building Boolean property to false, and we also update the exit date time property with the date and time when the external visitor exited the building. And then let's update the code to output text to the security team that the relevant external visitor has now exited the building. And we have just written the onNext method. So let's implement the code for the onCompleted method. So within the onCompleted method, we simply want to output the details contained within the _external visitors list to the console screen, and this serves as a report to the relevant security team, conveying information about the entry and exit times of external visitors throughout the day. So we can simply copy the implementation for the onCompleted method within the employee notify class to the onCompleted method within the security notify class, and then manually change the heading to reflect that this is a daily report for the security team regarding external visitors. So let's finish off this class by implementing our subscribe and unsubscribe methods. So you may have noticed that we would actually be repeating the code for the subscribe and unsubscribe methods across our observer classes, namely the employee notify and security notify classes. So if we repeat the subscribe and unsubscribe implementations here, we are violating the principle of DRY, which is an acronym that stands for Don't Repeat Yourself. Here we would be clearly repeating ourselves. So let's refactor our code so that the subscribe and unsubscribe methods are reusable across our observer classes. and are written in only one place. To centralize the functionality for these methods, let's create an abstract class named Observer. Let's make the Observer class implement the iObserver generic interface. Let's strongly type the interface with the external visitor class. So the rule here is that we must implement the members of the iObserver generic interface. In this case, however, we don't want to centralize the functionality for the onNext, onError, and onCompleted methods defined in the iObserver generic interface. We have different implementations for the onNext and onCompleted methods for our two different observer classes. So what we can do is we can create abstract method definitions for the relevant methods within our observer class. We can consolidate two member variables within this abstract class, i.e. the underscore cancellation member variable and the underscore external visitors member variable. The underscore cancellation member variable is of the iDisposable type and is used for unsubscribing an observer object. The underscore external visitors variable is of type generic list and is strongly typed with the external visitor type. The underscore visitors list maintains a central local storage facility for the relevant observer object of external visitor information. We can then centralize the functionality for the subscribe and unsubscribe methods so that these methods can be reused across both observer classes. As you may have guessed, the observer classes will inherit from this abstract class. So we can now change the class definitions for our observer classes, namely the employee notify class and the security notify class, to inherit from the observer abstract class. We then need to include the override keyword within the onNext, onError, and onCompleted methods within our employee notify and our security notify classes, which are of course classes that represent our observers. This is because we are no longer implementing the iObserver generic interface directly. We need to override the abstract method definitions for these methods that have been defined in the observer abstract class. So before we implement code in our main method and run the code, let's create a basic class that will help us differentiate between the text that will be outputted by our two observer classes, namely the employee notify class and the security notify class. So the obvious way that we can do this is by changing the color of the outputted text for each of these observer classes. So let's create a static class. Let's create a public enum and name it text output theme. Each list item value in this enum denotes an output theme. So let's name the first enum list item security. Let's name the second enum list item employee. Let's name the third enum list item normal. Let's add a method to the static class. Let's name this method change output theme. This method contains one parameter named text output theme and is defined as the enum we have just created, i.e. the enum named text output theme. Then the logic for the change output theme method simply evaluates through an if-else-if block the value passed into this method. So if the value passed into the change output theme method is the employee enum list item value, let's write code to change the background color to dark magenta and the color of the text to white. Else, if the value passed into the change output theme method is the security enum list item value, let's change the background color to dark blue and the color of the text to yellow. Else, let's reset the state of the text color and the background color back to their default colors. So let's go to the security notify class, and we can now change the color theme for the output text colors in the onNext method accordingly. And once the relevant text has been outputted, let's change the foreground and background colors back to their default values. And we can do this using our change output theme method like this. Let's go to the employee notify class and implement the same functionality, but of course change the color theme to the appropriate color theme we have defined for the employee notify output text. So now when we test our code, we will be able to differentiate between the output coming from an object derived from the employee notify class and the output coming from an object derived from the security notify class. Okay, so let's write some code in the main method to test our implementation of the observer design pattern. We have implemented code here for the purpose of understanding the observer design pattern, and to keep things simple and focused on the observer design pattern itself, we have used the console app.NET Core project template to create the infrastructure or framework to house our code logic. So before we write calling code in the main method to test our observer design pattern, it may be helpful to use our imaginations to picture a real-world representation of this example. So in the real world, we would have three types of entities. We have our two types of observers, namely an employee who works within the building and the building's security team. So the relevant observer employees, i.e. the employees who have subscribed to receive notifications when an external visitor enters or exits the building, may have apps running on a handheld device like tablets or smartphones that alert the employees when relevant external visitors enter or exit the building. The security team may have various personnel whose responsibility it is to monitor the entry and exit of external visitors. So the relevant security personnel may be notified through security-related software where one of its components is subscribed to receive notifications when an external visitor enters or exits the building. So the relevant security officer or officers may be sitting at a laptop or desktop monitoring the relevant notifications. Then we have the observable entity, which could be a server that resides on premises or in the cloud that is constantly receiving surveillance information from security cameras. It provides facial recognition functionality and assesses whether a registered external visitor can be authenticated and therefore enter the building. So in summary, the observers, i.e. employees within the building and a security team, are subscribed to the observable and receive notifications from the observable once a certain condition is met. In this case, the condition is an authenticated external visitor entering or exiting the building. With all this in mind, let's implement a few scenarios within our main method to test our implementation of the observer design pattern. So let's create an instance of our observable class. Let's create an instance of the observer class named employee notify and pass an employee object as an argument to the employee notify constructor. So we can imagine that Bob Jones is carrying a handheld device that receives a notification when an external visitor that has registered Bob Jones as the external visitor's point of contact arrives. Let's create another instance of the observer class employee notify and pass a new employee object as an argument to the employee notify constructor. So it's essentially the same scenario as before, but this time we can imagine that Dave Kendall is carrying a handheld device that receives a notification when an external visitor arrives that has registered Dave Kendall as the external visitor's point of contact. And these employees will also receive notifications once the relevant external visitor exits the building. Although they don't receive text output when the relevant external visitor exits the building, the notification is received and the relevant employee notify external visitors object list containing the relevant external visitor object is updated with relevant information, for example, the time the relevant external visitor exited the building. This information is relevant when the employee receives a report regarding external visitors, when the relevant cutoff time is reached, and all external visitors have exited the building. And let's create the other type of observer object, which is represented by the security notify class. This type represents a security team that must receive notifications whenever an external visitor enters the building and later exits the building. All observers will also receive a report once a cutoff time is reached and all external visitors have left the building. Remember, the cutoff time denotes a time after which no further external visitors are allowed to enter the building. So, for example, this cutoff time could be 6 p.m., which could be deemed as the end of the working day for the relevant company. So now we have 3 observer objects, which is comprised of 2 employees and the security team. And we have a provider, which can also be called the observable object, which is the central location where security-related data is processed. So let's subscribe all of our observer objects to receive notifications from the observable object. So when we call the subscribe method, we must also pass a reference to the observable object so we can call the confirm external visitor enters building method to simulate an external visitor entering the building. The arguments that we are passing to this method denote information about the external visitor, the time the external visitor enters the building, as well as the ID of the employee that serves as the contact point for the external visitor. So let's call the confirm external visitor enters building method to simulate the entry of an external visitor named Andrew Jackson and then an external visitor named Jane Davidson. Note that the last argument passed into the confirm external visitor enters building method denotes the ID of the employee whom the external visitors have registered as their point of contact. So the point of contact for Andrew Jackson is Bob Jones, and the point of contact for Jane Davidson is Dave Kendall. Let's then call a method to simulate these 2 external visitors exiting the building. We can do this by calling the confirm external visitor exits building method on the observable object. Once where the ID pertaining to the external visitor Andrew Jackson is passed into the method. We can then call the method again, but this time passing the ID of the external visitor Jane Davidson, signifying that Jane Davidson has exited the building. These 2 method calls to the confirm external visitor exits building method simulate these 2 external visitors exiting the building. So let's say that Andrew Jackson exited the building 2 hours after entering the building, and let's say that Jane Davidson exited the building 3 hours after entering the building. Lastly, let's call the building entry cutoff time reached method on the observable object, which denotes that the end of the working day has been reached. We have referred to this time as the cutoff time throughout this tutorial. If all external visitors have exited the building, a report of external visitors is sent out to all the subscribed observer objects. On a technical level, this is achieved through the observable object calling the onCompleted method on all relevant observer objects. We have structured the code in the main method so that all external visitors have left the building before the cutoff time. So a full report should be sent to all observers. And this also means that no further notifications will be sent for that particular day. So let's run the code. Okay, so an error is flagged because the underscore observers variable is null, and we have tried to call its contains method. So I've realized I forgot to include a constructor for the security surveillance hub class, where we should have instantiated an appropriate generic list object and assigned it to the underscore observers member variable, as well as instantiate an appropriate generic list object and assign it to the underscore external visitors variable. So let's fix this issue and implement the appropriate constructor code for the Security Surveillance Hub class. Let's try again. Let's run the code. Great. And if we look at our output, we can see that this is an expected result. Bob Jones, an employee, is notified when Andrew Jackson, an external visitor, enters the building. Dave Kendall, an employee, is notified when Jane Davidson, an external visitor, enters the building. The security team is notified when both external visitors have entered and exited the building. When the cutoff time is reached, an appropriate report is sent to the employee observer objects as well as the security observer object. The employee report contains information regarding external visitors where the employee served as the relevant external visitor's point of contact. The security observer object is notified of the relevant activities and relevant details of all external visitors for the relevant day through a report tailored for the security team. Great, so our observer design pattern has been implemented correctly and is therefore working as expected. Though I've noticed that the date-time output is not in the format I would prefer. I want to include whether the time is AM or PM. So we can do this by including TT within the date-time formatting string passed to the relevant toString methods. This is not ideal because notice that we are having to change this format in several places. In a professionally developed application, it would be good practice to configure this format in one place. For the purposes of this demonstration, we'll update the date-time string formatting in several places, but let's be cognizant that this is not the best way to implement this formatting functionality. Let's run the code again. Great. So let's simulate the scenario where the cutoff time is reached. So no further external visitors are allowed to enter the building past the cutoff time. But there are still external visitors in the building. So we can simulate this scenario by commenting out the line of code that simulates the external visitor Jane Davidson exiting the building. So in this particular case, Jane Davidson has not yet exited the building. Let's run the code. And the output reflects this. We see the correct output pertaining to the entry and exit of Andrew Jackson, but we only see an output for Jane Davidson entering the building and not exiting the building. This is an expected result. Note that we also do not see any of the reports outputted to the observers because these reports are only sent when the cutoff time is reached and all external visitors have exited the building. The code implementation for this is implemented in the building entry cutoff time reached method, contained within the observable class, i.e. the Security Surveillance Hub class. In the building entry cutoff time reached method, the onCompleted methods of all relevant observer objects is called, but only if all external visitors have left the building. And if we include the method call to the confirm external visitor exits building method for Jane Davidson, but call the unsubscribe method on the employee notify object after this external visitor has entered the building, but before the building entry cutoff time reached method is called. So let's appropriately call the unsubscribe method on the observer object pertaining to the employee, Bob Jones. Let's run the code. And you can see that Bob receives a notification when his external visitor enters the building, but a report is not sent to Bob Jones when cutoff time is reached because he has unsubscribed before cutoff time is reached. This is because if an observer unsubscribes, the observer will not receive any further notifications after the observer has unsubscribed. On a technical level, when the observer unsubscribes, the code removes the observer from the observers list contained within the observable object, and therefore that observer is excluded from the list of observers that is traversed and sent notifications when certain predefined conditions are met. I hope you have enjoyed this video on the observer design pattern. This completes the final video in a video series on C# events and completes the fourth part of a course on advanced C#. So in this video series, we looked at the basics of events in C#. We demonstrated how we are able to subscribe to an event contained within another class, and how we can designate a method to handle the event. Event handling code in C# is implemented by using a delegate as an intermediary between the event and designated method that is called when the relevant event is raised. We demonstrated the use of raising events through code logic, i.e., when certain logical conditions are met in a class where the relevant event resides, the event can be raised in order to invoke the methods that have been designated to handle the relevant event. We demonstrated how when a calling client subscribes or unsubscribes to an event, that this functionality can be encapsulated within add and remove accesses, which are similar in nature to the use of get and set accesses for properties. We demonstrated how events can be raised through user actions, for example, a button click. We used the UWP Universal Windows Platform project framework as a foundation for this demonstration. We briefly touched on how the MVVM Model View View Model design pattern is used to loosely couple front-end functionality from business rules-related functionality when implementing code for a UWP project. In this regard, we also discussed the advantages of separating concerns, for example, to allow for cleaner code, to facilitate easier unit testing, to facilitate better maintainability of code, and to allow for separate teams to specialize in different aspects of a project, so relevant aspects of the project can evolve independently and without adversely affecting one another. Lastly, in this video, we demonstrated an example where the implementation of the observer design pattern was deemed as suitable because its core functionality involves pushing notifications out to multiple entities from a central point when certain conditions are met. Please consider subscribing for more content on advanced C# concepts like this and much more. And please ring the bell so that you can be notified when this channel releases new videos. If you feel you have gained value from viewing this video, please hit the like button. It will be greatly appreciated. Please feel free to share any of the videos released from this channel with anyone you feel may benefit from their content. And please feel free to provide feedback about this video in the comments section. As always, the code can be downloaded from GitHub. A link to the relevant GitHub repository has been included below in the description. Hi, and welcome to the first part of a tutorial on C# generics. This tutorial is also the fifth part of a course on advanced C# topics. This video will serve as a basic introduction to generics in C#. We'll first answer the question, what is meant by generics? We'll look at a basic example of implementing generics in C# and the advantages associated with the use of generics in C#. So let's start with the question, what is meant by generics in relation to the C# programming language? Generics was introduced in C# version 2 and enables developers to use type parameters in code. This makes it possible to design classes and methods that defer the specification of one or more types until the class or method is declared and instantiated by client code. For example, by using a generic type parameter t, you can write a single class that other client code can use without incurring the cost or risk of runtime casts or boxing operations. We'll discuss what is meant by boxing operations and runtime casting a bit later in this video. Generic classes and methods combine reusability, type safety, and efficiency in a way that their non-generic counterparts cannot. Generics are most frequently used with collections and the methods that operate on them. For more content like this on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future content released from this channel. Let's look at a simplistic example to help us understand generics in C#. To help us understand generics as a whole, we are going to look at a C# collection type, the array list, versus a C# generic collection type, a generic list. An array list provides the advantage of encapsulating the functionality of dynamically increasing the size of the list as more items are added to the array list. In other words, unlike with an array, we do not have to define an array list with a size It will dynamically handle its size as items are added to the array list. The array list stores values as objects. This involves implicitly boxing value type items when they are added to the array list. Unboxing these items is required when these items are retrieved from the array list. We'll discuss boxing and unboxing in a bit. So we are only using an array list in this example to highlight the benefits that replacing an array list with a generic list provides. In doing so, we can understand the overall benefits provided through the use of generics. Note that Microsoft has stated that Microsoft does not recommend using the array list for future development. So we'll first use the array list collection in our example and later replace the array list collection with a generic list to highlight the benefits of generics. Let's create a console app.NET Core project. I'm going to name my project Generics Basics. Let's create a class named Salaries. Let's define a member variable as an array list. The array list type is a member of the system.collections namespace, so let's ensure that we include a directive to the system.collections namespace at the top of our code. And let's create a constructor. Within the constructor, let's populate our array list with data that denotes salaries. Let's create a public method named getSalaries that simply returns the array list that has been populated with the salary data. So this method returns an object of the array list type to the client code. So the code within our main method is our calling client code. The code here will create an instance of the salaries class and then call the getSalaries method and assign the returned collection from the getSalaries method to a local array list variable. So let's write the code in the main method to do this. Let's say there is a requirement to add a bonus of 2% to the second item within the collection. So let's write code to achieve this. We know that the salaries collection contains floating point numbers. So let's assume that we can assign a member of the collection to a local variable defined as float. So let's write the code for this. Okay, great. So this is good. We have a red squiggly line under the code where we are assigning the second item of the relevant array list to a variable we have defined as float. So a type incompatibility has been flagged by the C# compiler. If we hover our mouse pointers over the red squiggly line, we can see a message from the C# compiler which is telling us that we cannot implicitly cast an object to a float, but that an explicit conversion exists. So let's write code to explicitly convert the relevant object value stored in the relevant array list to the float data type like this. Great, and the red squiggly line goes away, and all seems well. Then we can finish off the code by writing code to write the salary, which now includes a bonus of 2%, to the console screen. Let's run the code. Oh, what is happening here? We have received a runtime error, specifically an invalid cast exception. The exception message states, unable to cast object of type system.double to system.single. Remember, float is an alias for system.single. So note that when we added the salaries to the array list within the constructor of the salaries class, we simply added literal values that are floating point values. We did not explicitly express the type of the relevant literal values. The type of floating point literals are by default interpreted as the double data type. we could have expressed the types for these literal values as float data types by adding an f after the relevant literal value, like this. But we did not do this. So in the main method, or in our client code, we assumed that a value within the array list was of the float data type, and this assumption resulted in a runtime error occurring. In a bit, we'll talk about how generics preemptively prevents such erroneous assumptions from causing runtime errors. Let's first discuss boxing and unboxing. Okay, so an array list stores values that are automatically typed as the root C# data type, which is the system.object data type. Note that all .NET data types ultimately inherit from the system.object data type. When a value type, in our case a numeric floating point value type, is stored within an array list, the value type is wrapped within an object type and stored in memory on the heap. This process is known as boxing. What does boxing mean? Boxing is the process of converting a value type to the type object or to any interface type implemented by this value type. So when the common language runtime boxes the value type, it wraps the value inside a system.object instance and stores it on the managed heap. For more information on data types in C#, please access a video created by this channel by clicking on a card made available in the top right-hand corner of your screen. A link to this video has also been included below in the description. So, when a value is retrieved from the array list, as we are doing in the main method, the value must first be unboxed. Unboxing extracts the value type from the object. Boxing is implicit. Unboxing is explicit. The concept of boxing and unboxing underlies the C# unified view of the type system in which a value of any type can be treated as an object. So this highlights two disadvantages of using an array list where a generic list can be used instead and can be implemented whereby the values contained within the generic list can be strongly typed through generics at compile time. Firstly, as we have proven, writing code in this way can result in runtime errors because the values in an array list are not strongly typed at compile time. Secondly, when a value type is stored within an array list, the value type is automatically boxed, and when a value type is retrieved from the array list, the value must be explicitly unboxed. This is done through explicit typecasting. This boxing and unboxing functionality carries with it a performance overhead. Boxing and unboxing can affect the performance of our applications. Using a generic list to strongly type the values stored within the relevant generic list has two distinct advantages. One, type safety. The code is type-checked at compile time, which preempts runtime errors. This makes typecasting at runtime not necessary, which eliminates the potential for type-related runtime errors occurring. Number two, enhanced performance. Unlike with an array list, the overhead of boxing is not necessary when adding a value to a strongly typed generic list, and the overhead of unboxing is not necessary when retrieving a value from the strongly typed generic list. Like an array list, a generic list carries the advantage of being able to grow dynamically, i.e., it is not necessary to define the size of the collection when it is declared. So with all that said, let's implement generics in our code. To implement generics, let's replace the array list within our salaries class with a strongly typed generic list. The generic list is part of the system.collections.generic namespace, so let's ensure that we have a directive to this namespace at the top of our code. Let's hover our mouse pointers over the list type in our code. So notice the T within angle brackets. This T serves as a placeholder for a data type. The developer is able to pass a data type as an argument to the generic list in order to declare that only the type passed into the T parameter must be stored within the relevant generic list. So we have passed in the float data type to our generic list. Notice how there is a red squiggly line under each of the floating point values we are attempting to add to our strongly typed generic list. The C# compiler is insisting that we express these floating point values as the float data type, and we know we can do this by adding an F to the end of each of these values like this. Through the use of generics, the C# compiler checks our code at compile time, which prevents the possibility of type-related runtime errors. So we are simply commenting out the code where we previously used the array list and in its place applying the relevant generic list code. Our list is now strongly typed with the float data type, which means that our list can only store value types that are of the float data type. This is the basics of generics. Let's run the code. Great! I hope you have enjoyed this video, which serves as an introduction to generics in C#. In the second video, we'll go further into generics and introduce associated concepts like, for example, constraints. For more videos on advanced C# concepts and much more, please consider subscribing, and please ring the bell so that you'll be notified of future content released from this channel. If you feel you've gained value from viewing this video, please hit the like button. It'll be greatly appreciated. Please feel free to share any of the videos released from this channel with anyone you feel may benefit from their content. Your comments are of course welcome. The code created in this tutorial can be downloaded from GitHub. Please see a link to the relevant repository below in the description. Hi and welcome. This video is the second part of a video series on C# generics. This video is also the second part of the 5th tutorial in a course on advanced C# topics. So in this video we'll create a class to encapsulate the bubble sort algorithm. This class will be a generic class that can be implemented to sort an array that contains values of any managed C# data type. This will include user-defined types. So in order to enable sorting user-defined types, the relevant user-defined type must implement the iComparable interface. The generic class that will implement the bubble sort algorithm will contain a constraint as part of its class definition. We'll discuss the significance of using constraints in the context of generics in C#, and we'll demonstrate the use of a constraint through the code example. For more videos on advanced C# concepts and much more, please consider subscribing. And please ring the bell so that you'll be notified of future content released from this channel. Firstly, to highlight the advantage of using generics in C#, I'm going to implement the functionality for this example in a non-generic way. We'll then modify the code to implement generics to create the equivalent functionality. So let's get started. Let's create a .NET Core console application and let's name this project Generic Bubble Sort Application. I'm not going to explain the details of the bubble sort algorithm in this tutorial. There are many available online tutorials regarding the bubble sort algorithm. If you'd like me to explain the details of the bubble sort algorithm, please let me know in the comments section and I'll be happy to make a video on the details of how the bubble sort algorithm works. Very basically, the bubble sort algorithm is a simple sorting algorithm that repeatedly steps through a collection of values, compares adjacent elements, and swaps them if they are in the wrong order. Our implementation of the bubble sort algorithm will work for any array of any C# value type, string data type, as well as any user-defined type that implements the comparable interface. So let's create a class that encapsulates a method containing the bubble sort algorithm. Let's first create this class as a non-generic class, so that we can later turn this class into a generic class, and in doing so highlight the benefits of using generics in our C# code. So let's create a public class named sortArray. Let's create a public method within the sortArray class named BubbleSort. This method does not return a value and contains a parameter which is an array defined as the system.object type. Remember, we are first implementing our code in a non-generic way. We want to be able to sort an array of any built-in value type, string type, and even user-defined types. We are using the object data type rather than generics to enable sorting arrays of varying data types. We are able to achieve this because all managed data types in C# ultimately inherit from the system.object data type. For value types, boxing functionality can be applied to store value type values inside an object reference type. For more information on boxing and unboxing, please click the card in the top right-hand corner of your screen to watch the first part of this tutorial on C# generics. A link to this video has also been included below in the description. So let's write the code for the bubble sort method. Firstly, let's set a local variable of the integer data type to the length of the array that will be sorted by our bubble sort code. This is the array that will be passed into this method at runtime. We are now going to create two for loops, an outer loop and an inner loop. Let's create the outer loop first. So this loop simply traverses all the elements of the array that will be passed into this method at runtime. For every traversal of the outer loop, the inner loop traverses all the elements of the array minus the current value of the outer loop's incremented value, in this case an integer value stored in a local variable named I. And of course we know that the -1 in both the outer and inner loops is there because arrays in C# are zero-based. So now, within the inner loop, we can write the code that compares the current element's value, i.e. the value currently being traversed, with the value of the adjacent element in the relevant array. So we can get the adjacent element by adding 1 to the value stored in the j variable, which is being incremented by the inner for loop statement. So notice the red squiggly line when we try to perform our comparison code using the greater than symbol. This is because the object type does not support the use of this operator for comparing one object value to another. So value types like, for example, int, float, long, etc., and the string data type implement the comparable interface. So we should be able to use the compareTo method to perform the comparison functionality we need for our bubble sort algorithm. The compareTo method definition is a member of the comparable interface. The system.object type does not implement the comparable interface, so we need to perform a runtime casting operation in order to use the compareTo method. This highlights the danger of using the object data type in code like this, because we are assuming that the elements of the array passed into this method at runtime will implement the comparable interface. So this code runs the risk of causing a runtime error and at the very least carries the performance overhead incurred when the casting operation is performed at runtime. So we can perform the casting operation like this. The way the compareTo method works is that the current value is compared to another value. And if the current value is greater in value than the other value, an integer value greater than 0 is returned to the calling code. If the values are equal, an integer value of 0 is returned from the compareTo method to the calling code. If the current value is less than the other value that it is being compared to, the compareTo method returns an integer value less than 0 to the calling code. So with regards to the bubble sort algorithm, if the compareTo method returns a value greater than 0, this means that the current value is greater than the value it is being compared to, and the two elements need to be swapped in terms of their positions in the array. So let's write the code for this. Let's set a variable named temp to the value of the current item being traversed. Let's then set the value for the current item in the array to the value of the adjacent item in the array, i.e. the value that the current item is being compared to. Then let's set the adjacent item's value in the array to the current item's value in the array, i.e. the value that is stored in the temp variable. So in effect, we have simply swapped the positions of two adjacent values in the relevant array. So in the interests of cleaner code, let's encapsulate this swapping functionality in a private method named swap. And that's it. We have implemented our bubble sort algorithm. So let's go to the main method and write code to test our sort array class. Let's create an array of integer values where the values are stored in no particular order. Let's write code to instantiate an object of the sort array type. Let's write code to invoke the bubble sort method and pass in the relevant array that we want sorted. Okay, there's a red squiggly line under the passed in array argument to the bubble sort method in our code. This is because we need to change our definition of the relevant integer array to an object array. Let's write the code to write the value stored in the relevant array to the console screen. Let's run the code. Great, and we can see that the values have been appropriately sorted. Let's test our bubble sort functionality for an array of strings. Let's run the code. Great. And let's now test our bubble sort code for an array of a particular user-defined type. Let's create our user-defined type. So let's create a class named employee. This will be the user-defined type that we'll use for this example where our bubble sort code sorts an array of a particular user-defined type. Let's keep this class simple and give it two auto-implemented properties, ID as int, name as string. Let's go to the main method and create an array of employee objects. I'm going to add made-up data for each employee object, and these employee objects are deliberately unordered. Let's run the code. And we are getting a runtime error. This is because our bubble sort code relies on the compare_to method to compare the relevant values in the relevant array. This means that the object stored within the relevant array must implement the iComparable interface. This highlights one of the reasons why our code should implement generics. We'll implement the generic version of this code in a bit. For now, to fix the runtime error, let's make the employee class implement the iComparable interface. Let's hover our mouse pointers over the red squiggly line under iComparable, click Show Potential Fixes, then let's click Implement Interface. We can now see that Visual Studio has created a method named compare_to. So we must implement code here that compares the current object's ID with the ID of the object passed into the compare_to method. So to get the current object, we can simply use the this keyword. The object that we'll compare our current object to is the object that will be passed into the parameter named obj, which is a parameter contained within the compareTo method. As you can see, the relevant parameter named obj is of type object, so we need to typecast this object to employee. Notice that we need to perform a lot of runtime casting to make this code work. This is not a good thing, and we'll solve this problem in a bit using generics. So, we are going to sort the employee objects in the relevant array by their ID properties. The ID property is of type integer. Integers in C# implement the compareTo method, so we can simply write code to return the result of the compareTo method to the calling code like this. So this code simply compares the ID of one employee object with the ID of another employee object and returns an appropriate value to the calling code. As stated earlier, a value greater than 0 if the current employee object's ID is greater than the other employee object's ID. 0 if they are equal in value, and a value less than 0 if the current employee object's ID is less than the employee object ID that the current employee object's ID is being compared to. The string data type also implements the iComparable interface, so we could replace this code with similar code that compares the current employee object's name property with the other employee object's name property. We'll test this a bit later. I'm also going to override the toString method in the employee class so that we can display the employee object's ID property followed by the employee object's name property when an employee item's values are written to the console screen. So when we write an employee item to the console screen, both the ID and the name properties of the relevant employee objects will be outputted to the screen. So let's run the code. Okay, so this is not the result we expected. In order for our override of the toString method to be executed, we need to typecast the item we are writing to the screen to the employee type. Note the need for more bad typecasting code. Let's try again. And now our code works as expected. You can see that the employee objects within the array have been ordered by their ID properties as expected. Great! So the sortArray class now works for multiple data types. We have achieved this functionality by using the system.object type. This is because all managed data types in C# ultimately inherit from the system.object type. For more information on C# data types, please click the card made available in the top right-hand corner of your screen to view a video on C# data types. So let's see how we can achieve the same functionality, but through the use of generics. We'll also see why it is more advantageous to use generics to avoid the performance penalties incurred by using the system.object type to achieve the desired functionality. So through our use of generics, we can also eliminate the risk of data type-related runtime errors. So let's change our sortArray class into a generic class. We can do this by adding a placeholder represented by a capital T within angle brackets after the sortArray class name in our class definition. Let's then replace all of our object type definitions with the placeholder data type represented by the capital T in our code. In the main method, we must add angle brackets after the sortArray type when we instantiate an object of type sortArray, like this. Within the angle brackets, we must include the relevant data type to strongly type the class. In this case, we are testing sorting an array of employee objects, so we must include the employee data type within angle brackets. We can now remove the casting operation from the code that writes the employee data to the console screen. Let's run the code. Great! We are using generics now, so let's remove the typecasting functionality where we are casting type object to type iComparable in the bubble sort method. Oh, but we now have a red squiggly line under the compareTo method call within the bubble sort method. The red squiggly line is a result of the fact that we have not told the C# compiler that type T implements the iComparable interface, which contains the compareTo method. So you'll notice when we add a dot after an item referenced in our array, the compareTo method is not available in the IntelliSense drop-down list. This is because Visual Studio and the C# compiler has no way of knowing that type T implements the iComparable interface. So, how can we declare that type T implements the iComparable interface? We can do this through the implementation of a constraint. By adding a constraint, we are constraining our T-type parameter to a rule that any type passed as an argument to the T parameter must implement the iComparable interface. So to add the desired constraint, we can add the following code to our sortArray class definition, where space T colon iComparable. So we have now implemented the desired constraint for our generic sortArray class, and the red squiggly line goes away. And now if we add a dot after our item referenced in the relevant array, we can see the compareTo method, which is a member of the iComparable interface in our IntelliSense drop-down list. So let's go to the main method. Let's first test our new generic version of the sortArray class that now contains a constraint with an array of integers. Now that we are using generics to implement the sortArray class, we can use the int type to declare our array of integers rather than the object type. So notice how we are passing in the int date type between the angle brackets for the code that instantiates the sortArray class. We are now able to strongly type our sortArray class. Let's test the code. Great! Let's test our string array, so this time we must include the string data type within angle brackets when we instantiate the sortArray class. Great! And then let's test our code with our array containing values of the user-defined type employee. But before we do this, you'll notice that we currently need to perform a conversion operation within the compareTo method of the employee class to convert the obj argument, which is defined as object, to an employee type. We don't want this extra overhead caused by the casting operation at runtime. So to solve this problem, we can implement the generic version of the iComparable interface. We can pass the employee data type as an argument to the generic version of the iComparable interface like this. So let's modify our code so that we are implementing the compareTo method contained within the generic version of the iComparable interface. To do this, let's first comment out our current compareTo method. Let's then hover our mouse pointers over the red squiggly line in our class definition. Click Show Potential Fixes and then click Implement Interface. You'll notice that the new version of the compareTo method generated by Visual Studio contains a parameter that is strongly typed with the employee user-defined type. So let's copy our old implementation of the compareTo method and paste it into our new version of the compareTo method. We can now remove the casting operation from our new strongly typed version of the compareTo method. So now there is a red squiggly line under the employee type being passed as a data type argument to the sortArray class in our main method. This is because in our sortArray class definition, we have a constraint which enforces a rule at compile time that any type passed into the sortArray class must implement the iComparable interface. Our employee class is now implementing the generic version of the iComparable interface. So we need to modify our constraint in our sortArray class definition to establish a rule that any data type passed to the relevant T data type parameter must implement the generic version of the iComparable interface. So, our constraint now pertains to any type that implements the generic iComparable interface. Following this modification, our code will still work for the integer data type, which is a value type, and the string data type, because both the int data type and the string data type implement the generic version of the iComparable interface. Our sortArray class will also work for any user-defined type like our employee type, that appropriately implements the generic version of the eye-comparable interface. Let's test our code. Great! So let's say we want to sort our employee objects by name. To achieve this, we can simply change the implementation of the compareTo method within the employee class, like this. Let's test the code. Great! Let's also test the code for an integer array. Let's firstly select the int date type in our code, right-click on it, and then select Go to Definition. You can see the int date type implements the non-generic version of the eye-comparable interface and also implements the generic version of the eye-comparable interface. Let's run the code. Great! Let's also test the code for a string array. Great! So we have written a generic class that can sort an array of any built-in value type, string data type, as well as any user-defined type that appropriately implements the eye-comparable generic interface. By using generics, we eliminated the need for a lot of type conversion operations, which would be performed at runtime and carries the risk of incurring runtime errors. Using generics can also enhance the performance of your application because the .NET runtime no longer has the overhead of performing these casting operations at runtime. Generics allows us to defer type specifications for a unit of code. This allows us to strongly type a unit of code, for example, a class, method, or collection type, at compile time. This means generics inherently has the advantage of compile time data checks to prevent the possibility of type-related runtime errors occurring. We used a constraint to indicate to the compiler that the generic type parameter, represented by the capital T between angle brackets in our class definition, must implement the generic eye-comparable interface. This allowed Visual Studio to make available the compareTo method on an object defined as T through IntelliSense, and ensured that the compareTo method is available on all relevant elements within the relevant array, which are of type T, at runtime. So generics and the use of a constraint has been implemented so that we can implement one pattern of logic, in this case the bubble sort algorithm, for any C# built-in value type, e.g. int, long, float, double, etc., the string data type, as well as any user-defined type that appropriately implements the generic eye-comparable interface. I hope you've enjoyed this video on using generics with constraints in C#. In the next video, we'll delve deeper into generics. For more videos on advanced C# concepts and much more, please consider subscribing. And please ring the bell so that you'll be notified of future content released from this channel. If you feel you've gained value from viewing this video, please hit the like button. It will be greatly appreciated. Please feel free to share any of the videos released from this channel with anyone you feel may benefit from their content. Your comments are of course welcome. The code created for this tutorial can be downloaded from GitHub. Please see a link to the relevant repository below in the description. Hi and welcome. This video is the third part of a video series on C# generics. This video is also part of a tutorial which is the fifth part of a course on advanced C# concepts. In this video, we'll look at generic delegates and events in C#. We'll also look at other concepts associated with C# generics, including the use of a generic C# built-in data structure, namely the Q data structure. We'll explore these concepts associated with generics through a practical example. The theme I've chosen for this practical example is a warehouse management system. For more videos on advanced C# concepts and much more, please consider subscribing. And please ring the bell so that you'll be notified of future content released from this channel. We need to use our imaginations a bit because the example will be highly simplified and expressed through a .NET Core console application. So the code will provide the functionality of a real-time monitoring system for items entering a warehouse and subsequently being processed. By processed, I mean the item is placed in a predefined location within the warehouse for storage. So an event is raised when an item enters the warehouse, and an event is subsequently raised once the relevant item has reached its predefined location within the warehouse. Note that when I refer to an item, I'm referring to a batch of units of a particular type. So in our example, the item can refer to a quantity of units. A unit in this example will be a hardware-related item. For example, a drill, hammer, ladder, etc. So if we use our imaginations, we can picture this scenario in the real world. An item enters the warehouse and is scanned. So let's say the item has a QR code attached to it that when scanned provides necessary information about the item. When the item is scanned, an event is raised. So for example, a supervisor could be monitoring the relevant activities relating to the warehouse, and when an event is raised, the relevant information is displayed on a screen in real time. So the supervisor could, for example, be monitoring these real-time events using a handheld device, a desktop computer or a notebook computer. The display could perhaps be a large screen TV that multiple employees can monitor. The use of events decouples the component that raises the event, which could, for example, be an on-site scanning facility, from the component that receives the event notification, which could, for example, be a handheld device used by a supervisor to monitor events either on-site or even remotely if required. So, for example, a box containing drills arrives to be stored at the warehouse. The QR code attached to the relevant box that the drills are in is scanned. The box is then transported to a predefined location in the warehouse to be stored. So when the box is placed in its relevant location, perhaps pressure pads at the location are used to detect that the box of drills has been processed. When I say processed, I mean has arrived at its designated location to be stored in the warehouse. So when the relevant pressure pad detects that the relevant box has been placed in its designated location in the warehouse, an event is raised. And the relevant information about the event is sent to the calling code, which will then display the relevant information about the event and the processed item to the supervisor's screen. So this is a real-time monitoring system for a warehouse. Please note, I've never actually worked in a warehouse, and this example is purely from my imagination. It's obviously always best when building a particular kind of application or system to consult with someone with the relevant domain knowledge. This example only serves to help with the understanding of generic delegates and events. Right, let's begin. Let's create a .NET Core console application and let's name this project Hardware Warehouse Management System. So this project will contain our calling client code. We want this project to reference another component responsible for generic functionality associated with a warehouse. So let's add a .NET Standard Library project, and let's name this project Warehouse Management System API. Let's create a reference to the Warehouse Management System API project from the Hardware Warehouse Management System project. So we'll start by building the generic functionality for our Hardware Warehouse Management System by adding code to our Warehouse Management System API project. So we have separated concerns here. We have created two components, one to handle the specific functionality of the hardware warehouse. This functionality will be encapsulated in the Hardware Warehouse Management System project. The code in this component will focus on displaying the status and data about specific hardware-related items to a screen in real time as certain events are raised. The other component is a generic component specifically created for handling the management of any warehouse. This component is responsible for raising events associated with any warehouse to the calling client code. When each event is raised from the Warehouse Management System API component to the Hardware Warehouse Management System component, the relevant data associated with the relevant event and item is displayed to the screen in real time to, for example, a supervisor. So let's write the code for our example. Let's start by deleting the default class from our Warehouse Management System API project. Let's add a class named Custom Queue. In the Custom Queue class, we are going to wrap the functionality provided by the built-in C# generic queue data structure. We are going to customize the functionality of the queue by adding two events. Simply put, one event will be raised when an item is added to the queue. The other event will be raised when an item is removed from the queue. As you may have guessed, when an item is added to the queue, this denotes an item, for example, a box containing drills, entering the warehouse. The second event denotes the event that will be raised, for example, once the relevant box containing the drills has been processed, i.e., has been placed in its specified location to be stored within the warehouse. So let's make our custom queue class a generic class. A generic class can contain more than one type parameter, but we are only going to add one type parameter for this class. So using the capital T is the generally accepted way to represent the placeholder for a type parameter in a generic type definition. If there were two type parameters, we could add a comma and then the capital letter U to represent a second type parameter. This generic class will only contain one type parameter, so let's remove the second type parameter. So by adding T within angle brackets following our class's name, we have created our custom queue class as a generic class. So let's create a private member variable of the inbuilt C# queue generic collection type. So let's define this member variable as the generic queue data type, and let's name our variable _queue. And you can see that a directive at the top of our code already exists to the system.collections.generic namespace. The queue data type is a member of the system.collections.generic namespace. Let's create a parameterless constructor for the custom queue class. Let's instantiate the _queue variable within our constructor. Let's create a read-only property and implement code that returns the number of items currently stored in the _queue collection. Let's create the definitions for the public methods that will be included in the custom queue class. We'll first add their definitions and then implement the code for each method. Let's create a method named addItem that contains a parameter of type T. This method will be called when an item is added to the custom queue. Let's create a method named getItem. This method will return an item stored within the queue to the calling code. This method returns a value of type T and contains no parameters. Let's create a protected virtual method named onQueueChanged. This method will encapsulate the functionality for raising the events of this class. It contains a parameter of a user-defined type that we need to create. The value passed to this parameter will store information about the relevant event being raised from within this method. So let's create a class definition for a class named queueEventArgs. This class will extend the functionality of the system.eventArgs built-in class, so let's write code so that this class inherits from the system.eventArgs built-in class. Let's add a read-write auto-implemented property named message to the queueEventArgs class. The message property will return a string narrative which will include details about the item to which the event pertains, as well as information about the event itself. So the last method we need to create is a public method named getEnumerator. So this method returns a value of the generic IEnumerator interface type to the calling code. So let's implement the code for this method. The implementation is one line of code which returns the value returned from the _q member variable's getEnumerator method. By implementing this getEnumerator method on our custom Q class, this will allow the calling code to traverse the elements stored within the custom Q class collection using a for each loop. We'll demonstrate this at an appropriate time during the development of this example. So let's create our delegate type, which will be used to define an event in the custom Q class, i.e. the event that is raised when an item is added to the queue, and also an event raised when an item is returned from the queue. Let's define our generic delegate type directly within the Warehouse Management System API namespace. Let's create a public delegate named QEventHandler that does not return a value and contains two generic parameters. The first parameter is of type T, and the second parameter is of type U. This is a generic delegate that contains two type parameters. So we must include the placeholder data types within angle brackets. The capital letter T represents a placeholder for the first generic data type parameter, and the capital letter U represents a placeholder for the second generic data type parameter. So now we can define the definition for the event contained within our custom Q user-defined type. So to do this, we use the event keyword. This is a public event to which we want our calling code to subscribe. So we precede the event keyword with the public access modifier. Then we follow the event keyword with the generic delegate type that we have just defined, the generic QEventHandler delegate. And let's strongly type our generic delegate. Let's pass the custom Q generic user-defined type to the first generic data type parameter, and let's pass the QEventArgs user-defined type to the second generic data type parameter. Let's name our event custom Q event. So let's implement the code for the onQChanged method. This method centralizes the code for raising the custom Q event. So the first argument passed to this event is of the generic user-defined type named custom Q, which is the class in which this method resides. So to get the current object, we can use the this keyword. The second argument is the argument passed to this method's parameter and will contain information about the event and is of type QEventArgs. So we pass the onQChanged method's argument A as the second argument to the custom Q event. So let's implement the code for the addItem method. Firstly, let's write code to add the item passed into the addItem method to the _Q collection. Note that in order to add an item to the built-in C# Q data structure, we must use the enQ method. So before we write the code to raise our custom Q event, which will be executed every time the relevant Q is changed, let's look at the Q generic collection type in C#. When we use the enQ method to add an item to a Q data structure in C#, the underlying functionality of the Q collection type is adding the relevant item to the back of the queue, as it were. So later, when we write the functionality to retrieve an item from the queue, we'll use the dequeue method. The dequeue method retrieves an item from the front of the queue. The queue data structure works on a FIFO basis. FIFO is an acronym for first in, first out. So the item in the queue that was the first item to be added to the queue when the enQ method was executed will be the first item to be retrieved from the queue when the dequeue method is executed. We'll use the dequeue method when we implement the functionality for the getItem method. Note that when the dequeue method is executed to retrieve an item from the queue, the first item added to the queue, which will be the item at the front of the queue, is removed from the queue, which means the item that was added to the queue right after the item that was just retrieved from the queue takes the position previously occupied by the item just retrieved from the queue. So the way the ordering of the queue data structure works is just like how a queue works in the real world. For example, consider people queuing to buy tickets to an event. When a person joins the queue, the person joins the queue at the back of the queue. The person at the front of the queue buys a ticket, then leaves the queue, making the person that was behind the person who has just left the queue now the person at the front of the queue. This person can now buy a ticket, and the cycle repeats. So after the enqueue method has been executed, this means the relevant queue has changed, so we want to raise an appropriate event to the calling client code to let the client code know that the relevant queue has changed. When the event is raised, we can pass two arguments to the calling client. The first argument is the queue itself, which is encapsulated in our custom queue generic class. The second argument contains information about the event as well as information about the item that triggered the event. This information is encapsulated in the queue event args user-defined type. So let's write code to instantiate an object of type queueVentArgs. And we want to send information about the item being added to the queue through the message property, which is a member of the queueVentArgs class, to the calling client code. Notice at the moment, if we include a full stop after the item variable, we don't get any properties in the IntelliSense drop-down list in Visual Studio. For example, we don't get the ID, name, or type properties that could provide useful information to the calling client code about the item that triggered the relevant event. So, how can we solve this problem? We can solve this problem by ensuring that items added to the queue implement a specific interface. Then we can add a constraint to our generic custom queue class that enforces a rule that type T must implement the relevant interface. So let's add an interface to our Warehouse Management System API project. Let's name this interface IEntityPrimaryProperties. Let's add three property definitions: ID as integer, name as string, and type as string. Let's go back to the custom queue class and let's add a constraint to our custom queue class. So we can add the constraint like this: where space t colon IEntityPrimaryProperties. So we now know that any item added to the queue will implement the IEntityPrimaryProperties interface, which means the item will have an ID property, a name property, and a type property. So because we have added this constraint, we should now be able to see these properties if we add a dot at the end of an object passed into the addItem method as an argument. So let's add a dot at the end of the item variable, and you can see the ID, name, and type properties in the IntelliSense drop-down list. This means we can include the information stored in these properties in our message to the calling client code. So in the message property, let's add a timestamp. So I'm going to add a new class named constants so that I can store a string constant that can be reused to represent a datetime format for this project. And let's include the formatting for the relevant date timestamp using our datetime format constant. Followed by the relevant ID, name, and type properties stored for the relevant item. Great, but let's say we want to include additional information in our message to the calling client code. We want to include the quantity of units that make up the item that has entered the warehouse. Remember, items are composed of units. We also want to include the value of each unit with the additional information. For design reasons, we don't want to include the quantity property and the unit value property in the iEntity primary properties interface. So let's add another interface to the Warehouse Management System API project, and let's name this interface iEntity Additional Properties. Let's add two properties to this interface: quantity as int, unit value as decimal. Let's go back to our custom queue class, and let's add another constraint to the custom queue class definition. To do this, we can simply add a comma and then iEntity Additional Properties to the custom queue class definition. Now let's see if our new properties appear in the IntelliSense dropdown when we add a dot after the item variable, which is of type T. And there you can see our additional properties, quantity and unit value. So let's include the quantity property in our message. The unit value property will be displayed to the user along with all the other properties in a tabular format every time the queue changes. We'll see this when we develop the calling client code. Let's add the following narrative text literal to the message property: has been added to the queue. So let's implement the code for the getItem method. So let's first assign the returned value from the relevant queue, i.e. the value returned from the dequeue method, to a local variable of type T. The dequeue method also removes the item at the front of the queue. So let's write the code that will notify the calling client that the queue has changed. Let's set the message property of the queueEventArgs object in much the same way as we did in the addItem method. The difference is that this method denotes that the relevant item in the queue has been processed, so let's reflect this in our narrative. So let's add the literal text has been processed to our narrative. So an item is removed from the queue once the item has been processed. By processed, we mean that the item has been placed in a designated location in the warehouse for storage. The item is added to the queue when it first enters the warehouse. Then the item is scanned. When the item is scanned, the event in the addItem method is raised. When a predefined amount of items are in the queue, the items in the queue are processed, i.e., each item is placed in a specific location in the warehouse to be stored. Each time an item is placed in its location for storage, a pressure pad is activated at the relevant storage location, which raises an event to notify the calling client code that the relevant item has been processed. We have now implemented the code for the custom queue class, and we have also completed the code for the Warehouse Management System API component. Let's implement the code for the calling client. So in this example, we have a warehouse used for storing hardware-related items. When we refer to an item in the context of this example, we mean a collection of a certain type of hardware item. So for example, we are going to use 4 distinct item types: drill, hammer, ladder, and paintbrush. So in this example, an item could refer to a collection of drills, a collection of hammers, a collection of paintbrushes, or a collection of ladders. So let's define an abstract class named hardwareItem, which must implement the interfaces we created in the Warehouse Management System API component, namely the iEntity primary properties and the iEntity additional properties interfaces. We have already created a reference from the Hardware Warehouse Management System project to the Warehouse Management System API project, but we must also ensure that we have included a directive at the top of our code to the Warehouse Management System API namespace. So let's do this. Great. Let's create auto-implemented properties for each property definition in the iEntity primary properties and the iEntity additional properties interfaces. So let's create classes representing a specific type of item that will be stored in the warehouse. Let's start with the drill. So we must make the drill class inherit from the hardware item abstract class. Let's say we also wish to create more specific properties or behaviors for the drill class. We can do this by adding an interface to define specific properties or behaviors relating to the drill class by creating an interface that the drill class must implement. So let's create an interface named iDrill. For the sake of keeping our example simple, let's just add one property definition for the iDrill interface. Let's make it a string property and name it drill brand name. So this property is only intended to acknowledge that we are able to extend each of the classes representing specific products in this example, but we won't be using these properties further than this. So let's ensure that the drill class implements the iDrill interface. Let's implement the same design for our other items, ladder, paintbrush, and hammer. Great! So let's go to our main method and simulate items entering the warehouse by adding items to a custom queue object. Let's instantiate an object of the generic custom queue class defined in the Warehouse Management System API component that our calling client code references. Let's strongly type our queue with the hardware item abstract class. We do this because all items in our warehouse will inherit from the hardware item abstract class. So the next step is to wire up a method to handle the event defined within the custom queue class. This is an event that is raised whenever the relevant queue changes. For example, an item is added to the queue, denoting a hardware item entering the warehouse, or an item is removed from the queue, denoting that the item has been processed, i.e. the item has been moved to a predefined location within the warehouse for storage. So to wire up the relevant event, we type the object reference custom queue, add a dot, and then we can see the relevant event in the IntelliSense drop-down list. So let's select the event named custom queue event. Then we can type in the plus equals operator to establish a method that we want to execute when the relevant event is raised. So we can auto-generate the relevant method through Visual Studio by pressing the Tab key. We can now implement the custom code we want executed every time the queue changes within the relevant method we have just generated. So let's first write code to clear the screen. So notice that the first argument passed to this method is an object of type custom queue. It is named sender because the event that is fired resides in this class. So the event notification is sent from the custom queue class when the relevant event is fired. So the second argument is of type queue event args and encapsulates relevant information about the relevant event. So let's write code to check if the sender object, which is an object of type custom queue, contains any items. So to do this, we can use an if statement to check the queue length property of the custom queue class. So if the queue length property is greater than 0, let's write the properties of the items stored within the queue to the console screen. Let's create a private method named WriteValuesInQueue to screen that contains a parameter of type custom queue, which is strongly typed with the abstract class hardware item. Let's write a for each loop to traverse the items in the queue and write each item's properties to the console screen. So these items will be written to the screen in a tabular format, so I've made sure that each column is set to a specific length. Let's call this method from the custom queue underscore custom queue event method, i.e. the event handler method. So let's go to the main method, create 10 hardware items and add them to the custom queue. I'm actually going to change the name of the variable we are using to reference the custom queue object to a more specific name. Let's change the name of this variable from custom queue to hardware item queue. So I've already uploaded the code for this example to GitHub. In the interests of time, let's copy the code that adds hardware item objects to the relevant queue from the code I have already uploaded to a GitHub repository. So let's navigate to this web page from within our browsers and copy the relevant code. And then appropriately paste this code into the main method. So this code, which adds hardware items to the custom queue, simulates items entering the warehouse. To give this example a more real-world feeling, to simulate that these items are entering the warehouse at random times, I'm using the system.threading.thread.sleep method to add a time delay between the lines of code that add items to the queue. So for example, here we are delaying the main thread for 2000 milliseconds, which equates to a 2-second delay. Let's go back to the custom queue underscore custom queue event method and add an else part to the top if statement. So if the queue does not contain any items, we want to output status information to the user. Let's output the following text to the user when the queue does not contain any items. Status: all items have been processed. So let's run the code. And you can see that each time an item is added to the queue, an event is raised and our calling client code writes the details of the item to the console screen. Great! So let's create the code for when items in the queue are processed. For the sake of keeping this example simple, let's say that when the queue contains 5 items, we want the items in the queue to be processed. So let's define a constant as an integer, and let's name this constant batch size. Let's set this constant to a value of 5. So we can now write a nested if statement in our custom queue underscore custom queue event method that checks if the queue has 5 items in it. If the queue has 5 items in it, we want code to execute that simulates the processing of each of the items in the queue. So let's write a private method named processItems. It contains one parameter of type custom queue that is strongly typed with the hardware item user-defined abstract type. Let's write code to simply traverse the items in the queue through the use of a while loop. The condition of the while loop is that iterations of the loop must continue while the queue is not empty. So we want to dequeue each of the items in the queue, meaning that the item has been processed. Remember that when the getItem method is called, the dequeue method on the underlying queue data structure is called, which means the item at the front of the queue is removed from the queue. Let's add a 3-second delay before each item is removed from the queue to simulate that the item is being processed. Let's go to the custom queue underscore custom queue event method and write code to call the processItems method. Let's run the code. Now you can see that when the queue is populated with 5 items, the items are processed and each item is removed from the queue once the relevant item has been processed. When the queue is empty, the next 5 items are added to the queue, and once 5 items have entered the queue, the items are processed one by one until the queue is empty. Great. So to further clarify to the user the status of each item in the queue, let's write the message property of the event args object to the console screen. This message property contains a narrative describing the relevant item and the event pertaining to the item. Let's run the code. Excellent. The supervisor can see relevant information about the item as well as the event. The supervisor can see status output for each item as it enters the warehouse and is processed. The final thing to do is enhance the formatting of the output. In the interests of time, let's copy and paste relevant formatting functionality from GitHub. So let's navigate to this location in our browsers. And please feel free to copy my actions here. Let's copy the code situated between the two comments that have the text headings. Let's then paste the code into our code editors. We can then write the code to call these output formatting related methods at appropriate points within the custom queue _ custom queue event method. Great, let's run the code. Excellent. So lastly, I'm going to put a few breakpoints in the code to clarify the execution path of the code. So in the calling client code, when the code adds an item to the custom queue, you can see the event that resides in the custom queue class in the Warehouse Management System API component is raised, and the code in the calling client handles the event through a method that was designated to handle the event when the calling client code subscribed to the relevant event. When the predefined batch size of 5 has been reached, i.e., when the custom queue contains 5 items, each item is processed. Once an item has been processed, it is removed from the queue. The event is raised to the client, and the client method that has been designated to handle the event is executed. When the calling client subscribed to the event in the custom queue class, a method that resides in the calling client code was designated to handle the event. When the event is raised, the relevant event handler method is executed. In this event handler method, we are writing status information to the screen so that this information is available to, for example, a supervisor in real time. I hope you have enjoyed this video, which demonstrates the use of the C# generic built-in queue data type, a generic class with constraints, and the use of a generic delegate used to define an event. For more videos on advanced C# concepts and much more, please consider subscribing. And please ring the bell so that you'll be notified of future content released from this channel. If you feel you have gained value from viewing this video, please hit the like button. It'll be greatly appreciated. Please feel free to share any of the videos released from this channel with anyone you feel may benefit from their content. Your comments are of course always welcome. The code created in this tutorial can be downloaded from GitHub. Please see a link to the relevant repository below in the description. Hi and welcome. This video is the fourth and final part in a video series on C# generics. The C# generics video series is the fifth part of a course on advanced C# concepts. In this video, we are going to first look at how, in terms of generics, the MSIL code, or Microsoft Intermediate Language Code, is handled by the Common Language Runtime under the hood, as it were. If you stick around till the end, I'll show you how a utility that ships with Visual Studio for Windows, named Intermediate Language Disassembler, can be used to disassemble an assembly, whereby the MSIL code can be extracted from the .NET assembly and inspected. We'll then look at a basic code example whereby the factory design pattern is implemented and generics is applied to our factory class so that this class can be reused to instantiate multiple types. We'll apply multiple constraints to our factory class to enforce design rules driven by the requirement for our code example. For more videos on advanced C# concepts and much more, please consider subscribing, and please ring the bell so that you'll be notified of future releases from this channel. So let's briefly look at how generics in the MSIL code, or Microsoft Intermediate Language Code, is handled by the Common Language Runtime. I'm not going to go into a lot of detail in this regard, but please check out this Microsoft document for a more detailed description regarding how generics is handled by the .NET runtime. This document explains how generics is handled differently for value types and reference types by the .NET runtime. Let's look at a few excerpts from this document. Specialized generic types are created one time for each unique value type that is used as a parameter. This means conversions are no longer necessary because each specialized generic class natively contains the value type. Generics work somewhat differently for reference types. The first time a generic type is constructed with any reference type, the runtime creates a specialized generic type with object references substituted for the parameters in the MSIL. Then, every time that a constructed type is instantiated with a reference type as its parameter, regardless of what type it is, the runtime reuses the previously created specialized version of the generic type. This is possible because all references are the same size. Because the number of reference types can vary wildly from program to program, the C# implementation of generics greatly reduces the amount of code by reducing to 1 the number of specialized classes created by the compiler for generic classes of reference types. So, two benefits are highlighted in this document with regards to value types and reference types in terms of generics. Conversions are no longer necessary because each specialized generic class natively contains the value type. Generics greatly reduces the amount of code by reducing to 1 the number of specialized classes created by the compiler for generic classes of reference types. My goal here was only to draw your attention to the extra information regarding how the .NET runtime implements generics in C# under the hood, as it were. Please read this document to gain a better understanding in this regard. So let's implement our code example where we'll implement the factory design pattern and use generics so that the object instantiation code is abstracted and can be used to instantiate multiple types. We'll use multiple constraints appropriate to our requirement so that special rules at compile time are enforced. Let's create a .NET Core console app and let's name it Digital Product Inventory Application. So in this very basic example, we're going to create classes for representing specific types of digital products. We'll also create classes for encapsulating data associated with the various categories of digital products. We are going to create a factory class used to abstract and centralize the construction of these different types into objects. We'll then copy code from a GitHub repository, and this code will serve as the calling client code. This client code includes a LINQ query used to compile a report containing digital product information and their associated digital product category information. Code is also included to output the results of this LINQ query to the console screen. This example is more about understanding the application of generics than understanding LINQ. Please don't worry if you don't fully understand the LINQ aspect of this tutorial. LINQ will be discussed in detail in upcoming tutorials. So let's create our factory class. This tutorial is not about design patterns, but the factory design pattern is used in this example as a device to show how generics and constraints can be implemented to abstract the construction of objects of varying types. Special rules will also be applied through the use of constraints. Let's name this class Factory Pattern. So this class contains two generic types. So let's include the constraints for the type T parameter in our definition of the Factory Pattern class. As we know from our previous tutorials, constraints enforce compile time rules on our type parameters. So this constraint is enforcing a compile time rule that type T must be a reference type denoted by the class constraint, must inherit from type U, i.e. the other generic type parameter, and the type T argument must also contain a public parameterless constructor. This is denoted by the new constraint. Note that when the new constraint is used with other constraints, the new constraint must be specified last. In our code, we are going to instantiate an object of type T. Note that a generic type cannot be instantiated if the new constraint is not specified for the type that must be instantiated. We'll prove this in a bit. So let's also add a constraint to our uType parameter. We can do this by including another where keyword, followed by the relevant constraint or constraints for the U data type. Note that this class constraint for this example is in fact redundant for the U parameter, and I will remove this from the relevant GitHub repository. I'm applying this constraint at this point in the tutorial to show how we are able to apply constraints to multiple type parameters. So let's add a method to our class and name it getInstance. So the code logic for this method is instantiating an object of type T, which is derived from type U. The instantiated object is then returned to the calling code. So now, just to show you that we cannot instantiate an object of type T unless the new constraint has been appropriately applied to the relevant class definition, let's comment out the new constraint. And you can see that the C# compiler immediately complains. We must ensure that we have appropriately applied the new constraint in order to be able to create an instance of type T. So let's now create an interface named iPrimaryProperties. Let's add two property definitions to our interface, ID as int and title as string. So now let's go back to the factory pattern class. Let's add a constraint to enforce a rule that type U must implement the iPrimaryProperties interface. So we can do this by adding a constraint like this. Remember, the class constraint can be removed from the uType parameter. The code will still work as expected with it there, but for this example, it is redundant. So let's add an abstract class named ProductBase that implements the iPrimaryProperties interface. Let's implement the properties defined in the iPrimaryProperties interface as auto-implemented properties. Let's create an abstract class named CategoryBase that also implements the iPrimaryProperties interface. Let's extend the ProductBase class by adding an auto-implemented property named CategoryID. The CategoryID property will be included within our LINQ query to join the data stored in a list containing objects of type CategoryBase to relevant product objects stored in a list containing objects of type ProductBase. We'll look at the LINQ query in a bit. Let's extend the CategoryBase abstract class and add an auto-implemented property named Description. So let's create our category classes. let's create our digital product classes. So our category classes inherit from the category base abstract class, and our product classes inherit from the product base abstract class. Note that both the product base abstract class and the category base abstract class both implement the iPrimary properties interface. Notice I am extending these classes with additional properties just for demonstration purposes. These additional properties won't be used further than this in this example. So I'm going to create a class named ProductViewModel, and this class will be used as a template to centralize information from the product-related classes with information from their relevant category-related classes. So we want our calling code, which we'll copy from GitHub, to create several product objects and related category objects. Then using LINQ, we'll return a collection of objects of type ProductViewModel to the calling code. This collection will be the result of a join operation, joining objects of type ProductBase with the relevant objects of type CategoryBase. LINQ is not the focus of this tutorial, but I thought I'd include the LINQ functionality to make our example more interesting. As stated earlier, we'll discuss LINQ in detail in upcoming tutorials, so don't worry if you don't understand the LINQ-related code. So I've already uploaded the code for this example to GitHub. So let's copy the code, which will serve as our calling client code, from the relevant GitHub repository, which can be found at this location. This URL has also been included below in the description. Let's copy all the code from within the program class like this. And let's select the main method within our program class in our code editors and paste the code we have copied from GitHub over the main method in our code editors like this. And you can see that we have red squiggly lines under our code relating to our generic lists. So to fix this, let's add a directive to the system.collections.generic namespace. And in our getProducts method, where we are executing a LINQ query, we have a red squiggly line here. So to fix this, we need to add a directive to the system.link namespace. Great. So let's look at the calling client code we have just copied from GitHub. The add properties to product method encapsulates functionality to add values to the properties of an object of type product base. The add properties to category method encapsulates functionality to add values to the properties of an object of type category base. You can see that these methods are currently public methods, but they don't need to be public, so we can change these methods to private. I'll update the relevant GitHub repository with this change. You can see here that our LINQ query is encapsulated in a method named getProducts. The LINQ query is selecting all product-related objects in the products list and joining each product with its relevant category. Each product is joined to its relevant category through the category ID property. The result of the LINQ query is a collection of objects of type ProductViewModel, which appropriately combines product information with relevant category information. As stated earlier, LINQ will be discussed in detail in upcoming tutorials. So let's look at the code in the main method. So notice how the factory pattern generic class is being used to instantiate each object of type product base. For example, we are instantiating an object here which represents a digital book entitled The Old Man and the Sea. We are instantiating an object here representing a movie entitled Shawshank Redemption. The factory pattern generic class is then reused to instantiate several objects of type category base. For example, we are instantiating an object representing the category with the title of movie here, and we are instantiating an object representing the product category here with the title of music. So the factory pattern class has been implemented to abstract the object creation functionality for this code example. We have adapted the factory design pattern to our requirements by imposing rules on the instantiation process through the use of constraints. So in the main method, we are instantiating our product-related objects, appropriately adding values to the relevant object's properties, then adding the objects to a list of product-related objects. We are doing the same thing for our category-related objects. We are then appropriately amalgamating information from the product-related objects with relevant information from the category-related objects into an object of type product view model through the use of a LINQ query. We are then looping through the items returned from the LINQ query and writing each item's properties to the console screen. So let's run the code. Great. I want to draw your attention back to the constraints in our factory pattern class. Note that we have implemented a constraint that the U argument must implement the I primary properties interface. So if, for example, we were to comment out the code in our class definition for the category-based abstract class that indicates that this class implements the I primary properties interface, look at how the C# compiler responds. Note how the constraint imposes a rule at compile time that the U argument must implement the I primary properties interface. For more detailed information on constraints, please navigate to this URL. So we were discussing earlier how the .NET runtime handles generics based on the MSIL code. We are able to examine the MSIL code for an assembly by using a utility like, for example, the IL disassembler utility. So now if we wanted to look at the MSIL code for this project, we can use this utility. This utility ships with the Visual Studio for Windows IDE. So let's run our developer command prompt for Visual Studio. Let's make the directory where our target assembly file resides our current directory. We can then type the following command. This command generates a file containing the MSIL code within the directory of the relevant assembly. This is the MSIL code that resides within the target assembly, created when we built our C# project. So now we can open the file we have just created in a text editor like Notepad and look at the relevant MSIL code. Great! For more detail on the IL disassembler, please navigate to this URL. All URLs mentioned in this tutorial can be found below in the description. Lastly, if you are interested in reading about generics and reflection, please navigate to this URL. If you are interested in reading about generics and attributes, please navigate to this URL. Reflection can be used to inspect generic types in C# at runtime, and this will be discussed in later videos created on C# reflection. Generics used with attributes will be covered in future videos created on C# attributes. In this video series, we discussed that generics was introduced in C# version 2. We looked at why it is better to use a strongly typed generic list to store a collection of items rather than an array list for this purpose. We discussed the benefits of generics. Generic classes and methods combine reusability, type safety, and efficiency in a way that their non-generic counterparts cannot. We looked at how constraints can be applied to generic type parameters in order to enforce compile time rules on generic type parameters. We created a code example representing a warehouse management system. In this example, we used the built-in C# generic queue collection type to store objects representing various hardware items, that enter the warehouse and are subsequently processed. Generic delegates and events were instrumental in this real-time monitoring system. Lastly, in this video, we briefly looked at how the MSIL code, or Microsoft Intermediate Language Code, is used by the .NET runtime to efficiently handle both value types and reference types in terms of generics. We also implemented a generic version of the factory design pattern in a basic code example to demonstrate how the use of multiple constraints can be applied to generic types in order to enforce special, requirement-driven compile time rules. I hope you have enjoyed this video series on C# generics. For more videos on advanced C# concepts and much more, please consider subscribing. And please ring the bell so that you'll be notified of future content released from this channel. If you feel you have gained value from viewing this video, please hit the like button. It will be greatly appreciated. Please feel free to share any of the videos released from this channel with anyone you feel may benefit from their content. Your comments are of course welcome. The code created in this tutorial can be downloaded from GitHub. Please see a link to the relevant repository below in the description. Hi and welcome. This is the 6th tutorial in an advanced C# course, and this is the first part of a video series on asynchronous programming using the C# programming language. In this video, we'll look at an overview of asynchronous programming in C# with a particular emphasis on Microsoft's recommended approach to using asynchronous programming for new development. Microsoft's recommended approach to including asynchronous behavior in new applications is to use the task-based asynchronous pattern, TAP. The two legacy methods for providing asynchronous behavior are event-based asynchronous pattern, EAP, and asynchronous programming model, APM. The event-based asynchronous pattern will not be discussed in this video series, but if you wish to learn more about this legacy pattern, please navigate to this URL. We have already covered the asynchronous programming model, APM, in the advanced course. In part 3.5 of this course, we looked at using a callback method and a built-in delegate to implement asynchronous behavior. Please navigate to this URL to view a video released on this channel that covers the asynchronous programming model, APM. As always, all links mentioned in this video can be found below in the description. Later on in this tutorial, we'll look closer at how using the task-based asynchronous pattern can result in asynchronous behavior for our applications and ultimately ensure that our users have a smooth user experience when using our applications. For more videos on advanced C# topics and much more, please consider subscribing, and please ring the bell so that you'll be notified of future videos released from this channel. Right, so TAP, or Task-Based Asynchronous Pattern, is the recommended design pattern for creating asynchronous behavior for new development. C# version 5 produced a simplified approach to asynchronous programming that leverages asynchronous support in the .NET Framework 4.5 and higher, .NET Core, and the Windows runtime. .NET Framework 4.5 or higher and .NET Core contain many members that work with async and await. These members can be identified by their names, which contain an async suffix. So what gave rise to the task-based asynchronous pattern? We live in an age where our applications should not only run on desktop computers and notebook computers, our applications in a lot of cases will also need to run on smaller devices. For example, handheld devices like tablets and mobile phones. These smaller devices may not have the powerful resources that desktop computers and notebook computers have to handle resource-intensive operations. So, an operation like, for example, downloading a large document from a remote server may ultimately result in poor performance of our applications. A poor UX, or user experience, with our applications can cause user frustration and cause our users to take a dim view of our applications. Implementing this pattern in our code can result in a smoother UX, user experience. The code is easy to implement, and even though the code results in asynchronous behavior, the code can be written in a synchronous way. We'll look at a code example to further elucidate this point in a bit. The C# compiler makes it very difficult for a developer to implement the task-based asynchronous pattern incorrectly. For example, in an IDE like Visual Studio, red squiggly lines will appear in appropriate regions of code if the relevant asynchronous code has been written incorrectly. Messages will also be made available to the developer from the C# compiler in Visual Studio to guide the developer on how to fix the incorrect code. So, how can long-running operations result in a poor user experience with our applications? Say, for example, a button is clicked, and within the event handler method of the relevant button click event, a long-running operation is invoked. If this operation were to be invoked synchronously, the thread of execution on which the relevant time-consuming operation is running is blocked until this long-running operation has completed. While the relevant thread is blocked, the application is unresponsive, meaning the user cannot perform other operations with the application until the long-running operation completes. So this ultimately results in poor user experience with our application. There are two kinds of blocking operations: CPU-bound operations and I/O-bound operations. So let's look at CPU-bound operations. This occurs when an intensive computation needs to be carried out by the device's CPU. For example, you might have a game running, and a single action from the user may cause multiple characters in the game to incur damages. The calculations of these damages may be CPU intensive. An operation like this, if done synchronously, can result in the UI to freeze or stutter. Running the calculations in parallel across multiple cores can alleviate this and make the UI, or user interface, perform smoothly and responsively. So the developer could use the task.run method to run calculations in parallel to alleviate the effects that handling these computations synchronously could have on the user's experience. Other examples of applications that may need to run intensive CPU-bound operations could be financial or scientific applications. So let's look at I/O-bound operations. I/O-bound operations are performed when requesting data from a network, accessing a database, or reading and writing to a file system. The blocking effect during an I/O-bound operation causes the CPU to wait for the relevant I/O-bound operation to complete. So the CPU will need to wait, basically lie dormant, while, for example, information is retrieved from an Azure SQL database that resides in the cloud. Once the information is retrieved and, for example, appears in local memory, the information can then be processed by the CPU. The CPU can only then continue processing other instructions. While the I/O-bound operation is running, the CPU is blocked from running any other operations. Performance will not be optimal for our applications when the code for these relatively long-running operations are handled synchronously. I/O-bound operations are the most common encountered blocking operations. So we are going to focus on resolving the blocking effect of I/O-bound operations through the implementation of the task-based asynchronous pattern in this video. Note that generally speaking, I/O-bound operations are far slower than CPU-bound operations. In business applications, I/O-bound operations will be far more common operations that will be encountered and should be handled asynchronously. And let me emphasize, I/O-bound processing is far slower than CPU processing. So let's look at a basic code example. We won't implement this particular code in Visual Studio. This code serves to give us a general idea of what the task-based asynchronous pattern looks like in C# code, and we'll also get an idea of how it works. Let's first look at the synchronous version of this code example. We'll then modify the code so that it is implemented using the task-based asynchronous pattern. So in this synchronous version of the code example, we have a high-level button click event handler named button_click. When the user clicks the button that invokes code within this event handler method, a call to a method named getDocumentContent is made. This method accepts an argument, which is the name of the remote file that our code needs to retrieve and process. So let's say that the path of the remote document is handled under the hood, as it were. A relatively long-running operation is encapsulated within a method named getDocumentContent_as_string, which is invoked within the getDocumentContent method. The long-running operation in this case is downloading a document from a remote server. After the long-running operation completes, a string is returned from the getDocumentContentAsString method containing the relevant document content. A method named saveDocumentLocally is then called, which, as the name suggests, saves the content returned from the getDocumentContentAsString method to a local file store as a new file. The document content is then returned to the calling code from the getDocumentContent method. Once the getDocumentContent method completes and returns the content to the button-click-event-handler method, the content is subsequently displayed to the user. This is denoted by a call to a method named displayContent. So while the code is performing the relatively long-running operation executed by the getDocumentContentAsString method, the thread of execution on which this operation is running will be blocked, leaving the CPU idle until the getDocumentContentAsString method completes and returns a value. So let's say that we are in luck and there is an asynchronous version of the getDocumentContentAsString method available to us named getDocumentContentAsString async. Note that this version of the method has the same name as the synchronous version, with the exception of the async suffix added to the end of the method's name. Adding the async suffix to the end of an asynchronous method's name is a naming convention used for asynchronous methods that are part of the implementation of the task-based asynchronous pattern. So the method we want to call is named getDocumentContentAsString async. So we need to use the await operator preceding the method call to the getDocumentContentAsString async method like this. This is telling the C# compiler that we wish to call this method asynchronously. If any of our method calls within the getDocumentContent method are awaitable, as is now the case here, where we are using the await operator, we need to include the async modifier in the method signature of the method where one or more asynchronous method calls are invoked, which, as stated, is denoted by the await operator preceding the relevant asynchronous method being called. So let's include the async modifier in the method signature for the getDocumentContent method. Let's also adhere to the correct naming convention, so let's rename the getDocumentContent method to getDocumentContentAsync like this. The getDocumentContentAsync method will return a string value once the async method has completed, but when it is first called and hasn't necessarily completed, a generic task object will be returned. I'll elaborate on what the task object and the generic task object is in a bit. So we must include the relevant generic task type in the method signature of the getDocumentContentAsync method like this. We are calling an asynchronous method from the button-click-event handler named button_click. So we need to include the await operator preceding a call to the getDocumentContentAsync method like this. We are now calling an awaitable method within the button_click event handler method, so we need to include the async modifier within the method signature of the button_click event handler method like this. We don't need to include a task type in the button_click event handler method signature because it is a high-level event handler. All asynchronous methods that are not high-level event handlers like the button_click event handler will return a task object if the relevant method does not return a value, or a generic task object if the relevant method does return a value, as is the case with our getDocumentContentAsync method, which returns a string. So, for example, the getDocumentContentAsync method returns a string value once it has completed. So to reflect that this method is an async method that returns a string value, we include the generic task type in its method signature, and this generic task type accepts the string data type as its argument. So basically, the new asynchronous implementation of this example code means that when asynchronous methods are called with the await operator, the control is immediately returned to the calling code, meaning that the thread of execution on which it is executed is free to process other operations while the asynchronous method is running. So the CPU is not left idle while an I/O-bound operation is underway, as is the case in this example where a file is retrieved from a remote server. In this asynchronous implementation, the CPU thread of execution on which the relevant, relatively long-running operation was invoked can be used to perform other operations while the remote file is being retrieved from the remote server. In this case, the UI thread is the thread of execution. So if, for example, the user needed to execute a different button click event, another operation could run concurrently to the long-running operation invoked by the getDocumentContent as string async method. This means the user's experience with the application will not be negatively impacted by this relatively long-running operation. The user experience is not adversely affected by the relatively long-running operation performed by the getDocumentContent as string async method. So when the getDocumentContent as string async method is called, a generic task object is returned immediately to the calling code. The string value that is returned only once the getDocumentContent as string async method completes is returned at that point of execution in the code, but at a later time. While the relatively long operation invoked by the getDocumentContent as string async method is running, other operations can be performed by the user without negatively impacting the user's experience with the relevant application. Basically, the task object is a state machine. If you'd like a comprehensive explanation of what a state machine is, please navigate to this URL. The task object encapsulates information about the asynchronous process and either delivers the final result back once the asynchronous method completes or throws an exception if an exception occurs within the asynchronous method. So we can put traditional try-catch code around the call to our asynchronous methods as if the methods were synchronous to handle exceptions that may occur in our asynchronous methods. So when the awaitable method is executed, a task object is immediately returned to the calling code. The string value is only returned later once the awaitable method completes. When the task object is returned, the relevant thread of execution is then immediately released to the caller. The thread of execution is not blocked while the asynchronous operation is running. So the async method first returns the task object, in this case a generic task object, that promises to return a string value at this point in the code once the operation performed within the relevant async method has completed. This model is known as the promise model of asynchrony. If you wish to read more about the promise model of asynchrony, please navigate to this URL. On the C# side of things, the C# compiler transforms your code into a state machine that keeps track of things like yielding execution when an await is reached and resuming execution when a background job has finished. The async modifier is doing two things. Number one, it is a message to the C# compiler that this method can use the await operator inside it. The await operator designates the suspension points in the execution. Number two, the method itself can be awaited by methods that are calling it. The async modifier also is a message to the C# compiler that the method can be called asynchronously using the await operator. The await operator is telling the compiler that the execution of code cannot continue past this point until the awaited method has completed. So in the meantime, control returns to the caller of the method, which is the UI thread in this case, which allows, for example, the user to click other buttons while the incomplete asynchronous task is still running. Under the hood, as it were, when you compile your code through Visual Studio, the C# compiler rewrites your code into intermediate language, splitting apart your async method calls into lots of callback methods. So we as coders don't need to worry about the complexity of implementing callback methods ourselves. With this explanation, I'm admittedly, in the interests of brevity, glossing over a mass of complexity involved in making this asynchronous abstraction model work. For more detail and a comprehensive diagram of how the underlying framework is handling the asynchronous code, please navigate to this URL. Note that the line of code that includes the await operator is in fact doing two things. It is returning a task object when it is first invoked, And then later, when the asynchronous operation completes, it is returning the value returned by the relevant method, in this case, a string value. So we can write the code like this to make this clearer. We could first assign the task object returned by the relevant asynchronous method to a variable of type task. This is done without the await operator. We can then call the relevant task object with the await operator later in the code. In this case, the string value will be returned from the task object when the relevant operation completes. In this particular example, we can write what is achieved by 2 lines of code here in 1 line of code like this. So let's put the code back to how we originally had it. So let's create a code example. We are going to create 2 .NET projects. One project will represent the calling client code, i.e. the code that will contain the user interface. The other project will represent the server-side code. The calling client will be implemented as a UWP project or Universal Windows Platform project. The server-side code will be implemented as a Web API project. This example is very basic. We'll implement a button-click event handler on the user interface, which will be included within the UWP project. Code within the relevant button-click event handler will asynchronously call a method included within the Web API server-side component. In the relevant Web API action method, we'll deliberately implement a delay to represent a task that is relatively time-consuming and should be awaited by our client code, i.e. should be called asynchronously. We'll implement another button-click operation on the UWP project's user interface, which will implement code that runs a much faster local operation. We'll run the code and demonstrate that when clicking the button that kicks off the time-consuming operation implemented in the Web API code, that this does not impede the user's experience, and the user is able to click the second button, which carries out a much faster local operation. Perhaps the user can click this several times while the application is awaiting for the more time-consuming operation carried out on the server side to complete and return a value to the calling client code. We'll prove that the fast local operations can run concurrently while longer asynchronous operations are running in the background. And because we have written the long-running operation to run asynchronously, that the user's experience is not adversely affected by running the relatively long operation. So let's create a Web API project and let's name this project Test Time Consuming Operation Web API. Note that when the Web API project is created, a controller class is automatically included in the Web API project. This automatically included class is named Weather Forecast Controller. Code within this controller simply outputs made-up data representing a weather forecast. We'll come back to this Web API project in a bit and create our own controller class. Let's create a UWP project and let's name this project Test Client Async UWP. Okay, so let's go back to the Web API project and let's create a Web API controller class. And let's name this controller Test Long Operation Controller. So the code in this method is faking a relatively long running operation that needs to be performed before returning a value to the client code. The call to the server-side component's relevant action method will be handled through an HTTP GET request from our UWP project. We'll write the code for this in a bit. Please note that this tutorial is not about UWP or Web API, so I'm not going to go into detail explaining these two types of projects. The focus is on writing code using the task-based asynchronous pattern in C# to ensure that the user's experience is not adversely affected by long-running operations, perhaps being run remotely through a Web API call. So note that we are not only going to use the task-based asynchronous pattern on the client side, we are also using the task-based asynchronous pattern for this action method in the server-side code. We have discussed how client-side UI synchronous code can negatively affect the user's experience, and that implementing the task-based asynchronous pattern on the client side can make the user's experience much smoother. The task-based asynchronous pattern can also be implemented for server-side components like, for example, a Web API component or an ASP.NET MVC component. This creates better performance on the server side, which ultimately can affect client-side UI responsiveness. On the server side, it means, for example, that the thread of execution on which a relatively time-consuming method runs will not be blocked while the relevant time-consuming operation is performed, and the relevant thread can handle other requests while the relatively time-consuming operation is running. In terms of the user's experience, if a time-consuming operation blocks the thread of execution because of synchronous code, this could tie up server-side resources, causing a delay in performance on the server side, and at worst, could cause, for example, a client's HTTP request to time out. So, server-side synchronous code can also adversely affect the user's experience. So in order to fake the long-running operation, I'm simply going to create an await statement and use the task class's delay method to pause the method at this point for 5,000 milliseconds. In other words, it will cause a delay of 5 seconds. Once the 5-second delay representing our long operation is finished, the code returns a string value. So let's return the text Web API long-running operation completed to the calling client code. So let's test the code. And you can see that the output from the weather forecast controller code is written to the browser window. Let's change the URI in our browsers to point to the controller code that we have just created. So let's make a GET request to our test long operation controller. Great! There is a clear delay of 5 seconds before the expected string result is written to our browser windows. Okay, let's write the calling client code in our UWP project. So, we are going to drag 2 buttons onto the design surface from our list of XAML controls. Let's drag our first button onto the design surface. Let's enlarge our button a bit. Let's name this button BTN Local Operation. Let's label this button Local Operation. So let's zoom in a bit so we can have a clearer view of our button. Let's drag our second button onto the design surface. So let's enlarge this button a bit. Let's name this button BTN Web API Call. Let's label this button Web API Call. So let's drag a list view component onto our design surface. You can see the list view is currently the same size as our design surface and is covering the whole design surface. Let's resize it so its contents will appear to the right of our buttons. Let's name our list view component LVW output. You may have noticed that creating a beautiful design for our UI here is not a concern for this video. But in the interests of saving time, this design will be adequate for what we are demonstrating here. It might be a good time to make the point that UX is not just about aesthetics, which of course is very important, but it is also about performance. We are focusing on how we can write asynchronous code to drastically improve the user's experience. So let's go to the code behind our design surface and let's write a private method named addListItem. And here we are writing a piece of reusable code for adding a string value to our list view component. Within each of our two button-click event handlers, we want to add relevant string results to our list view component. We'll write the code for the two button-click event handlers in a bit. Let's create two integer member variables, one named _local operation counter and the other named _web API operation counter. Let's write the code that executes when the button that performs the fast local operation is executed. So we can auto-generate the method signature for the relevant button-click event handler method by double-clicking on the relevant button on our design surface like this. So when this button is clicked, we want to increment the _local operation counter integer member variable by a value of 1 and append this integer value to the literal text fast local operation completed. We are adding this string value to the list view component that we named LVW output through a call to a private method named addListItem. So let's implement the code to call the web API method that implements the long-running operation. And we want this code to fire when we click the button we have named btn web API call. So let's double-click the relevant button on our design surface to auto-generate the relevant button-click event handler method like this. So the code here is a little bit more involved than the code that runs when the user clicks the button we have named btn local operation. Let's first write the code to increment the _web API counter integer member variable by a value of 1. So we are going to use the HTTP client built-in class to make a HTTP GET request to the relevant web API action method. So let's instantiate a HTTP client object like this. The HTTP class is a member of the system.net.http namespace. So let's ensure we include the relevant directive. Let's use a HTTP response message object to encapsulate the returned value, returned from our web API component's relevant action method. So we need to run this line of code asynchronously, which means we need to include the await operator before calling the getAsync method. Note the getAsync method has the async suffix, so we know that this is an asynchronous method. Note the red squiggly line here. This is because in order to run this code asynchronously, we need to include the async modifier within our btn web API call _click event handler method's method signature. Note that we don't need to return a task object from this button click event handler method because this method is a high-level event handler. So we need to pass the URI of our web API action method to the getAsync method, so that the relevant action method is invoked on the server when the user clicks the button named btn web API call. So let's run our web API component by running the relevant web API project. So a GET request is made to the weather forecast controller by default. Remember, this code was auto-generated when we created our web API project. Let's change the URI within our browsers so that a GET request is made to the GET action method within our test long operation controller class. Let's refresh our browsers. And note, a 5-second delay before the expected result is written to the browser window. So let's copy the URI that our browser is currently pointing to. Let's go to our UWP project and let's paste the URI here as a string argument to the http client.getAsync awaitable method. Let's call an awaitable method named readAsStringAsync to retrieve the content returned from our call to the Web API component. Then let's write code to add the returned string to the list view component that we named LVW output. We can do this through a call to our private method named addListItem. So let's move the code that increments the _Web API counter variable to just above where we have added our string result to the list view component. So we need to ensure that our Web API project is first running before we run our UWP client code. So let's do that. Let's run the UWP project so we can test the performance of our user interface. Let's first test that we are able to get a result back from our Web API component. So let's click the button labeled Web API Call. Great, the result appears on the list view as expected. The result is added to the list view, and we can see it as output on the client side, displayed within the list view component. Notice that there was a delay before the result appeared in the list view because we want this call to emulate awaiting a long-running operation. Now let's test that when we execute this long-running operation that the UI thread is not blocked. The UI thread should not be blocked because we are making our GET request to the Web API component asynchronously. So let's once again click the button to make our Web API request. And now let's click the other button several times to run our fast local operation several times. Great, and you can see that the local task is running even while awaiting the result from our remote long-running server-side operation. The UI thread is not being blocked, and our asynchronous code is working as expected. You can see that when the asynchronous operation completes, the appropriate result is added to the list view component. And while we were waiting for the relatively long-running asynchronous operation to complete, we were able to run several local fast operations. So the fast local operations are running concurrently with the long-running asynchronous operation. So let's make several requests to our Web API component, and let's also run our fast local operation concurrently several times. Great, and you can see by the output appearing in our list view component that the user's experience is smooth. The user's experience is not adversely affected when the long-running Web API operation is executed. The user is able to perform other operations using our application without the user's experience being impeded by other incomplete long-running operations. This is why the task-based asynchronous pattern is so powerful. This, in my opinion, is one of the reasons why the C# language is so powerful, because a lot of the complexity in making a long-running operation run asynchronously is hidden from the developer. This complexity is abstracted. The C# language makes the inclusion of asynchronous behavior in our applications easy to implement. Please download the code for yourself and play around with the code so you can experience how the relevant asynchronous code results in a far smoother user experience than if the same code were implemented synchronously. The links to the relevant GitHub repositories have been included below in the description. I hope you have enjoyed this video on using the task-based asynchronous pattern in our code to include asynchronous behavior in our applications. In my opinion, this is one of the most important concepts in C# programming. In an age where smaller devices are used to perform relatively long-running operations, we need to ensure that our users' experience with our applications are not adversely affected by poor performance of our applications caused by synchronous code implementations of relatively long-running operations. We can drastically improve the performance of our applications by running these relatively long-running operations asynchronously. This is now easy to achieve using the C# programming language. Please consider subscribing for more content on advanced C# concepts and much more. And please ring the bell so that you'll be notified of future content released from this channel. If you feel you've gained value from viewing this video, please hit the like button. It will be greatly appreciated. Please feel free to share any of the videos released on this channel with anyone you feel may benefit from their content. I of course love reading your comments, so please feel free to share your thoughts with me in the comments section. As always, the code examples that were created in this video can be downloaded from GitHub. A link to the relevant GitHub repositories can be found below in the description. Thank you, and take care. Hi and welcome to the second part of a tutorial on asynchronous programming using the C# programming language. This video is also the second part of the 6th tutorial in an advanced C# course. In the first part of this video series on asynchronous programming using C#, we specifically focused on the async modifier, the await operator, and the task object. We discussed that there are essentially two CPU blocking operations that we may encounter when developing our applications, namely I/O-bound operations and CPU-bound operations. These CPU blocking operations can result in poor performance of our applications and ultimately result in a poor user experience, UX, with our applications. With the increased use of smaller devices that may not have the capabilities of, say, for example, a notebook or desktop computer to handle resource-intensive operations, it is essential that we apply coding methodologies in our applications to ensure that the users are not negatively impacted by potentially resource-intensive CPU-bound or I/O-bound long-running operations. The way C# developers can solve these UX issues is through the implementation of asynchronous code. The C# programming language makes available several methodologies that can be implemented in our code to achieve asynchronous behavior, namely Asynchronous Programming Model, APM. This was covered in part 3.5 of this advanced C# course, Event-Based Asynchronous Pattern, EAP, and the Task-Based Asynchronous Pattern, TAP. Microsoft's recommended approach to implementing asynchronous behavior in our C# code is to use the task-based asynchronous pattern. I recommend that you watch the first part of this video series before watching this video. For more videos on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future content released from this channel. So in the first part of this video series on asynchronous programming in C#, we focused on how to apply the task-based asynchronous pattern to handle the negative UX effects that can be caused by long-running I/O-bound operations. In this video, we'll focus on how to apply the task-based asynchronous pattern to handle the negative impact on the user's UX that can be caused by long-running CPU-bound operations. So let's start by briefly going over what is meant by I/O-bound operations and CPU-bound operations. I/O-bound tasks are delegated to the I/O subsystem. And while the relevant I/O-bound operation is handled, the CPU thread on which the I/O-bound operation was invoked is blocked from running any other operations. So while the relevant I/O-bound operation is running, the CPU is idle. All other operations are blocked from being processed by the CPU. This can mean that if the relevant operation runs for a relatively long period of time, that a delay in the user's interface responsiveness can be noticed by the user. This means the user's experience is negatively impacted by the relevant, relatively long-running I/O-bound operation. So the characteristic of non-CPU-bound processes is that they don't occupy the CPU when they are performing other operations like I/O-bound operations. I/O-bound operations include tasks such as writing to your hard disk drive, waiting for a response from the network, or querying a database. These operations cannot be sped up by fast local processing, as performance is constrained by the I/O subsystem's hardware and performance. The hardware drive's write speed will dictate how long something takes to be written. The third-party server response time will determine how quickly you can process a request. CPU-bound means the limiting factor in a particular task or algorithm is doing calculations. The only way to speed up the relevant CPU-bound operation is increased CPU power. Adding more memory, a faster I/O, for example, will not help. Examples of CPU-bound tasks are video-audio content conversion compression algorithms, search algorithms, graphics processing, rendering games or videos, heavy mathematical computations like calculating factorials, matrix multiplication, finding prime numbers, etc., encryption, decryption operations. So basically tasks that require the CPU to perform computations. So tasks that perform particularly intensive calculations may cause performance issues and ultimately UX issues when a user runs our applications. The asynchronous handling of CPU-bound operations are implemented differently than the way I/O-bound operations are implemented. For a comprehensive explanation of how we can handle I/O-bound operations asynchronously in C# code, please view the first part of this video series. In this video, we'll focus on handling CPU-bound operations asynchronously. So let's look at a code example where we'll run a number of CPU-bound operations in parallel to one another. Which, as we'll demonstrate, will result in an overall performance advantage over running the same CPU-bound operations synchronously. So let's create a console application and name it Financial Trading Platform Application. So the theme of this code example is a trading platform. The user of this application can analyze stock market charts that will include technical indicators to help the user decide to open or close a position regarding a particular stock. I'm going to drastically simplify this code example so that we can focus on the principles involved in running multiple computational operations asynchronously. The technical indicator information that will be presented with the relevant stock chart will be calculated on the fly. So in this example, the technical indicators that will be calculated on the fly and presented to the user with the relevant stock chart are, for example, stochastics, fast-moving average, slow-moving average, and Bollinger Bands. I'm not going to go into detail regarding the meaning of these technical indicators. Basically, they aid the trader in deciding whether a stock is overbought or oversold, or whether it has growing price momentum or losing price momentum. Ultimately, these technical indicators aid the trader in the trader's decision to buy or sell a quantity of a particular stock. So, for example, the stochastics, the fast-moving average, the slow-moving average, and the Bollinger Bands can all be calculated in parallel to one another. These calculations can be coded to run concurrently rather than consecutively. So let's create a public class named Stock Market Technical Analysis Data. Let's create a constructor in our new class. Just for the sake of making this example feel more authentic, let's add 3 parameters to this constructor. We are going to keep this example very simple, and these parameters will not actually be utilized. The arguments passed into these parameters would be used as query criteria when getting the raw stock market data from a remote source. So the first parameter is stock symbol as string, representing a particular stock that the user wishes to analyze. For example, Apple, Amazon, Tesla, Anglo Gold, whatever it might be. The second parameter represents the start date and is defined as date time. The third parameter represents the end date and is also defined as date time. So the date time arguments passed into the second and third parameters will represent time period criteria pertaining to the time period over which the relevant stock market data was captured. In the interests of keeping this example simple, and in the interests of time, we are not going to include any code within this constructor. Let's simply comment that code would go here for retrieving data from a remote server. So let's use our imaginations and say that an IO-bound asynchronous HTTP request is made to a Web API component to download the relevant raw stock market data within this constructor. This data will be used to calculate relevant technical indicator information so that the user can glean meaningful information from the downloaded raw stock market related data. So let's create a few methods. The first 4 methods won't be all that computationally intensive. The first 4 methods will be responsible for getting the daily, opening, closing, high, and low prices for the relevant stock. We'll then include the more computationally intensive methods in this class, i.e. the methods used for calculating the relevant technical indicator information. For example, the stochastics, fast-moving average, slow-moving average, etc. So the first method will be responsible for performing an operation to get the daily opening prices for the relevant stock from the raw data that is retrieved within the constructor. So this method is appropriately named getOpeningPrices. So the returned values for all of these methods defined within this class will be an array of values of type decimal. This method will return an array of decimal values representing the opening prices for the relevant stock. So in each of the methods we'll create for this class, we'll write the method's name and the thread ID representing the thread on which the method will run to the console screen. We are going to run multiple methods in this class on multiple threads concurrently. So let's write code to output a narrative to the screen, which will serve as a substitute for presenting the actual data that would be required in a real-world application. To represent the duration of time the operation performed by the relevant method could take, let's make the thread on which the method will run sleep for a specified amount of time. So for this method, which won't require much computation, we'll make the thread of execution sleep for 1,000 milliseconds, which is 1 second. And then let's just return an empty decimal array. The data in this example is not important. In this example, we want to focus on the asynchronous principles rather than the real-world trading platform example that this code represents. Okay, and the other methods can be implemented in much the same way. Let's copy this method, and let's paste it 8 times. Then let's modify the code appropriately for each method. So the next method is named getClosingPrices and is responsible for retrieving the daily closing prices of the relevant stock from the raw downloaded stock market data. Let's say it runs for 1,000 milliseconds. The next method is named getPriceHighs. This method is responsible for getting the daily highs for the relevant stock. This operation also runs for 1,000 milliseconds. The next method is named getPriceLows. This method is responsible for getting the daily lows for the relevant stock. Let's say this method runs for 1,000 milliseconds. So all of the methods that we have added so far run for 1,000 milliseconds. Now we are getting to the methods that are more computationally intensive. This method is named calculateStochastics. This method is responsible for calculating technical indicator information to help a trader decide whether a stock is overbought or oversold, which ultimately aids the trader with the decision to buy or sell a quantity of a particular stock at the current stock price. So let's say that this may be a particularly computationally intensive operation. So let's say this operation takes 10 seconds to complete. So let's pass in an argument of 10,000 milliseconds to the thread.sleep method. The next method is named calculateFastMovingAverage. Let's say that this operation is also computationally intensive, so let's put the relevant thread to sleep for 6 seconds. The next method is named calculateSlowMovingAverage, let's put the relevant thread to sleep for 7 seconds. The next method is named calculate upper bound Bollinger Band. The next method is named calculate lower bound Bollinger Band. Let's put the relevant thread to sleep for 5 seconds. Let's put the thread on which this method runs to sleep for 5 seconds. The Bollinger Bands can also be used by traders to ascertain whether the relevant stock is overbought or oversold, which ultimately aids the trader's decision to buy or sell a quantity of the relevant stock. So you can see that the last 5 methods in this class could potentially be computationally intensive, as these methods perform the operations of calculating technical indicator information from potentially large amounts of raw stock market data. So let's go to the main method, where we'll write code to call the methods that we have just created in our stock market technical analysis data class. So let's first write to the console screen that the main method is being called. In this output to the screen, let's include the ID of the thread on which the main method will run. We can get the thread ID from the thread.currentThread.managedThreadID property. And we also want to include the thread name, which of course is the main method. So let's first demonstrate running the first 4 methods in the stock market technical analysis data class synchronously, so that we can later run these methods asynchronously and then compare the performance difference. So let's instantiate a new object from our stock market technical analysis data user-defined type. Let's say we want to download raw stock market data relating to the fictional stock represented by the symbol of STKZA for data captured between the dates 1st of January 2010 and 1st of January 2020. So we want the specified stock market data for a particular stock captured over a specified 10-year period. Let's write code to run these methods synchronously. So let's call the getOpeningPrices method. Then the getClosingPrices method. Then the getPriceHighs method. And lastly, the getPriceLows method. So in order to see how long it takes for all 4 methods to complete, let's capture and store the current date-time value captured before we call the relevant 4 methods. Then let's subtract the date-time value captured before the 4 methods are run from the date-time value captured after our 4 methods have completed. We are doing this so that we can see how many seconds have elapsed between the time we started to run our 4 methods and the time the operations carried out within these methods completed. So each of these methods have been coded to take 1000 milliseconds or 1 second to complete. Let's add a method that denotes adding the relevant data to the stock chart that will be displayed to the trader. Let's name this method displayDataOnChart. To keep things simple, we can simply write a message to the screen representing that this method has displayed the chart with all the requested data, including relevant technical indicator information, to the trader. So let's run the code. And we can see from the results that all of these methods are running synchronously on the main thread. The thread ID of all of these methods is 1. We can see that each method ran consecutively. We can see this because each of the 4 methods ran for 1 second and a total of 4 seconds was taken for all 4 methods to complete. So now let's run these methods asynchronously using the task.run method. So let's create a generic list to store the generic tasks that accept an array of decimals as the generic argument. Remember, each of our methods within the stock market technical analysis data class return an array of decimal values. Let's ensure that we include the relevant directives. So we need to include the system.threading.tasks directive, and we also need to include the system.collections.generic directive. To be explicit, let's first create our generic task objects and appropriately encapsulate the 4 method calls. And note that the generic argument for each of the generic task objects is an array of decimal values because each of the relevant methods that the task objects encapsulate returns an array of decimal values. Right, let's write the code to add each of the methods encapsulated within the task objects to our list. Now we can use the task.waitAll method to block the main thread until all the tasks have completed. So all of our tasks will run in parallel on background threads, and the main thread will be blocked by the task.waitAll method until all 4 methods have completed. For more information on the task.waitAll method, please navigate to this URL. So we need to pass our list of tasks to the task.waitAll method. But the task.waitAll method expects an array, so let's use the toArray method to explicitly cast our list of generic task objects to an array of generic task objects. So at this point in the code, i.e. after the task.waitAll method call, we know that all of our tasks have completed, so we can get the results of each of our tasks like this. Great, let's run the code. If we look at the output, we can see that the threads on which each of these methods ran have different thread IDs. Behind the scenes, our code has run these methods on different threads. When we ran these methods synchronously, these methods ran consecutively and ran on one thread, the main thread. So I've noticed there's a little problem with the text output. It says 1 seconds and should say 1 second. So let's add a ternary operator to our code so that when 1 second has elapsed, our code outputs 1 second rather than 1 seconds. We only want to output seconds if the time that has elapsed is greater than 1 second. Let's run the code to check our fix. Great! So let's write code to run all 9 methods synchronously, and after this, we'll run all 9 of these same methods asynchronously. So we'll now be running some of the more computationally intensive methods within our stock market technical analysis data class in this demonstration. Let's run the code. And you can see that there is a significant time lag when running this code synchronously before all our methods complete and output is presented to the screen. Let's write the code to run our methods asynchronously using the task.run method. Right, let's run the code. You can see by the thread IDs outputted to the screen that our methods are not running on the main thread and are running concurrently on background threads. So in this video, we have covered the basics of running multiple CPU-bound operations asynchronously. In this video series on asynchronous programming in C#, we have covered the basics of how we can improve performance of our applications through asynchronous programming when encountering either of the 2 types of blocking operations, namely I/O-bound operations and CPU-bound operations. In the next video, we'll look at the best practices and caveats of which we must be cognizant when running I/O-bound and CPU-bound operations asynchronously. For more content like this and much more, please consider subscribing and please ring the bell so that you'll be notified of future content released from this channel. If you feel you've gained value from viewing this video, please smash the like button. It will be greatly appreciated. Please feel free to share any of the videos created by this channel with anyone you feel may benefit from their content. I love reading your comments, so please feel free to share your thoughts with me in the comments section. All code created in these videos can be downloaded from GitHub. Please see below in the description links to the appropriate GitHub repositories. Hi and welcome to the third part of a tutorial on asynchronous programming using the C# programming language. This video is also the third part of the 6th tutorial in an advanced C# course. In the first and second parts of this video series, we looked at how to apply asynchronous code so as to alleviate the negative effects of blocking operations on an application's UX, user experience. Certain long-running operations performed by our applications can be the source of poor performance of our applications. For example, long-running operations performed from WPF, UWP, or Xamarin applications can cause the UI, user interface, to be periodically unresponsive. This can be frustrating for the user of our applications. The user will have a suboptimal user experience. C# provides us as developers with appropriate tools to handle these long-running operations asynchronously with relative ease. So let's discuss the difference between I/O-bound operations and CPU-bound operations, and this will set us up for later when we create a code example to help us understand best practices when applying asynchronous code to handle I/O-bound or CPU-bound operations. So in this video series, we have already discussed that the two kinds of CPU blocking operations are CPU-bound operations and I/O-bound operations. CPU-bound operations are operations that perform computations that need to be handled by the CPU, for example, mathematical operations, encryption-decryption operations, graphics-related operations, financial calculations, etc. Basically, computational operations. I/O-bound operations are operations that are delegated to the I/O subsystem to perform tasks such as writing to a hard disk drive, engaging the I/O subsystem to perform requests across the network, file handling operations, etc. We discussed that I/O-bound operations are more commonly encountered than CPU-bound operations. I/O-bound operations are also generally a lot slower than CPU-bound operations. So this video is about best practices when applying asynchronous code in our applications. Please view the first and second parts of this video series on asynchronous programming for a foundational understanding of I/O-bound operations and CPU-bound operations in the context of asynchronous programming in C#. The recommended coding methodology provided by Microsoft in the C# language to create asynchronous behavior in our applications is known as the Task-Based Asynchronous Pattern, TAP. Over the last two videos in this series, we have discussed why we should implement asynchronous code. The simple answer is to improve the performance of our applications. In this video, let's clarify the best practices when applying writing code to run the relevant code asynchronously. Let's start with I/O-bound operations. As we have discussed, I/O-bound operations refer to operations like, for example, file handling operations, making requests across a network, writing data to a database, reading data from a database, etc. Operations that engage the I/O subsystem. We can handle I/O-bound operations asynchronously, both on the client side, for example, in WPF, UWP, WinForms, or Xamarin applications. We can also handle I/O-bound operations asynchronously on the server side, in, for example, Web API or ASP.NET MVC applications. I/O-bound operations can be handled using async await. In simple terms, an asynchronous method that returns a task object can be preceded with the await operator, which means we can run the operation asynchronously using async await. So, for example, for a .NET client application, a button is clicked. Within the button click event handler method, an asynchronous method is invoked. So the asynchronous method is invoked on the UI thread. This means that immediately after the asynchronous method is invoked, the UI thread is free to be utilized to process other operations. The user interface, UI, does not freeze while the asynchronous method is running. The user is able to, for example, click other buttons and invoke other operations that can be invoked on the UI thread. When an asynchronous method is called to perform the relevant I/O-bound operation, the task is immediately delegated to the I/O subsystem. And instead of blocking the CPU, as would be the case if we were running the I/O-bound operation synchronously, the async modifier and await operator instruct the .NET runtime to ensure that the CPU is not blocked during the running of the IO-bound operation. This means that other operations can utilize the CPU even while the IO-bound operation is running. Very briefly, what is happening is that when the .NET runtime encounters the await operator, as discussed, the thread on which the operation is invoked, on the client this would be the UI thread for example, is immediately released. So at this time, code in the relevant method is suspended, i.e. the lines of code that follow the line of code that contains the await operator in the relevant method will not be executed until the asynchronous IO-bound operation completes. While the asynchronous IO-bound operation is running, however, the UI thread can be used to process other operations, for example, invoked from clicking another button on the UI. But a promise is returned to the line of code containing the await operator is made. So when the relevant asynchronous operation completes, the .NET runtime returns to the line of code containing the await operator, returns a value if required, and continues to execute the lines of code from that point in the relevant method. So the key point of this explanation is that unlike for CPU-bound operations, IO-bound operations generally don't require additional background threads. In this example, the .NET runtime is delegating the IO-bound operation to the IO subsystem and not to a new thread required from the thread pool. So I think before we continue, let's ensure that we have a clear understanding of what is meant by the following terms: thread and thread pool. Let's start with the term thread. A thread in computer science is short for a thread of execution. Threads are a way for a program to divide itself into two or more simultaneously or pseudo-simultaneously running tasks. Thread pool. A thread pool is a group of pre-instantiated idle threads which stand ready to be given work. So, a thread pool is created so that threads are readily available to a program, which means when a program requires a thread, the program can acquire the thread from the thread pool rather than incur the overhead of instantiating a new thread. So, let's go back to the example demonstrated in the second part of this video series, where the task.run method was used to run CPU-bound operations. We demonstrated how each method that was run through the implementation of the task.run method was run on its own dedicated background thread. So each time the task.run method is invoked, a new thread is taken from the thread pool and used to run the relevant CPU-bound operation. So this resulted in the methods that encapsulate the CPU-bound operations running concurrently, i.e. asynchronously, rather than running one after the other, i.e. synchronously. If you haven't yet viewed the second part of this video series, please view this video for a foundational understanding of running multiple CPU-bound operations concurrently on multiple background threads. So the key takeaway here is that when an IO-bound operation is run using the async modifier and the await operator, a background thread is not required to handle the operation. The operation is delegated by the .NET runtime to the IO subsystem. When a CPU-bound operation is run using the task.run method, a background thread is used to run the operation in the background concurrently with the main thread of execution. So now, with a foundational understanding of the differences of how IO-bound and CPU-bound operations are handled asynchronously, let's look at best practices regarding implementing each of these types of operations asynchronously. So with running IO-bound operations asynchronously, there's less to be concerned about, simply because of the way the IO-bound operations are handled under the hood. IO-bound operations can be delegated to the IO subsystem, and the need to use additional background threads is not necessary. With running CPU-bound operations asynchronously, under the hood, the .NET runtime employs additional background threads to run the CPU-bound operations. This, for example, means that multiple tasks can run on the additional background threads concurrently. There may be times where using multiple threads is undesirable and may not result in the desired performance benefit. There are times when running multiple threads to perform tasks in parallel may result in an overall poorer performance. An example of this is running CPU-bound operations from within server-side code, for example, code implemented for ASP.NET MVC applications or code implemented for Web API components. We'll discuss why CPU-bound operations should be run synchronously under these scenarios a bit later in this video. So let's create a code example to help us understand best practices when confronted with issues relating to asynchronous programming in C#. The theme of this client application will be the same as the theme we used in the previous video in this series, i.e., a financial trading platform. So in the last video, we created a console application to get a general idea of running CPU-bound operations. In this video, let's create a new blank UWP project. UWP stands for Universal Windows Platform. Let's name this project Financial Trading Platform UWP. Let's set up a basic UI, user interface. Let's drag a button onto the designer surface Let's enlarge this button a bit. And name it BTN Fast Local Operation. Let's label this button Fast Local Operation. Let's drag another button onto the designer surface, just below the button we have just added. Let's name this button BTN CPU Bound Operations. Let's label this button CPU Bound Operations. And lastly, let's drag a list view control onto the designer surface and position this control to the right of our buttons, like this. Let's name this list view control LVW output. So before we add code directly to this file, let's add another project to this solution. We want our code to be reusable across both server-side and client-side projects. So let's create a standard library project to our solution and let's name this project Stock Market Component. Let's add a reference to the Stock Market Component standard library project from our UWP client project. Let's delete the class file that has been generated in our standard library project and let's add a class named Stock Market Data to our project. Let's add a method named getDataAsync. This method represents retrieving relevant stock market data from a server, so it is an I/O-bound operation. The method will return a string to the calling client code. So let's include the async modifier in the method definition, as well as a generic task type that accepts a string as the data type argument. Notice that we have included the async suffix in our method name. This lets the developer know that this is code that should be called asynchronously. So when the calling client code writes code to call this method, the developer should include the await operator preceding the method call, as well as include the async modifier in the method definition of the method where the relevant async call resides. So in the interests of time, we'll simply include placeholder code for this method. So let's use the task.delay method to represent the time that the work could take to carry out our relevant I/O-bound task. So let's say this process takes 5 seconds. So let's pass 5,000 milliseconds to the task.delay method. Let's then simply return a string value representing the stock market data that has been retrieved from the remote server. So let's simply return the literal text stock market data from this method. We must also include the await operator preceding our call to the task.delay method. Let's add a new class, and let's name this class Stock Market Data Analysis. So let's add a constructor that contains a parameter named data, which will represent the downloaded stock market data. For the purposes of this example, we don't need to include any code within the constructor. So very much like the code example in the previous video of this video series, let's include methods that calculate the technical indicators that the user of our application can use to aid the user's decision to buy or sell a quantity of a particular stock. The technical indicators that we'll refer to in this example will be the fast-moving average, the slow-moving average, stochastics, and Bollinger Bands. If you are not familiar with these terms, don't worry. The only thing that you need to know to follow along with this example is that calculating the data for these financial trading-related technical indicators are CPU intensive. They are CPU-bound operations. This is why I've chosen these technical indicators for this example, i.e. to serve as intensive, long-running, CPU-bound operations. So let's include a method to calculate the fast-moving average. So for these methods that represent CPU-bound operations, we can simply put the current thread to sleep for a specified amount of time, representing the time that the relevant operation may take to complete. So for this method, let's put the thread to sleep for 6 seconds. Then, for the purposes of this demonstration, let's simply return the method name and the thread ID to the calling code. Let's duplicate this method 3 times. These additional 3 methods represent the calculation of other technical indicators. So we can maintain the general structure of the methods that we have just created as they are, and simply change the method names and the time durations that represent the time the method takes to complete. Please note that the time durations that are being specified here are completely arbitrary and have been chosen only for demonstration purposes. So this method represents calculating the slow-moving average. Let's name this method calculate slow-moving average. Let's put the relevant thread to sleep for 7 seconds. This method represents calculating the stochastics. Let's name this method calculate stochastics. Let's put the relevant thread to sleep for 10 seconds. This method represents calculating the Bollinger Bands. Let's name this method calculate Bollinger Bands. Let's put the relevant thread to sleep for 5 seconds. Great, so let's say that we now have a reusable standard library component for calculating stock market technical indicator information completed. So just to confirm that we have already referenced this reusable component from our UWP client application. Great. So let's add some code to add the output of our methods to our list view control that we named LVW output. So let's create a private method named addListItem. So you're of course welcome to follow me as I create the code for this method, or you can of course copy the code from GitHub. A link to the relevant GitHub repository is available below in the description. Great, so let's include code within our button-click event handlers. To create a button-click event handler definition, we can simply go to our designer surface and double-click on the relevant button, like this. So we are first going to create code for the fast local operation. So let's create the button-click event handling method definition for the method that will execute our CPU-bound operations. These CPU-bound operations are encapsulated within the methods in our stock market data analysis class that reside in our standard library project. Let's ensure that we have a directive to the stock market component namespace. So let's instantiate an object from our stock market data analysis class, which resides in our stock market component standard library project. For now, let's simply pass in the literal text data to the constructor of the stock market data analysis class to represent the raw stock market data downloaded from a remote server. So let's write code first to run all of these CPU-bound operations in parallel to one another in much the same way as we demonstrated in the code example in the previous part of this video series. So firstly, let's create a list of generic task objects that accept the string data type as their data type arguments. So we know that the task.run method returns a task object or generic task object. The methods we wish to call all return strings, so each item in the relevant list must be strongly typed with a generic task object that accepts the string data type as an argument. Right, so let's add the tasks we wish to run to our list, like this. Then we can call the task.waitAll method, and in a bit I'll explain why the task.waitAll method is not the best method to call in this context. So in the code following the task.waitAll method, we know that the relevant methods that have run asynchronously have completed, so we can add the returned values from our methods to our LVW output list view control. Let's write the code to do this. Right, let's run the code. So now when I press the button marked CPU-bound operations, notice that our UI is unresponsive when we try to perform any other operations. So I'm attempting to click the button marked Fast Local Operation. The button cannot be clicked because the screen is frozen, and therefore the output from this action is not presented to the screen in our list view component. The UI is unresponsive when I click the button labeled Fast Local Operation, because the UI thread is blocked. We have written our code to run a batch of methods asynchronously, but we have also written code to block the UI thread while our CPU-bound operations are running. The waitAll method blocks the UI thread until all the relevant tasks have completed. So even though the CPU-bound operations, like for example, calculate stochastics, calculate fast-moving average, etc., are running in parallel to one another on background threads, which will give us a performance advantage, the UI thread is being blocked while these CPU-bound operations are running. This is not ideal. So we can solve this issue because we can in fact use the await operator when running a batch of CPU-bound operations. We can achieve this by using the whenAll method instead of using the UI blocking waitAll method for running a batch of CPU-bound operations on background threads. So let's replace the waitAll method with the whenAll method. For more information on the whenAll method, please navigate to this URL. So please note that the waitAll method does not return a task object or generic task object. So this means we cannot call this method using async await. The waitAll method blocks the UI thread until the tasks within the relevant batch have completed. The tasks will be run concurrently on separate background threads, but the UI thread will be blocked while the tasks are running. The whenAll method, however, does return a task object or generic task object. This means we can call the whenAll method using async await, which means that we can call the whenAll method to run our tasks concurrently without blocking the UI thread. The UI will still be responsive even while we are running a batch of CPU-bound operations when we are using the whenAll method. So let's proceed our call to the whenAll method with the await operator, like this. We of course need to also include the async modifier in the relevant button click event handler method's signature, like this. Let's run the code. Let's click the button marked CPU-bound operations. And now when we run the code, the UI thread is not blocked and we are able to perform the fast local operation while the CPU-bound operations are running in the background. We can perform other operations concurrently while the relevant CPU-bound operations are running. So the task.run method returns a task object or generic task object. This means we can use the await operator when we call a CPU-bound operation in this way. So to prove this, rather than calling a batch of CPU-bound operations, as we are doing here, let's run just one of the CPU-bound operations using the task.run method. So let's run the calculate stochastics method using the task.run method. So we can call this method on a background thread asynchronously like this. Let's run the code. Let's click the CPU-bound operations button, and you can see that while the calculate stochastics method is running, we are able to click the fast local operation button. the fast local operation button can run concurrently with the operation performed by the calculate stochastics method. And as we have already proven, we can also run a batch of CPU-bound operations on background threads without blocking the UI thread using the when_all method. So let's change the code back to the way it was so that we can call a batch of CPU-bound operations using task.run, async await, and when_all. Then we could reuse this functionality because we have written our CPU-bound operations in a reusable library component. This brings us to an important best practice when implementing asynchronous code for CPU-bound operations. The developer should never include the task.run method within reusable components. Always let the developer decide whether to run an operation synchronously or asynchronously. So the consumer of the component should always have the choice to run an operation contained within, for example, a library component synchronously or asynchronously. In our example, we have chosen to run our operations encapsulated within the stock market data analysis component project asynchronously, but we could have chosen to run them synchronously. We have proven in our demonstration that running the CPU-bound operations asynchronously gives us a huge performance advantage. We did, however, have the choice to run these operations synchronously or asynchronously because the operations are not implemented to run asynchronously within any of the methods of the component itself, i.e., we have not implemented the task.run method within the stock market data analysis component project. So in the stock market data class, we have written an IO-bound operation that is responsible for downloading the raw stock market data from a remote server. This is different to a CPU-bound operation because it engages the IO subsystem and not the thread pool to acquire a background thread. So let's write code to run this IO-bound operation in order to download the relevant raw stock market data before calculations are performed from the raw stock market data. So we could invoke the IO-bound method lazily like this. So let's create a member variable named _data. Then within the relevant button click event handler, we can check to see if the _data variable is null. If it is null, we can then run the IO-bound operation. If the _data variable is not null, then it means we have the data and can pass it into the stock market data analysis classes constructor when instantiating the relevant object. It is best to include the task.run method close to the relevant event handler method, as we have done here. We have control over whether we want to run these operations using the task.run method on background threads or run them synchronously. So calling the task.run method directly from the relevant event handler method, like for example a button click event handler, is a best practice. Another best practice is that if the relevant method's code doesn't need to run on the original thread once the CPU-bound operations have completed, then we can in fact gain a bit of a performance boost by not returning to the main thread. The rule of thumb here is don't run code on the main UI thread unless you have to. So we can achieve this performance boost by using the configure await method. So the when_all method returns a task object, which implements the configure await method. This means we can call the configure await method like this. Notice we are passing in false as the parameter to this method. We are saying that after the calculations are performed by the CPU-bound operations, don't return to the main thread. So for example, a context where this would be appropriate would be once the calculations are completed, we want to save the calculated data to a file. So in this scenario, we don't want to display the data on, for example, a stock market chart. We only want to save the data locally. In this context, there's no reason to return to the main thread. However, in a context where we need to display the information on a chart, we of course would need to return to the main thread. The last best practice I would like to include in this video is that we should avoid including the task.run method within methods implemented in server-side components. If, for example, we implemented our trading platform calculation functionality as a software as a service application, For the purpose of providing calculated technical indicator information to web-based client trading platforms, we should not implement these CPU-bound operations using the task.run method. On the surface, it may seem like this would give us a performance advantage, but in reality, this puts an unnecessary strain on server resources and ultimately can adversely affect performance. The reason for this is that with a server-side component, say for example implemented as an ASP.NET Web API component, you may have thousands of HTTP requests coming in to the relevant Web API component. Each HTTP request requires a thread from the server's thread pool. If the code within the relevant server-side method is coded to run 4 operations asynchronously through the use of the task.run method, then your Web API component needs to acquire an additional 4 threads to carry out the instructions implemented in the relevant method. This could cause an unacceptably high use of server resources, which could adversely affect the overall performance of the relevant server and ultimately negatively impact the user's experience with the relevant application. So the moral of this story is avoid running additional background threads on the server side. Rather run CPU-bound operations synchronously on the server side. You can still ensure that the client-side UI is responsive by calling the server-side code using async await. Remember, an HTTP request from the client's perspective is an IO-bound operation. Note that running IO-bound operations on the server is different to running CPU-bound operations on the server. An example would be downloading the raw stock market data from the server. Perhaps the server-side code simply retrieves the raw stock market data from a database before returning the relevant data to the client. This IO-bound operation can be written on the server using async await. The IO-bound code does not require additional threads and therefore additional server-side resources. When a client request is made to run the method responsible for running the relevant IO-bound operation on the server, the thread used for processing the request can be released to handle other requests while the relevant IO-bound operation is being performed. CPU-bound operations that are invoked using task.run will require additional threads, which means additional server resources will be required. In summary, when it comes to best practices in terms of asynchronous programming in C#, know the nature of your asynchronous code. Ask the question, is the operation CPU-bound or IO-bound, and then apply the relevant asynchronous code appropriately. Avoid writing CPU-bound operations within reusable library components using the task.run method. Let the consumer of the library component choose whether to run the CPU-bound operations synchronously or asynchronously. Methods that run IO-bound operations asynchronously, included within reusable library components, should include the async suffix as part of the relevant method's name. This will let the consumer of your library know that the relevant method should be run asynchronously using async await. On the client side, run CPU-bound operations close to the relevant UI event handler method. For example, use the task.run method directly within the relevant button-click event handler method. If, for example, a button-click event handler method needs to perform a CPU-bound operation asynchronously on a background thread and subsequently code within that method does not require a return to the UI thread, explicitly let the .NET runtime know that it is unnecessary to return to the UI thread once the CPU-bound operation has completed by appropriately calling the configure await method. This can result in a performance boost. Avoid running CPU-bound operations on the server side using the task.run method. These operations require additional threads, which can result in a strain on server-side resources, and the issue will be compounded if the server is handling hundreds or thousands of HTTP requests. Running IO-bound operations, for example, retrieving information from a Web API component, reading data from a database or writing data to a database on the server side using async await, is good practice because the main thread of execution is free to handle other client requests while the relevant IO-bound operation is running. So in this video, we covered how to implement best practices in our code when running code asynchronously in C#. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future videos released from this channel. If you feel you've gained value from viewing this video, please smash the like button. It will be greatly appreciated. Please feel free to share any of the videos created by this channel with anyone you feel may benefit from their content. I love reading your comments, so please feel free to share your thoughts with me in the comments section. All code created in these videos can be downloaded from GitHub. Please see below in the description links to the appropriate GitHub repository. Hi and welcome to the fourth and final video in a video series on asynchronous programming in C#. This video is also part of the 6th tutorial in an advanced C# course. This video is a continuation of the last 3 videos in this video series on asynchronous programming, so please view each of the preceding videos in this video series before viewing this video. In this video, we are going to look at how to use a cancellation token source object to explicitly cancel an asynchronous task or many asynchronous tasks in code before the relevant task or tasks have completed using one cancellation token source object. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future content released from this channel. Right, so to gain an understanding of how we are able to implement code to cancel one asynchronous operation or multiple asynchronous operations using one cancellation token source object, let's look at a practical code example. So I'm going to base this code example on an example included in the Microsoft Docs. So please navigate to this URL. A link to this URL has been included below in the description. You can see that this web page is entitled Cancel a list of tasks, in brackets C#. So let's first look at the prerequisites section of this document. I want to draw your attention to the first prerequisite. So this tutorial requires the following: .NET 5 SDK. I'm actually not going to install the .NET 5 SDK on my Windows platform at this time, and we'll be creating this example using the .NET Core version 3.1 runtime. We are able to run this example using the .NET Core version 3.1 runtime, but we will need to make a small modification to the code to get this working. If you do decide to install the .NET 5 SDK, know that the version available at the time of writing this tutorial is not yet the official release. It is an RC release, which stands for Recommended Candidate. So if you install .NET 5 SDK, I recommend reading all associated content that can be found at this URL, that we can navigate to when we click the link here marked .NET 5 or later SDK. This content can guide us in, for example, which version of Visual Studio should be installed to support the current RC version of .NET 5. I also recommend reading this blog post posted by Richard Lander. This blog post can be found at this URL. For a foundational understanding of .NET 5, I recommend viewing a video created by this channel, which can be found at this URL. As always, I have included all relevant links below in the description. I'll demonstrate how we are able to implement and run this code example, so even if you decide not to install .NET 5 SDK at this time, and your latest version of the .NET runtime is .NET Core version 3.1, you're still able to follow along with the implementation of this example. To enable running this code using the .NET Core 3.1 runtime, we only need to apply one simple code modification. We'll apply this modification when appropriate. Let's look at the first paragraph on this web page. In the first paragraph on this web page, it states, you can cancel an asynchronous console application if you don't want to wait for it to finish. By following the example in this topic, you can add a cancellation to an application that downloads the contents of a list of websites. You can cancel many tasks by associating the cancellation token source instance with each task. If you select the Enter key, you cancel all tasks that aren't yet complete. So we are going to base our practical code example on the example here provided in this web page in the Microsoft Docs. However, we are going to implement our code example as a UWP Universal Windows Platform project instead of how it is implemented in this Microsoft example as a .NET Core Console application. We are going to copy aspects of the code provided in the Microsoft code example over to our code editor in a step-by-step fashion. So let's create a UWP project and let's name our project Cancel Download Async Operations UWP. Let's set up a basic UI, user interface. So let's start by dragging a button onto our designer surface. Let's name this button BTN Cancel Download, and let's label this button Cancel Download. Let's drag another button onto the designer surface just below the button we have just added. Let's name this button BTN Download Content. Let's label this button Download Content. Let's drag a list view control onto the designer surface and position it so that the contents of the list view control will appear to the right of our buttons. Let's name this list view control LVW Output. So let's access the main page.xaml.cs file to add the relevant functionality for our UI. Firstly, let's ensure that we include all the relevant using directives. Let's copy them from the relevant section of the relevant Microsoft web page and paste them into our code editor like this. Let's then copy and paste the relevant fields like this. These fields contain an object reference variable of type cancellation token source that will be used to cancel the relevant asynchronous tasks, a collection of URLs of type IEnumerable that will store the addresses of the web pages that will be downloaded by the relevant asynchronous operations, and an object reference variable of type HTTP client that will handle the connection to the relevant web pages and also handle the download functionality. So in our application, these fields don't need to be static, so let's remove the static keywords. Let's read the explanation provided under the relevant code fragment containing the fields we have just copied. The cancellation token source is used to signal a requested cancellation to a cancellation token. The HTTP client exposes the ability to send HTTP requests and receive HTTP responses. The s_URL list holds all the URLs that the application plans to process. So the next section of the Microsoft web page is an explanation of the code within the entry point of the application, i.e. the main method. As discussed, the Microsoft Code example is based on the .NET Core console project template. We are basing our application on the UWP Universal Windows Platform project template, so our code implementation will be slightly different. So the main difference between our code and the Microsoft example is that the Microsoft example is implemented so that when the user presses the Enter key, this action will trigger the cancellation of the relevant operations, i.e., the operations responsible for downloading the contents of a collection of web pages. The UWP project template makes our code implementation simpler because we can leverage a button-click event handler for this purpose. So in this Microsoft example, the tasks responsible for downloading the content and outputting the relevant information about the content are invoked through a call to the method named SumPageSizesAsync. The cancellation functionality is handled in the code above this method call. The method is implemented through a lambda expression here. Code is implemented here using the whenAny method. The whenAny method basically accepts an array of task objects. So the SumPageSizesAsync method returns a task, and the relevant lambda expression responsible for the cancellation functionality is run using the task.run method, which also returns a task object. Then an array containing a task object encapsulating the cancellation operation, as discussed, this is implemented as an asynchronous method in the form of a lambda expression, and the download operation, which is implemented as a named method, are passed into the whenAny method. The task.whenAny method will complete when any one of the operations passed within the relevant array argument completes. This means that if the user presses the Enter key before the download operation, i.e., which is invoked by the call to the SumPageSizesAsync method, completes, this will effectively cancel the asynchronous web page download operations and associated functionality, for example, summing up the number of bytes downloaded, etc. So we used the whenAll method in the previous video, which allowed us to run a collection of tasks in parallel without blocking the main thread. The whenAny method is similar, but the difference is that the whenAll method completes when all the relevant operations have completed. The whenAny method completes when any one of the relevant operations have completed. Like the whenAll method, the whenAny method does not block the main thread. So this means that in the context of the Microsoft example here, if the user presses the Enter key before the operations invoked by the SumPageSizesAsync method complete, this will result in the downloading operations being cancelled. The cancellation operation will complete before the download operations complete, resulting in the download operations being cancelled. So we are going to implement similar code within our example. The difference is that we'll implement a cancellation button to enable the user to cancel the download operations by pressing the cancellation button, rather than implementing code to allow the user to press the Enter key for this purpose. With our UWP project, we have the benefit of a rich user interface. So let's go to our code behind class, i.e. the mainpage.xaml.cs file, and write a private method that will encapsulate the functionality to add a list item to our list view control, i.e. the control we have named LVW output. We have already written a private method encapsulating this functionality in our previous example, so let's navigate to the relevant GitHub repository and copy this private method. This URL has been included below in the description. So here we can see the relevant method named addListItem. Let's copy this method to our clipboards and appropriately paste this method within our mainpage.xaml.cs file. So we can now write the codes to handle the button-click events. Let's start with the download functionality. First, let's create two private methods that are responsible for downloading the relevant content, calculating the size of the relevant content, and outputting status information to the user regarding the relevant downloaded content. So in the Microsoft Docs webpage, let's look at the section entitled Create the Asynchronous SumPageSizes method. Let's copy this method and appropriately paste the method within our mainpage.xaml.cs file. In our example, this method does not need to be static, so let's remove the static keyword from the method definition of the SumPageSizes async method. And let's include the private access modifier within the SumPageSizes async method's method definition. The next thing we need to modify in our example for the SumPageSizes async method is where the code writes text to the console screen. Our output will be added to the list view control that we named LVW output. So let's replace the console.write methods with a call to our private method named addListItem. We can remove the \n character sequences from the relevant text because we don't need a line feed, due to the fact that we are adding each item of text as its own item within the list view control. Let's read the brief description of this method provided within the relevant Microsoft web page. The method starts by instantiating the starting of a stopwatch. It then loops through each URL in the s_URL list and calls process URL async. With each iteration, the s_cts.token is passed into the process URL async method, and the code returns a generic task where tResult is an integer. So within the relevant Microsoft web page, let's look at the section entitled Add Process Method. So the first line in this section reads, add the following process URL async method below the SumPageSizes async method. So let's copy the process URL async method to our clipboards like this and appropriately paste it within the mainpage.xaml.cs file like this. Let's remove the static keyword from the process URL async method's method definition. Let's include the private access modifier within the process URL async method's method definition. Let's replace the console.write method with the addListItem method, like this. And if you'll remember, before we started implementing this example, I spoke about one of the prerequisites for creating this code example. The prerequisite being the installation of the .NET 5 SDK. So this is the only line of code that doesn't work if we do not have the .NET 5 SDK installed, and if we are running this example using the .NET Core 3.1 runtime. So if you are running this project using the .NET Core 3.1 runtime, simply remove the argument named token from the line of code that calls the response.content.readAsByteArray async method. So let me just say that it is preferable to pass in the token argument to this method, but if you don't wish to install the .NET 5 SDK at this time, we are still able to run the code by removing the token argument. This is not ideal, but we are still able to gain an understanding of the cancellation token source object and how we are able to cancel one or more asynchronous operations using one cancel token source object. Let's read the explanation of this method in the relevant Microsoft web page. For any given URL, the method will use the client instance provided to get the response as a byte array. The cancellation token instance is passed into the HTTP client.getAsync and HTTP content.readAsByteArray async methods. The token is used to register for requested cancellation. The length is returned after the URL and length is written to the console. So obviously where it says the URL and length is written to the console, in our example, we are instead adding the relevant text to our list view control. Okay, so let's implement the code for the button that invokes the download operations. Let's go to our designer surface and double-click on the button labeled Download Content. Let's implement the code that calls the awaitable SumPageSizes async method to perform the downloading of the relevant content. the calculation of the size of the content, as well as the outputting of the relevant information about the content to our list view control. So in order to call this method asynchronously, we need to include the await operator. We also need to include the async modifier within the method definition of the relevant button click event handler. Let's implement the cancellation functionality. Let's go to our designer surface and double-click on the button marked Cancel Download. Within the relevant button click event handler, let's implement the cancellation functionality. To add the operation, we can simply call the cancel method on the relevant cancellation token source object, like this. Okay, let's run the code. Firstly, let's demonstrate what happens when we click the Download Content button. So let's allow the operations to complete so we can see what happens when we don't cancel the operations. We can see that the appropriate output is presented to us as each operation completes. When the content for a particular web page has been downloaded, the web page URL followed by the number of bytes downloaded is presented on our list view control. And then once all the operations have completed, we are presented with the total number of bytes downloaded as well as the time that has elapsed between the time when we started to download the content and the time that the relevant download operations completed. Great! So let's run the code again. Let's click the Download Content button, and we are presented with the relevant output in our list view control as expected. Right, let's see what happens when we press the Cancel button. And a runtime error occurs. So in order to handle the cancellation operation appropriately, we need to handle a particular type of exception. So when the cancel method is called while the asynchronous operations are running, an exception of type task cancelled exception is thrown. So we can simply include our code that calls the sum page sizes async method within try-catch code like this, and handle the task cancelled exception appropriately. So we could access the thrown exception object to access details about the exception, but in this case, we only want to output status information to the user that the operations have been cancelled. So let's do this. Let's simply add the literal text, download operations cancelled. So remember, we are passing a token object as an argument to the getAsync method here in the process URL async method. The process URL async method is called within a loop from within the sum page sizes async method. This token object allows us to trigger a cancellation of all running asynchronous tasks that reference this token object. When the cancel method is invoked on the relevant cancellation token source object, an exception of type task cancelled exception is thrown, and we can appropriately handle this exception in our code. Right, let's run the code. So let's click the Download Content button, and we are presented with the relevant output as expected. So let's see what happens when we cancel these operations. And there we have it. The task cancelled exception is thrown when the cancel method on the cancellation token source object is invoked, and we are handling the thrown exception in our custom way, i.e., in a way that suits our application. So we can see the output text, download operations cancelled, which is an expected result. Okay, so we are also able to automatically cancel the operations after a predefined duration of time. So let's say we wanted our download operations to be cancelled if they haven't completed within a specific time duration. The way we can do this is by calling the cancel after method on the relevant cancellation token source object. We can call this method before the relevant operations are invoked, like this. We need to pass in the duration of time in milliseconds to the cancel after method. This number represents the time elapsed from the moment the relevant operations are invoked. So let's specify 3,500 milliseconds or 3.5 seconds. Let's run the code. And you can see that after 3.5 seconds, the relevant operations are automatically cancelled. So you can see how this functionality can be useful when we want to automatically cancel an operation or operations after a specified amount of time. Great! For further information about asynchronous programming in C#, I recommend reading relevant content provided in the Microsoft Docs. So to summarize, in this video series, we looked at Microsoft's recommended approach for implementing code to run an operation or multiple operations asynchronously, namely the task-based asynchronous pattern. We discussed that running certain relatively long-running CPU blocking operations can adversely affect the performance of our applications. To alleviate these negative effects on user experience, UX, we can run these relatively long-running CPU blocking operations asynchronously. In order to implement the asynchronous code correctly, we first need to know the nature of the operations that we wish to run asynchronously. We need to first ask the question, is the relevant operation a CPU-bound operation, or is the relevant operation an I/O-bound operation? In the first part of this video series, we focused on running I/O-bound operations asynchronously using the async modifier, the await operator, and the task or generic task object. In the second part of this video series, we looked at running CPU-bound operations asynchronously using the task.run method to run operations on background threads. We also looked at the task.waitAll method. In the third part of this video series, we looked at best practices when implementing operations in C# to run asynchronously. We also looked at the task.whenAll method and how it differs from the task.waitAll method. In this video, which is the final part of this video series, we looked at how we can provide the user with the ability to cancel one or more running asynchronous operations before the relevant operations have completed using one cancellation token source object. We also demonstrated how we can automate the cancellation of running asynchronous operations after a specified amount of time by calling the cancel after method on the relevant cancellation token source object. I hope you have enjoyed the final video in this video series on asynchronous programming in C#. The next topic in this advanced C# course will be LINQ, Language Integrated Query. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future content released from this channel. If you feel you have gained value from this video, please hit the like button. It will be greatly appreciated. Please feel free to share any videos released from this channel with anyone you feel may benefit from their content. I really enjoy reading your comments, so please feel free to share your thoughts with me in the comment section. As always, the code in this tutorial can be downloaded from GitHub. A link to the relevant GitHub repository has been included below in the description. Hi and welcome to the first part of a video series on LINQ. This video is also the first part of the 7th tutorial in an advanced C# course. Later in this tutorial, we'll look at a code example to help with our understanding of LINQ. But let's first answer the question, what is LINQ? LINQ stands for Language Integrated Query. LINQ is defined in the Microsoft Docs as the name for a set of technologies based on the integration of query capabilities directly into the C# language. LINQ was originally released as a major part of .NET Framework 3.5 in 2007. Here is a paragraph from the Microsoft Docs which provides an excellent overview of what LINQ is. Language Integrated Query, LINQ, is the name for a set of technologies based on the integration of query capabilities directly into the C# language. Traditionally, queries against data are expressed as simple strings without type checking at compile time or IntelliSense support. Furthermore, you have to learn a different query language for each type of data source: SQL databases, XML documents, various web services, and so on. With LINQ, a query is a first-class language construct, just like classes, methods, events. You write queries against strongly typed collections of objects by using language keywords and familiar operators. The LINQ family of technologies provides a consistent query experience for objects, LINQ to objects, relational databases linked to SQL, and XML, LINQ to XML. Note that you can write LINQ queries in C# for SQL Server databases, XML documents, ADO.NET datasets, and any collection of objects that support the IEnumerable interface or the generic IEnumerable interface. So, for example, you can perform LINQ queries against collection types like an array, generic list, generic dictionary, generic queue, generic stack, etc. Basically, any collection type that implements the IEnumerable interface or the generic IEnumerable interface. LINQ support is also provided by third parties for many web services and other database implementations. You can create custom providers using iQueryable. Custom providers will not be discussed in detail in this video series. If you would like to learn more about implementing your own custom provider, please navigate to this URL. In this video series, we'll primarily focus on LINQ to objects and LINQ to entities. LINQ to entities provides language integrated query, LINQ, support that enables developers to write queries against the Entity Framework conceptual model using either Visual Basic or Visual C#. So, Entity Framework Core is a modern object database mapper for .NET. It supports LINQ queries, change tracking, updates, and schema migrations. Entity Framework Core, or EF Core, can be used to work with many databases, including SQL databases, on-premises and Azure, SQLite, MySQL, Postgres, and Azure Cosmos DB. In this video series, we won't look at LINQ to dataset or LINQ to XML. Please navigate to this URL for more information on LINQ to dataset, and please navigate to this URL for more information on LINQ to XML. To get started with LINQ, in this video we'll focus on LINQ to objects so that we can first get a basic idea of what the implementation of LINQ looks like in code and how it can be used for querying C# collections. So in the spirit of cross-platform development, I've decided to demonstrate this code example on my Mac platform using Visual Studio 2019 for Mac Community Edition. If you have a Mac platform and wish to follow along on your Mac and you don't yet have Visual Studio installed, you are able to download and install Visual Studio Community Edition 2019 free of charge from this location. All links mentioned in this video are available below in the description. If you are using a Windows OS, please don't let the fact that I'm using a Mac platform put you off following along with this tutorial. In terms of the code example that we'll create in this video, the coding experience using Visual Studio for Mac is almost exactly the same as the coding experience using Visual Studio for Windows, so this should not be a barrier for a learner to follow along with this demonstration. If you haven't yet installed Visual Studio 2019 on your Windows platform, please view a video created by this channel which provides a guide to installing Visual Studio 2019 Community Edition free of charge. So firstly, let's create a .NET Core console application. Let's name this project the Pretend Company application. Before we write calling client code in the main method, we are going to add two standard library projects. Let's first add a standard library project named TCP Data. Let's then add another standard library project named TCP Extensions. So let's now go to our project that we named TCP Data. Let's delete the class that has been automatically generated for the TCP Data project. Let's add a new class named Employee. Let's add 6 auto-implemented properties to the Employee class. ID as int, first name as string, last name as string, annual salary as decimal, isManager as boolean, and lastly, department ID as int. Let's add another class to the TCP Data project. Let's name this class Department. Let's add 3 auto-implemented properties to our department class. ID as int, short name as string, and long name as string. Let's add a class named Data to our TCP Data project. Let's make this class a static class. So let's add 2 public static methods to the Data class. Let's first create a static method named getEmployees, which returns a generic list strongly typed as employee. Let's ensure that we include the appropriate using directive for the use of generic list objects at the top of our code editor. So let's include a using directive to the system.collections.generic namespace, like this. Let's write the code to add some made-up employee records to a generic list that is strongly typed with the user-defined type employee. Let's write code to return the list of employee records to the calling client code. Let's add another static method and let's name this method getDepartments. This method also returns a generic list object, but this generic list object is strongly typed as department. Let's write the code to add some made-up department records to a generic list that is strongly typed with the user-defined type department. Let's write code to return the list of department records to the calling client code. So as you can see, the getEmployees method returns a list of employee records, and the getDepartments method returns a list of department records. So in order to gain an understanding for how LINQ works, let's ensure that we properly understand two fundamental concepts, i.e. the concept of extension methods and the concept of lambda expressions. So let's go to our TCP extensions project. Let's delete the class that was auto-generated by Visual Studio when we created the project. Let's add a class named extension. So in order for our extension method to work, we must make the extension class a static class. So we are going to add a method named filter. The idea here is we want a way where we can extend the functionality of any generic list that is strongly typed with any C# data type, including user-defined types. We can achieve this by creating our own extension method. So for example, if we want to filter employee records by criteria that we are able to specify through a lambda expression on a generic list that is strongly typed as employee, we can do this through our filter extension method. This will be demonstrated in the calling client code in a bit. So how do we create our own custom extension method? So I'll first create the method signature for the filter extension method. First, notice that our method, like the class in which it resides, must be static, which is achieved by including the static keyword in the relevant extension method's method signature. So if we look at the first parameter in the filter method's method signature, we can see that we are using the this keyword preceding the data type of the first parameter, which is a generic list of type T. The this keyword in this context indicates to the compiler that the relevant method can be called on an object of the data type of the relevant parameter. In this example, that is a generic list which contains a type T placeholder. As we know from the video series on C# generics, a developer is able to pass a data type argument to the parameter of type T, which can be any C# data type, including user-defined types. The data type specified will be chosen depending on the requirement that needs to be met by the calling client code. We'll demonstrate the consumption of client-side code for the filter extension method in a bit. So let's look at the second parameter, which is of the delegate type func. For more information about the func delegate type, please view a video created by this channel on this topic. A link to this video is available below in the description. The first data type parameter passed to the func delegate type represents the first data type of the first parameter of the method referenced by the relevant argument passed into this parameter. The last parameter in the func delegate type definition is the return type of the method referenced by the argument passed into this parameter. So the first parameter passed into the func delegate is of type T, and the second parameter is of type bool. Note that a predicate delegate type can be used to define method definitions for a method that returns a Boolean value. So we could replace the func delegate type with a predicate delegate type. Let's use the func delegate type, but please note that we could also achieve the same end using the predicate delegate type. And as you can see, this method will return a list of objects of type T to the calling client code. So let's complete the logic for this method. Let's implement the code for the filter method. So basically, we are looping through the list on which the filter extension method is invoked. We are then adding its elements to a new generic list, also of type T. Whether or not we add this list item is based on the Boolean value returned by a method reference passed into the second parameter of the filter method. So the relevant method reference is stored in the argument passed to the parameter named func. As you can see, the method that the variable named func references accepts an argument of type T. So we are passing in each item stored in the calling client's list, which is the generic list on which calling client code will invoke the filter extension method. If the method that the func variable references returns true, the item stored in the iterated list is added to a new list. We then return the new list containing the filtered items to the calling client code. So this effectively means that the calling client code is able to use our filter method to filter any generic list based on a method created in the calling client code. This method created in the calling client code will contain the logic for filtering the relevant generic list. A reference to this method will be passed into the second parameter of our filter extension method and must adhere to the method definition represented in the second parameter of the filter method, i.e. the definition represented in the func delegate type. So we are now going to implement the calling client code, and you'll see that the method passed into the second parameter of our filter method will be an anonymous method, i.e. a method that is not named. This method will be expressed as a lambda expression. We'll now see how we are able to filter a generic list using our filter extension method through calling client code in the main method of our application. Right, so let's go to the .NET Core Console project and write the calling client code in our main method. Firstly, let's reference our two standard library projects from our .NET Core Console project. So let's right-click the Dependencies node in the .NET Core Console project and tick TCP data as well as TCP extensions. So let's test our filter extension method. In a bit, I'll further elucidate why it is important to understand extension methods and lambda expressions with regards to LINQ. Through the magic of how extension methods work in C#, we should be able to call the extension method on any generic list object. So let's define a generic list that is strongly typed as the employee user-defined type. So we have a red squiggly line under our generic list type definition. So to fix this, we need to include a directive at the top of our code to the system.collections.generic namespace. We can see that there is a red squiggly line under the code that strongly types our generic list as the user-defined type employee. So to fix this, let's include a directive at the top of our code to the TCP data namespace. Great. So through the magic of extension methods, we should see the filter method appear in the IntelliSense drop-down list when we add a dot after the employee list variable. Okay, so why are we not seeing the filter method appearing in our IntelliSense drop-down list? The reason for this is because we haven't included a using directive to the appropriate namespace. So let's include a using directive at the top of our code to the appropriate namespace, i.e. TCP extensions. So now if we add a dot immediately after the employee list variable, the magic of extension methods is revealed to us, and we can see our filter method in the IntelliSense drop-down list. So note that when we open brackets to pass in appropriate arguments to the filter method, we see that only one parameter is required. This parameter was the second parameter we defined for this method. So why is the first parameter in the filter method not listed when we open the brackets in this way? Well, the answer to that question is this is how extension methods work. The consumer of the code, i.e. the calling client code, does not need to pass in the first parameter. This is automatically handled behind the scenes, as it were. By default, the first parameter is the object on which the relevant extension method is invoked. So in this case, the list of employees stored in the employee list variable is passed into the filter method into this parameter automatically. So if we look at the filter extension method, we can see that this keyword precedes the definition of the first parameter. The this keyword in this context is telling the C# compiler that the argument passed into this parameter is the object on which the relevant extension method is invoked. So we have access to the argument passed into the first parameter automatically. Okay, so the second parameter accepts a delegate object that points to a method that needs to be created on the calling client. So this method that we'll create essentially tells the filter method how we want our list filtered. So we are able to define this method in the calling client code through the use of a lambda expression. A lambda expression is a concise way to represent an anonymous method. If we look at the definition of the relevant delegate parameter, we need to define a method that accepts an argument of type T and returns a Boolean value. So the C# compiler has enough information to infer that the intended type for type T is employee in this context. We are calling the filter extension method on a strongly typed generic list. The generic list is strongly typed with the employee user-defined type. So say we want to filter our employee list based on the value of each relevant employee item's isManager property. We want to filter the list where we only want to return those employee records where isManager is true. So we want to return all the records from our list where the relevant employees are managers. So to achieve this, we can pass in this lambda expression. Here we are telling the filter method how we want our list filtered. Let's write code to print the results to the console screen. Right, let's run the code. Okay, so we have no data. We of course need to populate our employee list with data. So let's assign the value returned from data.getEmployees to the employees list variable. Right, let's run the code. Great, and you can see that only the employee records where the relevant isManager property value is set to true are returned to the calling client code. Great. And we can of course inject the converse of this logic into our filter method through the relevant lambda expression like this. So we are now saying we only want to bring back employees who are not managers. Let's run the code. Great. And for good measure, let's modify our lambda expression so that the filter method only returns employees that earn less than $50,000 a year. Great. And because we have used generics for our filter method, we can call the filter method on a list of various C# types, including user-defined types. So let's prove this and call our filter extension method on a list of departments. Let's filter the departments based on the department's short name. So let's bring back the finance department and the human resources department. Great! Let's bring back only those departments with IDs greater than 1. So the point of this is to show you the flexibility that the combination of extension methods and lambda expressions create when writing the calling client code. The combination of extension methods and lambda expressions not only provide this flexibility, but at the same time ensure that the calling client code is clean and concise. Once we understand how extension methods and lambda expressions work, they are incredibly powerful tools. So, how do extension methods and lambda expressions work in relation to the topic of this video, LINQ, Language Integrated Query? Extension methods and lambda expressions are fundamental to how LINQ is implemented in C#. The enumerable class and the queryable class are two static classes that contain extension methods. The enumerable class and the queryable class are both members of the system.link namespace. So to gain access to the extension methods provided through LINQ, we can simply include a using directive to the system.link namespace. Without including a using directive to the system.link namespace, you can see that we are not able to access the where extension method provided by LINQ to perform our filtering operation on a collection that implements the IEnumerable interface. So let's include the system.link namespace. We now have access to LINQ's where extension method, so we can now replace our custom filter extension method with the where LINQ extension method like this. We don't need to create our own filter extension methods to perform such queries on our data. LINQ has got us covered for this. LINQ also provides us with a SQL-like query syntax. So for example, if we wanted to produce a query result by joining selected fields from data selected from our collection of employee objects with selected fields, or field in this case, from data in our collection of department objects, we can use LINQ query syntax to perform our inner join operation on these two collections of data, like this. In the LINQ query, we want to include the department long name field so that we can have a descriptive name for our department in our results set rather than displaying a result that only contains the department ID, which is available in the employee type. So we can achieve this result by using the join clause in a LINQ query to perform our inner join on our collection of employee objects with our collection of department objects. We have the department ID property in the employee type, so we can join using this department ID property in the employee type to the ID property, which is a member of the department type. So say we were to write the equivalent query using Transact SQL against a SQL Server database that contained an employee table with the same data schema as our employee type and a department table that contains the same schema as our department type. The Transact SQL query syntax would look something like this. We are using an inner join to join data in an employee table with data in a department table. We are able to make the join because the employee table contains the department ID, which can be joined in our query the ID of the department table. So you can see the similarities in syntax between the Transact SQL syntax and the LINQ query syntax. The LINQ query is dealing with objects encapsulating the employee and department records. The employee list collection is like the employee table, and the department list is like the department table in this particular context. We have a select clause, a from clause, and a join clause in the syntax for both the LINQ query and the Transact SQL query. However, the from clause in the LINQ query appears at the beginning of the query, and the select clause in the LINQ query appears at the end of the query. So there are differences in the ordering of the clauses when comparing the syntax of the transact SQL query with the syntax of the relevant LINQ query. An advantage of LINQ is it can be leveraged in our C# code to query data in a standardized way that is independent from the format of the underlying data source. The data source could be a MongoDB database, a SQLite database, a SQL Server database, etc. This will not affect the syntax of our LINQ queries. So the object layer provided by LINQ can be used for abstracting our queries of the data from the underlying data source. And by using LINQ, we also have the added advantage of compile time, strong typing, and the type checking provided by the C# compiler. Let me draw your attention to the select clause. We are able to return the data as an IEnumerable collection of anonymous types. We are assigning the collection returned by the LINQ query to a variable preceded by the var keyword. Beginning with C# version 3, variables that are declared at method scope can have an implicit type var. Through the use of the var keyword, the C# compiler is able to infer the types included in the collection returned from the query. So we are able to return a collection of objects that are of an anonymous type that we have defined directly within the LINQ query. Anonymous types provide a convenient way to encapsulate a set of read-only properties into a single object without having to explicitly define a type first. You can see how the use of anonymous types can provide the developer with flexibility and convenience when constructing relatively complex queries. Note that Microsoft recommends using the query syntax where possible as opposed to using relevant extension methods for the same purpose. This is because of the readability advantage provided in the relevant query syntax. There are, however, times where you'll need to use appropriate extension methods included within the LINQ namespace, because some functionality in LINQ does not have a query syntax counterpart. For example, if we wanted to calculate the average salary for all employees, we would need to use the average extension method like this. The same applies if we wish to query for the highest salary from a list of employee records. We would need to use the max extension method like this. This functionality cannot be performed through the use of query syntax. But where possible, query syntax is preferable due to the code readability advantage that this syntax provides. I hope you've enjoyed this video, which provides an introduction to LINQ. This video was created to help with the understanding of the fundamentals of LINQ, the advantages that LINQ provides, and how we are able to implement basic LINQ queries in code. LINQ provides us with an integration of query capabilities directly into the C# language. It is a very powerful technology that decouples query logic from relevant types of underlying data formats. LINQ provides a layer of abstraction that provides the developer with easy-to-implement syntax for querying collections of objects. The relevant collection types must implement the iQueryable or generic iQueryable interface or the IEnumerable or generic IEnumerable interface. Note that the iQueryable interface inherits from the IEnumerable interface and the generic IQueryable interface inherits from both the IEnumerable interface and the generic IEnumerable interface. A suite of extension methods and query syntax are made available to C# developers, which provide flexibility when constructing powerful, readable queries against data encapsulated within appropriate C# collections. This video is a basic introduction to leveraging LINQ in the C# language. In the next tutorial, we'll delve deeper into this subject matter. Hi, and welcome to the second part of a video series on LINQ. This video is also the second part of the 7th tutorial in an advanced C# course. LINQ stands for Language Integrated Query. In the first part of this video series, we looked at an overview of LINQ. We discussed that LINQ is the name for a set of technologies based on the integration of query capabilities directly into the C# language. In this video, we'll demonstrate examples where we'll create LINQ queries using method syntax and subsequently show how we can express the same LINQ query using query syntax. As discussed in the previous video, in this series, query syntax is recommended because the logic within the query syntax is easier to read. In this video, we'll look at code examples using the following LINQ operators: select, where, join, and group join. We'll discuss what is meant by method chaining and demonstrate an example that makes use of method chaining in the context of a LINQ query. We'll look at what is meant by deferred execution of LINQ queries and what is meant by immediate execution of LINQ queries. We'll discuss the inherent advantages of deferred execution in the context of LINQ. To further clarify our understanding of deferred execution, we'll create a code example where we'll implement deferred execution for our own custom extension method for an IEnumerable type. We'll demonstrate how the C# yield keyword is implemented in the relevant code example as part of code to implement deferred execution. At the end of the tutorial, we'll look at the join operator and the group join operator. We'll create code examples to help clarify our understanding of these two LINQ operators. In the first part of this video series, we discussed that extension methods and lambda expressions are fundamental to how LINQ works. We created our own extension method for filtering a generic list that can be strongly typed with any C# type, including user-defined types. We then demonstrated how a lambda expression can be created in calling client code, which enables the calling client code to determine how the relevant list of data must be filtered. The reason we created our own filter extension method was to help us understand the fundamentals of LINQ. LINQ functionality is encapsulated in two static classes that are members of the system.link namespace. These two static classes are named queryable and enumerable. These classes mostly contain extension methods As with the previous video in this series, I'm going to demonstrate the code examples in this video on my Mac platform. If you are using a Windows platform, the fact that I'm using Visual Studio for Mac should not be a barrier to follow along with these code examples. The code creation process is almost exactly the same experience when compared to implementing the same code using Visual Studio for Windows. So, let's create a .NET Core console project. Let's name this project LINQ Examples _1. So to save time, let's copy data-related code that we created in the previous video of this series from the appropriate GitHub repository. So please navigate to this URL in your browser to access the relevant GitHub repository. As always, all URLs referred to in these videos can be accessed through appropriate links included below in the description. So let's copy the data-related functionality from this repository to the project we have just created. So in your browser window, click the directory icon labeled TCP data, like this. Click the class icon labeled employee. Let's copy the code for the employee class from this page to our clipboards, like this. And simply paste the contents of the clipboard below the program class in our new project. Let's also copy the code for the department class like this to our clipboards. And paste the contents of our clipboards below the employee class within our new project. Let's then copy the code in the data class to our clipboards. Then paste the contents of our clipboards below the department class in our new project like this. So we have some red squiggly lines within our data class. To fix this, let's include a directive to the system.collections.generic namespace at the top of our code, like this. We are just creating throwaway code in this video to help us understand the relevant topics discussed in this video. So we are not too concerned with code neatness in this video. In our main method, let's create a strongly typed generic list. That is strongly typed with the employee user-defined type. Let's name our generic list variable employee list. Let's assign the value returned from the data.getEmployees method to the variable we have just named employee list. This line of code will populate the employee list collection with made-up data that was hard-coded in the data class in the previous video of this series. Let's define a generic list that is strongly typed with our department user-defined type. Let's name our variable for this list department list. Let's assign the value returned from the data.getDepartments method to the variable we have just named department list. This will populate the department list collection with made-up data that was hard-coded in the data class in the previous video of this series. So let's create a LINQ query that makes use of the select LINQ operator. In order to use a LINQ operator, we of course need to include a using directive to the system.link namespace. For this query, we want to select everything from the data stored in our employee list collection. We can do this by simply invoking the select method on the employee list object, like this. The select method is an extension method provided to us through LINQ. We can shape our data through the use of a lambda expression like this. We discussed anonymous types in the previous video of this video series. So, the select operator returns an IEnumerable collection of objects. The lambda expression passed into the select extension method provides an instruction on how we wish to shape each item of data within the returned IEnumerable collection. This is specifically expressed through this anonymous type. Anonymous types provide a convenient way to encapsulate a set of read-only properties into a single object without having to explicitly define a type first. You can see how the use of anonymous types can provide the developer with flexibility and convenience when constructing queries. So here we are providing an instruction that we want each item of data in the returned IEnumerable collection to contain a full name property, which is a concatenation of the first name and the last name properties of the relevant employee record, and a property containing the employee's annual salary. So let's write the code to output the results of this query to the console screen. Let's see the code in action. Great! So if we want to filter this data, We can do this by chaining the where extension method to our select operator like this. Method chaining is a common syntax for invoking multiple method calls in C#. Each method returns an object, allowing calls to be chained together in a single statement without requiring variables to store the intermediate results. So the select operation will return an IEnumerable collection object. We can filter this returned IEnumerable collection within the same LINQ query by chaining the where extension method to the select extension method. The where extension method filters the data stored in the IEnumerable object returned from the select method through a lambda expression passed to the where extension method. The lambda expression provides instructions to the where extension method on how the data must be filtered. Once the data has been filtered through the where extension method, an IEnumerable collection of results is assigned to our results variable. We are then traversing our results using a for each loop and displaying each item in the IEnumerable collection to the console screen. We discussed the var keyword, which allows for local implicit typing within methods in the previous video of this series. Please view the previous video in this series for more details. So here we are implementing LINQ explicitly using the extension methods provided by LINQ. We are using the select operator and the where operator in a LINQ query implemented using method syntax. Let's run the code. Great! We can execute the same functionality using query syntax. So let's comment out the previous code and include a comment to label this code so that we are able to refer to this code later if need be. So let's first implement the LINQ query using query syntax without the where clause. Let's run the code. Great! Let's implement the LINQ query implemented using query syntax, and this time include the where clause within the LINQ query using query syntax. Let's run the code. Excellent. And we get exactly the same result when compared to running the query that we implemented using method syntax. But we have constructed our LINQ code using LINQ query syntax as opposed to using relevant extension methods. The query syntax is more readable, and we don't need to chain our extension methods, as we did in the previous example where we changed the where extension method to the select extension method. Let's take a closer look at our query where we used method syntax versus the same query where we used query syntax. Note that standard query operators in our query syntax are converted into extension methods at compile time. So standard query operators are essentially the same as their counterpart extension methods. Microsoft recommends using query syntax as opposed to directly implementing the relevant extension methods where possible. As discussed, this is due to the readability advantage inherent in the query syntax. There are times when you will need to use extension methods directly where equivalent query syntax is not available. We looked at a few examples of this in the previous video of this series. For example, using aggregate functionality, like for example finding the average, min, or max annual salary for a collection of employee records. We would need to use the respective average, min, or max extension methods to calculate and return the relevant values. The developer is able to execute LINQ queries with deferred execution or immediate execution. So let's first understand what is meant by deferred execution. Deferred execution means that the evaluation of an expression is delayed until its value is required. This improves performance because only necessary executions are carried out, i.e., at the point where the relevant value is required. Let's use our last query example to illustrate this point. So when we first assign the value returned by our query to our results variable, the query is not executed. It is only when we traverse the items in our results variable that the actual execution takes place, i.e., with each iteration of the for-each loop, an execution is performed, whereby the relevant item is evaluated and returned from the collection. Another advantage of deferred execution is that an update to the relevant data collection will immediately be reflected in the results. So, for example, let's add a record to our employee collection. Note, the salary for this new employee is above 50,000, so this employee should appear within our results. Let's run the code. And you can see that this is proof that the results are evaluated within the for-each loop, and the query itself is not executed at the line of code where the relevant query is located. The execution of the query is deferred until the results are traversed within the relevant for-each loop. To further understand the concept of deferred execution, let's create a code example where we'll implement deferred execution for our own custom extension method for an IEnumerable type that is strongly typed as the employee user-defined type. Let's create a static class named Enumerable Collection Extension Methods. Let's create a static method within the static class that we have just created, and let's name this method getHighSalariedEmployees. We discussed extension methods in the previous video for this video series. For more information on extension methods, please access a link to this video. As discussed, a link to this video is available below in the description. So let's implement the code for the getHighSalariedEmployees extension method, like this. Note the use of the yield keyword. You can use a yield return statement to return each element one at a time. The sequence returned from an iterator method can be consumed by using a for-each statement or LINQ query. Each iteration of the for-each loop calls the iterator method. When a yield return statement is reached in the iterator method, the relevant value in the IEnumerable collection is returned, and the current location in code is retained. Execution is restarted from that location the next time that the iterator function is called. Let's go to our main method and implement a query that calls our extension method on the employee list collection. Let's copy and paste the code that we have already written to traverse the results and output the relevant data. And let's add another employee record to the employee list collection as we did before. Let's run the code. And you can see that the new employee record is reflected in the results. The results are kept up to date due to deferred execution. Note that deferred execution reevaluates on each execution, which is known as lazy evaluation. The converse of deferred execution is immediate execution. Immediate execution means the relevant query is executed immediately. To execute a query immediately, we need to apply an appropriate to-conversion method to the query. So let's copy the previous code example. Let's uncomment the relevant code. Let's change this code so that the query executes immediately. We can use the toList conversion method for this purpose. We are using query syntax here, so in order for us to use the toList conversion method, we first need to wrap the relevant query in brackets, add a dot, and then the toList conversion method. We are explicitly typecasting the IEnumerable value returned from the query to the list type through the implementation of the toList conversion method. We are also executing the query immediately. Let's uncomment the rest of the relevant code for this example. And let's run the code. You can see that the execution of our query is immediate, because this time, after we've added a new employee, the query has not been evaluated again to include the new employee record in the results. This is, of course, why the new employee does not appear within the results output to the screen. This proves that our query has executed immediately at the line of code where the query is located. And remember that query syntax does not support two operators, so we need to wrap our query in brackets, as we have done here, and call whichever to method is appropriate, for example, toList, toArray, or toDictionary. By calling the relevant to method, in this case the toList method, we are causing our query to execute immediately. Without the toConversion method, the relevant query execution would be deferred until the relevant results are iterated. So let's move on to the join operator, and then we'll look at the group join operator and highlight the difference between these two join operations. In the previous video in this series, we looked at the join operator and discussed how we can perform an inner join on two IEnumerable collections using a LINQ query. So here we have two collections that we wish to join. In this specific use case, we need to include a descriptive department name in our results displayed to the user. We only have a department ID field in our employee type, so in order to merge the properties from our employee type with the relevant property from our department type, we need to join records of type department that reside within our department list collection with records of type employee that reside within our employee list collection. We can do this by matching the ID field in the department records that reside in the department list collection with the department ID property of employee records that reside in the employee list collection. We can do this through LINQ by using the join operator. Later, we'll demonstrate a join operation, but using the group join operator. We'll also discuss the differences between the join operator and the group join operator. Let's look at the relationship between the collection of department records with the collection of employee records. Department records have a one-to-many relationship with employee records. A specific department can have many employees as members. A specific employee cannot belong to more than one department at a point in time. Data collections can also have one-to-one relationships with one another or many-to-many relationships with one another. So in this example, we are going to look at how we can use LINQ to implement a join operation between two collections of records that have a one-to-many relationship with one another, i.e., one department to many employees. So let's implement a query that joins the department list collection with the employee list collection, where the ID property of the relevant objects of type department match the department ID property of the relevant objects of type employee. So the syntax for this LINQ query would look like this when we implement the join operation using method syntax. So to join department records to appropriate employee records, we can use the join extension method and invoke the extension method on the department list collection. The first argument we need to pass into the join method is the collection on which we want to join the department list collection. So we pass in the employee collection object here. The second argument is the key from the outer collection, the department list collection. So the outer join key is the ID property that resides in the department type. We can express this argument as a lambda expression like this. The third argument is the inner join key, which is the department ID property which is a member of the employee type. We can express this argument as a lambda expression like this. So we are joining on the ID property which is a member of the department type with the department ID property which is a member of the employee type. We can define an anonymous type where we are able to shape the data for each item in an IEnumerable collection that we want returned from the relevant query. Here we are defining an anonymous type within our LINQ query that includes the employee full name, which is a concatenation of the employee's first name and last name, the employee's annual salary, as well as the relevant department object's long name property. The long name property will give us a descriptive department name in our results. We are including the department type's long name property in the relevant anonymous type. This is the whole point of joining the department list collection with the employee collection, so that we are able to include a descriptive department name within our results. We only have the department ID as a member of our employee type, so if we only returned results from the employee list and wanted to include department information, we would be restricted to the department ID property, which is an integer value and is unlikely to be meaningful to a user. Let's run the code. Great! But as discussed, where it is possible to use query syntax rather than method syntax for our LINQ queries, we should use query syntax because the logic expressed in the relevant query is far easier to read. So let's write the same query using query syntax. As you can see, it is far easier to read, and it is also similar to query languages with which we may already be familiar, for example, Transact SQL. Let's express what a similar query in Transact SQL might look like. So let's imagine that we have a table in a SQL Server database that could map to our employee type. Let's say this table has the same name as our employee type. Let's also imagine that we have a table in the same SQL Server database that contains a table schema that could map to our department type. Let's say this table has the same name as our department type. So the Transact SQL would look something like this. You can see how the from clause, the join clause, and the select clause are implemented in both the LINQ query syntax and the Transact SQL syntax. Even though the LINQ query contains the same clauses in a different order to the comparative clauses in the Transact SQL query, for someone who is familiar with Transact SQL and not necessarily familiar with LINQ query syntax, this LINQ query syntax at a glance should be fairly easy to understand. So the point here is that LINQ query syntax is similar to query syntax with which many of us will already be familiar. So this makes the implementation of LINQ queries using query syntax more intuitive. As discussed, the LINQ query syntax is also more readable than the equivalent LINQ query implemented using method syntax. So the key takeaway here is to use LINQ query syntax rather than method syntax where possible, because it is more intuitive to implement and easier to read. Let's run the code. Great. So let's look at the group join LINQ operator and why we might want to use the group join operator in our LINQ queries. We have just performed an inner join using the join operator. This query will only return those records based on the ID property of relevant objects of the department type in the department list collection, matching with the department ID property of relevant objects of the employee type in the employee list collection. Diagrammatically, an inner join query can be represented like this. What if we wanted to return, through a LINQ query, all the department records in our department list collection and only employee records where the department ID property of employee objects in the employee list collection match the ID property of department records in the department list collection? So if we were to write the Transact SQL version of this query, it would look something like this. We would use a left outer join to achieve the desired result. This query would bring back all department records, but only those employee records where the relevant employee records department ID values match the ID property of the relevant department records. So, diagrammatically, we can represent a left outer join query like this. So let's look at the diagram representing an inner join operation and compare the diagram to the diagram representing the left outer join operation. So let's use our group join operator in a LINQ query to return all department records from the department list collection, but only the employee records from the employee list collection with a department ID property that matches an ID property of a department record in the department list collection. So here we are implementing our query using method syntax. You can see the implementation of the group join operation using method syntax is very similar to the way we implemented the join operation in the previous example. Let's run the code. Note, the way we have structured our output is clearly different when outputting the results of our group join query when compared to the way we structured our output of the results of our join query. But note that at the moment the same join between department records and employee records has occurred. The reason for this is not because the group join and the join operators perform the same type of join operation. It is because currently each of the records in the employee list collection match with a department record in our department list collection. Let's change our data to highlight a key difference in the join operation and the group join operation. Let's do this by going to the code where we have hard-coded, made-up employee and department records and added these records to their respective collections. Let's ensure that the technology department, which has an ID of 3, does not match with a department ID property of any of the employee objects in our employee list collection. We only currently have one employee that is in the technology department according to our data. Let's change the relevant department ID so that there are no employees that are members of the technology department. So let's change this department ID property. Now, no employees are members of the technology department according to our data. Let's run the code. So you can see our technology department record is being returned along with all the other department records in the department list collection, even though its ID property doesn't match the department ID property of any employee records stored in the employee list collection. So, simply put, department information for departments that contain employees are included in the query results, and departments that don't contain any employees are also included in the query results. In this example, the technology department is returned even though it contains no matching employee records. So here we have performed a left outer join query using LINQ's group join operator. So let's rewrite this LINQ query using query syntax. You can see here that the group join extension method does not get explicitly called when we implement our query using query syntax. The into keyword is used within the query to create a group of employees for each department. So as discussed, LINQ query syntax does not match exactly when comparing LINQ query syntax to familiar query languages like Transact SQL. But in many ways, it does resemble a language like Transact SQL. In this sense, LINQ query syntax is more intuitive to implement than method syntax when implementing LINQ queries. And just to labor the point, as discussed, it is also better to implement LINQ query syntax for our LINQ queries than implementing method syntax for the same purpose because of better readability. Let's run the code. Great! And we get the exact same result as when we ran the same query that was implemented using method syntax. Now that we have changed the data so that the technology department does not match with any employee records, let's run our join operation that we created earlier. Notice that the results of the join operation doesn't include the technology department. This is because the join operation performs an inner join, and with the group join operation, we are able to perform a left outer join operation. So let's comment out our join query and uncomment our group join query. And for good measure, let's run the code again. And as you can see, the technology department is now included in the results displayed to the screen, even though the technology department does not have any matching employee records. Great! So the left outer join operation returns all records from the outer left collection in the query, but does not return records from the inner collection, where the inner collection records do not match any of the outer collection records. So if there were employee records in the employee list collection that did not match any of the department records in the department list collection, these employees would not appear in the results outputted to the screen. We can prove this. Let's change the department ID of this employee record where the first name property is Bob and the last name property is Jones. We have changed the department ID property for this record to 6, and there is no matching department record, i.e. no department record has an ID of 6. Let's run the code. And you can see that the employee record with first name Bob and last name Jones does not appear within the results. However, even though the Human Resources Department has no matching employee records, it is still included in the results outputted to the screen. Great! Let's add Bob Jones back into the Human Resources Department like this. And let's run the code. Excellent. So hopefully this made it clear how we are able, through LINQ, to use the join operator to perform inner join queries between two object collections, and how we are also able to perform left-outer join queries using the group join operator. Hi, and welcome to the third part of a video series on the LINQ technology using C#. This video is also part of the 7th tutorial in an advanced C# course. LINQ was introduced with C# version 3, which was released on the 19th of November 2007. LINQ stands for Language Integrated Query. In this video, we are going to focus on code examples that make use of several LINQ operators. The code examples demonstrated in this video will hopefully help us gain an understanding of a broad array of operators that are made available to us through LINQ. We'll learn how we can use these operators to query and transform data. This quote from the Microsoft Docs provides a basic definition of standard query operators and can be found at this URL. The standard query operators are the methods that form the LINQ pattern. Most of these methods operate on sequences, where a sequence is an object whose type implements the generic IEnumerable interface or the generic IQueryable interface. A lot of the more frequently used query operators have dedicated C# keyword syntax that enables them to be called as part of a query expression. As discussed in the previous video in this video series, it is advantageous to use query syntax rather than method syntax where possible because query syntax is more readable. Note that query expression clauses are translated into calls to query methods at compile time. For a useful tabular representation of standard query operators that have equivalent query expression clauses, please navigate to this URL. We discussed what is meant by deferred execution and immediate execution in the previous part of this video series. For a useful tabular classification of operators in terms of deferred execution or immediate execution, please navigate to this URL. For additional information on deferred execution versus immediate execution and method syntax versus query syntax, please view the second part of this video series. So to gain an understanding of several useful LINQ operators, let's create a few code examples. As with the previous video in this series, I'll be demonstrating these code examples on my Mac platform using Visual Studio for Mac. The code creation process for these code examples is almost exactly the same process as creating the equivalent code examples on a Windows platform using Visual Studio for Windows. The fact that I'm using Visual Studio for Mac should not be a barrier for a learner to follow along with the creation of these code examples. So, let's start by creating a .NET Core Console project. We created a project in the previous video named LINQ Examples _1. Let's name this project LINQ Examples _2. In order to save time, let's copy data-related classes that have already been created in the previous videos of this series and incorporate these classes into our new project. These classes contain class definitions for an employee and a department record, as well as code that adds several made-up objects of type employee and department to their respective collections. As in the previous parts of this video series, we can then use these collections of strongly typed objects in our LINQ query examples. So to copy the relevant code, let's navigate to this URL, i.e. to a GitHub repository that was created in the previous video. Let's click on the directory icon labeled LINQ Examples _1. Then let's click on the file icon labeled program.cs. Let's copy the employee class to our clipboards. And paste the contents of our clipboards within the new project that we have just created. Let's copy the department class to our clipboards and paste the contents of our clipboards below the employee class within our new project. Lastly, let's copy the data class to our clipboards and paste the contents of our clipboards below the department class within our project. So in the previous video, we looked at the following operators: the select projection operator, the where filter operator, the join and group join operators. In this video, we'll create code examples that implement the following operators. We'll start by looking at the following sorting operators: order by descending, then by, and then by descending. We'll then look at these grouping operators, group by and toLOOKUP. We'll then look at these quantifier operators, all, any, and contains. We'll then look at the following filtering operator, of type. Note that another example of a filtering operator is the where operator. We have looked at the where filter operator in the previous parts of this video series. Lastly, we'll look at the following element operators: element at or default, first or default, last or default, single or default. We'll look at even more LINQ operators and create code examples in the next video. The next video will be the final video in this video series on LINQ. Right, let's get started. So let's start by looking at the data-related classes that we copied from GitHub. We have the employee class, which provides a definition for an employee record. We have the department class, which provides a definition for a department record. We have the data class that contains code where lists of hard-coded, made-up employee and department objects are added to their respective collections within their respective methods and returned from their respective methods. In the previous video in this series, we looked at join operators, namely the join operator and the group join operator. So in the context of join operations, the department collection has a one-to-many relationship with the employee records in the employee collection. This simply means that one or many employees can be members of a specific department. A specific employee can be a member of only one department at a point in time. So let's go to our main method. We can use the data.getEmployees method to return a collection of made-up employee records. Let's use this method to assign the relevant collection of employee records to a local variable named employee list. The employee list variable is defined as a generic list that is strongly typed as employee. So here we have red squiggly lines because we need to include a using directive to the system.collections.generic namespace. Let's use the data.getDepartments method to return a collection of made-up department records that have a one-to-many relationship with the relevant collection of employee records, and let's assign the relevant returned collection of department records to a variable named department list. The department list variable is defined as a generic list that is strongly typed as department. So let's get into the creation of our examples. Sorting operators. Order by. So let's create an example for the order by operator. In this example, we want to return all employee records from the employee list collection and order by department ID. To make things a little bit more interesting, let's say we want to include the department name within our outputted results. The problem here is that the department name does not exist in the employee type, so we need to join the employee list collection to the department list collection so that we can include the department name in our results. We can do this by using the join operator. So let's write this query using method syntax so that we can see all the LINQ extension methods used in the relevant query. So we first need to make sure that we include a using directive to the system.LINQ namespace. This directive will give us access to the relevant LINQ operators that we will be implementing in our code examples. We know that the system.LINQ namespace contains two static classes, namely enumerable and queryable, and these static classes mostly contain extension methods. Our LINQ operators, which are implemented in the form of extension methods, are implemented within the enumerable and queryable static classes. So this LINQ query joins the employee list collection to the department list collection on the department ID property of each of the relevant employee records with the ID property of relevant department records. Before we run this query, let's alter the data a bit. Let's make the employee record pertaining to Sarah Jameson a member of the technology department by changing the relevant department ID property from 2 to 3. Let's also change the department for the employee record pertaining to Jane Stevens to the technology department by changing the relevant department ID from 2 to 3. This change to the data will make the effects of our sorting operators more apparent when we view our results. So if we run the query first without the use of any order by operators, note that the data appears to us in the same order as it was added to the employee list. But now let's say there is a requirement to order our results by the department ID property in ascending order. We can do this by chaining the order by extension method to the end of the query, like this. For more information on method chaining, please view the previous video in this series. So we can pass in a lambda expression to the order by extension method to indicate that we wish to order the results by the department ID property. Let's run the code. And you can see that the results are now ordered in ascending order by department ID. If we look at the code that added each department to the department collection, we can see that the Human Resources Department has an ID of 1, the Finance Department has an ID of 2, and the Technology Department has an ID of 3. Our results have been ordered in ascending order based on the department ID property of the employee record. So we can clearly see the effects of the order by operator on our results. Great! If the requirement changed such that we needed to order our results by the department ID property in descending order, we can chain the order by descending extension method instead of the order by extension method for this purpose. Our results are now ordered by department ID in the reverse order when compared to the previous output. Great! So let's say that we want to order our results by the department ID property in ascending order and then by the annual salary property also in ascending order. So let's replace the order by descending extension method with the order by extension method in our results like this. Then let's chain the then by extension method to the query like this. We can then pass a lambda expression to indicate that we wish to further order our results by the annual salary property. The then by extension method will order the results produced by the order by sorting operator in ascending order. Great! And if we want to order by the annual salary property in descending order, we can replace the then by extension method with the then by descending extension method for this purpose. Excellent. We can represent sorting operations within LINQ queries that are represented using query syntax like this. Note the order by and descending keywords in the query syntax version of the relevant query. We use the order by keyword within our query to order by our first specified property. If we want to subsequently sort on other properties instead of chaining the then by extension method to our query, in query syntax, subsequent properties by which we wish to sort are separated by commas. The descending keyword can follow any of the properties that we wish to sort in descending order. The default order is ascending order. So let's look at the group by and toLOOKUP grouping operators. Let's start with the group by operator. So this operator is akin to the group by clause we would apply in a transact SQL query. So we can implement the group by operator using the group by extension method, or the group and the by keywords within query syntax to perform the same operation. So let's say we wish to query the employee list collection and group our results by the department ID property. The query using query syntax would look like this. This query is simply grouping our results by the department ID property. Using method syntax, this query would look like this. In all of the LINQ query examples using query syntax that we have looked at up till this point, in this video series, we have ended all our queries with a select operator. Notice that this query does not end with a select operator. It is important to note that a LINQ query implemented in query syntax must either end with a select operator or a grouping operator. Notice how this query does not end with a select operator, but a grouping operation is being performed at the end of this query. So we can traverse the results of this grouping operation using nested for each loops. The outer loop traverses each group that has been created based on the department ID property. The inner loop traverses the item members within each of the groups that have been created in our query based on the department ID property. Great! We could also include the order by operator within our query like this. Let's run the code. Great! We can implement the same query using method syntax using the toLOOKUP extension method like this. Great! We can also include sorting functionality through the order by operator through the implementation of method chaining like this. Great! Note that the toLookup method performs the same operation as the groupBy operator. The only difference is the execution of the groupBy operation is deferred, whereas the execution of the toLookup operation is executed immediately. We discussed deferred execution and immediate execution in the previous part of this video series. For more information on deferred execution and immediate execution, please view the second part of this video series. A link to this video has been included below in the description. Note that the results returned from a groupBy operation and a toLookup operation return a group contained in a special type of collection that implements an iGrouping generic interface . So let's look at the all, any, and contains quantifier operators. Let's first look at the all and any operators. Let's create a variable named annual salary compare and assign it with a value of 20,000. Let's implement a block of code related to the all operator. Let's implement a similar block of code related to the any operator. So, the all and any operators return a Boolean value. The return value will equal true if the elements in the relevant collection satisfy a condition passed to the relevant method. This condition can be passed in the form of a lambda expression. This query will return true if all employee records have annual salary property values that are greater than 20,000. This query will return true if one or more employee records have an annual salary property value that is greater than 20,000. Let's run the code. Great! This is an expected result. Let's change the annual salary compare variable to 100,000. Great! And let's change the annual salary compare variable to 40,000. So let's move on to the contains operator. So we want to be able to assess whether an employee record exists within our collection of employee records. The contains operator will return true if we pass in an object that is equal in value to an object within the relevant collection. To understand how the contains operator works, let's create an employee record that we know matches an employee record within the employee list collection. Let's copy this record for the employee named Douglas Roberts that is a member of the relevant employee collection. And paste it in our main method. Let's name the variable that stores a reference to the employee record we wish to find within the employee list collection search employee. So how can we assess whether the employee record pertaining to Douglas Roberts exists within the employee list collection? We can use the contains extension method. We can simply pass the variable we named searchEmployee to the contains extension method, which we have invoked on our employee list collection object. So the contains method returns true if the searchEmployee object matches any of the objects within the employee list collection, and false if the searchEmployee object does not match with any of the objects stored within the employee list collection. So let's write code to write an appropriate narrative to the screen based on the Boolean value returned by our query. Let's run the code. And this is not the result we expected because we literally copied and pasted the code representing one of the employee objects that has been added to the employee list collection from our data class to the main method as our search object. So Y is our output indicating that the searchEmployee object does not match any of the objects stored within our employee list collection. This result is unexpected. The answer is that the compiler knows how to compare built-in C# types like, for example, integer or bool. The employee type is a user-defined type or custom type. We need to tell the compiler how we wish to compare two objects of type employee to establish whether two employee objects are equal. So we can do this by creating a class that implements the generic iEqualityComparer interface. The iEqualityComparer interface is a member of the system.collections.generic namespace. We have already included a using directive to this namespace within our code. So let's create a class named EmployeeComparer, and let's indicate that we want the EmployeeComparer class to implement the iEqualityComparer generic class that is strongly typed with the employee user-defined type. So let's hover our mouse pointers over the red squiggly line and create the stubs for the methods that we need to implement, like this. So two method stubs have been generated, one named equals and the other named getHashCode. So the getHashCode method is used for the purpose of uniquely identifying an object. We can implement the code for the getHashCode method by returning the hash code of the ID property of the relevant employee object, like this. The equals method must be implemented in a way that establishes how we wish employee objects to be compared when determining whether two employee objects are of equal value. So let's say that we are satisfied with comparing the relevant employee objects based on their ID, first name, and last name properties to establish equality between the relevant employee objects. So we can achieve this with the following code. If the relevant properties are equal, return true, else return false. So we are already passing in the searchEmployee object to the contains method. Let's also pass a newly instantiated object of type EmployeeComparer to an overload version of the contains method, like this. And now we are telling the compiler how we want to compare our employee search object with the objects stored within the employee list collection. Let's run the code. And this is an expected result. The contains method now returns true as expected because our search record matches the employee record for Douglas Roberts within the collection on which we are performing our search. Great. So now let's look at the of-type filter operator. So before we use the of-type filter operator in our code examples, let's create a method named getHeterogeneousDataCollection. Heterogeneous in this context, of course, is referring to the storage of objects of multiple different data types within the same collection. So we can store objects of multiple different data types in an array list. Note that Microsoft does not recommend using array lists for new development. It is far better to use strongly typed lists to store collections of data. For more detail as to why strongly typed lists are recommended, please view a video on generics created by this channel. A link to this video has been included below in the description. So, a use case where we could apply a LINQ query on an array list could be perhaps we have a legacy piece of code that includes an array list containing objects of multiple types, and we need to filter the relevant array list based on specific types. We can achieve this using the of-type LINQ operator. We'll look at how we can do this in a bit. Let's first add some made-up data to an array list. So the array list stores integers, strings, objects of the employee user-defined type, and objects of the department user-defined type. Let's go to our main method and write code to use the of-type operator to query this array list based on specified data types. Let's query for all string values in our array list. Great. So let's query all integer values in our array list. Great. Let's query for all objects of the employee user-defined type. Great. Let's query for all objects of the department user-defined type. Excellent. So you can see how we can query an array list for objects of a specified type using generics and the of-type operator by passing in the relevant type between angle brackets like this. This will return those objects within the array list that are of the specified type. Let's move on to the element operators. Let's look at the element at or default, first or default, last or default, single, and single or default element operators. So let's first look at the element at operator. So the element at operator is used for querying for an item in a collection that resides at a specified ordinal location within the relevant collection. So we can pass an integer value representing the relevant element's location in the relevant collection into the element at method to return the desired item's value from the relevant collection, like this. Great, and our query has returned the value for the relevant element. But what happens if we pass in a value representing a position in the relevant collection where an element does not exist? So let's try this. Let's pass in a value of 8. Right, so it is important to note that no item exists within the relevant collection at ordinal position 8. So in this case, an argument out of range exception is thrown. This brings us to an important point about the difference between the element at and the element at or default method. If we replace the element at method with the element at or default method, and we query the relevant collection for an item at a position where the desired item does not exist within the relevant collection, the element at or default method does not throw an exception, but rather returns the default value for the desired item's relevant data type. Let's briefly discuss what we mean by a default value for a particular data type. The C# language associates default values for C# data types. So if, for example, we are querying a collection of integers using the element at or default method for a value that did not exist at the specified location in the relevant collection, the element at or default method would return the default value for the integer data type, which is a value of 0. The integer value of 0 is the default value for the integer data type in C#. If, however, we are querying a collection containing a reference type object like an object of our user-defined type employee, the default value returned by the element at or default method would be null. Null is the default value for reference type data types like user-defined types or the string data type. For more detail regarding default values in C#, please navigate to this URL. So let's use the element at or default method to query the relevant collection of employees for a value at position 8, i.e. where no employee object is present within the relevant collection. We can then write code to check if the returned value is null. And you can see that an exception is not thrown and no results are outputted to the screen, which is an expected result because the query returned a null value. Let's pass in a value of 2 and then 1, and in both cases the appropriate result is outputted to the screen. So let's write code to output an appropriate narrative to the user based on the value returned from the element at or default method. So let's pass in a value of 12. The output indicating that the return value is null, i.e. the employee object does not exist in the collection, is outputted to the screen. This is an expected result. Great. So the first operator returns the first element in a collection if no condition is specified. We have the option of passing a condition to the first method, or we can leave the brackets following the first method empty. If we do not specify a condition, the query will return the first element in the relevant collection. If a condition is specified, the first operator will return the first element in the collection that satisfies the specified condition. We can specify a condition in the form of a lambda expression. Right, to prove this, let's first create a strongly typed list of integer values. So if we query this collection using the first operator and don't provide a condition passed as an argument to the first method, the query returns the first item in the collection as expected. So let's pass a condition in the form of a lambda expression to the first extension method. So this condition is simply querying the collection for the first even number in the collection. Let's run the code. Great. But now what happens if we alter the collection of values so that no value satisfies the condition, i.e. no even numbers exist within the relevant collection? An invalid operation exception is thrown. So if we don't want an exception to be thrown, we can replace the first operator with the first or default operator. As you may have guessed, where no items in the relevant collection satisfy the relevant condition, this method will not throw an exception, but will rather return the default value of the relevant data type. We know that the default value for the integer data type is 0. Let's write code to output an appropriate narrative to the screen if the relevant condition is not satisfied. Let's run the code. And this is an expected result. So let's include an element in the relevant list that does satisfy the condition. Excellent. So the last and last or default operators work in much the same way as the first and the first or default operators. The only difference is that the last item in the collection is returned where no condition is specified, the last item that satisfies a specified condition in the collection is returned when a condition is specified. The last method will throw an exception if an appropriate element is not present within the relevant list. We can use the last or default method rather than the last method to return the default value for the relevant data type in the case where an appropriate element in the relevant collection is not present. Great! So let's move on to the single and single or default element operators. The single operator returns the only element in a collection or one element that satisfies a specified condition from a collection. We have the option of passing a condition into the single method through the use of a method overload, or we can leave the brackets following the single method empty, which means we have chosen not to pass in a condition into the single method. If we choose not to pass in a condition into the single method, and there is more than one element or 0 elements in the collection, an invalid operation exception will be thrown. If, however, there is only a single element in the collection, the value for this element will be returned by the query. If we do choose to pass in a condition and 0 or more than one element satisfies the condition, an invalid operation exception will be thrown. If we pass in a condition to the single method and only a single element satisfies the condition, the value for this single element will be returned from the relevant single operation. Let's apply the single operator to a collection of employees. Let's first modify the data for our list of employees so that only one employee element exists within the relevant employee collection. Let's write code using the single operator to query the relevant employee list. Great, this is an expected result. Let's now include the employees that we just commented out back within the relevant employee list. Let's run the code. And an invalid operation exception is thrown as expected. This is because more than one employee resides in the list. If there is only one item in the relevant collection, the value for this item is returned. If there are 0 items or more than one item in the collection, and a condition is not specified for the single operator, an invalid operation exception is thrown. So let's test the single method, and this time specify a condition where one item within the relevant collection satisfies the specified condition. Great! Let's specify a condition where more than one item in the relevant collection satisfies the specified condition. As you can see, an invalid operation exception is thrown. So let's test the same scenario, i.e., more than one element in the relevant collection satisfies the specified condition, but this time, let's use the single or default method. That's interesting. So note, where more than one element satisfies the specified condition when the single or default method is applied in the relevant query, an invalid operation exception is thrown, just like when the single method is applied to perform the same operation. So we can use the single or default method instead of the single method if we don't want an exception to be thrown under the scenario where no elements exist within the collection. The default value for the data type will instead be returned by the query. If a condition is specified for the single or default method and no elements satisfy the condition, the same result will be produced, i.e., the default value for the data type of the element stored in the collection will be returned by the query. If a single item is present within the relevant collection and the single or default method is applied to perform a query against the relevant collection, the single element's value that exists within the relevant collection will be returned by the query. Hi, and welcome to the fourth and final part in this video series on the LINQ technology using C#. This video is also part of the 7th tutorial in an advanced C# course. This video is a continuation of the previous 3 videos in this video series on LINQ, so I recommend viewing the previous 3 videos in this video series before viewing this video. In the previous video in this series, we looked at code examples where certain LINQ operators were implemented to query and transform data. This video is a continuation of the previous video in this series, where we'll create code examples using some of the other LINQ operators to gain a broader understanding of what can be accomplished using the LINQ technology in C#. So in the previous videos in this series, we have created code examples using the following LINQ operators. The sorting operators, order by descending, then by, and then by descending. The grouping operators, group by and to lookup. The quantifier operators, all, any, and contains. The filter operators, of type and where. The element operators, element at or default, first or default, last or default, single, and single or default. The join operators, join and group join. We have already looked at the select projection operator, and we'll also look at the select operator in this video, and in addition to this, we'll also look at the select many projection operator. So in this video, we'll look at the following LINQ operators. The equality operator, sequence equal. The concatenation operator, concat. The set operators, distinct, except, intersect, and union. The generation operators, default if empty, empty, range, and repeat operators. The aggregate operators, aggregate, average, count, sum, and max. The partitioning operators, skip, skip while, take, and take while. The conversion operators, toList, toDictionary, and toArray. And lastly, the projection operators, select and select many. We'll also look at the following keywords that are useful when used in queries implemented in query syntax, namely the let and into keywords. We have looked at the select projection operator already in previous videos, but we'll look at this operator again in this video as well as look at the select many projection operator. We'll then be able to gain an understanding of the difference between the select and the select many projection operators. As in the previous videos, I'll be demonstrating the code examples on my Mac platform. If you are using a Windows platform, to follow along, the experience of creating these code examples will be almost exactly the same. So the fact that I'm using Visual Studio for Mac should not be a barrier for a learner using Visual Studio for Windows to follow along with the creation of these code examples. Okay, so let's create a .NET Core console project. So the official release of .NET 5 has now been released. So I'll be running this project using the new .NET 5 .NET runtime. For more information on the significance of the .NET 5 runtime, please view the second part of this advanced C# course. I've included a link to this video below in the description. The project we created in the last video was named LINQ Examples _2. Let's name this project LINQ Examples _3. So as we did in the previous video, let's navigate to this URL where we can access code on GitHub for the project that was created in the previous video of this series. Here we can copy the data-related code that we created in our previous project so that we can reuse these data-related classes in this project. Let's click the directory icon labeled LINQ Examples _2. Let's then click the file icon labeled program.cs. Let's copy the class named employee and paste the contents of our clipboards to our new project. Let's do the same for the department class and the data class. Okay, so we won't be using the getHeterogeneousDataCollection method that resides in the data class in this video, so let's delete this method. Let's refresh our memories about the classes we have just copied and pasted from GitHub. The employee class contains a definition for an employee record. The department class contains a definition for a department record. The data class contains hard-coded, made-up data for employee records and department records. The employee records are stored in a generic list strongly typed as employee. The department records are stored in a generic list that is strongly typed as department. We can access the data stored in the employee list collection from calling client code, in this case, this will be the main method, by calling the static method named getEmployees. We can access the data stored in the department list collection by calling the static method named getDepartments. Note that the data class in which these methods reside is a static class. Let's navigate to the main method, and before we create our example code, let's add the appropriate using directives. First, let's add a using directive to the system.collections.generic namespace. The generic list type is a member of this namespace. Let's also add a using directive to the system.link namespace. Once we have added our system.link using directive, we can access our link operators on collection types that implement the IEnumerable interface. So, for example, list types implement the IEnumerable generic interface. So we are able to access extension methods stored within the enumerable static class, which is a member of the system.link namespace, by including a using directive to the system.link namespace. The queryable static class also includes link extension methods and is a member of the system.link namespace. For more information on how extension methods work in C#, please view the first video in this video series. A link to this video has been included below in the description. Before we get started creating our code examples, I want to draw your attention to what might be an issue for Visual Studio for Mac users. When we run our code interactively through Visual Studio for Mac, by default, the output may appear in the terminal console window within Visual Studio for Mac, like this. This is absolutely fine for testing code, but you may prefer to present the output externally, i.e. in a terminal console window outside of Visual Studio for Mac. If you would prefer to present your output externally, i.e. outside of Visual Studio for Mac, please navigate to Visual Studio for Mac Preferences, then under the heading marked Other, select the item labeled Terminal. In the right pane of the relevant dialog box, ensure that the Enable Integrated Terminal checkbox is unchecked. This is obviously not a functional issue, it really comes down to personal preference. Let's define a generic list variable named employee list that is strongly typed as employee, and let's assign the collection of employee records returned by the data.getEmployees static method to the employee list variable. Let's define a generic list variable named department list that is strongly typed as department, and let's assign the collection of department records returned by the data.getDepartment static method to the department list variable. Okay, so we are now ready to query and transform data using LINQ. So let's start with the equality operator, sequence equal. So the use case here is we want to compare two lists of data, and we want to know if these two lists contain elements of equal value and each element in each of the relevant lists are stored in the same order. If each item in each list matches in terms of value and order, the sequence equal method will return true. If any of the items in each of the relevant lists does not match in terms of value and order, the sequence equal method returns false. Let's create a generic list named integer list1 that is strongly typed as integer. Let's copy and paste this line of code to the next line. Let's change the name of the second list to integer list2. Let's run the code. And the sequence equal method returns true, because the values and sequence of elements in integer list1 is identical to the values and sequence of elements in integer list2. Let's change the order of the items in integer list2, so this sequence of values is not equal to the sequence of values stored in the list named integer list1. Let's run the code. And this is an expected result. Let's change integer list2 once again for good measure. And this is an expected result. Great. So let's change the data in integer list2 so that the order and values in the lists are equal. And now the result is true, which is an expected result. That was pretty straightforward, i.e., comparing two sequences of values of a primitive data type, i.e. the integer data type. But what if we want to test this type of equality between two lists that are strongly typed with a complex type? Like, for example, our employee user defined type. So let's define a variable named employee list compare as a generic list type that is strongly typed as employee, and let's assign the collection returned from the data.getEmployees static method to our employee list compare variable. Let's run a sequence equal operation and compare the values stored within our employee list compare collection with the values stored within the employee list collection. So one would expect the result of this sequence equal operation to return true because both collections contain exactly the same data. Let's see what happens. Oh, and false is returned. The reason why false is returned is because we need to tell the compiler how to establish equality between objects of the relevant complex type, i.e. in this case, the employee type. So we achieved this in the previous video in this series by implementing the built-in iEquality comparer generic interface. So let's copy the relevant code for this that we implemented in the previous video in this series. Let's navigate to the GitHub repository at this URL. That contains the code we created in the previous video in this series. Let's copy the class named Employee Comparer to our clipboards and paste the contents of our clipboards to our projects like this. We have red squiggly lines, so let's fix this by bringing in the appropriate using directive. So here we have implemented a class named Employee Comparer that implements the generic I-equality comparer interface that is strongly typed as employee. This gives us a way of telling the compiler how we want objects in our lists of type employee to be compared when determining equality between the relevant objects. So we are explicitly doing this here in the equals method, where we are comparing the ID, first name, and last name properties between two employee objects. We are returning true if the relevant properties of the relevant two objects are equal, and false is returned if any of the relevant properties of our two objects are not equal. Within the getHashCode method, we are returning the hash code of the ID property of the relevant employee objects. For more information on hash codes, please navigate to this URL. So now let's go to our main method, and we can pass in a new instance of the Employee Comparer class to an overloaded version of the sequence equal method. This object will tell the compiler explicitly how we want our employee objects to be compared. Let's run the code. And now the sequence equal operator works as expected. So note that we need to tell the compiler how we want objects that are defined as complex types to be compared when determining equality between the relevant objects. We can do this by creating a class that appropriately implements the I-equality comparer generic interface. Great! Let's move on to the concatenation operator named concat. We can use the concat operator to append one collection of data to another collection of data. So let's see the concat operator in action. Let's create a collection of integer values. Let's then create another collection of integer values. Let's append the second collection of integer values with the first collection of integer values using the concat operator. Let's write code to output the results of this concatenation operation to the screen. Let's run the code. Great! Let's do another example, but this time let's append a collection that contains a collection of objects of a complex type to another collection of objects of the same complex type. The complex type we'll use in this example will be our employee user-defined type. Once again, we can use the concat operator to achieve what we want here. Let's run the code. Great! Let's move on to the aggregate operators. Let's first look at the aggregate operator. Using the aggregate operator, we can perform a custom operation on values within a collection. Let's say we have a requirement where we need to provide a total for the annual salaries of our employee records. We also need to include the addition of an appropriate annual salary bonus in the final result. Let's say a manager gets a bonus of 4% and employees that aren't managers get a bonus of 2%. So let's say we have a use case where we need a result that is a total of all employee annual salaries, which must include each employee's bonus. We can take this added complexity into account when totaling up our employee annual salaries through the use of the aggregate operator. So the first argument is the seed value. So let's provide 0 for this argument. Using this argument, we are initializing the value that will be returned by our aggregate operator. The next argument is of a delegate type, where we can include the logic for our aggregation functionality in the form of a lambda expression. So as you can see in our logic for the relevant lambda expression argument, we are checking to see if the relevant employee is a manager, whereby we need to add a bonus of 4% to the relevant employee's annual salary. If the employee is not a manager, we need to add a bonus of 2% to the relevant employee's annual salary. We can then include the appropriate bonus amount in our calculation. So we are adding up all employee annual salaries, which includes each employee's appropriate bonus. Let's run the code. Great! Say we want to output a comma-delimited string from our employee list collection. Each delimited item containing the employee full name, a dash, then the employee annual salary. Each annual salary must include the appropriate bonus. We also want to include a label preceding the comma-delimited string. We can achieve this using the aggregate operator, like this. The first argument is the label, where an appropriate value could be something like employee annual salaries including bonus. Then the logic of our aggregation functionality can be expressed in a lambda expression for the second argument, like this. We can apply the same logic to include appropriate bonuses from our previous example. Let's run the code. Great, but we have a slight issue where a comma is presented at the end of our string. We don't want this comma in our final result. We can express this by passing a lambda expression as our third argument to an overloaded version of the aggregate operator. This argument allows us to perform a final operation on the results produced by the lambda expression passed in as the second argument. We first need to include another data type argument with an angle brackets following the aggregate method to declare the data type of the final output, i.e. provided by the lambda expression we are passing in to the last parameter of this overloaded version of the aggregate method. In the lambda expression passed in as our final argument, we are using the substring method to remove 2 characters from the end of the result, which means a comma and a space will be removed. This result is what we want. Excellent. So let's move on to the average aggregate operator. So to find the average annual salary for a list of employees, we can apply this code. Great! If we want to find the average salary for all employees in the technology department, we can use method chaining and the where operator to achieve this, like this. Great! For more information on method chaining, please view the second part of this video series. Let's move on to the count aggregate operator. So if we want to know how many employee records we have in our collection of employee records, we can apply the count operator like this. Great. If we want to know how many employees are members of the technology department, we can pass in a condition as an argument to the count operator. The condition that is passed in as an argument to the count method can be expressed in the form of a lambda expression. Great. Let's move on to the sum aggregate operator. So let's keep this simple we just want the sum total of all annual salaries of all employee records stored in our employee list collection. We can apply the sum operator to achieve this. Great. Let's move on to the max aggregate operator. So if we want to return the highest annual salary property of all employee records stored in our employee list collection, we can apply the max aggregate operator in a LINQ query like this. Great! Let's move on to the generation operators, namely default if empty, empty, range, and repeat. Let's first look at the default if empty operator. So we can use the default if empty operator to return a new IEnumerable collection that when, for example, we apply the element at method on the new collection to check if the new collection is empty, the operation will return the default value for the relevant type used to strongly type the relevant collection. A query using, for example, the element at method against a collection returned from a default if empty operation will not throw an exception if the collection is empty. The default value of the type with which the relevant collection is strongly typed will instead be returned. For more information on default values for C# data types, please navigate to this URL. We'll see later how we can pass in a value to the default if empty method to specify our own default value that we'd prefer to be returned when, for example, the element at method is used to check if the relevant collection is empty, rather than the default C# value for the relevant data type. Let's look at an example using the default if empty method. So let's create an empty list of integer values. Let's perform a default if empty operation on this collection of integer values and assign the returned collection to a new collection of integer values. Let's use the element at operator and pass in 0 to the element at method to check if the collection is empty. You can see that the element at operator returns the default value for the integer data type, which is 0. This is an expected result. Let's create another example, but this time let's use the employee data type to strongly type our collections. As discussed, the default value for a reference type in C# is null. But as discussed, we can pass in a default value that we would prefer to be returned by, for example, the element at operator when the relevant collection is empty. So let's pass in an employee object where the ID property of the relevant employee object is set to 0. Null is not returned, as would be the case if we hadn't passed in a value to the default if empty method, because we have specified our own default value where the ID property of the default employee object is 0. Great. Similarly, we could have set the default value for our integer collection example by, for example, passing in 999999 to the default if empty method. Instead of returning the default C# value for an integer, which is 0, 999999 is returned. This is an expected result. Excellent. Right, let's look at the empty method. So we can use the empty method to generate a new empty collection. So for example, we want to create a new IEnumerable generic collection of employee records. We can do this by using the empty operator like this. Note, the empty method is not an extension method of IEnumerable or IQueryable like other LINQ methods. It is a static method included in the enumerable static class. So for example, we could instantiate a new empty generic list strongly typed with the employee user-defined type through the use of the empty method. We can then chain the toList conversion operator to this operation and return an empty generic list. We are using the toList operator to convert an IEnumerable generic collection that is strongly typed with the employee data type to a generic list that is strongly typed as employee. So for good measure, let's add a new employee item to our new list that we have generated through the use of the empty method and the use of the toList conversion operator. Let's write code to write the items, or in this case one item, stored in our new list to the screen. Great. Right, let's move on to the range generation operator. We can use the range operator to return a collection of values that are within a specified range. So let's clarify this with an example. We want to return a range of integer values in a collection where the first item in the range has a value of 25 and each subsequent item is incremented by a value of 1 until there are a total of 20 values in the relevant collection. We can achieve this by using the range method like this. In this example, the first argument specified is 25. This is the value of the first element, and the second argument specifies the number of elements to include in the relevant generated collection. When each item is added to the collection, it is incremented by a value of 1. So the second item will be 26, the third item will be 27, the fourth item will be 28, and so on. Let's run the code. Great. So using the range operator, we have generated a collection of integer values that fall within a specified range. Excellent. Let's say we want to generate a collection of a specified amount of elements where a value for each element in the collection is repeated. We can use the repeat operator for this purpose, like this. Great. Let's move on to the set operators, namely distinct, except, intersect, and union. Let's start with distinct. So let's say we have a strongly typed generic list that contains a list of integer values, some of which are repeating values. We want to perform a query against this list of integer values where we only want distinct values returned. We can achieve this by applying the distinct operator to our query like this. Great. Let's say that we have two collections of a specific type and we want to return elements with values in our first collection that are not equal to any of the values of the elements in our second collection. We can achieve this by using the except operator. Let's look at an example of using the except operator applied to two collections of integer values. So 1 and 2 are returned in our results collection because these values exist in our first collection and don't exist in the second collection. The values 3 and 4 exist in our first collection and also exist in our second collection. The values 5 and 6 exist in our second collection, and even though these items don't exist in our first collection, the except operator does not return these items as part of the results collection, because in this example, the except operator returns values that exist in the first collection and don't exist in the second collection. Let's try an example using complex types. Let's use our employee type. Let's create a generic list strongly typed as employee. Let's copy data that we know will exist within our employee list collection and add these items to the list we have named employee list 2. Let's add some additional items to the employee list 2 collection. Let's then call the accept method on the employee list collection and pass in the employee list to collection as an argument to the accept method. Then let's assign the results of this operation to an implicitly typed variable named results. We have, of course, used the var keyword to implicitly type our results variable. Let's write code to traverse the results and output the results to the screen. Let's run the code and see what happens. And this result is not expected. The output contains all items within the employee list collection. I would have expected that the items that were copied from the data class and added to the employee list to collection, as well as the other items that we added to the employee list collection, would be excluded from the results. The reason for the unexpected results is because we have not told the compiler how to compare employee objects when determining if one employee object is equal to another employee object. So how can we let the compiler know how we want one employee to be compared to another employee within our collections when determining equality between the two relevant objects? You may have guessed already how we can achieve this. We first need to create a class that implements the iEquality comparer generic interface. We can then write code to establish how one employee object should be compared to another employee object when determining equality between the relevant objects. We have already included the code for this, which we applied when we created code to perform a sequence equal operation on two lists that were strongly typed as employee. So we have our class named employee comparer that implements the iEquality comparer generic interface. So we can reuse this class for our example that performs an accept operation on two generic lists that are strongly typed as employee. So all we need to do is create a new object of type employee comparer and pass this object into an overloaded version of the accept method like this. Let's run the code. Great! This is now an expected result. Let's move on to the intersect operator. So we can use the intersect set operator to return a collection containing only those items that exist in the employee list collection that are equal to the items that exist within the employee list to collection. And now that we know we are comparing elements in two collections that are strongly typed with the employee complex type, we need to pass in a new object of the employee comparer type, i.e. a type that appropriately implements the generic iEquality comparer interface. This tells the compiler how to compare two objects of type employee when determining if the relevant employee objects are equal. Let's run the code. And this is an expected result. Great. Let's move on to the union operator. The union extension method requires two collections and returns a new collection that includes distinct elements from both the collections. We can again use the same data we have used in the previous two examples to test the union operator. Right, let's write the code for this. You will notice we are also passing in an object of type employee comparer to the union method. Let's test the code. Great! So let's see what happens in this example when we don't pass in an object of type employee comparer to the union method. You can see that duplicate records are included in the results as a consequence of not passing in an object derived from a class that appropriately implements the generic iEquality comparer interface. And of course, we know we have already created such a class. So let's ensure that we pass in our object of type employee comparer to the union method so that only distinct employee objects are included within our results. Excellent. So let's move on to the partitioning operators. These partitioning operators include the skip while, take, and take while operators. Let's first look at the skip operator. Use the skip operator to skip over a given number of elements in a sequence and then return the remainder. So let's query our employee list collection using the skip operator. Let's skip over 2 of the elements stored in our employee list collection and return the remainder of the elements using the skip operator. Great, this is an expected result. Let's look at the skip while operator. Using the skip while operator bypasses elements in a sequence as long as a specified condition is true, and then returns the remaining elements. Let's see this operator in action. So the condition here is skip elements in our sequence of employee objects in the employee list collection while the relevant employee object's annual salaries are above 50,000. Great, this is an expected result. Just to make things a little bit more clear on how this operator works, let's add a new employee record to the employee list collection. This employee record has an annual salary of 100,000, which of course is above 50,000. Let's run the code. And you can see that while the condition is true, the items in the relevant collection are skipped, i.e., will not be returned from the query. However, all subsequent elements in the sequence will be returned once the condition returns false. Even though the last element in the relevant sequence has an annual salary property greater than 50,000, it is still returned, because the third element in the sequence caused the condition to return false. The fact that the last element has an annual salary above 50,000 and therefore causes the condition to be true doesn't mean that the last item will be returned by our query. Note that once the condition returns false, all items from that point will be returned from our query. Right, let's move on to the take partition operator. The take operator is used to return a specified number of contiguous elements from the start of a sequence. Let's see this operator in action. This is an expected result. Great. The first 2 elements in the relevant sequence of elements in our employee list collection are returned by our query. So let's move on to the take while partitioning operator. The take while operator returns elements from a sequence as long as a specified condition is true, and then skips the remaining elements. So let's use the same condition that we used in the skip while operator example. So here we are using the take while operator to return elements from the relevant sequence that have an annual salary above 50,000. So the first 2 elements in the sequence are returned by our query. As soon as the third element is evaluated and the condition returns false, the elements from that point onwards in the relevant sequence will not be returned by our query. So for example, the fact that the 5th element in the employee list collection has an annual salary property that is greater than 50,000 is irrelevant, because when the third element causes the condition to return false, and in terms of the take while operator this means that from that point onwards, the rest of the elements in the relevant sequence will not be returned by our query. Great! Let's look at the conversion operators toList, toDictionary, and toArray. So let's look at the toList conversion operator. A query written in query syntax will return an IEnumerable collection containing the results of the query. What if we need our results to be returned as a generic list? We can achieve this using the toList conversion operator. Let's create an example to clarify this point. So for this example, let's query our employee list collection for employee records that have an annual salary property greater than 50,000 using query syntax. Note the red squiggly lines here. This is because we are attempting to assign an IEnumerable collection to a variable of type generic list. The compiler is telling us that we have created a type mismatch. So we can use the toList operator to convert the IEnumerable collection returned by our query to a generic list by wrapping the relevant query in brackets, adding a dot after the last bracket, and applying the toList operator like this. So now you can see the red squiggly lines disappear because we have removed the type mismatch. Let's run the code. Excellent. As discussed earlier in this video series, wherever a to conversion operator is applied to a query, as we have done here, this causes the query to execute immediately, i.e., query execution is not deferred, it is executed immediately. So if we want to convert an IEnumerable collection returned from a query to a dictionary object, we can apply the toDictionary operator to the query. Let's create an example to clarify what is meant by this. So, as in the previous example, here we have a standard query written in query syntax to query our employee list collection for all elements where the relevant elements have annual salary properties that have values greater than 50,000. So this is a basic query that will return an IEnumerable collection. But what if we want to return a collection where each element has a unique key associated with the relevant element? We can do this by converting the query result to a dictionary generic collection type. So let's alter our code so that the IEnumerable collection returned by our query is converted into a generic dictionary collection. So within angle brackets after toDictionary, we need to pass in two data types. The first data type declares the data type of the value stored in the dictionary. The second data type declares the data type of the key that will be used to uniquely identify each element in the collection. So the first data type is of type employee, and the second data type is of type int. Note that we want each element to be keyed on the employee ID property. We can express this by passing in an appropriate lambda expression to the toDictionary method like this. So let's traverse the key values stored in our dictionary object using a for each loop. Note how we are able to use the key values to retrieve the values of each element stored in the dictionary. We are doing this by passing in the relevant key within square brackets to the dictionary object. Here we are outputting the key as well as each employee's first name and last name to the screen. And as you can see, we have each employee's ID, which we have designated as our key value, followed by the corresponding employee's first name and last name properties. Excellent. We have successfully converted a query result from an IEnumerable collection to a dictionary object. As discussed, when we call any of the two conversion operators on a query result, this causes our query to execute immediately. For more information on deferred execution versus immediate execution, please view the second part of this video series. For good measure, let's also create a result using the toArray conversion method. So if we try to assign the results of this query to a variable defined as an array of employees, the compiler complains of a type mismatch. The query result is returned as an IEnumerable collection and not an array of employee objects. To remove the type mismatch, we can apply the toArray method like this. Great. So let's discuss the let and the into clauses that can be applied when using query syntax to represent a LINQ query. Let's look at the Microsoft Docs for an overview of the let clause. This overview of the let clause can be found at this URL. In a query expression, it is sometimes useful to store the result of a sub-expression in order to use it in subsequent clauses. You can do this with the let keyword, which creates a new range variable and initializes it with the result of the expression you supply. Once initialized with a value, the range variable cannot be used to store another value. However, if the range variable holds a queryable type, it can be queried. So let's look at a basic example using the let keyword in a LINQ query. Let's say we wish to query our employees based on employee initials. Now, we don't have an initials property for an employee record, but within our query, using the let keyword, we can extract the initials from each employee record's first name and last name properties and assign the result of this extraction process to a variable named initials directly within our query using the let keyword. This allows us to use the initials variable in our where clause as well as reuse the initials variable within our select clause. Through the use of the let clause, we can also apply a condition, and based on the evaluation of that condition, store a value in a variable that can be used later in the query, like for example within a where clause. Here we have a condition where we need to add an appropriate bonus to the annual salary property, based on whether the employee is a manager or not a manager. If the employee is a manager, we need to add a bonus of 4% to the relevant employee record's annual salary property. If the employee is not a manager, we need to add a bonus of 2% to the relevant employee record's annual salary property. We can store the relevant annual salary plus bonus value for each employee record by assigning the value returned by a ternary operator to a variable. We have named this variable annual salary plus bonus. The let clause in this example enables us to reuse the annual salary plus bonus variable, both within the where clause and the select clause later in the query. Let's run the code. Excellent. Let's look at the into keyword. We can use the into keyword in a LINQ query to collate data within a group, and then after this operation, we are able to perform a filter operation within the same query, if required, on the grouped data through the use of a where clause. So for example, let's use a LINQ query to first create a group of high-earning employees based on a condition. Let's say that the employee must earn above $50,000 to fit into the relevant group. We can use the where clause at this point in the query to appropriately filter the relevant employee records and the into keyword to put the filtered data into the relevant group of high-earning employees. So we can use the into keyword to group the high-earning employees into a group named high earners. Let's say we then want to further filter this group of high-earning employees by management status. So we only want these employee records where the isManager property is set to true returned from our query. We want to know which of those high-earning employees are managers. So we can use another where clause within our query to filter the high earner group based on the relevant condition. We have used a where clause earlier in our query to create the group of high earning employees. Then once the group is created through the use of the into keyword, we can further filter the group of high-earning employees based on each employee record's isManager property. So we are able to include another where clause in our query to filter the grouped data. Let's run the code. Great. So lastly, let's look at the select and the select many projection operators. In this video series, we have already looked at the select projection operator. So the focus in this example is on the select many operator. We want to know how it differs from the select operator and in what circumstances we may wish to apply the select many operator in a LINQ query. Let's navigate to a Microsoft Docs webpage to see what the Microsoft Docs say about these two projection operators. Projection refers to the operation of transforming an object into a new form that often consists only of those properties that will be subsequently used. By using projection, we can construct a new type that is built from each object. You can project a property and perform a mathematical function on it. You can also project the original object without changing it. Select projects values that are based on a transform function. Select many projects sequences of values that are based on a transform function and then flattens them into one sequence. To understand the difference between the select many operator and the select operator, let's modify our department class so that it includes a property that stores a collection of employees. We have already discussed that department records have a one-to-many relationship with employee records. So each department object will now store a collection of related employee records. Let's also alter the getDepartments static method that resides in the data static class so that the getDepartments static method accepts an argument containing a collection of employee objects. Then for each department object added to the department list collection within the getDepartments static method, let's include a query to return an appropriate collection of employees, i.e. those employee records that have a department ID property matching the ID property of the relevant department object. So let's go to the main method and pass in the collection of employees to the getDepartment method. So now the getDepartments method will return a collection where each department contains a related collection of employee records. So now, what if we want to query the department list collection for all employees? We can achieve this using the select operator, but when traversing the results of the select operation, we will need to use an outer and an inner for each loop, like this. In this scenario, the select many operator is better to use for this purpose. The select many operator is better in this case because we can use one for each loop to traverse the results of our query, unlike where we needed to use an additional nested for each loop to traverse the results of our query, where we used the select operator. Behind the scenes, as it were, the select many operator appropriately flattens the results, and this means we don't need to use a nested for each loop to traverse the results of our query. We are able to use one for each loop for this purpose. Excellent. So we have covered a lot of ground in this video series on LINQ operators. I would encourage you to practice using these operators to become proficient in writing LINQ queries. This is a very powerful technology and is used with Entity Framework to perform database queries in modern .NET applications. Entity Framework is now the recommended technology to use in .NET for implementing database-related functionality in .NET applications. If we navigate to this Microsoft Docs webpage, we can see this paragraph that states, Entity Framework Core is a modern, object-based mapper for .NET. It supports LINQ queries, change tracking, updates, and schema migrations. EF Core works with many databases, including SQL Database, on-premises and Azure, SQLite, MySQL, Postgres, and Azure Cosmos DB. This makes LINQ a very important technology to learn for .NET developers. LINQ enables developers to write one set of code that can be applied to handle data-related functionality for multiple different data sources. In LINQ, expression trees are used to represent structured queries that target sources of data that implement the generic iQueryable interface. If you would like to delve deeper into expression trees, please navigate to this URL. So let's summarize what we have learned in our 4-part series on using the LINQ technology in C#. In the first part of this video series, we created our own extension method to filter data. We also demonstrated how a lambda expression can be used to express a condition that can be passed into our extension method to filter the data and return the filtered results from a query. The reason we created the filter extension method is because LINQ is mostly made up of extension methods stored in 2 static classes, namely a static class named enumerable and a static class named queryable. We are able to access the extension methods within these static classes by including a using directive to the system.link namespace. The enumerable and queryable classes are both members of the system.link namespace. In the second part of this series, we demonstrated examples using the select, where, join, and group join operators. We also discussed the difference between when a query is executed with deferred execution or immediate execution. We discussed how a LINQ query is executed with deferred execution, but we can make the LINQ query execute immediately by applying a to-conversion operator to the query. For example, to-list, to-dictionary, or to-array. In the third video in this series, we demonstrated code examples using the following LINQ operators. Sorting operators: order by descending, and then by descending. Grouping operators: group by and to lookup. Quantifier operators: all, any, and contains. Filter operators: of type and where. Element operators: element at or default, first or default, last or default, single, and single or default. In the fourth and final video in this series, we demonstrated code examples using the following LINQ operators: the equality operator, sequence equal; the concatenation operator, concat; the set operators, distinct, except, intersect, and union; the generation operators, default if empty, empty, range, and repeat operators; the aggregate operators, aggregate, average, count, sum, and max; the partitioning operators, skip, skip while, take, and take while; the conversion operators, to list, to dictionary, and to array; projection operators, select, and select many. In this video, we also looked at code examples using the let and the into keywords. I hope you have enjoyed this video series on using the LINQ technology in C#. Hi and welcome to the 8th part of this advanced C# course. In this video, we'll focus on the use of attributes in C#. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future content. If you like this video at any point, please consider giving it a thumbs up. It will be greatly appreciated. So, let's discuss attributes. Attributes allow the developer to add metadata in a declarative way to program elements in code, for example, classes, methods, properties, parameters, etc. A declared attribute is instantiated into an object at runtime, and at compile time, we can declare attributes against program elements to provide additional metadata to relevant program elements. The developer is also able to declare global attributes against assemblies, and in doing so add or modify metadata about the relevant assembly. So, the developer can use attributes to add or modify metadata about a particular program element or the assembly itself. In this video, we'll also briefly look at reflection. Reflection is a technology that we can use to read the metadata provided through the use of attributes at runtime. We are then able to, for example, implement code logic based on the metadata provided through the use of attributes. We'll look at how we can do this later in this video. There are two broad categories for attributes: predefined attributes and custom attributes. Predefined attributes are built into the base class libraries in .NET. In this video, we'll look at two main types of predefined attributes: global predefined attributes and general predefined attributes. Global attributes, like for example assembly version attribute and assembly description attribute, facilitate adding and modifying metadata for an assembly. General attributes, like for example conditional attribute, obsolete attribute, and attribute usage, can be applied to appropriate program elements. We'll start by implementing a code example using the assembly version attribute and assembly description attribute, which are global attributes. We'll use reflection to read the relevant assembly metadata and output the assembly metadata to the console screen. We'll then implement a code example using the following general attributes: conditional attribute, obsolete attribute, and attribute usage. The attribute usage attribute will be declared on our own custom attributes that we'll create a bit later in this video. We'll use custom attributes and reflection to implement field validation functionality. We'll demonstrate how custom attributes can be created by creating classes that inherit from the built-in system.attribute class. Later in this video, we are going to create custom attributes as part of validation logic that imitates how the ASP.NET MVC framework provides flexibility to developers through the use of reusable validation-related attributes. This video sets us up well for the next video provided by this channel, which will be a demonstration of creating a basic ASP.NET MVC application on .NET 5. Right, let's create our code examples so that we can gain an understanding of attributes in C#. Let's create a .NET Core console application project. Let's name this project Attributes Examples. Let's ensure that we are using .NET 5 for this project. If you haven't yet installed .NET 5, please see a link below in the description where you are able to download the .NET 5 SDK. Note that you'll mostly be able to follow along even using earlier versions of .NET, but it is advisable to download .NET 5 to follow along with this tutorial and future tutorials. One of my core aims is to keep these tutorials right up to date. Please view a video created for this channel about the significance of the release of .NET 5. A link to this video can be found below in the description. So let's say that we wish to declare the assembly version global attribute in our code. We are able to do this by declaring this global attribute between the namespace declaration and the using directives. Okay, so why can't I see the assembly version attribute in the IntelliSense dropdown? The reason is that the assembly version attribute is part of the system.reflection namespace. So let's add a using directive to the system.reflection namespace. And now we are able to see the assembly version attribute along with other global attributes in the IntelliSense drop-down list. And we can now declare the global attribute against our assembly, like this. So here we are attempting to set our attribute version number to 2.0.1 through the declaration of the assembly version global attribute. Great, so let's see what happens when we attempt to compile the code. So we have a compile time error. Let's look at our error list to take a look at the details of this error. The description of the error is duplicate system.reflection.assembly version attribute. So let's double click on the error item in our list that is causing the compile time error to occur. Okay, so a new file is open and we can see a red squiggly line under the offending code. It is a file that has a name that contains the assembly name followed by the suffix .assembly.info, and we are able to find this file within our project's directory structure. And if we look at the comments within this file, it is clear that this file has been auto-generated. It's in fact been auto-generated by MS-Build. Let's navigate to this URL to read a bit about MS-Build. The Microsoft Build Engine is a platform for building applications. This engine, which is also known as MS-Build, provides an XML schema for a project file that controls how the build platform processes and builds software. Visual Studio uses MS-Build, but MS-Build doesn't depend on Visual Studio. By invoking msbuild.exe on your project or solution file, you can orchestrate and build products in environments where Visual Studio isn't installed. Visual Studio uses MS-Build to load and build managed projects. The project files in Visual Studio .csproj, .vbproj, .vcxproj, and others contain MS-Build XML code that executes when you build a project by using the IDE. Visual Studio projects import all the necessary settings and build processes to do typical development work. But you can extend or modify them from within Visual Studio or by using an XML editor. So the basic point I'm trying to make here is that many of these global attributes will be automatically declared in the assembly.info file when compiling your code using the Visual Studio IDE. You can gain access to some of these global attributes through the Visual Studio IDE. If you try to declare a global attribute, as I have attempted to here, you may get a compile time error because MS-Build has automatically declared the global attribute in the assembly.info file. As we have seen, this results in a duplication of the relevant global attribute declaration, which ultimately results in a compile time error occurring. You are able to declare certain global attributes in the way we tried to declare the assembly version attribute. For example, let's declare the assembly description attribute. Let's comment out the assembly version attribute declaration. Let's add our own assembly description metadata to our assembly through a declaration of the assembly description global attribute. Let's pass a value of myAssemblyDescription to the constructor of the assembly description attribute. Note that depending on how the relevant attribute has been written, when the developer declares an attribute, the developer is able to provide custom metadata to the relevant attribute through the attribute's exposed public properties or the relevant attribute's constructor parameters. So, we know that the purpose of attributes is so that we can add or modify metadata against certain program elements or even against the assembly itself. Note that attributes on their own do not change application behavior. The metadata provided through attribute declarations can be read at runtime through the use of reflection. Relevant metadata can then be evaluated by our code, and appropriate code logic can be invoked based on the declared metadata. So this is how the Microsoft Docs describes reflection. Reflection provides objects of type that describe assemblies, modules, and types. You can use reflection to dynamically create an instance of a type, bind the types to an existing object, or get the type from an existing object and invoke its methods or access its fields and properties. If you're using attributes in your code, reflection enables you to access them. Right, so let's use reflection to access and read certain metadata that has been added through the use of global attributes. So we need a using directive to the system.reflection namespace, which has already been included in our code. So let's write some code in our main method. Let's get a reference to the current assembly. We can do this by getting a reference to the program class's type and then assigning its assembly property value to a variable. We have named our variable this assem, referring to the current assembly. We can then get the relevant assembly name by using the assembly reference stored in the thisAssem variable and calling its getName method. And we can access the assembly's version information through the version property. Now we want to read the assembly's description, which should be the description that we included when we declared the assembly description global attribute. To get a reference to the assembly description attribute, we can call the getCustomAttributes method on the thisAssem object and pass in the type of the attribute of interest to us. Note that we are using the typeOf method to get a reference to the object type of the relevant attribute. Remember, attributes in C# are objects at runtime. An object instantiated from the assembly description attribute class should be the first item in our object array. We can use the as operator to cast the object to the assembly description attribute type. If the casting operation fails, null will be returned. If the operation succeeds, an object of the assembly description attribute type is returned. Let's write code to write out the metadata information about the current assembly that we have been able to retrieve through reflection to the console screen. Let's run the code. Great! So we have looked at examples of global predefined attributes. Let's look at some general predefined attributes. Let's start with the conditional attribute. Let's first add a new standard library project to our solution. And let's name our project Logging Component. Let's remove the automatically created class named Class1 and add a new class named Logging to our new project. Let's add a public static method to the logging class named LogToScreen. It contains one parameter named MSG and is defined as a string. The code for this method simply outputs the value referenced by the MSG argument to the console screen. Let's declare the conditional attribute against the LogToScreen program element. We have a red squiggly line because the conditional attribute is a member of the system.diagnostics namespace. So let's add a using directive to the system.diagnostics namespace. And now let's pass in an argument into the constructor of our conditional attribute. Let's pass in the text log_info. So what does log_info mean? Log_info is a piece of text that I've made up. This text represents a symbol in our code. We can use the define preprocessor directive and include the log_info symbol in our code. If the log_info symbol is defined using the preprocessor define directive within a file containing method calls to the log_to_screen method, the code within the log_to_screen method will be executed at runtime. However, if the predefined processor directive is not used to define the log_info symbol in the file where the log_to_screen method is called, its code will not be executed at runtime because we have used the conditional attribute to declare to the compiler that we would like this behavior to occur regarding the log_to_screen program element. So, the combination of the conditional attribute and the use of the define preprocessor directive can act like a switching mechanism, i.e. using this mechanism we are able to switch certain code on or off. This is especially useful for debugging purposes. If this is not clear, don't worry. We will demonstrate what is meant here through a code example. We are able to define our log_info symbol through the use of a preprocessor directive. We are going to use the define preprocessor directive for this purpose. Preprocessor identifiers are used to help in conditional compilation. If we navigate to this URL, we can see some of the preprocessor directives available in C#. For more information on preprocessor directives, please use this section of the Microsoft Docs as your guide. So here we have the hash define preprocessor directive that we can use to define a symbol in our code. So let's see how we can use a particular preprocessor directive in conjunction with the conditional attribute to conditionally output information to the console screen through our log-to-screen method. We must add our appropriate preprocessor directive code right at the top of our program.cs file in our code editors like this to implement the desired functionality. You can see we have the define preprocessor identifier in this line of code, as well as the log_info symbol that we made up and passed as text to our conditional attribute, which was declared against the log-to-screen program element. Let's include a using directive to our logging component namespace. In our main method, let's make a call to the logging.log-to-screen method and pass in the following text as an argument to the MSG parameter. This code is testing logging functionality. Let's run the code. And as expected, the appropriate text is written to the console screen. So now let's see what happens when we comment out the relevant preprocessor directive code and run the code again. And you can see that nothing has been outputted to the console screen. Using our preprocessor directive, we can switch the execution of the code against which the relevant conditional attribute is applied on and off at compile time. This functionality can be very useful for debugging purposes. So let's say we have a change to our logging component where we want all logging to be done to a text file rather than to the console screen, and we want the consumers of our code to use the method that logs the information to a text file rather than to the console screen. So how can we let the consumers know to use the log-to-file method rather than the log-to-screen method? We can simply declare the obsolete predefined general attribute against the log-to-screen method. Let's create a public static method named log-to-file. In the interests of time, rather than writing the code to actually log the value passed into this method to a file, let's just write code to output the value to the console screen and pretend that its method logs relevant text to a text file. Okay, so let's declare the obsolete attribute against the log-to-screen method. And let's pass a meaningful message to the constructor of the obsolete attribute. So we want any calling code that is currently using the log-to-screen method to receive the following warning message. The log-to-screen method has now been deprecated. Please use the log-to-file method instead. So now, if we go to our main method, we can immediately see a green squiggly line under the code that is calling the log-to-screen method. And if we hover our mouse pointers over the green squiggly line, we can see that the text that we passed as an argument to the obsolete attribute is presented to us. And note that if we want to force the user of our code to not use the log-to-screen method at all, we can set a second parameter in the obsolete attribute to true. If this value is set to true, an error is flagged when a user attempts to use the deprecated method, i.e. the log-to-screen method. Now you can see that the green squiggly line has turned into a red squiggly line, meaning that we no longer just receive a warning message. We are receiving an error message. This means we won't be able to compile the code. The last predefined attribute that I wish to discuss is the attribute usage attribute. We are going to create our own custom attributes and use reflection to read the relevant metadata added to relevant program elements through our custom attributes. So reflection and attributes will be implemented to provide flexibility to developers using our custom attributes to declare how relevant fields should be validated. This code is going to be very similar to the code that the ASP.NET MVC framework implements for field validation. In ASP.NET MVC, we can declare certain validation-related attributes against relevant program elements, and the MVC framework automatically handles validation of relevant fields for us behind the scenes, as it were. In this code example, however, we are going to create the custom attributes used for declaring how we want relevant fields validated, and we will also write code using reflection to read the attribute data declared against relevant program elements. In this case, the program elements will be properties. We will also write the validation code related to each of our custom attributes. Okay, so let's add a new standard library project to our solution. Let's name this project Validation Component. Let's delete the class that was automatically created by Visual Studio. Let's create a new folder named Custom Attributes. Let's add our first custom attribute class to the Custom Attributes folder. Let's right-click the Custom Attributes folder and add a new class. Let's name this class Required Attribute. Note that we must include the attribute suffix in the class name of our custom attribute. However, when we declare our custom attribute, you'll see that in the declaration we can omit the attribute suffix from the attribute name. We are, however, allowed to include the attribute suffix in our attribute declaration, but functionally this is unnecessary. We'll demonstrate this a bit later. The code for this attribute is very simple. Let's create a public auto-implemented property of type string named errorMessage. Let's add code to a parameterless constructor whereby the errorMessage property is set to a default value. So let's say we want a default error message of you cannot leave field, and then in curly brackets we have a 0 followed by the word empty. So the 0 in curly brackets allows the relevant field name to be inserted into the message at a later time. This is achieved through the use of composite formatting. If you are not familiar with composite formatting regarding string values, please view a tutorial created for this channel on C# strings. A link to this tutorial has been provided below in the description. Right, let's create a parameterized constructor. This will allow the developer to pass in a custom error message when declaring the required attribute against the relevant program element. The declaration of the required attribute will be demonstrated a bit later. In order for our class to be recognized as a custom attribute, we must ensure that our class inherits from the built-in system.attribute class. A custom attribute must inherit from the system.attribute class either directly, as we are doing here, or indirectly. For example, if our class inherited from another user-defined class that inherits from the system.attribute built-in class. So now all that is left to do is apply the predefined attribute usage attribute against our required attribute class. Like with the obsolete predefined attribute, the attribute usage predefined attribute is a member of the system namespace. Basically, the attribute usage predefined attribute allows us to provide metadata to the compiler. That will tell the compiler which elements are allowed to have our predefined attribute declared against them. So we can apply rules or constraints through the use of the attribute usage predefined attribute against our custom attribute at the class level. This is an example of declaring an attribute against a class. So in the first argument passed into the attribute usage attribute, we can declare which program elements are allowed to be decorated with our custom attribute. So if we have decided that we only want our custom attribute to be declared on the following program elements, fields, parameters, and properties, we can declare this by passing in this code to the first parameter of the attribute usage attributes constructor like this. So here we are declaring which target program elements are able to be decorated with our required custom attribute. We can optionally set a property of type Boolean named allow multiple through our declaration. If we set the allow multiple property to true, this means multiple instances of our custom attribute can be declared against a single program element. We only want one instance of our custom attribute to be declared against a single program element, so let's set the allow multiple property to false. We also have a property named inherited that we can optionally set through this declaration. Setting this property determines whether the relevant custom attribute is inherited by a derived class. In this example, we won't set this property. And that's it. We have now created our required custom attribute. So let's create our next custom attribute. Let's add a new class file to our custom attributes folder, and let's name this class string length attribute. Let's add 3 public auto-implemented properties to our string length attribute class. Max length, for the storage of an integer value denoting the maximum number of characters that a user can enter for a field related to a property against which the string length attribute has been declared. Error message, for the storage of a string value denoting the message outputted to the user when the user has entered an invalid value into a field related to a property against which the string length attribute has been declared. Min length, for the storage of an integer value denoting the minimum number of characters that a user can enter for a field related to a property against which the string length attribute has been declared. So let's create a private method named setProperties that we can reuse for setting our public properties. This method will be called from a number of constructor overloads that we'll implement in a bit for this class. This method does not return a value and contains 3 parameters that correlate to the public properties that we have already created. The first parameter is max length, which is defined as int. The second parameter is error message, defined as string. The third parameter is min length, defined as a nullable integer. The question mark symbol following the int keyword denotes that this parameter is nullable. So, it is a nullable value type parameter, because it's defined as an integer, which is of course a value type. Let's also make our min length parameter optional. We can do this in C# by simply assigning the relevant parameter a default value within the method definition like this. So if a value is not passed into this parameter, by default the min length argument will have a value of null. Before we move on with our example, let's go to the Microsoft Docs, specifically to this location, to read a bit about nullable value types. A nullable value type T ? Represents all values of its underlying value type T and an addition of null value. For example, you can assign any of the following 3 values to a bool ? variable: true, false, or null. An underlying value type T cannot be a nullable value type itself. Very basically, a null value means that a value for the relevant variable has not been set. Adding a question mark at the end of the value type definition for a variable or a parameter means we have the option of storing a null value in the relevant variable or parameter. Note that optional parameters must be included at the end of the parameter list in the relevant method's method signature. Okay, so let's implement the logic for the setProperties private method. So firstly, let's check to see if the error message argument contains an empty string. If it does, we want to set a default error message value. In order for our error message to contain appropriate text, depending on whether the min length value is set, we can create a nested if statement. So if the min length value is null, let's appropriately set our default error message. If the min length value is not null, let's include appropriate text relating to the min length value within our default error message. So if the developer does not pass in an error message when declaring the string length attribute against an appropriate program element, a default error message will be used. For the scenario where an error message value is set when the relevant attribute is declared against a program element, the error message provided must be assigned to the error message public property of the attribute. Then let's set the max length property. This is a property value that the developer must pass in when declaring the string length attribute against an appropriate program element. Let's then assign the appropriate value to the min length property. So let's use a ternary operator to check if the min length argument is null, i.e. has not been set by the developer declaring the string length attribute against an appropriate program element. If the min length argument is null, let's assign 0 to the min length property. If the min length argument contains a value, let's assign the value to the min length property. So let's create our constructor overloads. Firstly, let's create a constructor that contains just the max length parameter. Then within our constructor, let's call our private setProperties method to assign values to the appropriate public properties of the string length attribute class. Okay, I also want to make the error message parameter in the setProperties method an optional parameter. We can do this by simply assigning default value to the error message parameter like this. Note that the parameter after the error message parameter in our parameter list is also the last parameter in the parameter list and is optional. So it is perfectly legal to make our error message parameter optional. Remember, the optional parameters must be included at the end of the relevant parameter list. Let's create a constructor overload that contains the max length parameter and the error message parameter. Then let's use our private setProperties method to assign values to the appropriate public properties of the string length attribute class. Let's create a constructor overload that contains the max length parameter and the min length parameter. Let's use our private setProperties method to assign values to the appropriate public properties of the string length attribute class. Note how we are passing in a value to the min length optional parameter of the setProperties method. We need to be specific as to what parameter is being passed an argument here, because in this case, we are not passing in an argument to the error message parameter. The fact that the error message parameter and the min length parameter are both optional means in cases like this, we have to make it clear which parameter we want to pass our argument to. Let's create one more constructor overload. This constructor overload contains the max length parameter, the error message parameter, and the min length parameter. Let's use our private setProperties method one more time to assign values to the appropriate public properties of the string length attribute class. Let's ensure that we include the code whereby our class inherits from the system.attribute built-in class. So now let's declare the attribute usage predefined attribute against our string length attribute class. So we can copy the attribute usage declaration from our required attribute class and appropriately paste it in to declare the attribute usage attribute against our string length attribute class. Great, so we have now completed two custom attributes, the required attribute custom attribute and the string length custom attribute. Let's create one more custom attribute. This attribute will be responsible for indicating, when declared against a program element, that the input field's value related to the relevant program element should match a specified regular expression pattern. So regular expressions are great for defining patterns that an input field value must match for field types that must be constrained to a particular format, like, for example, postcodes, phone numbers, credit card numbers, email addresses, etc. So the validation code for fields like this will be simple. If the relevant input field value matches the specified regular expression pattern, the user's input is deemed as valid. If, however, the input field value does not match the specified regular expression pattern, the user's input is deemed as invalid. We can implement the validation logic related to our custom attributes once we have completed the code for this final custom attribute. So let's add a class to our custom attributes folder, and let's name this class regular expression attribute. Let's create two public auto-implemented properties. The first property, named errorMessage, is of the string date type. The second property, named pattern, is also of the string date type. The pattern property denotes the regular expression pattern that must be supplied by the developer when the regular expression custom attribute is declared against an appropriate program element. Let's create two constructor overloads. The first constructor overload contains one parameter named pattern. The developer is able to pass an appropriate regular expression pattern argument to this parameter when declaring the regular expression custom attribute against an appropriate program element. The error message argument is not passed into this constructor, but we can provide a default error message in this constructor and assign it to the error message property. Let's create a constructor overload. This constructor contains two parameters, one denoting the regular expression pattern and the other denoting the error message. So this constructor allows the developer to pass in a regular expression pattern argument, as well as a custom error message to a declaration when declaring this attribute against a program element. So all we need to do within the constructor is assign the public property members of this class with the appropriate values passed into the relevant constructor as arguments. Let's ensure that we include the code whereby our class inherits from the system.attribute built-in class. The last step is to appropriately declare the attribute usage predefined attribute against the regular expression attribute class. This declaration will be the same declaration applied against our other two custom attribute classes. So let's copy the appropriate declaration from one of our other custom attribute classes and appropriately paste the contents of our clipboards into our regular expression attribute class file. So now we have created three custom attributes implemented in three separate files. The first custom attribute we created is named required attribute. When this attribute is declared against an appropriate program element, this means that the associated input field must not be left empty. If it is left empty, the field value is deemed as invalid. The second custom attribute we created is named string length attribute. When this attribute is declared against an appropriate program element, this means the associated input field must contain a character length that falls within the boundaries defined by a specified minimum value and a specified maximum value. The third custom attribute we created is named regular expression attribute. When this attribute is declared against an appropriate program element, this means that the associated input field must contain a value that matches a specified regular expression pattern. So through the declaration of one or more of our custom attributes, a developer can express how a certain input field should be validated. Without the logic to implement the validation rules, however, these attributes are useless. These custom attributes perform no functionality other than to add metadata to relevant program elements. So the next step is to write the validation code. we must write the validation logic that correlates with each of our custom attributes. Through the use of reflection, we'll be able to read the metadata added to the relevant program elements through the use of our custom attributes. The use of our custom attributes is for the purpose of declaring how validation logic is related with relevant program elements, which are also related to relevant input fields. So let's write the relevant validation logic. So to do this, let's first add a new class named validation directly to the project node. So we want this class to be separate from our custom attribute classes. We are going to implement our own validation code in this class. So we first want to create the validation logic that corresponds to each of our custom attributes: the required attribute, the string length attribute, and the regular expression attribute. Let's encapsulate this functionality within 3 private methods. Let's first implement the validation logic that corresponds to the required attribute. So let's create a private static method named fieldRequiredIsValid that returns a Boolean value. This method contains one parameter. Let's name this parameter enteredValue and define it as a string. The logic for this method is basic. If the entered value passed into this method as an argument is not null or empty, return true, because this means the user has entered a value, which makes the input field entry valid. If the code that returns true is not executed, this means the entered value is invalid and false must be returned to the calling code. Let's implement the validation logic that corresponds to the string length attribute. The method signature for this method is the same as the fieldRequiredIsValid method, except we need to also pass in a field of type string length attribute to this method, in addition to the parameter representing the entered value. This is so that we can access the min length and max length public properties that we implemented for the string length attribute class. The values stored in these 2 properties are integral to the validation logic performed against relevant inputted values. Let's name this method fieldStringLengthIsValid. So to implement the validation code, let's implement an if statement where the condition evaluates the entered value argument to see if its character length is greater than or equal to the min length property and is less than or equal to the max length property. If the character length of the entered value argument falls within the range defined by the min length and max length property values, the entered value is valid, so we can return true to the calling code. If, however, the character length of the entered value does not fall within the specified range, we must return false because the entered value is not valid. So let's now implement the validation private method that corresponds to the regular expression attribute. So the method signature is almost the same as the fieldStringLengthIsValid method's method signature. Let's appropriately name this method fieldPatternMatchIsValid. Instead of including a parameter of type string-length attribute, let's include a parameter of type regular expression attribute. This is so that we can access the public property named pattern, which is a member of the regular expression attribute class. The pattern property will contain the regular expression pattern against which we need to validate the entered value. So let's use the regex class to perform our validation logic. This class is a member of the system.text.regularExpressions namespace, so let's include an appropriate using directive. The regex class contains a public static method named isMatch. We can use this method to validate the entered value against the relevant regular expression pattern. If the isMatch method returns true, this means the entered value is valid, so we must return true to the calling code. If, however, the isMatch method returns false, this means the entered value is not valid and we must return false to the calling code. Okay, so we have now implemented the validation logic that corresponds to our custom attributes. Let's create a public static method named propertyValueIsValid that returns a Boolean value. This method is responsible for calling relevant validation code that is relevant to a specific program element and a user inputted value. The validation code executed is determined by the custom attributes that have been declared against the relevant program element. In the interests of keeping this code simple, the code will only be relevant to a program element that is a property. So the first item in the parameter list for the property value is valid method is a parameter of type type. This parameter represents the type that contains properties against which our custom attributes may have been declared. For example, a user-defined type representing an employee record. The next parameter represents the value that a user enters, i.e., an input field, which is correlated to a particular property and needs to be validated by our code. This parameter is appropriately named entered value. The next parameter represents the program element, which will be a property in this case, that is a member of the type represented in the first parameter. So, for example, the program element could be the first name property, which is a member of a user-defined type named employee. The last parameter for this method represents the error message that will be displayed to the user if the user's input is deemed as invalid. We want to output the error message value, so let's include the out keyword in the relevant parameter definition. Let's implement the logic for this method. Firstly, let's get a reference to the relevant program element. So the program element in this example will be the property on which one or more of our custom attributes has been declared. So, for example, if we are validating the first name property on the employee user-defined type, the element name argument will contain the literal text first name, which is the name of the first name property. To get a reference to the user-defined type, in this case employee, the calling code would pass in type of employee. This means we can use reflection to inspect the relevant program element to ascertain which custom attributes have been declared against the relevant program element. Using reflection, we can then ascertain how we should validate the relevant entered value. So let's write code to get a reference to the relevant program element, which in this case will be a property. Reflection can be used to get relevant information about a program element. We want to know in our code what custom attributes have been declared against the relevant program element. So we can use the property info type, which is a member of the system.reflection namespace, to gain access to the property information that we need. We must include a using directive to the system.reflection namespace. Let's define a variable named prop as the property info type, and let's assign a value returned from a call to a method named getProperty, which is invoked on the type argument passed into the t parameter of this method. Note that we need to pass the element name argument to the getProperty method. The element name argument will store a reference to the name of the relevant property. We now have a reference to the relevant property information. We can use the getCustomAttributes method to return a collection of custom attributes that have been declared against the relevant property. We can assign the returned value to an array of type attribute. The getCustomAttributes method is returning a collection of type IEnumerable, and I want to store a reference to the relevant custom attribute objects in an array. So let's use LINQ's toArray extension method to convert the IEnumerable collection into an array. Let's initialize the error message output parameter to an empty string. Let's write code to perform a for each loop and loop through each attribute object declared against the relevant program element. Then within the for each loop, let's implement a switch statement and use pattern matching code to get a reference to the relevant custom attribute objects so that we can perform appropriate validation on the entered value. So the switch statement evaluates the type of each relevant attribute object using pattern matching. Using pattern matching, we are able to get a reference to the attribute objects that have been declared against the relevant program element. This is the magic of pattern matching in action. Pattern matching was introduced in C# version 7. It allows the developer to write code to assess whether an object type matches the object type specified in a case statement. If there is a match, a reference to the relevant object is made available on the same line of the code as the case statement. So here we have case required attribute. If the object referenced by the attr variable is of type required attribute, the RA variable is assigned the value referenced by the attr variable. We are then able to use the RA variable in our validation code that resides within the relevant case block. So we can call the appropriate private method for validating required fields that we implemented earlier to validate the relevant user entered value. If the entered value is deemed as invalid, we can output an error message to the user through the error message output parameter, which has been appropriately marked with the out keyword, meaning we can output a value through this parameter to calling client code. If the relevant user input fails validation, we need the property value is valid method to return false. So let's include the other case statements pertaining to the other two custom attributes. So let's implement the case block for the string length custom attribute. And lastly, let's implement the case block for the regular expression custom attribute. Great. Let's write the calling client code. Let's go to the .NET Core Console project. Let's start by creating classes that can represent data models. The first model will be a class that represents an employee record. So let's create a new folder and name it Models. Let's add a new class named Employee to the Models folder. This class contains 6 auto-implemented properties: ID as int, first name as string, last name as string, phone number as string, email address as string, and postcode as string. Great. So we are now going to appropriately declare our custom attributes against the properties we have just added to the employee class. These attribute declarations will indicate to our validation code how the input values associated with the employee class's relevant properties should be validated. Let's include an appropriate using directive at the top of our code to the validation component.customattributes namespace. So let's apply the required attribute to the ID program element. Notice how when we declare our custom attributes, we don't need to include the attribute suffix. So even though the class representing the required attribute is named required attribute, when we declare the attribute against the relevant program element, we can omit the attribute suffix. So in this case, we can declare the attribute using the name required. Let's declare the string length attribute against the first name property. Let's pass appropriate values to the constructor of the string length attribute. So let's say the maximum character length for the first name input field should be 15. Our next argument is the error message we wish to output to the user if the user enters an invalid value for the first name field. For the last parameter, let's say the user must enter a value for the first name field that has at least 2 characters. Let's declare the required attribute against the first name property, so we can copy and paste the custom attributes declared against the first name property to the last name property. Now the phone number property will include the same attributes and settings applied against the first name and last name properties. But we also want to validate the phone number against a regular expression pattern that can be used to validate UK phone numbers. So let's navigate to this URL. I find this website very useful for finding regular expression patterns. Let's do a search for UK phone numbers. Let's copy an appropriate pattern from our search results. We can then appropriately pass this pattern as an argument to our regular expression custom attribute. So let's appropriately paste our pattern into our code. Note that we may need to include the @ symbol preceding the string references of the regular expression patterns. This is because the pattern may include backslash characters which need to be escaped because the backslash character is used by C# within strings for escape sequences. For example, the \n escape sequence denotes a new line within a string. The \t escape sequence denotes a horizontal tab character within a string, etc. So by including the @ symbol preceding the string, we are indicating that any backslash character should be interpreted as a literal backslash character and not as part of an escape sequence. So let's apply the custom attributes for the email address property. Let's find an appropriate regular expression pattern and appropriately paste it into our code. Let's do the same for the postcode address. Let's say we need the postcode to be a valid UK postcode. Great. So now let's build a basic front end so that we can test our validation code. Let's write a reusable private method that contains logic to prompt the user for a relevant field value. We need this code to run within an infinite loop, which we can implement using a do loop. Once the user enters a valid value, the code will break out of the infinite loop. The getInput method returns true once the user has inputted valid data for the relevant input field. We can use the out keyword to make the last field an output parameter where we can pass the valid data to the calling code. Let's go to the main method and implement the calling code. Let's instantiate an object of type employee. Let's ensure that we have a using directive to the attributes_examples.models namespace. Because of course the employee class is a member of this namespace. Let's create 3 local string variables: empid, first name, and postcode. We need to get a reference to the employee class's type. We can do this using the typeOf method, like this. Let's write code to handle the user input for the employee's ID. So once the user has entered a valid value for this field, the valid data can be assigned to the ID property. The ID property of the employee type is an integer value. So let's write code to convert the relevant string value to an integer value. Let's write code to handle the user input for the employee's first name field. Once the user has entered a valid value for this field, the inputted value can be assigned to the first name property. Let's write code to handle the user input for the employee's postcode. So let's write code so that once the user has entered valid information for the relevant fields, a message stating that the user has now entered valid data for the relevant employee is outputted to the console screen. Great, let's test the code. So if we press the Enter key without entering an employee ID, we get an expected output. An appropriate error message is outputted to the console screen. Let's enter a valid ID. Great. So if we leave the first name field blank and press the Enter key, we get an appropriate error message outputted to the console screen. If we enter just one character for the first name field, the string length validation code deems our input as invalid and an appropriate error message is output to the console screen. So now if we enter a value for our first name field that contains a character length that falls within the character length range, which is between 2 and 15, this input is deemed as valid. If we leave the postcode field blank, we are presented with an appropriate error message. Let's enter a valid UK postcode. Great. Just to demonstrate that we are able to reuse our custom attributes on other user-defined types, let's create another model. Let's create a class to represent a department record. Let's apply some of our custom attributes. Let's go to our main method and test our code. In the interests of time, we'll only include the department short name field in our test here. Excellent. So let's use a predefined attribute that already exists in a .NET library. So the attribute I want to use is named JSON_ignore. So we want to add functionality to output our employee object to the console screen in JSON format. Using the JSON_ignore attribute, we can choose which fields to exclude from our employee object JSON output. Let's declare the JSON_ignore attribute against the phone number property and the postcode property. Let's go to our main method and write the code to serialize the employee object in JSON format. Let's run the code. And you can see that the JSON output does not include the phone number and the postcode fields. Great. Let's comment out the JSON_ignore attribute declarations so that we can include all of our property values for the relevant employee object in our JSON formatted output. Okay, so I accidentally inputted Bob's surname, which is Jones, for the postcode field, and I've noticed that there is a bug in our code. The error message format outputted to the screen is incorrect. The validation was run correctly, i.e. clearly Jones is not a valid postcode, but the error message itself is incorrect. The 0 wrapped in curly brackets in the appropriate code should serve as a placeholder for the property name of the property against which the relevant attribute has been declared. The 1 wrapped in curly brackets should serve as a placeholder for the regular expression pattern specified for the purpose of validating that a postcode entered by the user is in a correct UK postcode format. So I can see what is causing this issue. We need to remove the dollar symbol preceding the error message specified in this constructor. We want to use composite string formatting and not string interpolation for this string value. For details on composite formatting versus string interpolation, please view a video on C# strings created by this channel. A link to this tutorial is available below in the description. So let's repeat the input that we specified in the previous test. Great, the validation code is correct, and the outputted error message is also correct. Okay, but in our outputted JSON text here, the postcode field is null. So, it looks like we have another bug here. Oh right, so when I copied and pasted the code here, I forgot to change the relevant code so that the postcode property is set to the user's input. Okay, let's correct this. And let's test the code again. Excellent. We looked at how attributes are used in code to add metadata to program elements like classes, methods, properties, etc. And reflection can be used to read the metadata added through the use of the attributes at runtime. We discussed that there are two broad categories in C# for attributes, namely predefined attributes, which are built into the .NET base class libraries, and custom attributes, which allow the developer to implement the developer's own attributes by creating a class that inherits from the system.attribute built-in class, either directly or indirectly. We created code examples using predefined global attributes, namely assembly version attribute and assembly description attribute. This demonstrated how global attributes can be used to add and modify metadata at the assembly scope. We created code examples using predefined general attributes, namely conditional attribute, obsolete attribute, and attribute usage attribute. This demonstrated how we can add and modify metadata for program elements. We then created our own custom attributes as part of code logic used for the purpose of field validation. The use of reflection was also employed as part of this code logic. This code implementation imitates how the ASP.NET MVC framework uses attributes for field validation. I hope you've enjoyed this video on using attributes in C#. In the next part of this course, we'll create a basic ASP.NET MVC application where we'll use technologies like attributes, LINQ, and entity framework, along with front-end technologies like HTML, Bootstrap, CSS, and more. Please consider subscribing for more content on advanced C# topics and much more. And please ring the bell so that you'll be notified of future content. If you liked this video, please give it a thumbs up. It'll be greatly appreciated. Please feel free to share this video with anyone you feel may benefit from its content. I really enjoy reading your comments, so please feel free to engage with me in the comments section. As always, the code created for this video can be downloaded from GitHub. A link to the relevant GitHub repository is available below in the description. Hi and welcome to the 9th and final part of this advanced C# course. I was going to end the advanced C# course with an example of creating an ASP.NET MVC web application using C#. The more I delved into writing the tutorial on ASP.NET MVC, the more I realized that ASP.NET MVC at least demands its own video series. So I'm currently working on a video series where we'll build an ASP.NET MVC web application using C#. I'll bring these videos to you as soon as I can. As I had originally intended, I'm going to finish the advanced C# course focusing on the topic of C# reflection. So let's get into it. Let's first gain a basic understanding of reflection, and then we'll write a code example using the reflection technology in C#. So, what is reflection? Reflection provides objects of type that describe assemblies, modules, and types. You can use reflection to dynamically create an instance of a type, bind the type to an existing object, or get the type from an existing object and invoke its methods, or access its fields and properties. If you are using attributes in your code, reflection enables you to access them. For content like this and much more, please consider subscribing, and please ring the bell so that you'll be notified of future content. If you like this video at any point, please give it a thumbs up. It will be greatly appreciated. In the 8th part of this advanced C# course on C# attributes, we used the reflection technology to read metadata provided through the use of our own custom attributes from relevant program elements. When I say program elements, I'm referring to classes, methods, fields, properties, etc. So reflection allows the developer to access metadata within .NET assemblies at runtime. .NET assemblies are self-describing entities, which means the metadata data about the relevant assemblies reside within the assembly itself. So at runtime, we are able to load a target assembly and read its metadata using reflection. Using reflection, we are able to, for example, instantiate objects from classes that reside within the target assembly and invoke the relevant object's methods or get and set the relevant object's property values. So in this video, we are going to create a code example that will serve as a test harness. We are going to create code that loads a target assembly and displays a list of relevant classes that reside within the target assembly. We can then select an item in the relevant list that represents a class and test the functionality within each of the class's methods. The important thing to note here is that in this example, we will not reference the target assembly from within the project that contains our calling client code. We are using reflection to late bind to the classes that reside within the target assembly, so that we can instantiate objects and test the object's functionality at runtime. Note that when I refer to the target assembly, I am referring to the assembly that contains the functionality we wish to test through our test harness. We will be using what is known as late binding to test the methods that reside within the relevant classes contained within the target assembly. So, what is late binding? When we reference an assembly from a project through, for example, Visual Studio, and subsequently write code to instantiate an object from a class that resides within the referenced assembly, this is known as early binding. When we reference an assembly like this, the compiler has information about the target assembly at compile time. Late binding occurs when we don't set a reference to a target assembly at compile time, and we instantiate an object from a class that resides within the target assembly at runtime. The obvious disadvantage to late binding is that late binding is prone to runtime errors. When early binding is employed, the compiler has relevant knowledge, for example, relevant type information about the target assembly's constituents at compile time. So compile time errors can be flagged and corrected at compile time. Potential errors are averted at compile time, and therefore certain runtime errors are avoided. With late binding, reflection can be employed to gain necessary information about the target assembly itself and its constituents at runtime. So let's create our test harness code example where we'll use late binding to test the functionality that resides within a target assembly. Let's create a .NET Core Console application named Test Harness. Let's create a .NET Standard library project named Utility Functions. The Utility Functions project will be compiled into our target assembly. Now, it is important to note that I have included the Utility Functions project, which of course, when compiled, is compiled into a .NET assembly, in the same solution as the .NET Core Console project where we'll write our calling client code. This is important to note because we are not going to explicitly reference the Utility Functions assembly from the .NET Core Console project. So if we were to early bind to the Utility Functions assembly, we would reference our Utility Functions project like this. But let's cancel this dialog box because we are going to load the Utility Functions assembly at runtime using reflection. We are not going to set a reference to it at compile time. We want to late bind to the Utility Functions assembly at runtime. This is obviously just a mock example and not a real-world application. But you can see how we could put a number of assemblies within a directory, traverse the assemblies within the relevant directory, and automate the testing of functionality within the target assemblies at runtime. We would not have to reference any of these assemblies within our test harness project, because using reflection, we can access all the information we need for each assembly and test the functionality within the assemblies. So the advantage of this loose coupling of our test harness application with the assemblies that we are testing is that we don't need to early bind to the assemblies at compile time. We can simply put an assembly or assemblies in an appropriate directory, and our test harness application can learn about the assembly or assemblies at runtime by accessing the relevant assemblies metadata at runtime through reflection. But we will simplify this example and focus on classes within a particular namespace within one target assembly. Our target assembly in this case will be the utility functions assembly. If this doesn't make sense to you at the moment, please bear with me, and this will become clearer as we progress with creating this code example. Let's include basic functionality within our utility functions project. Once completed, this project will be compiled into an assembly which will serve as our target assembly, i.e., the assembly against which we'll perform our reflection functionality. Through the use of reflection, we'll be able to read relevant information about the assembly, instantiate objects from its classes, and test its methods. So, let's write the code for the utility functions assembly. Let's start by deleting the class that was auto-generated by Visual Studio. Let's add a class named Basic Utility Functions. Within the Basic Utility Functions class, let's create 4 very simple methods. Let's create a method named WriteWelcomeMessage. The WriteWelcomeMessage method contains no parameters and returns a welcome message as a string. Let's write a method named integer+integer. The integer+integer method contains 2 integer parameters and returns an integer value. The returned integer value will be the mathematical result of the first integer argument plus the second integer argument. We can appropriately name our parameters operand 1 and operand 2 respectively. Let's write a method named concat3strings. This method contains 3 string parameters and returns a string value. The returned string is a concatenation of the arguments passed into the concat3strings method. The order in which the string arguments are concatenated is the order in which their corresponding parameters appear in the relevant parameter list, from left to right. Let's write a method named getStringLength. It contains 1 string parameter. This method returns an integer value, the character length, of the string argument passed into the getStringLength method. And that's it. That is our very basic utility functions class completed. Let's create another basic class. Let's name this class Basic Math Functions. Let's create 2 really simple methods in this class. Let's create a method named divideOperation, which contains 2 parameters of type double. This method returns a value of type double. That is the result of a divide mathematical operation. In this method, the second argument is divided into the first argument, and the result of the divide operation is returned to the calling code. Let's create a method named multiplyOperation, which contains 2 parameters of type double. This method returns a value of type double. That is the result of a multiplication mathematical operation where the first number argument is multiplied by the second number argument. The returned value will be the product, which of course is the result of the multiplication of the first number argument by the second number argument. Okay, so we now have 2 classes in our utility functions project. So now we want to be able to decorate certain program elements with a custom attribute that we can use to provide additional information to the calling code about the relevant program elements. In this case, the program elements will be classes and methods. Let's create a custom attribute named Information Attribute. For more information on custom attributes, please view the previous part of this course, which is a tutorial entitled C# Attributes. I have included a link to the relevant video below in the description. So, in order to create a custom attribute, the relevant class must inherit from the system.attribute built-in class. Let's keep this class really basic, so let's add one auto-implemented property named description. This property will enable us to provide a custom description about a program element that we'll decorate with our information attribute custom attribute. We want to constrain our information attribute custom attribute to the decoration of only class and method program elements. So we can do this by decorating our information attribute custom attribute class with the attribute usage built-in attribute. We can then pass the following bitwise operation to the constructor of the attribute usage built-in attribute. So let's pass attribute targets.class or attribute targets.method to the constructor of the attribute usage built-in attribute. So this means that only classes and methods can be decorated with our information attribute custom attribute. So next, let's apply our custom attribute to the relevant classes and methods. Let's go to the basic utility functions class and let's decorate the class itself and its methods with the information attribute custom attribute. So let's set the description property for our custom attribute declared against the basic utility functions class to this class contains basic utility methods. Let's set the description property for our custom attribute declared against the writeWelcomeMessage method to this method returns a welcome message. Let's set the description property for our custom attribute declared against the integer plus integer method to this method returns the sum of two integer operands. Let's set the description property of our custom attribute declared against the concat 3strings method to this method concatenates 3 strings in the same order as they appear in the parameter list from left to right. Let's set the description property for our custom attribute declared against the getStringLength method to this method returns the character length of a string argument. So let's move on to our basic math functions class. Let's decorate the basic math functions class with our information attribute custom attribute like this. So here the description property is set to this class contains basic math functionality. Let's decorate the divide operation method with our custom attribute, where the attribute's description property is set to this method divides the first number by the second number and returns a result of this divide operation. And lastly, let's decorate the multiply operation method with our custom attribute and set its description property to this method multiplies the first number by the second number and returns a result of this multiplication operation. So we have included in the metadata for our utility functions assembly very basic descriptions about method and class program elements through the use of our information attribute custom attribute. Now let's write the calling client code. So in the calling client code, we want to provide functionality that targets a particular namespace within the target assembly. In this case, our target assembly will be the utility functions assembly and reads all the relevant information about the assembly's classes and methods that are members of the relevant namespace. We'll create functionality where the user can choose a class from a list of classes that reside within the relevant namespace. Once the user has chosen the class that the user wishes to test, the user can then choose a method from a list of methods that are members of the relevant class. The user can then select from a list of methods the method that the user wishes to test. Once the user has chosen the method that the user wishes to test, the user is prompted for values for each of the parameters contained within the relevant method's method definition. Once the user has provided values for all the relevant parameters, our code will invoke the method, and the result returned by the method is displayed to the console screen. So you can see that this test harness application can be used to test functionality within an assembly. Note that you can extend the code that we are about to write to traverse a number of assemblies within a directory and automatically test particular functionality within the assemblies. So you could write your own automated test facility based on the code we are about to write. For the purposes of this tutorial, however, the code will be simplified. So let's write the code for our test harness project, which is our .NET Core console project. The first thing to do is within our calling client code is include a using directive to the system.reflection namespace, like this, so that we can make use of reflection in our application. So let's start writing our code in the main method. Let's first create two local string constants. The first constant stores the target assembly file name, utilityfunctions.dll. The second constant stores the target namespace that contains the classes that the user will be able to test through our test harness application. So the namespace is utility functions. Let's write the code that will load the target assembly at runtime. So we are using the assembly.load method to do this, but we may need to replace this with the assembly.load file method. When we test and debug the code later in the tutorial, we'll know which method needs to be employed here, either the load or load file method. So we'll leave it as load at this point. We pass in the path of where the target assembly will be in order to load the target assembly into memory. So later in this tutorial, just before we test our code, for the sake of simplicity, we'll copy the target assembly into the same directory as where the assembly for this project will reside. So let's write code here to point to the path of the target assembly, which will be the current directory, the same directory as where the test harness assembly will reside. Let's use the path.combine method to combine a path with the name of the file. The path class resides in the system.io namespace, so let's include a using directive to the system.io namespace. So we are able to get the current path from the appdomain.currentdomain.base directory property. This is the directory where the assembly that we are currently working on will reside. Let's pass this value as the first argument to the path.combine method. Then let's pass the name of our target assembly, which is utilityfunctions.dll, as the second argument into the path.combine method. The return value from the assembly.load method will be the object of type assembly. So let's assign a variable of type assembly, the value returned from the assembly.load method. So we have now got a reference in memory to our target assembly. Let's write code to get a list of classes from the target namespace within our target assembly. So the namespace within our target assembly is named utility functions. So let's use LINQ to get a list of types or classes from within the utility functions namespace. Let's ensure that we have a using directive to the system.link namespace. So we can use the assembly object's getTypes method to return a collection of classes that reside within the target assembly. We can use the where method to filter on the assembly's utility functions namespace, like this. Let's assign the returned result to a generic list that is strongly typed as system.type. Then let's convert the IEnumerable collection returned by the LINQ query to a list, and we can do this by using the toList conversion method, like this. Let's write a method that encapsulates writing a prompt to the user. Let's write code to display a message prompting the user for input to the console screen. As you can see, we are prompting the user to press a number key to indicate to the application which class the user wishes to test. So it is better to encapsulate this prompting functionality in a method that we can reuse for this purpose throughout the creation of this application. This method encapsulates the functionality of displaying text to prompt the user for input to the console screen. So next we want to write code to display a list of classes to the console screen, so that the user can select the class that the user wishes to test. So we can simply write code that traverses the items stored in the classes list, which contains the result of our LINQ query, and output the relevant class names to the console screen in sequential order. So let's do this. In our list of classes, each class name is preceded by a number, which will allow the user to press a number key to select the class that the user wishes to test. Let's write the code where the user can press a number to select a class from the classes list. Let's use a switch statement to return the relevant item from the list. So now we want to create an object instance from the user's chosen class or type. We can use the activator.createInstance method to do this. And here we are writing code to late bind to a class within the target assembly. We can assign the returned object from the activator.createInstance method to a variable of type object. You can see that when we late bind like this, we do not have the benefits of type safety. So code like this is prone to runtime errors. This highlights a disadvantage of late binding like this in code. So because at compile time, we don't know the type that will be returned at runtime by the activator.createInstance method, we need to use a variable of type object to reference the returned value. So we have now written the code enabling the user of our application to choose a class from a list of classes by pressing a number key associated with the relevant class. Once the user has chosen a class, the user will be presented with a list of relevant methods. Let's write code to clear the screen once the user has chosen the class from the list of classes. Let's write a method where we can encapsulate code to output a heading to the console screen. On the screen that displays a list of methods belonging to the class that the user has selected, we want to include a heading at the top of the screen containing the class name that the user has chosen. Let's go to the main method and write the code to output the relevant heading to the console screen. Let's write code to prompt the user to choose from a list of relevant methods. We now want to write code to output a list of relevant methods to the console screen. So logically, the code to present the user with a list of methods is exactly the same as the code that presents the user with a list of classes. So we have an opportunity here to refactor our code by creating a reusable method that encapsulates functionality to output a list of both classes and methods. So this will be one block of code that can output a list for both classes and methods. In this method, we need to account for the difference between the type representing a class and the type representing a method. In this context, classes are of type system.type and methods are of type methodInfo. So to solve this problem, we can apply generics. Let's create a method named displayProgramElementList. Let's include the t placeholder between greater than and less than symbols to indicate that this is a generic method. Let's base the code for this method on the code that we have already written in the main method to output a list of classes. You can see that we are writing this code in a more generic style because this code will output the items of a generic list that is strongly typed as system.type and a generic list that is strongly typed as methodInfo. Great. So let's replace the code in the main method that outputs a list of classes with a call to our displayProgramElementList method. The type that represents a class in terms of reflection is system.type. We have another opportunity to refactor our code because the code to return an object of type system.type from our list of classes or types logically is the same as the code to return an item of type methodinfo from a list of methods. So let's write code to encapsulate this functionality in a method named return program element reference from list. So we need to include generic functionality within the method definition of the return program element reference from list method. We also need to return a value of type t from this method. And we can copy the code for this method from our main method and paste it into our return program element reference from list method. So let's replace the code in our main method that enables a user to choose from a list of classes with a call to the return program element reference from list method. So let's call the getMethods method on the type choice object, which represents the class that the user has chosen from the relevant list, and assign the returned value to a generic list that is strongly typed as method info. Note that a generic list that is strongly typed as system.type is used to store references to classes or types, and a generic list that is strongly typed as method info is used to store a list of methods. We can now reuse the display program element list method in our main method to display a list of methods. We can pass in the method info type to the relevant type parameter, but we don't actually need to do this here because the compiler has enough information to determine the type. Let's call the return program element reference from list method, which will enable the user to choose a method from a list of methods displayed to the console screen. Let's write an if statement to check if the method info object returned from the return program element reference from list method is not null. Let's write code to clear the screen. Let's write code to output a heading containing the class name and the method name of the class and method that the user has chosen to test. So the next step is to prompt the user to provide a value for each parameter of the relevant method. So we are able to get a list of parameters from the relevant method by implementing the method info object's getParameters method like this, and we can assign the returned result to an array of type parameter info. The next step is to invoke the method chosen by the user and pass in the relevant parameter values that will be provided by the user's input, i.e. if the relevant method contains any parameters. If the relevant method does not contain any parameters, the method can be invoked without any arguments passed to it. So let's encapsulate the functionality for this in a method named getResult. In order to execute the functionality for the getResult method, we need the relevant class instance object, the relevant method info object, and the array containing the relevant array of parameter info objects. So in the getResults method definition, let's include a parameter of type object to accommodate the class instance. Let's include a parameter of type method info to accommodate the relevant method to be executed. And let's include a parameter that accommodates an array of type parameter info. So the invocation of our method is going to be different in terms of code implementation when the method that is invoked requires a number of arguments, to when the method requires no arguments passed to it, i.e. the relevant method's method definition contains no parameters. So let's create an if statement that checks to see if the parameter's argument contains any items. If it does not contain any items, we can call the method info object's invoke method and pass null into the second argument. The first argument must be passed an argument that references the appropriate class instance. This class instance or object contains the method that we are invoking here through this line of code. The else part of the if statement invokes a method that does contain parameters. So we must write code to prompt the user for a value for each parameter. So let's create a method that allows for an argument which will contain an array of parameter info objects to be passed to it. So let's name this method return parameter value input as object array. Let's create a one-dimensional array named param_values and provision the array to hold a number of items equal to the number of items stored in the array passed into this method, i.e. the array of type parameter info. Let's create a counter variable named itemCount and initialize it to a value of 0. Let's create a for each loop to loop through each item in the parameters array. Let's write code to prompt the user to enter a parameter value. So let's say that we know that the parameter type can only be one of the following: string, int, or double. So let's write an if statement to check the type of the relevant parameter. If the parameter is a string, then no type conversion of the console.readLine method value is necessary because this method returns a string. So we can then write code to assign the user's input to the relevant position in the parameter values array. So the code for when the relevant parameters of type int or double is slightly different. We must include an explicit type conversion from string returned by the console.readLine method to the relevant type before assigning the inputted value to the appropriate position in the param values array. We must increment the item count variable by 1 for each iteration of the loop. In the location in our code editors where the loop has exited, we can write the code to return the param values array to the calling code. Great! So let's go back to the getResult method and call the return parameter value input as object array method. Then we can write code to invoke the relevant method and pass in an array argument containing the user's input for each parameter as the second argument to the method.invoke method, like this. As stated earlier, the first argument passed to the invoke method is the relevant instantiated object, instantiated from the class that the user has chosen to test. To finish this method off, let's write the code to return the result returned by the relevant method to the calling code. Let's then go to the main method and call the getResult method. Let's write the code to display the returned result from the getResult method to the console screen. Great! Before we test the code, let's compile our two projects. Let's find the target assembly and let's copy the assembly to our clipboards. Then let's go to the directory of our test harness project and paste the target assembly into this directory. Let's test our code. Okay, so we have a little bug here. So I suspect this is because we need to use the load file method instead of the load method. So let's change the code accordingly. Let's run the code again. Great! We can see our class is displayed in a list, but our information attribute custom attribute class is also present in the list, and this is not desirable. We don't have any methods in the information attribute custom attribute class to test. So, if we select one of the classes that we wish to test, like, for example, the basic utility functions class, we are presented with a list of methods, which is great. There are some methods listed here that we are not interested in testing, like, for example, the equals method or getHashCode method. These methods belong to the object class, which, as we know, is ultimately the base class for all types in C#. So we only want to test the methods that perform functions directly related to the class we have selected, in this case, the basic utility functions class. We'll modify the code to filter out undesirable code elements in a bit. For now, let's continue with our test. Let's select the integer plus integer method. Oh, we should be receiving a prompt to enter a value for each of the parameters contained within the integer plus integer method. So we have another bug to fix. So here's where we need to fix the bug. I forgot to include the prompt text in the return parameter value input as object array method. So let's include a prompt for each parameter item. Let's test the code again. Let's select the basic utility functions class from our list of classes. Let's select the integer plus integer method. So we are now prompted to enter a value for the first parameter. Great. So let's do that. Let's enter 5. We are then prompted to provide a value for the second parameter. Let's enter a value of 6 for this parameter. Once we press the enter key, the correct result of 11 is presented to us. Great! So except for the fact that certain program elements that we have no desire to test are appearing in our lists, the basic functionality of our test harness is working as expected. So let's write the code to filter out those unwanted program elements. We are going to use the information attribute custom attribute for this purpose. Let's say that we only want those program elements that are decorated with our information attribute custom attribute to appear in our lists of program elements to test. So let's write a method that checks to see if a program element, i.e. a class, or a method is decorated with the information attribute custom attribute. If the program element is decorated with the information attribute custom attribute, we want to include the relevant program element in our list of program elements to test. If, however, the program element is not decorated with the information attribute custom attribute, we must exclude the relevant program element from our list of program elements to test. So let's write a private static method named hasInformationAttribute. And let's include one parameter within its method definition. This parameter will represent the program element that we need to check. So we need the hasInformationAttribute method to check if the information attribute custom attribute has been declared against the relevant program element. In the context of the requirement of this application, the program element can either be a class or a method. So the parameter must be of a type that can accept a class or a method as an argument. In this particular case, those types will either be of type system.type or of type method.info. We could include two methods named hasInformationAttribute and differentiate their method definition, where each method definition contains a parameter of a different type. One version of the hasInformationAttribute method can contain a parameter of type system.type, and the other version of the method can contain a parameter of type method.info. So we could use method overloading to perform the desired check for if a custom attribute has been declared against a program element, i.e. either a method or a class. However, we can achieve what we want with only one version of the hasInformationAttribute method, because the system.type and method.info types both inherit from a common class, the member.info class. If we right-click the text in our code editors representing the type class and select Go to Definition, we can see that the type class inherits from the member info class. If we do the same thing against the method info class, we can see that the method info class also inherits from the member info class. If we look at the member info class definition, we can see that it contains a method named getCustomAttributes, and this is the method we need to use to check if the relevant program element is decorated with the information attribute custom attribute. So the point is we don't need to overload the hasInformationAttribute method. We can simply define the parameter for the hasInformationAttribute method as memberInfo in one method. This will mean we can pass both types of arguments to the hasInformation method, i.e. an argument of type system.type, a class program element, or an argument of type methodInfo, a method program element. So let's look at the code for the hasInformationAttribute method. We have created a local string constant to store the name of the type of our information attribute custom attribute. So this name includes the namespace of where the information attribute custom attribute resides, a full stop, and the attribute class name. We have written code to loop through all the custom attributes that may be declared against the program element type passed into this method. As you can see, we are able to call the getCustomAttributes method for both class and method program elements in our method, because the system.type class, which represents class program elements, and the methodInfo class, which represents method program elements, both inherit from the memberInfo class, which contains the getCustomAttributes method. Within our for each loop, we first get the type of the current attribute. So we have written typeAttrib equals attrib, the current attribute object, dot get type. We then check to see if the name of the type attribute is equal to the information attribute custom attribute's name. If it is, this means that the information attribute custom attribute has been declared against the program element type passed as an argument to this method, so we can return true to the calling code. If all attributes have been traversed and none of the attributes match our information attribute custom attribute, this means that the program element passed as an argument to the method does not have our information attribute custom attribute declared against it, so we must return false. So this method can be used in our calling code to filter out program elements based on whether or not the relevant program element is decorated with the information attribute custom attribute. So how can we use our method for this purpose in our main method? The answer is we could modify the relevant LINQ queries to include our hasInformationAttribute method. And we can include our hasInformationAttribute method in the relevant where filters. So let's first modify the LINQ query for returning a list of class program elements. We can simply include a call to our hasInformationAttribute method in the where filter method like this. To filter out methods that aren't decorated with the information attribute custom attribute, we can modify the appropriate LINQ query like this. Let's test our code. Excellent. You can see that only those classes in our target assembly that are decorated with the information attribute custom attribute appear in the relevant list. If we select the basic math functions class from our list of classes, we can see that its methods that are not decorated with the information attribute custom attribute have been filtered out of the relevant list. Great. Let's also include functionality to appropriately output to the console screen the description property value of the information attribute custom attribute for our relevant program elements. In terms of the user's experience, this functionality will provide additional information about the classes and methods that the user wishes to test. So let's write a private static method named return information custom attribute description. This method returns a string and contains a parameter of type member_info. Remember, both the system.type class and the method_info class inherit from the member_info class, so this method can be reused for both class and method program elements. We want to read the description property, so let's create a local string constant that references the text description. Let's create a for each loop that loops through the custom attributes that may have been declared against the relevant program element, which in this case will either be a method or a class. So within the loop, let's reference the attribute type like this. We can then apply an if statement to check if the current attribute is the information custom attribute. Okay, so let's refactor our code here so that the target information attribute type constant can be accessed from both this method and the hasInformation attribute method. If the current attribute is the information custom attribute, then let's access its description property. We can do this using a reflection like this. So we are attempting to check if the property info object is not null, but the compiler is complaining. This is because the project is currently built on .NET Core version 3.1. Checking for nulls like this is only allowed in a later version of C#. So I'm going to change the version of .NET to .NET 5 for this project. Great, and you can see now that this line of code is now supported, i.e. using the isNotNull line of code. But I'm going to use the old way of checking for nulls anyway, just in case the followers of this tutorial are using an older version of .NET for their projects. So we have now written the code to read the description property from objects derived from the relevant information custom attributes that have been declared against relevant class and method program elements. So let's write the code to appropriately output the program element descriptions declared through the use of our information attribute custom attribute to the console screen. Let's create a method named displayElementDescription for this purpose. This method only needs one parameter, which will be the text we wish to output to the console screen. Let's write code to check if the argument passed to this method is not null. If it is not null, let's write its value to the console screen using a different background and foreground color to the default console screen colors so that the text stands out. Then let's use the console.resetColor method to reset the color back to the default console foreground and background colors. Let's go to the main method and use the displayElementDescription method to output the relevant program element descriptions to the console screen. So we can pass the result of the return information custom attribute description method into the displayElementDescription method on one line like this. This code will display our custom descriptions of the program elements that the user wishes to test. Let's test the code. Okay, so we are getting a bug and this is because the load file method cannot find the target assembly. The reason for this is because when we changed our version of .NET for the test harness project, a new directory for .NET 5 was created. This directory contains the assembly for the test harness project, but it doesn't, of course, contain the target assembly. So let's copy the most recently built utility functions assembly to the .NET 5.0 directory. Let's run the code again. And you can see that our custom elements are displayed, and we are able to test the functionality of methods and classes that reside within our target assembly. We have used the reflection technology to accomplish this. You can also see that additional information about the relevant program elements is outputted to the console screen. This was made possible through the use of our information attribute, custom attribute. Excellent! To finish off the application, let's add code to enhance the user's experience. As you may have noticed, once the user has tested a method, the application automatically ends. We currently have no way of navigating back to the first screen, where we are presented with a list of classes that we may wish to test. We want the user to have the option of returning to the list of classes so that the user can carry on testing other classes and methods. So we can do this by putting the relevant code within an infinite loop. Once the user has tested a particular method, the user can either press, let's say, the spacebar key to end the application, or any other key to return to the screen that contains a list of classes. Let's test the code. Excellent! So the last thing I'd like to bring to your attention is the technology encapsulated in the system.reflection.emit namespace. Using this technology, a developer is able to generate code dynamically. So the developer is able to generate dynamic methods or even dynamic assemblies on the fly. The user could, for example, generate intermediate language code on the fly based on user input. So because of functionality like this, you can see how incredibly powerful the C# language is. I recommend navigating to this location to read more about this powerful aspect of reflection. I hope you've enjoyed this tutorial on C# reflection. We have now come to the end of this advanced C# course. If you've got this far, congratulations. This channel now provides 2 complete in-depth courses on features of the C# language, a beginner's course and an advanced course. The next series of videos will focus on the ASP.NET MVC framework, where we'll build an application in C# using the ASP.NET MVC framework on .NET 5. During this time, I will also produce other videos relating to C# and other technologies. So let's end this video by summarizing what we have learned about C# reflection. Reflection provides objects of type that describe assemblies, modules, and types. You can use reflection to dynamically create an instance of a type, bind the type to an existing object, or get the type from an existing object and invoke its methods or access its fields and properties. If you are using attributes in your code, reflection enables you to access them. We demonstrated using reflection to create an application that can serve as a test harness. The test harness allows a user to add a target assembly to the same directory where the test harness application resides, and choose a class that the user wishes to test from a list of classes that belongs to a specific namespace that resides within the target assembly. When the user selects a specific class from the class list, that class is instantiated into an object through the use of late binding. This is how the test harness is able to test the functionality within a target assembly without referencing the target assembly at compile time. In the test harness application, reflection is employed to instantiate the relevant class into an object. When an assembly is referenced by a project at compile time, this is known as early binding. With early binding, the compiler has relevant information about the types within the target assembly at compile time. Late binding is used when the compiler does not have compile time knowledge of the target assembly. So, a technology like reflection is used to access the relevant information about the assembly, which allows for late binding to occur at runtime. It was noted that late binding has the disadvantage of being prone to runtime errors. When early binding is employed, a specific type can be instantiated into an object using the new operator, and we have the advantage of compile time type safety. We do not have the advantage of compile time type safety when late binding is employed in code and the activator.create instance method is used to instantiate an object from a type. Lastly, we briefly discussed the technology encapsulated within the system.reflection.emit namespace. Functionality for generating intermediate language code or IL code dynamically resides within the system.reflection.emit namespace. A developer can use the functionality within the system.reflection.emit namespace to create code for dynamically generating methods and even assemblies at runtime. For content like this and much more, please consider subscribing and please ring the bell so that you'll be notified of future content. If you like this video, please give it a thumbs up. It will be greatly appreciated. Please feel free to share this video with anyone you feel may benefit from its content. I really enjoy reading your comments, so please feel free to engage with me in the comments section. The code created in this tutorial can be downloaded from GitHub. A link to the relevant GitHub repository has been included below in the description. Thank you, and take care. Let's go back in time to the end of February 2002 with the first release of the .NET framework. This is when C# was first released. It is a new, fully object-oriented general-purpose programming language. Visual Basic, through its .NET evolution, has been upgraded from a largely event-based language tightly coupled with the Visual Basic 6 IDE to a new object-oriented version of itself called Visual Basic.NET. A managed version of C++ could also run within the .NET sphere. New languages like F#, which was first released in 2005, could also run within the .NET environment. These languages are all interoperable, which essentially means, for example, a C# application can consume a .NET component written in Visual Basic, or an application written in Visual Basic can consume a component written in C#. What makes this possible is the Common Intermediate Language, or CIL. All high-level .NET programming languages like C#, Visual Basic, C++, etc. are first compiled into the Common Intermediate Language before further compilation into machine language by the Common Language Runtime. All code that runs within the .NET runtime is considered managed code. The .NET runtime also makes available a number of libraries that can be leveraged by our custom .NET code. This is essentially done through a library of files called the Framework Class Libraries, or the abbreviation of this, FCL, which provide generic functionality for our applications to consume. The Common Language Runtime, or CLR, can be described as the .NET virtual machine and provides services like just-in-time compilation, memory management, security, and exception handling. It is important to note that the .NET framework will only run on appropriate Windows operating systems and must be installed in its entirety on the target computer. There have been many versions of the .NET framework released since its inception, and they are able to run side by side on the same computer. The latest version of the .NET framework at the time of writing this tutorial is .NET Framework version 4.7. Let's go back in time again, to June 2016, when the first stable version of the .NET Core runtime was released. It can be described as a cross-platform, more agile, modularized, lightweight version of the .NET framework. It supports appropriate standards so that multiple languages can run and be managed within the .NET runtime, and also provides language interoperability. Each .NET Core language compiles into the Common Intermediate Language, or CIL. .NET Core provides some of the standard framework class libraries, which can be called the Core FX and can be described as a partial fork of the framework class libraries. .NET Core's virtual machine can be referred to as Core CLR or Core Common Language Runtime, and it provides services like improved just-in-time compilation, memory management, security, and exception handling. Unlike the .NET framework, .NET Core can run on Mac OS, Linux, as well as Windows. .NET Core also provides a modular framework so that only the modules that your application uses are shipped with your application. An important difference between .NET Core and the .NET framework is that you no longer need the entire .NET framework installed on the target computer, but only those components of the .NET runtime that your application needs. This is why .NET Core is often referred to as a more agile version of the .NET framework. .NET Core is open source software which makes things like the bug fix release process more efficient. It is optimized for the cloud. It is designed for high performance, provides a great base for microservice architecture, it is designed to be highly scalable. .NET Core is definitely a significant evolution of the .NET runtime, but it must be noted that it does not replace the .NET framework. Please see in the description below a URL for a Microsoft Docs webpage containing recommendations for when to use the .NET framework and when to use .NET Core as the .NET runtime for your server applications. .NET 6 completes the unification of the platform and adds new capabilities for building web, native and hybrid apps for Linux, Windows, Mac, iOS and Android with a single code base. This video is an overview of what to expect with the release of .NET 6, which is due to be released on the 9th of November of this year, 2021. For content like this and much more, please consider subscribing, and please ring the bell so that you'll be notified of future content. Please feel free to share this video with anyone you feel may gain value from its content. Before I give a brief summary of what new features and improvements to expect with the release of .NET 6, I'd like to present you with a brief summary of my personal experiences as a developer with the technological innovations that have been made over the years. I remember working as a young developer in the late 90s on enterprise web applications. When I look back, I'm proud of what we were able to achieve using what is now known as Classic ASP, or Classic Active Server Pages. Classic ASP was introduced as Microsoft's first server-side scripting technology for creating web applications. The ASP files were coded in VB-Script. I remember we wrote our business logic in Visual Basic and compiled our code into COM components. We then installed our COM components in an environment known as MTS. Microsoft Transaction Server. The Microsoft Component Object Model, COM, and Microsoft Transaction Server, MTS, later evolved into COM+. Using active server pages, our code was written in VB and we would call our COM components from our active server pages. COM+ handles many of the resource management tasks that previously needed to be programmed by the developer, such as thread allocation and security. Classic active server pages allowed a developer to implement code logic using VB and output HTML, client-side JavaScript, and CSS code to the client's browser. So back then, we typically created our applications using a 3-tier architecture. Classic ASP contained code and logic to output HTML code, JavaScript, and CSS to the client's browser. COM components that contained business rules ran in MTS, later known as COM+. SQL Server was used for our backend storage facility. In the early 2000s, I moved to London. My move to London coincided with the first release of C# and .NET. .NET was a gigantic step forward for Microsoft technologies. Visual Basic 6 was the last version of Visual Basic before the dramatic change that was to follow in the form of .NET. .NET was a complete rethink. Visual Basic was still offered as a language, but instead of being limited to being a largely event-based language tightly coupled with the Visual Basic 6 IDE, was now known as Visual Basic .NET and is a fully object-oriented programming language. The first version of .NET was named .NET Framework. Programs written in .NET Framework executed in a software environment, in contrast to a hardware environment. This software environment is named the Common Language Runtime, CLR. A number of class libraries, called the Framework class libraries, are built into .NET Framework and are available to be consumed by .NET applications. Developers can produce their software by combining their source code with .NET Framework class libraries. So .NET Framework provides a library of classes that can be leveraged from our applications. .NET applications run in an environment known as the Common Language Runtime, or CLR, which can be described as the .NET virtual machine and provides services like just-in-time compilation, memory management, security, and exception handling. So .NET Framework provided developers with a sophisticated environment that would revolutionize the developer's experience. In the early 2000s, I was now working on web applications using a .NET version of Active Server Pages, known as ASP.NET. And I was able to write my code using a new, fully object-oriented programming language known as C#. So, in the early 2000s, the introduction of .NET was a massive leap forward. .NET Framework was interoperable, meaning you could write code in any language that supported the common type system. So we could write our applications using, for example, C#, Visual Basic, C++, etc. This was great, but .NET Framework could only run on Windows platforms and required a monolithic installation. .NET Framework does not run on Linux or Mac OS. Mono was released on June 30th, 2004. Mono is a free open-source implementation of Microsoft's .NET Framework based on the ECMA standards for C# and the Common Language Runtime. Mono was a version of .NET that could run on multiple platforms. Mono can run on Windows, Mac OS, and Linux. On June 27th, 2016, the first version of .NET Core was released. .NET Core is the .NET successor to .NET Framework. .NET Core is primarily developed by Microsoft employees by way of the .NET Foundation and released under the MIT license. .NET Core supports the use of NuGet packages. .NET Core can be described as a lightweight, modular, cross-platform, and more agile version of .NET Framework. To prevent future fragmentation of .NET implementations, .NET Standard was introduced. The motivation behind .NET Standard was to establish greater uniformity in the .NET ecosystem. .NET Standard is a formal specification of .NET APIs that are available on multiple .NET implementations. The specification is maintained by .NET implementers. Specifically, Microsoft includes .NET Framework, .NET Core and Mono, and Unity. .NET 5 was a significant release of .NET and was released on the 10th of November 2020. .NET 5 is the first release of a version of .NET that attempts to unify all features of all versions of .NET under one implementation of .NET. The idea behind this version of .NET is to have one .NET moving forward that can target Windows, Linux, macOS, iOS, Android, tvOS, watchOS, and WebAssembly, and more. .NET 5 is the future of .NET Core and is almost a complete reimagine of the old .NET framework. In fact, .NET 5 is the first major update since the 2016 release of .NET Core. .NET 5 was a direct evolution from .NET Core 3.1. And the reason why it was called .NET 5 and not .NET 4 is because the last release of .NET Framework was version 4.8, which was released on July the 25th, 2019. Both .NET Core and Framework were maintained in parallel, allowing you to choose between one or the other. You could leverage .NET Standard to make shared libraries between the two. The release of .NET 5 meant that .NET Framework will be deprecated. This means you can only use .NET Framework as long as your operating systems, for example Windows Server 2019, will support it. So .NET 5 was the first step forward to unify .NET. And finally, we get to the release of .NET 6. The main significant aspect of .NET 6 is the fact that it delivers the final parts of the .NET unification plan that started with .NET 5. Here is a brief overview of the new features and improvements that we can expect with the release of .NET 6. C# version 10. The significance of version 10 of C# and future versions of C# that are to be released in line with each new version of .NET is that the developer can write less code. With the evolution of C#, there's a strong focus on simplification. Much of the boilerplate code that needed to be written when using previous versions of C# do not need to be written when using C# version 10. So this improves the clarity and simplification of a developer's code and potentially increases productivity, allowing the developer to focus more on application business logic. .NET Multi-Platform App UI for native mobile and desktop apps. .NET Multi-Platform App UI, or .NET MAUI, is an evolution of Xamarin. It allows the developer to create applications for multiple different types of platforms using a single code base. You can write one project that can be compiled into an application that runs on Android devices, iOS devices, Windows desktops, Windows devices, as well as Mac OS. So, one code base written in, for example, C# that can leverage native capabilities on multiple heterogeneous devices. Blazor desktop web apps with native device capabilities. So one advantage of this is that if you are a web developer and don't want to learn XAML to implement your front-end code, as you would when developing an application using, for example, WPF, UWP, or Xamarin Forms, you can use HTML5, CSS, Bootstrap, and JavaScript, i.e. the web technologies with which you are already familiar, to create desktop applications. Through Blazor desktop web apps, you will still be able to leverage native device functionality and not worry about learning new technologies to leverage these native functionalities. Minimal web APIs for cloud-native apps. This is a great feature that allows a developer to be up and coding, for example, a simple microservice a lot quicker than if the developer were to code that microservice using a typical web API that implements the MVC architecture. There is far less ceremony involved in getting started. More device targets, including Apple M1. .NET 6 will support single file deployments for Windows with up to 50% smaller file size. .NET 6 supports ahead-of-time compilation. Productivity enhancements like hot reload. If, for example, you've developed Angular applications with Node, you may be familiar with the hot reload feature. This feature is now coming to .NET developers. This means improved productivity simply because there's less need to stop and start the running of our code during the development of our applications. Continued performance improvements in runtime and build time. EF Core performance is now 70% better on the Tech and Power benchmark. So that was a brief overview of what you can expect with the release of .NET 6.
Hi and welcome, I'm Gavin Lon. In this video, we are going to look at some of the great features and improvements that are due to be released with .NET 7. We'll cover these aspects thematically. For more details of what to expect with the release of .NET 7, I've included relevant links below in the description of this video.
This video will give you a broad overview of some of the improvements and new features that stand out to me that will be included in the official release of .NET 7, which is due to be released in November of this year, 2022. Since the release of .NET 5, on November the 10th, 2020, Microsoft committed to a new release of .NET in November of each year moving forward. So .NET 6 was released on the 8th of November 2021, and in November of this year, we are expecting the release of .NET 7. .NET 5 was what's known as a current release, and .NET 6 was what's known as a long-term support release, LTS release. Note that there is no quality difference between long-term support releases, LTS releases, and current releases. The only difference is the length of support. LTS releases get free support and patches for 3 years. Current releases get free support and patches for 18 months. At the time of creating this video, the latest preview release of .NET 7 is Preview 6. I've included links below in the description to blog posts that contain details of each of the preview releases of .NET 7. The official release of .NET 7 will be a current release, which means it will be supported for 18 months. The release of .NET 8, due to be released in November 2023, will be a long-term support release, which means it will be supported for 3 years. Preview releases are typically not supported, but they are offered for public testing ahead of the final release. A preview or release candidate release are supported through Microsoft Developer Support only if they're specifically designated Go Live. A brief history of .NET. This channel has released several videos on the history of .NET. The first video I released on .NET is a video on the difference between .NET Framework and .NET Core. I've since released a video on the .NET 5 release and a video on the .NET 6 release. In each video, I've provided foundational content on the evolution of .NET. Please see a link to a playlist below in the description to view the videos released by this channel on the progression of .NET. So in this video, I'll give a brief overview of the history of .NET before we look at the new features due to be released in .NET 7 and also the improvements and optimizations that are due to be released in .NET 7. .NET Framework was released February the 13th, 2002. At the time, it was a revolutionary release for Microsoft as it fundamentally changed the environment in which Microsoft applications run. .NET applications run on what can be described as a virtual machine, similar to how Java applications run on the JVM, Java Virtual Machine. The virtual machine provided in the .NET Framework is known as the CLR, Common Language Runtime. .NET Framework, however, can only run on Windows platforms and requires an installation of all the base class libraries shipped with the .NET Framework. .NET Core was released on the 27th of June, 2016. It is a free open-source managed computer software framework that is cross-platform. It can run on Windows, Linux, and macOS operating systems. Only the base class libraries that are needed by an application need to be shipped with that application, so it is a more agile version of .NET when compared to the .NET Framework. So, .NET Framework and .NET Core is being supported concurrently. This resulted in the fragmentation of .NET. To alleviate this fragmentation, the .NET Standard was introduced. The first steps to properly unify .NET under one umbrella, as it were, came with the release of .NET 5 on November the 10th, 2020. The release of .NET 6 came approximately 1 year later, on the 8th of November 2021, which shipped with many great enhancements, but most significantly, .NET 6 further cemented the unification of .NET. So, .NET 6 is unified free open source software that is cross-platform and agile. It is an extremely versatile framework in terms of the types of applications that can run on .NET, and the performance of .NET has been optimized for the cloud. It is also versatile in terms of the number of platforms on which it can run. .NET 6 is supported on multiple operating systems: Windows, Linux, macOS, Android, iOS, tvOS, including macOS Silicon and Windows ARM 64. So what is coming with .NET 7? .NET MAUI. There is significant investment in .NET MAUI for .NET 7. .NET Multi-Platform App UI, .NET MAUI, is a cross-platform framework for creating native mobile and desktop apps with C# and XAML. Using .NET MAUI, you can develop apps that can run on Android, iOS, macOS, and Windows from a single shared codebase. .NET MAUI is open source and is the evolution of Xamarin Forms. With the release of .NET 7, you can expect performance improvements and better tooling in .NET MAUI. Cloud native and containers. Cloud native computing is an approach in software development that utilizes cloud computing to build and run scalable applications in modern, dynamic environments such as public, private, and hybrid clouds. So, common technologies used in building cloud-native applications are, for example, Docker containers, a set of platform-as-a-service products that use OS-level virtualization to deliver software in packages called containers. Kubernetes, an open-source container orchestration system for automating software development, scaling, and management. And microservices, a collection of loosely coupled services that run inside Docker containers. There'll be a broad set of investments in cloud native and containers in .NET 7, in terms of, for example, simplifying authentication, improvement of performance in terms of startup performance and runtime performance, and better integration with containers. There's also investment in better alignment with the Orleans technology. Orleans is a cross-platform framework for building robust, scalable, distributed applications. Orleans scales with a single on-premises server to globally distributed, highly available applications in the cloud. Orleans uses the virtual actor model, where grains serve as the fundamental building blocks of Orleans applications. Grains are entities comprising user-defined identity, behavior, and state. So with .NET 7, there will be investment in better alignment of Orleans with .NET. Modernizing existing .NET applications. With .NET 7, there is investment to make it easier to upgrade older .NET applications to modern .NET applications. For example, you may wish to upgrade an old ASP.NET MVC application to an ASP.NET Core MVC application. For .NET 7, Microsoft is making investments into its Upgrade Assistant to make these types of upgrades easier. The Upgrade Assistant can, for example, change code written for older .NET environments to be appropriate for modern .NET environments. It will also be made easier to upgrade applications in sections rather than upgrading the entire application at once. There are framework investments for application modernization in .NET 7. Abstractions will be provided that, for example, allow the sharing of parts of the ASP.NET side of the application with parts of the ASP.NET Core side of the application, so the upgrade can be done in an incremental fashion rather than all at once, which may not be a practical solution. .NET 6 contained many performance improvements. Investments are being made in .NET 7 to make .NET even faster and more efficient. ASP.NET Core. HTTP 3 will become part of the .NET framework in .NET 7. HTTP 3 is a new standard in development that will affect how web browsers and servers communicate. Unlike previous versions, which relied on the well-established TCP, HTTP3 uses QUIC, a multiplexed transport protocol built on UDP. HTTP3 includes significant upgrades for user experience, including performance, reliability, and security. Minimal API. Minimal APIs are architected to create HTTP APIs with minimal dependencies. They are ideal for microservices and apps that want to include only the minimum files, features, and dependencies in ASP.NET Core. Minimal APIs provide developers with the advantage of less ceremony when setting up Web API applications. They are lightweight. Minimal APIs hook into ASP.NET Core's hosting and routing capabilities and allow you to build fully functioning APIs with just a few lines of code. In .NET 7, Minimal API will be more consistent in terms of what can be achieved when compared to Web APIs that use the traditional MVC design pattern. One new feature in .NET 7 is providing a way to group minimal APIs together with a common root prefix, so that they represent one part of the API space, as it were. A developer can take the APIs and put them in different files, so that it is more manageable from a project and code management perspective. Currently, you can apply action filters to controllers in a Web API component. The ability to implement such code for cross-cutting concerns will now be available for minimal APIs. The concept of endpoint filters will be available in .NET 7 to apply the same cross-cutting functionality that, for example, action filters provide for controllers. gRPC. gRPC was created by Google to speed up data transmission between microservices and other systems that need to interact with each other. With .NET 7, there is investment in gRPC JSON transcoding. The feature allows gRPC services to be called like RESTful HTTP APIs, with JSON requests and responses. So, for example, this will make it easy for JavaScript code running within a browser to call a gRPC service. SignalR. SignalR is a free and open source software library for Microsoft ASP.NET that allows server code to send asynchronous notifications to client-side web applications. SignalR was built for high performance and is one of the fastest real-time frameworks around. In .NET 7, there will be support for strongly typed clients and returning results from client invocations. A new client source generator for SignalR will be included. The SignalR client source generator generates strongly typed sending and receiving code based on interfaces that the developer can define. .NET 7 will come with various improvements to the Razor compiler to improve performance resilience and to facilitate improved tooling. Blazor. Broad improvements will be made to Blazor. For example, mixed mode AOT, ahead of time compilation, will allow for certain assemblies to be ahead of time compiled rather than the entire application needing to be ahead of time compiled. When ahead of time compilation is implemented, this makes the overall size of the application to be downloaded to the browser much larger. So although runtime speeds are increased for the application, the file size is much larger. Enabling mixed mode means that parts of the application can be optimized for speed. Those parts of the application that require greater speed can be ahead of time compiled, leaving the rest of the application to be interpreted. So speed can be increased where it counts, and a balance is maintained between less size of the application and the benefit of speed optimizations. Most browsers are now capable of facilitating multi-threading, so .NET 7 will take advantage of this and will provide multi-threading to Blazor WebAssembly applications. Web crypto simply means that cryptographic functionality available in browsers can be leveraged from Blazor applications. With the release of .NET 7, there will be enhancements in hot reload support. Data binding improvements, more flexible pre-rendering. Pre-rendering Razor files into HTML allows parsing of static files, which, for example, makes SEO, search engine optimization, effective in Blazor applications. More control over the lifecycle of Blazor service circuits. Improved support for micro front-ends. Micro front-ends are a new pattern where web application UIs, front-ends, are composed from semi-independent fragments that can be built by several teams using different technologies. Support for custom elements is an exciting feature where you can shrink wrap, as it were, a Blazor component in a standard custom HTML element. This means you could reuse the relevant custom element created in a Blazor application within, for example, an Angular or a React application. So that's a super exciting feature. MVC. .NET will include improvements made to endpoint routing, link generation, and parameter binding. Orleans. The ASP.NET Core and Orleans teams are investigating ways to further align and integrate the Orleans distributed programming model with ASP.NET Core. Orleans 4 will ship alongside .NET and focuses on simplicity, maintainability, and performance, including human-readable stream identities and a new optimized version-tolerant serializer. This video provides a brief overview of some of the features and improvements to expect with the next official release of .NET, which is due to be released in November of this year. .NET 7 will be a current release, meaning it will be supported free of charge for 18 months, and will contain many great new features, many performance and optimization improvements. With this new release of .NET and the commitment to release a new version of .NET every year moving forward, makes it a great time to be a .NET developer. If you liked this video, please give it a thumbs up, and please feel free to share this video with anyone you feel may benefit from its content. For content like this and much more, please consider subscribing. And please ring the bell so as to be notified when new content is released. I really enjoy reading your comments, so please feel free to leave a comment below in the description. I hope you've enjoyed this video. Thank you and take care.